Hi everyone and welcome back to PrepFusion. So today we'll start a new chapter of engineering mathematics, that is calculus. So it is a very vast and big chapter, right? So we have to break this down into steps and slowly understand the core concepts. What happens is many educators, what they do is they assume initially that you have already studied very well in 11th and 12th, and they directly start with the difficult things, right? They directly start with the formulas, but it may so happen you may have forgotten few things, right? Because 11th and 12th was many years back. So what I will try to do here is start from basics, okay, and take you to the next level, take you to 100%, from 0% to 100%. So few things, like few students, what may happen with them is that they already know this stuff. So the first few lectures, right, will always be from basics. So if you already know, or if you haven't forgotten anything, you can directly watch it in 2x, okay, so that you can get a quick revision, or you can go through the notes and you can get a quick revision, right? If you already know these things. If you don't know, obviously you have to watch the lecture, right? Because there are my students maybe from diploma also who haven't learned mathematics that well, so I have to take care of them as well, right? I have to take care of the toppers as well, of the students who have not studied that much, right, previously. So I have to go along with both of them. So if you already know all this stuff, so you can watch it in 2x or watch the notes and revise from there, right? So in this first lecture we will start with basically functions and graphs. So basically from the basics, right? Many students, they don't know what does a function mean, what are the standard graphs for those functions, and what are a few standard functions, right? So we'll learn those. So let's start with first variables. So what do you mean by variables here? So a variable is an entity whose value is not fixed, so its value varies. That's why the name is variables. It can vary. Variables are generally denoted by letters x, y, and z, okay? So here generally we denote it as x, so because x is very important, if you know what I mean by x, okay? So variables are very important, right? Variables are things which we can vary. If you vary that, I am varying my input. Let's say I am varying my input. Let's say you are varying the speed of your car. You are inside a car, you're driving the car, right? And what happens? You press the accelerator knob, whatever you call that, I don't know. So you press the accelerator, right? Then what happens? The speed of the car is varying. Basically, you varied some parameter, you gave it some input, right? Okay, you gave it some input, then the speed also varied, increased, right? It gave you some output. So you're varying the input, and it is also varying the output. So basically you're varying the power consumption or whatever, right? There are many mechanisms inside a car, so that is varying. So that is what we mean by variation and variable. So you're varying x, and in the output we will get something. So what is the output? Output is basically this, right? We will understand that in the next few slides. So now let us define the types of variables. We have mainly three types of variables, right? So real variables. What are real variables? Real variables are, if x and y is real variable, then x will vary from minus infinity to plus infinity, and y will vary from minus infinity to plus infinity. All of them should be real quantities, okay? So I hope you understand what do you mean by real and complex numbers. Complex is basically another form, right, which is under root of -1, okay? So when these are real, right, so they will only lie in the real domain. So x can vary from minus infinity to plus infinity, or y can vary from minus infinity to plus infinity. Now if we have vector variables, just the difference will be that my variables, right, will have some direction associated with it, right? So here x I cap, y j cap. So you have studied in physics what is I cap. I cap is in I cap direction, unit vector in the I cap direction, and j cap is the unit vector in the I j cap direction, right? So vector variables can be defined like this. Mainly we will work with the real variables in engineering mathematics, so you don't have to worry that much. Next is complex variables. So when we will study the complex chapter, right, complex calculus chapter or complex variable chapter, there we'll use complex variables. So this is vector variables. This is generally used in physics, okay? Here x and y component are there, and I and j are the directions of it. So you might say a car has velocity. If a car has velocity, it will obviously have magnitude of speed, right? Okay, it is moving, right? It is moving. Then in the x direction it will have some speed. In the y direction it will have some speed. In the z direction it will have some speed. We are in the 3D plane, right? Here all of this is in 3D. And also it will have some direction associated with it, because velocity means two things, magnitude and direction. So this is how we define the velocity of a car, right, with direction and magnitude. Okay, so we will need vector variables over there, right? Now what are complex variables? So complex variables are complex number, right? Complex numbers where we will have a real component and a imaginary component, a combination of real and imaginary component. Here also x is varying from this minus infinity to plus infinity, and y is also varying minus infinity to plus infinity. But z, right, z is a complex variable. It is very important to understand that z will be a complex variable. Okay, I'm just slowly giving you a few definitions. You already know all this, but still, like, for the people who don't know, for the students who don't know, right? So what will be the topics that we'll cover in this whole calculus chapter? So this calculus chapter can be divided into two parts. One is differential calculus, another is integral calculus. Okay, so mainly we'll study calculus of real variables. There is another specific different chapter for complex variable. We'll study that later on. Okay, but obviously I'm going according to what are the most important. I forgot to tell you that this is also, or calculus is also almost for all the branches, right? All the branches. I hope you have watched my lecture 0 where I have told the syllabus for each of the main branches, right? Syllabus for each of the main branches. So this is limits, continuity, differentiability. Okay, in the differential calculus we'll study, then mean value theorem we'll study, Taylor series we'll study, application of derivative, that is AOD we'll study, then partial derivative. So these are the topics for differential calculus. Okay, I hope you have heard these names, or if you are in your college, so you must have studied all this, but there we don't have the concept clarity. We just simply solve the questions. We know the formulas, we just simply solve the questions. But what is the concept behind that? That also we have to understand, right? Yeah, mathematics is mostly about applying formulas and solving questions, but sometimes in GATE they may play with language. So mostly the questions from mathematics are asked generally easy, but sometimes they get asked difficult as well. Okay, and when they get asked difficult, no one is able to solve them. So you have to solve them also if you want to become a topper, right? So yeah, this is about the differential calculus. And what about the integral calculus? So in the integral calculus, basically we'll learn about the integration, right? So single integral, double integral, and triple integral. Okay, so first we'll cover this, then we'll cover this. Okay, so yeah, let's first understand what a function is, right? So what a function is defined as a relation between a set of inputs having one output each. So input must have at least one output. It cannot have two outputs. Input can have one output, cannot have two outputs. What do you mean by this? Here I have input, right, and here I have output. So if you press the accelerator of a car, then you should get a particular acceleration at the output, right? Or if I want to say, if you are changing your what do you say, steering wheel, right? If you're changing your steering wheel, let's say 30 degrees, so it should move only 30 degrees, or should move particular angle. If you change your steering wheel 30 degrees, and what happens, it moves 30 degrees on the right, and then again left, right and left, right and left. So obviously that is not possible. If you move your steering wheel 30 degrees, it will only move a particular direction and remain at that. Okay, and remain at that. That is, for a particular input, it is mapping to a particular output. It is not mapping to two outputs. If I move my steering wheel 30 degrees, the tires should move in the right angle, on the right 30 degrees, not 30 and 45. How can it move 30 and 45? It has to at least go to 30 degrees, right? So that is what this statement is telling us. Okay, trying to explain to us. So let's understand this visually here also. So let's say I have ABC inputs, right? Any function, I have a block over here. Right? Let me draw the block if I can. I have a block over here. If you have studied control systems for me, you will understand. Okay, if you have studied control systems for me, right, it will be added advantage for you, because there also I have taught you few mathematical concepts, so that will be used here. Okay, and yeah, so now basically what is happening over here, so this is the input and this is the output, right? This is the output, and here some function is there, that is the f of x function is there. Now if I give this input as a, x is equals to a, right? If I give this x is equal to a, it is giving me some output. Okay, I should not write this as x, y, z. I could have written this something else. What should I write this? That is what I'm thinking. What should I write this? I can write this D E F, right? So if I give input A, I'm getting in the output D value. Basically, let's say if I'm rotating it by 30 degrees, it is rotating 20 degrees because there is some other things, right? Exactly 30 degrees rotation won't give me 30 degrees rotation at the tires. Okay, so yeah, so it is giving me D. Now tell me, can this happen? If I'm rotating it 30 degrees, can it also give me F, let's say 45 degrees? Can it happen? No, right? It can't happen. It has to give me a single value. A single input has to give me a single value for a relation to be a function. Okay, a relation to be called a function, okay, it has to have, for a set of inputs, it has to have at least only one output each, right? So no, this is not possible. Okay, now for B, let's say I'm getting E. Now is this possible that for C also I'm getting E? Is this possible? Now read the statement again. Function is defined as a relation between a set of inputs having one output each. C has one output, fine. B has one output, fine. A has one output. Okay, so this is satisfying this statement, right? This is satisfying this statement. So this is a valid function. Okay, it doesn't necessarily mean that for another input I have to get different output. These both of this B and C can map to the same output. Okay, so a function, the mapping of a function can be called many to one or one to one also. Okay, mapping, let me write this over here in small letters. Mapping, basically I'm talking about mapping. Mapping basically is many to one or we can say one to one, right? What do you mean by many to one? So this you can look it up in Google. I will just explain this in briefly. Okay, in brief. So basically what do you mean by many to one? Many to one means many inputs are mapping to single output. That is possible. A function, that is possible for a function. What does one to one mean? For each input I am getting a specific output, not the same output again. So that is what one to one mapping means. So yeah, this is a brief talking about one to one and one to one mapping. You can just search it up. Relation, these are called also relation. Okay, you can look it up, relations, right? In simpler words, a function is a relationship between inputs where each input is exactly related to one output. Exactly one output it should be related, not two outputs, right? More than one output. Every function has a domain and a codomain or range. Okay, this is very important. Every function has a domain and codomain or a range. We'll understand these terms. A function is generally denoted by f of x, where x is the input. X is the input, and f of x basically is this block, and output is the y basically. Okay, so where x is the input, the general expression of a function is y equals to f of x. So output is y and input is x, and this f of x is the blocks that is basically manipulating the variables. X in our case is the independent variable to get a particular output y. Okay, so x is a variable over here because I am varying my x. Look, I am varying my x. My y is also varying, so y is also a variable, but there is a slight difference between these variable and that variable. This is the independent variable because I can give it any input. Obviously it should lie in the domain. We'll understand what does domain mean, and output I will get according to the input. So output is dependent on the input. That's why it is called a dependent variable, and this is called independent variable. More on this later on. Let's understand this few basic terms. What do you mean by open and closed interval? So open interval and a closed interval are used to represent a range of numeric values. So it is basically used to represent range of numeric values, right? Whenever a range, so my input is varying from A to C continuously, so I can represent that with open and closed intervals. I will just give you an example and there you will understand. The open interval includes only the values between the endpoints and is represented as this normal round brackets. So they are called round brackets. Let me write this. Round brackets. And this closed interval, right? They are called this is called open intervals. Wherever round brackets are there, they are called open intervals, and the closed interval includes even the endpoint of the range of values and it's represented by square brackets. So this is called square brackets. Okay, so these are called square brackets. Okay, that is one thing. So now let me take a few examples. From there you will understand better. So let's say you have already seen this notation, so don't worry. I'm taking an example. So if I write something like this, x, this is a belongs to sign, right, epsilon a comma b, and here I have round brackets. What does this mean? Let's read this statement. So the open interval includes only the values between the endpoints, is only the values between the endpoints, and is represented as round bracket. So it includes between the endpoints. So my x, this sign is belongs to. So I will explain the definition. This is belongs to. And here, what does this mean? This means that x lies between a and b, excluding a comma b. Okay, so excluding a comma b, it lies between a and b. So basically, if we have 1 comma 2, right, x will lie between 1 comma 2, between 1 and 2, 1.5 valid, 1.3 valid, right, but 1 is invalid. If something like this is written 1 comma 2 in round brackets 1, if I write x equal to 1, that will be invalid. X cannot be equals to 1. Okay, because it is excluding a and b. So I should write a and b. Now what about the second example? Second example is x belongs to, okay, I will not take the conventional one, I will take the different one. This is a comma b and this bracket, right, a comma b, this bracket. So can you tell me where does this x lie? Can you tell me again? Right, this statement will be correct only. X lies between a and b. This statement is correct. Okay, but here I have to write two statements. So what will be included and what will be excluded? As you can see here, I have a square bracket. So if I have a square bracket, it will include the endpoints also. So square bracket on the right hand side only I don't have a square bracket on the left hand side. So it will include including this what do you say, including b, right, but excluding a, because x has a round bracket with it, right, x has a round bracket with it. So these two statements are very important, because anyways we know that a and b are written, so that will lie within the range, that is fine, but what is included and what is excluded, that is also very important to understand, right? So yeah, including b and excluding a. So this is the important point that I want to say about the difference between open interval and closed interval. So okay, so I hope you got this point, right? So yeah, if like this is given, so it will, x will lie between a and b, but it will not include a and b. Okay, but here if square bracket is given, so x will lie between a and b, and it will also include b, right? It will also include b. Now what about the domain of a function? What do you mean by domain of a function? We just heard about this word, right, in the previous slides. So let's first read the definition. The set of all possible values which qualify as inputs to a function is known as domain of the function. So basically this set of all the possible values which qualify as inputs to a function is known as domain of the function. So it sometimes it may happen that I will not be able to give all the inputs to the function, right? Why? Can you rotate your steering like this and then again like this and then again like this, right? So like you have rotated already 360 degrees. I think there is some provision, right? After that you have to stop. So can you give it 400 degrees input? Can you give it that? No, the steering will break. The steering will break. The function will not work, right? So just like that, here also we can't give it any inputs, right? We have to stop somewhere. We have to stop somewhere. So obviously in steering wheel you stop in 360 degrees, right? Or I don't know, I haven't drove a car. I don't know, will I drive a car future? That also I don't know. But yeah, I like people who have already like driven a car, they will know, right? They will understand what I'm trying to explain. So there is some limitation, right? So that is what this limitation is talking about. So that is what this domain is. So we can't give any input to the function. So we have to define a range. So that range, how to represent the range, I've explained you, and why we can't give any inputs, that also I've explained you just now with an example. Okay, so it can also be defined as the entire set of possible values for independent variables, basically the x values, right? A domain of a function refers to all the values that can go into a function without resulting in undefined values. Because let's say in a car you give it 700 degrees input, the steering wheel, okay, you rotate it 700 degrees, what will happen to the car? Undefined, we don't know, right? Because it won't respond to anything, because the steering has already broken, okay, steering wheel has already gone broken, it has already been damaged, so we don't know what the car will give output, okay? That's why it is known as undefined. So this is a visualization of this. So here, from here also you can understand it. So domain of x is basically 1 2 3 4 x, and like we are defining the domain by ourselves. Domain is something that we define by ourselves. If nothing is set, then obviously we will exclude those values which will give me undefined values. But if set like generally we define the domain for ourselves, because for the steering wheel, what is the domain? 0 degree to 360 degree, right? So we can only rotate 0 to 360, we cannot rotate more than that. So we define it for ourselves. Okay, if nothing is set, we try to find out a domain whose for which inputs it gives me undefined values. What do you mean by undefined? Infinity, 1 over 0, all those things are undefined, right? You already know what are undefined values, I hope. So we'll also learn about those in the later chapters, like limits, in a much deeper manner. But for now I'm just giving you a brief about undefined values. Okay, so how to find the domain, basically. Okay, you have already learned this, so let's go quickly through this. So domain of any polynomial linear quadratic cubic function is real, and domain of a will be all real numbers, because anyways this, right? Let's say I'm taking an example. Okay, I'm taking an example, x square plus 2x plus 1, y equals x square plus 2x plus 1. So you can give it any values, right? It doesn't matter, any real value. Yeah, sorry for the interruption, actually the current went off. So as I was explaining here, right? So I have this function y equals to x square plus 2x plus 1. So what can I give input to this, right? What can I give input to this? I can give input anything, right? So x can be any value, negative, positive, it can be real number. So x can be any real number. So that's why the domain is any real numbers. Now, what is the domain of a square root? So I should add this in a second line. Domain of a square root. So domain of a square root function will be always that x has to be greater than 0. Okay, because I want my y to be real as well, right? Just hold on a second. Is everything fine? Yeah, I want my y to be real as well. So if I want my y to be real, that means that this domain has to be greater than 0. X has to be greater than 0, because if x is less than 0, it will become an imaginary number. Basically under root of a negative number is imaginary number. We don't want that. We want our output to be real in this case, right? We want our output to be real. Okay, so that is the thing, that is the reason why x is greater than 3. So let me take an example. So this was the first example, so let me take another example, like y equals to under root x minus 3. Now can you tell me the domain here? So in this case, right, in this case my x belongs to minus infinity to plus infinity, all real values. Obviously I cannot never reach infinity, that's why this is round bracket, this is not square brackets, because I can never reach infinity, right? I can never reach infinity. What is infinity? We don't know. It is very high value. Okay, that's why these are round brackets. Whenever infinity is present, you will represent those with round brackets. Okay, now here, can you tell me what is the domain of this? So the domain of this will basically be x greater than 3, right? X any positive value, or x equals to or greater than 3. So x has to be equals to or greater than 3, right? X has to be equals to or greater than 3. Okay, so if x has to be equals to or greater than 3, what does this mean? This means that how can I represent this in the open interval and closed interval format? So here, right, x can be equals to 3, so I will include 3, and obviously infinity is there, but I can never touch infinity, so I will represent infinity with round brackets. So x be 2. If x is equals to 2, this will become -1, which is not possible because my y is real. My y is real, right? So for y to be real, x has to be greater than 3. That is the main important thing. So then domain of an exponential function is all real values. So e to the power x, a to the power x, right? A to the power x will be all real values. I am not going to that right now. Okay. So then domain of a logarithmic function is this. Domain of a rational function y equal to fx, set the denominator not equal to 0. So let's take an example for a rational function. So if I take an example for a rational function, let me just go to the next page. So let me take that y equals to 2 by x minus 2, right? Y equals 2 by x minus 2. So if y is equals to x minus 2, then my denominator cannot go to 0. If my denominator goes to 0, okay, then it will become 2 by 0, which is undefined, right? Which is undefined. What is 2 by 0? We don't know. What is 2 by 0? You might say it is infinity, okay, but we don't know, right? In the limits chapter, we'll understand this better. So it is 2 by 0. So basically, we never want our x to become that value which makes my denominator 0. So x cannot be equals to 2. So x should exclude 2. X can include any values. Okay, x can include any values, but should not include 2. So how you can represent this? Okay, how you can represent this? So either you can represent like this, that x belongs to all real numbers minus this particular value 2. You can represent like this, or what you can do is x belongs to basically from minus infinity to plus 2. Okay, from minus infinity to plus 2, but it cannot be equals to 2. It cannot be equals to 2. So obviously we have to put a square bracket over here, right? Then it includes, this is not union, this is intersection. Okay, no, not intersection, this is union. So basically union means this or this, right? Intersection means this and this, okay, and or 2 to plus infinity. Okay, hence there are round brackets over here because this will not include 2, okay, but it will include anything except 2. So that's why minus infinity to plus infinity we have, but just excluding these 2. So these both ways you can represent, right? So I'm not going too much into this because this will just waste our time. Okay, these are basics and I hope you're understanding these things. Now what is the range? The range of function is the set of all its output. Okay, basically whatever output I'm getting, that is the range, right, for particular inputs, right, which are in the domain. Okay, the range of a linear function is R. The range of a linear function is R. Okay, basically any linear function you can say y equals to x. Okay, it will be any real number, right? Any real number, y equals to x, y equals to 3x plus 1, y equals to 2x plus 1, anything, right? Okay, the range of a quadratic function y equals to, okay, this is actually, I should not have written this. This will be a square actually. This will be a square, right? Now where is it? Yeah, k is y greater than k, greater than equals to k if a is greater than 0 and y is less than equals if a is less than 0. So this is about the range. We will learn this in the quadratic graphical representation. From there we will understand. Okay, what is important? The range of a square root function will always be greater than equal to 0. This is important. This quadratic function we will already solve this in graphs. From there we will understand. So I gave you the previous example, right? Y equals to under root x minus 3. Okay, what is the range of this? This will always be positive. The square root function will always give me positive values. Okay, square root function always gives me positive values. Why is this the case? Because like many students get confused like this, that if my y square equals to x minus 3, I can write y as under root x minus 3. Okay, but they miss out on this plus minus sign. They miss out on this plus minus sign because this, right? Here in this case y can be negative as well. In this case y can be negative as well, right? But this, right, this cannot, x cannot be ever less than 3. X cannot be less than 3 because we have y square over here, and if this is a real number, so if we square that, we always get some positive number. So x has to be greater than 3, right? X has to be greater than 3. That's why we did this, right? That's why we did this, that x has to be greater than equals to 3 because it has to be positive. Why it has to be positive? In this case, right, we're squaring a real number. Y is a real number, we're squaring it. So if you're squaring a real number, we should get a real number and positive real number. Okay, hence this has to be positive. For this to be positive, x has to be greater than 3. Now, yeah, sorry, again the light went off. Recording here is just so stressful. I'm really sorry about the interruptions. So basically now, right, so this, if I take the under root of this here, right, I will get both plus minus. Okay, that is the interesting fact. But I will obviously ignore the negative sign, because here the function is like this, right? Function is like this. Okay, hence I will ignore the negative sign, because y cannot be negative. So I will ignore the negative sign. Okay, I will ignore the negative sign, because function is defined like this. Now, like, this was just for showing you the example. Now, what is the range? Range will be obviously always positive, because x will be equals to 3 or greater than 3, right? So it can be like, at minimum y can be 0. Okay, so my range of y, okay, range of y is basically, it will include 0, okay, and it will obviously, it cannot include infinity, exclude infinity, right? So this will be my range of y. Okay, this will be my range of square root function. Okay, so you can check all this, right? Range of logarithm function, range of exponential function, you can do it for yourself. Okay, and for where denominator is like, it's a rational function and denominator can go to 0, you can check the range for that as well. Okay, I won't do it. These are basic things. I won't go much into depth to this, because this will just take more of our time. So here I have just given you a brief summary about domain, codomain, and range. So what can go into a function is called a domain. What may possibly come out of the function is called codomain. What can possibly come out of function, not comes out of the function. Okay, what actually comes out of the function is called range. So for the particular domain, what I am giving the input, okay, for the domain, what is actually coming out of the function is known as range, right? Which is actually coming out of function. Now, what may possibly come out of the function is called codomain. What may possibly come out of the function. Okay, this is a possibility and it is actually. So that is the difference between range and codomain. We haven't I haven't like taught you about codomain yet. So from here, this example, so we understand what do you mean by codomain. So set of A is the domain. So what are the valid inputs I am able to get? Okay, set of B is the codomain. What are the outputs that I can possibly get? So this is set. So, and like this, right, these are my range. Sorry, here I've written something wrong. These are not 3, 5. Wait a second. My set of inputs is 1, 2, 3, 4. Set of codomain is 1, 2, 3, 4, 5, 7. Actually, not up until 8. So yeah, this will be 7 only. Okay, and my this range, right? Range will be 2, 3, 4, 5. Range will be 2, 3, 4, 5. 2, 3, 4, 5. Okay, so basically, what do you mean by this? So if I have a function, right, if I have a function which is y equals to x plus 1, y equals to x plus 1. Okay, if I have function y equals to x plus 1, now what can happen? X can be anything, right? Here I have defined my domain as 1, 2, 3, 4, but x can also take x equals to 0 as well, and for that I can get 1 as well. Okay, but my domain is defined. I have defined my domain like this, 1, 2, 3, 4. So for this particular domain, what I am getting is 2, 3, 4, 5. So these are my range as explained over here. So these are my range and this is my domain. Now for x equal to 0, I can get 1 as well. For x equal to 6, I can get 6 as 7 as well. All those things, right? So that is my codomain. That is my codomain, in which I can give it some different values as well, and I can get some different outputs as well. But currently my domain is defined like this, so I will take care of this. So if you are getting confused, don't worry. You have to just understand about domain and range. So you have been given this domain, and for this particular domain I am getting this particular outputs. So these are the relations, right? So this will be my range and this will be my domain. That is the most important fact. Codomain, if you don't understand, you don't have to care about that. Codomain is just the extra part. What are the possible outputs I can get? So these are my all possible outputs that I can get. Okay, and many more, right? Codomain is all of this, and range is this. Okay, so this is the basically difference between codomain, range, and domain. Okay, now let's understand about dependent and independent variables. I have talked about this previously, so let's again try to understand this in a better manner. So y equals to fx. Y is a function of x. So y is dependent on x. Okay, whatever values x changes, y will change to some other value according to the relation between y and x. So x is called independent variable. We can assume any value for x independently within the domain of the function. Y is called dependent variable. Value of y is obtained after substituting the value of x in the function and hence depends on x. As we are substituting the value of x in the function and then we are finding the value of y, so y is dependent on x. Whatever value x can take, x can take any value and y will depend on that value of x. That is the basic difference of independent and dependent variables. Now let's learn about graphs. Okay, so basically the graph of y equals to f of x, where f is a function, consists of points whose coordinates are x and y. We already know all this. Satisfy x and y. Satisfy y equals to f of x. Actually, satisfy y equals to f of x. Not this. Y equals to f of x. Also, it is such that lines drawn parallel to the y-axis do not intersect the curve more than at one point. What does this statement mean? So this is known as a vertical line test. If you have studied in 11th, you will recall this. This is known as the vertical line test for a relation to be a proper function, right? For a relation to be a proper function. So basically, what do I mean by this? What do I mean by this? So as I explained at the start of the lecture, that the output, okay, basically for a particular input I will get a single output only. I can't get multiple outputs. So what is my input is in the x-axis. Generally the independent variable will be in the x-axis and the dependent variable will be in the y-axis. So this is known as y and this is known as x. Okay, and y is equals to f of x. Y is a function of x, that's why this is known as the dependent variable. Now basically these are my inputs, right? So for a particular input I should get only one output. For a particular input, if I am getting, like here also for a particular input I am getting a output here and here also, then it will not be a function. It will not be called a function. Okay, because I should get only one output. That's why what do? I take vertical lines, right? I take a vertical line, I take a line parallel to the y-axis or a perpendicular to the x-axis, and I go through each of these points, right? Each of these points, like this x1, x2, x3, and test those. So if my line, right, is only touching at a single point, if my line is only touching at a single point, okay, intersecting with the curve at a single point, then what can I say? I can say that yes, this is a proper function. Okay, this is a proper function. If it is touching more than one point, let's say it is touching here also and here also, then it is not called a function. Okay, it will not be called a function. Okay, so it has to only intersect at one point. Okay, intersect only once, then it will be called a proper function. We'll learn more about this in the later chapters also about this graph. So I just wanted to give you a brief about graphs. Okay, so like from here, can you tell me which are proper functions and which are not proper functions, like which cannot be a graphical representation of function? So this is the first question. Try to attempt this. How will you attempt? Try to use the vertical line test. So let me start. So in this circle, this is a circle. I hope you know the equation of circle. X square plus y square equals to 1. So you start going in the vertical line test. Okay, you start going in the vertical line test. What do you see? Like for this particular value of x, right, I am getting 2 inputs. Okay, and for this particular value of x, I am getting 2 inputs, which is not possible. Hence, this cannot be a graphical representation of function, right? So this is not a proper function. Okay, we can write the equation x square plus y square equals to 1. That is fine, but this is not a proper function. Because for a single value of x, I am getting two outputs. Okay, now here, is this a proper function? If I go through this, right, I will always touch at a single point only. This is like a parabola. So this is a proper function. So this can be a graphical representation of a function. Okay, function and relation are different. X square plus y square equals to 1. That is okay. That is fine. But this will not be called a function, right? This will not be called a function. Okay, next is this C, right? See, if I apply the vertical line test, so this will again be wrong. Because I am touching my y-axis twice for this particular input. So again, this cannot represent a function. But what we can do, we can interchange the x and y, and from there you will see that I am getting this graph. So then this will be a proper function. So like I have to interchange my y and x. So in this case, right, what is the problem here? The problem is my x should be the dependent variable and y should be the independent variable. If I interchange those two things, then this will also be called a proper function. Okay, so it is also important that what is my dependent variable and what is my independent variable. Now let's go to the D, right? Let's go to the D. So here, like if like you may recall this function, this is a very famous function from your school days. So this is the greatest integer function, right? Greatest integer function. Okay, so greatest integer function is equals to, simply we will define this later on, is equals to n if my x is integer. If my x is integer, basically the n itself, and uh, just hold on a second, and equals to n minus 1. Okay, if my x is not integer, right? Not integer, x is not integer. Okay, I will define this later on, don't worry. Greatest integer function, I will define this later on. So here, if I go through my vertical line test, is my line, right, vertical line, touching the curve twice at any point of x? No, right? No. So this is a proper representation of a function. Here, if I go through this, what is happening? I'm touching here multiple points. For a single value of x, I'm getting multiple outputs. So this will not be a proper function. So again, this is not a correct representation of a function. So A, C and E will be my answers in this case. A, C and E will be my answers. Okay. A, C and E will be my answers. Okay. So let's now learn about few standard functions of real variables. We're only talking about real variables right now, not complex variables. So we have algebraic and transcendental. So what are algebraic? Basically, algebraic involves only algebraic operations, addition, subtraction, division, all those things, right? Transcendentals are a bit different, like trigonometric. I hope you know what are trigonometric functions, right? Or exponential, or logarithmic, or inverse trigonometric. So here, these are polynomial functions. So they are simply x square plus 2x plus 3, all those things. Then rational functions, x plus 1 divided by x minus 1, all those things, right? Then power functions, like k into a x raised to power a, something like that, right? Y equals to x raised to power a, something like that. So let me just give you examples here. Y equals to k x raised to power a. Rational will be something like x plus 1. So mainly we will talk about these functions, x plus 1 by x minus 1. Then polynomial is x square plus y equals to, these are all y equals, right? Y equals to x square plus 3x plus 1. Okay, so these are the case. Right? So here, right, transcendental will never be a polynomial, will not be a polynomial, not a polynomial, right? Not a polynomial. Okay, can I write this better? I can definitely write this better. Not a polynomial, right? So it can be trigonometric, exponential, logarithmic, and inverse trigonometric graphs. So we'll like see the standard graphs, so there we'll understand. So before going to those standard graphs, right, I want to like tell you a few more definitions. So first one is even and odd functions. What do you mean by even and odd functions? Just hold on a second. Let me check everything is recording or not. Yeah, everything is recording. So what do we mean by even and odd functions? So basically, even function means let me just color these things, because this. Okay, how do I color these things? Just hold on a second. Now I can color. Not this. Yes. And odd function also have to color. Okay. So even function for a real valued function f of x, when the output value of f of minus x is same as f of x, then for all values of x in the domain of f, the function is said to be even function. So basically, what can be even function? Let me take an example over here. So if just hold on a second. If my y equals to x square, right? If my y is equals to x square. So if my y is equals to x square, that means what? If I do f of minus x, so y is f of x, right? So y is f of x just hold on a second, equals to x square. Now if you replace x to be equals to minus x, what will happen? Minus x square. Minus x square means what? Minus 1 whole square is 1 only, so it will be again x square. So f of x will be equals to f of minus x, hence it will be even function. Why? Because for the left hand side of my x-axis, like in this graph, right, left hand side of my x-axis and the right hand side of my x-axis will be symmetrical. Okay, will be symmetrical, will be same. We'll see with examples. So this is the relationship. Now about the odd function. So if for a real valued function, if my f of x is equals to minus of f of minus x, then it will be called a odd function. So what will be the example of this? The example of this is simply y equals to f of x equals to x cube. Okay, or you can take x as well. So now if you replace x equals to minus x, what will happen? This will be minus x, so minus 1 times x, so it will be minus times f of x, right? Minus times f of x. F of minus x will be minus times f of x. Okay, so hence this will be called a odd function, right? So yeah, as x is equals to f of x only. Now this is the relationship. Now there is only one function which is both even and odd. What is that function? That is x equals to 0. So x equals to f of x equals to 0. F of x equals to 0 is a both even and odd function because it is always 0, right? It is always symmetrical. So for odd function, right, what do you call? We call it odd function is symmetrical about the origin. Even function is symmetrical about the y-axis. Okay, y-axis. So odd function is symmetrical about the origin. So how can I write this? I can write this here in very short manner. About origin. Okay, and my even function is symmetrical symmetrical about y-axis, right? About y-axis. Okay, this space is a bit cramped, but I hope you will be able to understand this point. Okay, so a real valued function can be also neither even or not odd. So it doesn't necessarily mean a function has to be either even or odd. It can be neither even nor odd. So it is neither of those two things. So if it does not satisfy these two relations, it will be called a neither even neither odd function. Any you know. Okay, so what can be the example of that? So you can take the example of that as y equals to this 2 raised to power x, right? So if you take this example, right, y equals 2 raised to power x, if you plot this graph, right, you will see it is neither even neither odd, because if you replace x with minus x, it will be 2 raised to power minus x. Is there any relationship between this? No, it is basically 1 by f of x. So if I replace this, so just hold on a second. So if I replace this, right, with f of minus x, what will this become? This will become 2 raised to power minus x. So this will be 1 by 2 raised to power x. So if this is 1 by 2 raised to power x, this will be simply 1 by f of x, right? So this relationship is something different. Okay, this relationship is something different than this. These are satisfy these two equations. So here, like, I don't have space, so I will try to cram in space here. So my y, so for the first case, right, my y is equals to f of x equals to, I give you an example, x square. So now if I replace this with f of minus x, what will happen? This is minus x square, not minus x square, this is minus x whole square, right? I'm replacing x with minus x. So this will become f of minus x will be simply equals to x square itself, which is equals to f of x, right? Which is equals to f of x. Hence this relationship is satisfied. Now if I use the second one, right? If I use the second one, so y is equals to f of x is equals to x, right? Simple x. So now if I replace x with minus x, what will happen? X, f of minus x is equals to minus x, right? So if it is equals to minus x, then what can we call this portion, right? This portion is f of x itself, right? So this will be f of minus x will be equals to minus of f of x, right? Minus sign is outside and this is f of x. So f of minus x equals to f of minus x. Okay, so this is satisfied. This is satisfied. So yeah, so this is an odd function and this is an even function, right? This relationship is for even function and this relationship is for odd function, and for neither even neither odd, they won't follow this relationship, they will follow some other relationship. Okay, I've explained these two. So let's go to other definitions. So what is explicit and implicit function? So an explicit function is basically an algebraic function where the dependent variable can be explicitly expressed in terms of independent variable. It is an algebraic function. This thing you have to have a mind of. Okay, so don't worry, like I'm telling you all these definitions, you might say, sir, like these are so many definitions. Don't worry, just read these ones and that's it. These are very simple and fundamental things. Just hold on a second. These are very simple and fundamental things. You don't have to worry about this much, right? So just read these ones and these will come into your brain very easily, right? These are not that much of difficult things. Okay, so basically it is an algebraic function and it can be explicitly expressed in terms of independent variables. So after we study about the implicit function, there we'll understand like the difference between these two, actual meaning of this explicit function, right? So basically we have been given this equation, right? Can I, like my y, it is said that they have said that y is my independent variable. So y is the independent variable. So can I express my independent y is a dependent variable and x is independent variable. Can I express my y as a function of the independent variable? Can I do that? Okay, so let me try to manipulate this thing algebraically. So I can take y common over here, so this will be x minus 1, and I can take this x, right, this and this on the right hand side, so this will be x plus 1. So this will become y equals to x plus 1 divided by x minus 1. Okay, so y equals to x plus 1 divided by x minus 1. Y equals to x plus 1 divided by x minus 1. Okay, so here my y is the independent variable. Okay, y is the independent variable, dependent variable, and my x, right, x is the independent variable. So I can easily express my dependent variable as a function of independent variable. Okay, okay, so this is what y equals to f means. So now let's talk about the implicit functions. So from here we'll understand the better meaning of explicit function. So implicit function is a function defined for differentiation of functions containing the variables which cannot be easily expressed in terms of y equals to fx. So here it can be expressed y equals to function of x, right? Here it cannot be. Can you explain? Can you separate these out, right? You can't, right? Simply you can't separate y because here we have y square term and we have a y term. Okay, you cannot simply do that. It will be difficult. Okay, so here what we do, we simply write this like this, right? So we write this f of xy equals to 0. So this is known as an implicit function where they are implicit to each other. They can't be separated. Y and x can't be easily separated, right? So, or sometimes they are represented like this phi of xy equals to 0. Whenever these types of things are given, right? So they are talking about implicit function. Okay, they're talking about implicit function. So implicit functions can have 3 variables also. So x square y square plus 3xyz plus z cube equals to 0. Okay, this can also be happen, right? This can also happen, minus 1 equals to 0. Okay, so here also I will represent my implicit function like phi of x y z equals to 0. Now why am I teaching you all this? Just so that you don't get surprised in the question paper if like some format like this comes up. If some format like this comes up, you will be able to understand that yes, this is an implicit function. I have already learned this, so you should not panic in the examination. That's why I am teaching you all this. Okay, so basically so this will be composite function. So what is composite function? Next is composite function. I've written this wrong. So like I hope you got the point, the difference between the implicit and implicit and explicit function. Explicit means I can explicitly represent my y as a function of x, right? I can explicitly represent that, right? But implicit function I cannot. Okay, so what is a composite function? The composite function is the composition of functions the composition of functions is the process of combining 2 or more functions into a single function. Okay, what do we mean by this? So here, right, this is an implicit function. They are two variables are independent and one is dependent. Now here what is happening, that composite function, in the case of composite function, let me take a function u which is a function of x and y. Now the interesting fact about x and y is that my x, right, x is another function of t, y is another function of t, right? So y is another function of t. Okay, so just let me make this colors different. So x is another function of t, y is another function of t, right? So can I give you a practical example? Yes, right? So I'm moving in the x direction, I'm moving in the y direction, a car is moving in the x direction and y direction, so it can be a function of time as well. That's why t is written over there. So in the x direction it is a function of time, and y direction it is a function of something, some other function of time. Okay, in the x and y direction. Okay, and the overall x and y, right, overall x and y I can write in terms of a function u. Okay, so if I write my u is equals to x square plus 2y. Okay, if I write my u is equals to x square plus 2y, then I can represent this in terms of single variable as well, right? Okay, u can be written like a function of g of t as well, right? You can be written like g of t. Basically, sorry, you can be written like this. Okay, I'm sorry, I should write this like this. This is a phi of t. Sorry, phi of t only. So like x and y both are functions of t itself. So I can write my u as, just hold on a second, this is f only, right, as a function of this, right? I can write like this. This is known as a composite function inside a function, or this is also represented like this, f of fog. Okay, generally like this is g of t only, so I should represent this in g actually, like that is the normal terminology. So this is g of t, this is g of t, and it is written f of fog of t. Okay, so they can write like this also, they can write like this also. This is g, this will be g only. Okay, so yeah, this is the case basically. So I hope we got the point, right? So basically my x and y can be anything, so x can be simply equals to t, y can be simply equals to minus t, right? It can be anything. Now here I can write my u as t square minus 2t. So I can directly write my u as a function of time instead of writing it in terms of x and y. Sometimes this is helpful. Okay, sometimes I want to know this x and y. Okay, sometimes this is helpful. So you have to know both ways, right? So this is what a composite function means. Basically combining two or more functions into a single function. Here I combine this into a single function, right? Here this x was a function of t, this y was a function of t. I combine these two into a single function. Okay, that is the basic meaning of composite function. So all these are done. Okay, basic definitions, don't have to go too much into this, just lightly study all this. Okay, next is some standard curves. So we have to see some standard curves. You have already, I hope you have already learned all this. Okay, if you have forgotten, you can quickly watch these two. So the first one is the most simplest one, is y equals to x, which is the linear line, right? Linear, y equals to x. So it's simply a straight line. Okay, and like there are many parameters of this, like the slope one. Okay, what is the slope of this? The slope of this is 1, right? How do you find out the slope? You find out the slope from here, right? Whatever coefficient this x term has, so that will be the slope. Like slope means how fast I am changing, as I am moving forward, how fast I am changing. So this is the slope. The rate of change will be constant. This is basically the differentiation, right, of the curve. Okay, so this is our slope. What is the y-intercept? The y-intercept is x equals to 0. Here we don't have plus c, so that's why y-intercept is x equal to 0. So that is one important point about y-intercept and slope. So for a straight line, you have to understand only the slope and y-intercept. So I have already taken the example, right, previously, that this will be a odd function. This will be a odd function, right? Odd function. So why this is symmetric? If you see it graphically, this is symmetrical about the origin. This is symmetrical, right? Symmetrical about the origin. Okay, so if you break this down, right, this will be symmetrical about the origin. This portion and this portion are same. Okay, or if you want to prove it from the function, that relation, I've already done it mathematically. Now let's go to the second graph, that is f of x equals to x square. So f of x equals to x square. It is a parabola basically. Don't go into my drawing. So my drawing is not that much good. I will try to make this better actually. Just hold on a second. Try to make this better. Yeah, this is much better. Okay, so this is a parabola basically. This is a parabola. Okay, so basically what is this? This is y equals to x square, right? Y equals to x square. F of x equals to x square, y equals to x square. Now here what do you see? It is symmetrical around the y-axis, symmetrical around the y-axis. So this will be even function. This will be a even function, right? Graphically also you can understand. Okay, now here, right, my y is always positive. Y is always positive because I am squaring a real number. If I am squaring a real number, y cannot never be equals to less than 0. So range of y will be always positive. X has domain of minus infinity to plus infinity, but range of y will always be positive. We'll ignore the negative sign, right? We'll ignore the negative sign. Okay, so that is another important point. So basically domain of f of x is basically x belongs to minus infinity to plus infinity, and the range of f of x, the output that I am getting, right, the output that I am getting is equals to y. Basically y can be only positive values. It can be 0. Okay, it cannot be non-negative values. Sorry, it can only be non-negative values. So non-negative includes 0 as well. Positive does not positive is not included, like 0 is not included in positive numbers. That is also another important fact. So infinity, right? So yeah, this is my range of f of x and this is my domain of f of x. No further discussion on this. So let's go to the cubic, right? So f of x is cubic, so my graph will look something like this for a cubic function. Okay, so why is it like this? So basically it was like this only, but for a cubic, right, it is an odd function. Like if you replace x with minus x, you will see it is an odd function. It is satisfying the odd relationship. That's why it will be symmetrical about origin and not about y-axis. Okay, so that's why this thing, right, doesn't come up here. This thing comes up here in symmetric about origin part. So y is equals to x cube. Okay, and this is the odd function. You can prove it for yourself. You can prove it for yourself. Okay, so next is basically this rectangular hyperbola, right? If you see y equals to this 1 by x, so y is equals to 1 by x. Now if I replace this, right, I can do one thing. X, I can like manipulate the variables. My x and y will be equals to 1 itself. X and y will be equals to 1, right? So my x and y is equals to 1. So this is also called as a rectangular hyperbola. It is also called as a rectangular hyperbola. Okay, this is also called as a rectangular hyperbola. So this is called a rectangular hyperbola. Now the shape is something like this. The shape is something like this. At x equals to 1, y should be also equals to 1, because if I put x equals to 1, y has to be equals to 1. If I put x equals to minus 1, y has to be also equals to minus 1. Okay, because minus 1 into minus 1 will be 1. In these 2 points only they will be equals to 1, but the product of them will be always 1. So basically as my x is increasing, right, as my x is increasing, y has to reduce. That's why y has reduced. As my y is increasing, x has to reduce, right, because the product of x and y are constant. Okay, so basically like they are going towards infinity. Here also they are going towards infinity. So there is one special name, that is the asymptotes. So asymptotes basically touch the curve at extreme points. These are lines, these are straight lines. I should write this lines. Let me do one thing. Okay, basically these are lines that touch the curve that touch the curve at extreme points. These are lines that touch the curve at extreme points. Okay, So what are the asymptotes of this? So the asymptotes will be something like this. So the asymptotes I'm drawing here, okay, basically these are my asymptotes, right? These are my asymptotes, because what are the extreme points? Extreme points are this minus infinity, x equals to minus infinity, y equals to infinity, x equals to what? X equals to uh, infinity. Okay, just x equals to, hold on a second, yeah, x equals to infinity and y equals to infinity. Now in this case, right, my what is the equation of my asymptotic line? Equation of asymptotic line will be something different, right? So equation of asymptotic line will be something different, as it is tending towards 0, right? It will obviously tend towards 0. Okay, obviously it tends towards 0, hence this line, right, the equation of this line will be what? The equation of this line will be y equals to 0, and the equation of this line will be x equals to 0, because at x equals to 0, like it will almost touch my x and y axis. So asymptotes in this case are my x and y axis, right? Okay, so in this case asymptotes are my x and y axis, because as I keep on increasing my x, y as my x is going towards plus positive infinity, my y will go towards negative infinity, right? So 0, y will go to 0, because the product of those two has to be 1. So if my x is 500, y has to be 1 by 500. X is 1000, y has to be 1 by 1000. X is 10,000, y has to be 1 by 10,000. You can see, right, y is reducing, going towards 0. Okay, going to 0, and x is increasing very high. So you can relate like that. So asymptotes in this case, right, asymptotes are my x and y axis. Okay, x and y axis, right? So also one more thing to notice about this is, just after this 0, right, like this is going to infinity plus infinity, just after this is a 0, like x equal to 0 line, right? So just after this my y is, f of x is positive infinity. Just before this my f of x is minus infinity. So what can we interpret from this? There are many things we will be able to interpret in the limits chapter. So just wanted to give you a sneak peek of this, that f of 0 plus, right, just after 0, this is, we're going into transient now. So just after 0, this is going towards plus infinity. Okay, so f of x is plus infinity. Now just before 0, this is going towards negative infinity. This is going towards negative infinity. Okay, just before 0, this is going towards negative infinity, right? Negative infinity and positive infinity. So these two the other things. So like these two, right, these two are not equal. What does this signify? We'll understand it is in the limits chapter. So f of 0 plus is not equals to f of 0 minus. So what does this signify? We'll understand in the limits chapter. So here also this is some different relationship. This is like the f of x equals to 1 by x square. So we have 1 by x square, so this relationship will be like this. And here basically my asymptotic lines will be only this, right? These are my asymptotic lines, x equals to 0. So this is also tending towards y equals to positive infinity. This is also tending towards y equals to positive infinity. And here, right, this is tending towards x equals to negative and positive. Anyways, we're going through all of this x axis. So here, what is the interesting fact? The interesting fact is, just after x equals to 0, this is my function is tending towards positive infinity. So I can write that f of 0 plus is positive infinity, right? I should write it like this. This is tending, right? This is tending, this is tending, like equals to infinity, something else. So okay, fine. So we can, anyways, okay, we shouldn't write tending, we can write this equals to, anyways. Okay, we can write this equals to, no worries. So this equals to positive infinity, and just before this, right, just before this, f of 0 minus will be simply positive infinity again. F of 0 minus will be simply positive infinity again. So this is also positive infinity, this is also positive infinity. So these two are equal. Okay, these two are equal. So this, if these two are equal, what does this signify? We will understand this in the limits chapter. Okay, so we will understand the limits chapter. So 0 minus is here, some neighborhood of 0. 0 minus and 0 plus are the neighborhood of 0. So this is 0 minus and this is 0 plus, right? So this is also 0 minus and 0 plus, just the neighborhood of 0. And the neighborhood of 0 is very important to us. Why? We will understand. So one key point I want to say is that if something is like this, right, that y is x raised to power m, x raised to power m means this, right? Okay, and then y equals to x, this is a linear function, and y is x raised to power 1 by m. This is basically the square root function. We haven't done the square root function, so in the next example I will take to compare all the three, right? This is like example of square root function if m is equals to 2, if m is equals to 2. So in this case, right, so m has to be integer, that is the first thing. M has to be integer, m has to be integer. So if m is integer, okay, so if m is integer, and also m has to be greater than equal to 2, because m equals to 1 doesn't like make sense, because it is simply the linear line itself. So m has to be greater than equals to 2. Okay, so m has to be greater than equals to 2. So this is the first thing. So basically if m is equals to 2, that means this is a square root function, and my graph for a square root function will look something like this. Graph for a parabolic function will look something like this, right? Quadratic equation you can say, and they all of them will meet at 1, because square root of 1 is 1, so 1 square is 1. Okay, but what are we observing here? So as my as my x is lying between 0 to 1, it will be something lower than 1. Why is that the case? So let m equals to 2. Let m equals to 2. So if m is equals to 2, what does that mean? That means that my y equals to x square. Now y equals to x square. If I pick any number between 0 to, just hold on a second, 0 to 1. So if I pick any number between 0 to 1, let me pick 0.1. So if I pick 0.1, what is the square of this? This will be 0.01. So y is even lower than that. Y is even lower than x. So always it will be lower than the whatever I choose, right? At 1 it will compensate almost. Okay, at 1 it will almost compensate. So it will always be less than the straight line. Y will always be less than x. So it cannot cross this line, right? It will be always less than this, right? That is the first thing. Next, let's take the example of a square root function. Square root function. Y is 1 by 2, right? 1 by 2. So let me take a simple square root function. So if I take x equals to 0.01, 0.01, and I am taking the square root of that. What will the square root of that? The square root of that will be simply 0.1, right? So if you take the square of this 0.1, you will get 0.01. If you take the square root of this, you will get 0.1. I hope you got the point. Now I am getting 0.1, which is basically greater than x. Whatever x I have chosen, which is greater than x. That's why this is over this x equals to y equals to x line. So that's why my square root function will always be over this y equals to x line, and my this square function will always be lower than this x equals to y, y equals to x line. But after 1, everything changes. So after 1, what will happen? 2 square will be 4, 4 square will be 16. So obviously my x is like y is greater than x always. So this, right, this will always lie above the y equals to x line. Now in this case, right, what is happening? In this case, basically I can say that under root of 4 is what? 2. So it is lower. What I have chosen x as 4, but it is lower than my x 2, right? So that's why this will be always lower than my y equals to x line. So this is how we generate the curves. And for higher order, same thing, same relationship follows, just the numbers are different. Okay, so like this was just an intuition that I wanted to give, right? So another key point I wanted to explain is that we already know this. If you don't know, then please know, okay, that under root of -1 is plus of under root of -1, which is iota, right? Which is iota. I hope you already know this. Now under root of -1/3, under root of -1/3 is cube root of -1, which is minus or 1 itself. It has other two solutions as well. It has two solutions. Okay, basically this, right, this is also like two solutions, which is plus minus iota, right? So because if I square minus iota, that will also yield me -1, but we will only take this positive value, okay, in our case. Okay, next is this -1. So this has three solutions, because whenever I am doing cube root, right, this has three solutions. This is also known as cube root of unity. If you recall that it was equals to 1 plus omega square equals to 0. If you recall correctly, that was cube root of unity. But in our case, up in this chapter, we'll only stick with real values. Hence, this will be equals to -1. Okay, and this will be equals to iota and not minus iota. Okay, so these two things, I hope you got clear, right? I hope you got clear. Okay, so like how to solve this? Basically, you can solve this using this, right? that x square plus 1 equals to 0. So x will be equals to plus minus under root 1. Okay, so here x is equals to plus minus under root 1, but I am only concerned about plus under root 1. That's why I will pick only iota. I will pick only plus I. Okay, and here how you will solve this. So here if you solve this, right, like this is cube, right, this is cube. So I will write x cube plus, sorry, this is minus 1, this is plus 1 equals to 0. Now if you take the square root of this, obviously you will get 3 solutions. I will only choose one, that is minus 1, because we are taking with only the real solution, right? So we ignore the imaginary solution. So here let's go to this graph, right? X under root. So I first explain this to make you understand the under root graph. So this will be like this only. It will obviously be initially higher than the y equals to x curve, then it will be lower than the y equals to x curve, right? Then from here what you can understand is that y equals to x square is a even function, that we know, right? Y equals to x square is a even function. Okay, y equals to x square is a even function. Then y equals to x is basically a odd function. Y equals to x is an odd function because it extends up to here as well. It extends up to here as well. But one thing to notice here is that x cannot extend, right? Sorry, this function, right, this blue function cannot extend in the negative values of x, because domain of x is greater than 0 only. Okay, x can be greater than equal to 0 only. Okay, it can be only greater than equal to 0 only, right? So yeah, this is the case. So basically it is neither odd neither even. Okay, I have got the point. This is neither odd neither even. So this is another example of neither odd neither even, right? So this will be neither even neither odd. Okay, so I have got the point, right? So like here I have plotted for x equals to like y equals to cube root, right? Cube root of x. Okay, y equals to cube root of x. So here I've compared this with x cube and y equals to x 1 by 3. So as you can see, these are always like some symmetry is there, right? Some symmetry is there always. So as I this is what I was trying to explain here. There will be some symmetry between the y equals to x raised to power m and y equals to x raised to power 1 by m. Okay, and this obviously straight line y equals to x. So here what is happening is that obviously this is the same reason why this is below and this is above the y equals to x line, the same reasons, right? But here also same reason. So this will also be like, this is an odd function, right? This is an odd function, so obviously this will be similar to this only, but this will be symmetrical to the origin. Okay, and this will be this. So you can calculate this in graphs and you can understand this, right? I'm not trying to explain anything. So basically at minus 1, right, these will be equal, because cube root of minus 1 is minus 1, because minus 1 into minus 1 into minus 1 is minus 1, minus 1 into minus 1 then into minus 1 again is minus 1. So this will be minus 1. Okay, and yeah, this will be this, and they will meet at this. So like you can understand, right? All these graphs you can just put it in the calculator and you can calculate, right? You can observe the relationship. So I was just trying to explain you the symmetry. So this x raised to power y equals to x raised to power 1 by 3, right? This can take in negative values. Square root cannot take in negative values, but this can take in negative values. So hence, what does this become? What type of graph is this? This is a odd graph. So this is a odd graph, right? Because x of minus like f of minus x equals to minus f of x, because if I replace this with minus x, so f of x equals to x raised to power 1 by 3, right? Now if I replace f of minus x, right, x with minus x, so this will become minus x 1 by 3, and this will be minus 1 by 3 x of 1 by 3. So what is like cube root of minus 1? It is minus 1 itself, right? It is minus 1 itself. So I will simply replace this with minus 1, and what is x raised to power 1 by 3? X raised to power 1 by 3 is f of x, so it will be f of x only. Okay, so f of minus x equals to f of minus x minus f of x. That means this is an odd function, so that's why I have written this is an odd graph. So this has already been proved, so this will also be odd graph, right? So minus 1 cube is minus 1 itself. So this will also be odd graph. So this is also odd. Okay, so next is we have to plot the quadratic equations. Before plotting that quadratic equation, we have to understand what a quadratic equation is. We already know this, like f of x equals to x square plus bx plus c. This was with us, I think, from class 5 or 2. Just hold on a second, let me turn on one thing. Actually, the currents were going so frequently that I forgot to turn on one of the lights. Okay, so anyways, without lights also I look good, I hope. Okay, or you guys can say in the comments. So y equals to f of x equals to ax square plus bx plus c. This is a quadratic equation. Now in this case, if my a is greater than 0, it will be concave upwards. What do you mean by concave upwards? It will be something like this. Shape is concave, right? Concave means like some cave shape, right? Cave shape. So in like hilly areas, you know what a cave is, like bears stay there, make their own what do you call, igloo or something, I forgot the names. So they make their own cave. So this is concave up. So this is like, this shape is known as concave up. Okay, up. And this is known as concave down. Okay, down. So you just try to remember that concave down means this and concave up means this. Slowly you find some analogy, and from there you will be able to understand. Okay, so for a greater than 0, it is concave upwards. So it is always upwards, right? Going, touching plus infinity, y is touching plus infinity. That's why we call it upwards. Downwards mean minus infinity. So which place you want to become? You want to go upwards or downwards? We all of us want to go upwards, right? So that's why concave upwards plus infinity. Concave downwards, we don't want to go down, minus infinity. Like this you can remember. Okay, so and these are what, alpha, beta, or what are the roots where my y value has become 0. Okay, y value is becoming 0 for particular x values, right? So alpha, beta, and roots, and I have given you the explanation. And the root side from the Sridhar Acharya formula is this side. Now this is known as the discriminant. This b square minus 4ac is known as this discriminant. And if d is greater than 0, my roots will be real and distinct roots. If d is equals to 0, my roots will be real and equal roots. If d is less than 0, roots will be complex or no real roots. Okay, no real roots. Roots will be complex because they will never touch the x-axis. They will never touch the x-axis. Okay, then my discriminant will be less than 0. Okay, I won't have a real root. I have taken the first case where discriminant is greater than 0. That is, I will always get real and unequal roots. Real and unequal roots. This we have already studied in the control systems chapter. Okay, in the time response chapter. For zeta, right? If you recall, for zeta. So real and distinct roots I am getting, and this is touching my x-axis, but for a greater than 0 and less than 0. Then if my d is equals to 0, I will get real and equal roots. So I will get only one root, and like basically equal roots. I will get two roots always, but those are equal. So I will see only one root over here, and they will be touching my x-axis here, right? So yeah, and this is concave upwards and concave downwards. Now again here, right, if my d is less than 0, it can never touch the x-axis because I don't have any real values of x. This line, right, represents all the real values of x. I don't have any real values of x, so this will never touch this. Okay, so if this never touches this, so this will be either here and here, right? These are the possibilities. Also this can be here as well. This can be here as well. Okay, this can be here as well. This can touch the y-axis as well, like x can become 0 as well. That is a possibility. Okay, but the broader picture, I hope you got the understanding, right? So again, this is concave upwards and concave downwards, negative infinity and positive infinity. Okay, so like now let's come to the conic sections. So these are similar, only the same things, only just we are doing quick recapitulation of whatever we learned. So we haven't learned this, right? Y square equals to 4x. Okay, I told you, right? I told you in one of the examples for the graphical representation, this can't be a proper function because if this is the dependent variable and this is the independent variable, we are seeing that it is touching twice. Okay, but we can write the relationship, right? We can write a relationship because sometimes you have to make the relationships work. Okay, even though you have difficulties. So basically in this case, right, what I have assumed is that a is positive. In this case, a is positive, right? A is positive. Just hold on. Also my x has to be positive in this case. X also has to be positive because y square is a real number, right? Okay, I have already written this. Is positive, so y square is already real number, so x has to be positive because y square has to be always positive, because it is a real number, right? It is a real number. So like minus 1 whole square is 1 itself. So it will also has to be positive. So that's why I'm saying that I'm always lying in the right hand side of my x-axis, right? For all positive values of x. Okay, so this is the case, and this is y equals to again 4ax, right? This time the difference is that my a is negative. So if my a is negative, then my x has to also become negative, right? X has to also become negative, right? If my a is negative, x has to also become negative. Okay, so x has to also become negative. That means I will always lie in this left hand side, right? Left hand side. Okay, so okay, what am I doing wrong? So this will be only, this will not be negative, this will be plus a only, this will be plus a only. Okay, so yeah, you can either write it like this, or another way you can write. Okay, another way to represent this is let me take this. Okay, not this, this. You can write y square equals to minus 4ax and a is positive. Okay, you can represent it like this also. Then also my x has to be obviously negative, right? X has to be negative. So either way, both way works. Both way works. Okay, so the interesting thing is that always it will lie on the left hand side, because y square has to be positive. Y square has to be positive. Y can be negative. Y can be negative because minus 1 whole square is 1. So minus 1 is negative, but the resultant square is positive. So y square has to be positive. So this whole quantity has to be positive. So if a is negative, then x has to also be negative. That's why I made it like this. So a is negative. So don't get confused. This confuse it as positive. This is a is minus 1 minus 2. This is negative. That's why it is lying over here. So what is a comma 0? Basically, when my y is 0. So when my y is 0, basically this is a vertex, so don't get confused. This is something other, something else, so you don't have to worry about this right now. Okay, then you don't have to worry about this. This is like the few terminologies about the conic sections. We don't need to study all that. Okay, those things are not required for game. Okay, so this is about the parabola. We have different type of parabolas also. This parabolas, right? So this is like x square equals to 4ay. This is like y equals to x square, like that. So we have already studied that. So here a is again positive. So if a is positive, this is something like this, x square equals to 4ay. Now in this case, right, like my x square has to be always positive. X square has to be always positive. So if x square has to be always positive and a is positive, so y also has to be always positive. That's why I am always lying above the x-axis, above the x-axis. Okay, here my x square is equals to minus 4ay. Okay, so x square has to be positive. Now a is a positive quantity, like you can assume anything. Okay, you can assume anything, but here I am assuming a is a positive quantity. So if a is a positive quantity, y has to be negative. So to make this overall positive, so that's why I'm always lying below the, always lying below the x-axis. Okay, in this case y has to be greater than 0. Okay, so I have got the point. Again, like you can choose, you can write like this, that x square equals to plus 4ay, where a is negative. You already assume that a is negative, then also y has to be negative. Okay, you can do it like that also, whatever suits you. Now next conic section is ellipse. Okay, what are ellipse? It is related like this, that x square by a square plus y square by b square equals to 1, where a square is greater than b square. That is very important. A square is greater than b square. If a square is greater than b square, my major axis will be x and minor axis will be y. Okay, like you can remember like this, a is greater than b, that is the x denominator is greater than the y denominator. Hence my major axis will be my x axis and minor axis will be my y axis, and the diameter of the major axis is 2a and diameter of the minor axis is 2a. Okay, and this is known as ellipse. Now if my a is equals to b, right, if a is equals to b, what shape we get? We get a circle, right? We get a circle. We get a circle. Okay, so yeah, this is what we get. Next, let me go to another ellipse. So this time, right, my b square is greater than a square. Basically the denominator of b square is greater than a square. That means it will be, the major axis will be y axis and minor axis will be the x axis. Okay, so yeah, this is basically for ellipse. I'm going a bit fast because these are not that important. Just revising a few things. Okay, again, this rectangular hyperbola, right? If there is a minus sign instead of a plus sign here, this will become a rectangular hyperbola. We have other variations as well, like y equals to 1 by x. That was also another variation. We have already learned that. Okay, so from here, this is a even function. Is this a even function? This already ellipse, right? This already ellipse. So this is symmetrical about y axis. So we can say this as even function. Here also we can say this as even function. Okay, you can say this as even function because what is happening? If I put x equals to a, this will be cancelled out and y will be equals to 0. So we'll start from here and go towards infinity. Okay, why we are going towards infinity? Because if I make x infinity, right? If I make x infinity, what will happen? Let me do one thing. So x is very high, right? X is tending towards infinity. So I can write this function as y square by b square equals to 1. Just hold on a second. X square by a square minus 1. So if x is very high, right, tending towards infinity, this 1 doesn't matter. Okay, this 1 doesn't matter. X is very high, so I can ignore this one. So basically, my y square by b square will simply be equals to x square by a square, right? So now what can I do? I can take the under root, right? I can take the under root. So my x is going towards infinity, my y will also go towards infinity itself. Okay, let me just show you. I can take the under root, right? So this will be plus minus b by a into x. So if x is going towards infinity, y will also go towards infinity, but it will depend, right? It can go towards negative infinity as well, positive infinity as well. Now what are the asymptotes in this case? What are the asymptotes? So the asymptotes, okay, asymptotes are something like this, right? This line and this line. What are these lines? Can you represent this in terms of equations? Yes, we can. So here these are the asymptotes, right? What are asymptotes? Towards the extremums, towards the extreme points. Extreme points means what? Where my x is tending towards infinity. So this is basically I like derive the equation here basically. So this is already written over here, asymptotes. So that's how this came, right, from this derivation. So here basically what is this line? This line is y equals to b by a x, right? Simple straight line, right? Simple linear straight line. Okay, the slope is just different in this case. And what is this line? This line is y equals to minus b by a x. The slope is negative because this is reducing instead of being increasing. Okay, so I hope you know basis of slope and differentiation, all those things. I hope you know, right? So yeah, that is what my slope is. Okay, and that is what my equation of asymptotes is, right? So this is the derivation of asymptotes. You just tend x tending to infinity, and then you find the value of y, and from there you will be able to find the equation of the asymptotes, right? Okay, so yeah, that was the derivation. Now just before going to a function, okay, mod function, I haven't taught you the mod function yet, so that is one important thing. Okay, actually basically these are the ends of the conic section, and I forgot to put the modulus function here. Modulus function will be taught in the next lecture. So if you know a bit about modulus function, you can plot this function, right? So first what you do, try to plot this, right? Then you try to plot this modulus of this. If you know already this, if you already know this, that will be good, right? That will be good. 2x minus 1 mod. Okay, please, okay. So this is what this is. So f of x is 2x minus 1 and f of x is x into x plus 1. So you try to plot these three functions, and in the next lecture I will start with these questions and more graphs, and then more about functions, more standard functions, and we'll end the topic of functions and graphs. Okay, so I hope to see you in the next lecture. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start with lecture 1b, the second lecture of calculus chapter. So in the previous lecture we learned about standard functions, what are actually functions, okay, what is the definition of functions, and we saw a few standard graphs from there. Okay, and yeah, those are important because if some basic question comes up, right, in gate examination, then you won't be able to solve those if you don't know the basic things. So those are also important. I know many of you haven't studied the basics. If you have, obviously you can watch this in 2x. So this also you can watch this in 2x if you have already studied the basics. Okay, this and the limits first lecture will you can also watching to x, right? If you are already accustomed with all of these concepts. But before starting this lecture, we have to solve the questions that I gave you in homework. So these were the questions, right? So I will tackle this modulus question later on. I will tackle these two questions. Okay. So this is very simple, right? Basically, for a straight line, you have to know two properties. Basically, its slope and its y-intercept, right? So what is y-intercept? Y-intercept is when my x is 0. So when is my x 0? X is 0. When is my x0? When I put my x0. So if I put my x0, y is equals to -1. Okay, put my x0, y is equals to -1. Okay, so -1, and its slope is positive, right? Positive, so hence it will be something like this, not like this. When slope is negative, the straight line is like this. When slope is positive, straight line is like this. Basically, this, what does this represent? This represents increasing. Slope positive represents increasing. As I increase my value of x, y should also increase. That is what this represents, right? And here it is 2. So if slope 1 is like this, then slope 2 will be like this. It will be more steeper. It will increase more faster because rate of change has increased, right? So it will be something like this. Okay. And what will be my x-intercept? X-intercept will be when my y is 0. When is my y 0? When I make the y 0. So if I make y 0, 2x minus 1 equals to 0. So x equals to 1 by 2. So x will be 1 by 2 here. So let me just change these points. This is my this is 0 minus 1. And this is 1 by 2 comma 0. 1 by 2 comma 0, right? Okay, so this is my x and this is my this is my x-intercept and this is my y-intercept, right? So yeah, this is basically straight line, and this is basically the plot of the first function, that is the 2x minus 1. Okay, and what is this? Basically, what do I call this? Y-intercept equals to -1, and x-intercept we have already found out. Only we need 2 points, right? 2 information we need, and that is enough. Sorry, I forgot 1 point. Yeah, we need, actually you can do it with slope also, or you need 2 points. So you can take x-intercept and y-intercept. Okay, for a straight line you need 2 points. Intercept. Okay, which is equals to 1 by 2. Okay, so yeah, that is it basically for this function. I will come to this function later on. Let's come to the third one, right? Let's come to the third one. So let me just copy this one up. Paste this. The third one is actually pretty interesting. We generally solve this using a method known as wavy curve method. I've already solved this in one of my, I've already explained this in one of my control systems lectures, so you can refer to that. Okay, or you can look it up in YouTube or somewhere else. What is a wavy curve method? So basically, right, wavy curve tells us about the what do you say, the sign of the function. Wavy curve method tells about the sign of the function when we have a factorized form like this, right? When you have factors, right? When you have factors, basically. So what we do, we have to find out the sign of this, right? That is what I'm interested in right now, because plotting this will be difficult for me. Plotting this exactly will be difficult for me. I will try to find the rough sign, whether this will be positive within certain range or negative, and after that I will plot the graph. Okay, obviously exactly plotting is not possible for me. That's why this is known as wavy curve method. Why, I will explain. So basically, now what are the roots? What do you mean by roots? Roots is when this function is equals to 0. For what values of x this function is equals to 0, those values will be called as roots. Okay, those values will be called roots. Okay, now if those values is called roots, so this will be equals to this, right? This will be equals to, okay, and now what next? Now I will obviously mark the roots over here in this number. This is a number line, right? This is, let's say this is the number line, this is the x-axis. Okay, everything is recording, right? This is recording, and this is, yeah, this is also recording. This is my x-axis, right? So this is my x-axis. Okay, so I'm varying, I'm going from -1. -1 is one of the roots because x equals to -1 equals to 0, and then I have 0 also another root, and also I have 1 also another root, right? 1 is also another root. So if -1, 0 and 1 is also another root, then what does that means? That means basically at this juncture, right, the sign changes. Okay, all of this I've explained in my Voivika method. You can watch that video. Okay, so if you have studied control systems, you will know. So basically now from where to start? I will start from the leftmost root. So I will try to find out what is the sign before this -1 point. Before I go, like I'm moving along this direction, okay, what is my sign before this -1 point, right? So just let me bring this more closer to me. So the sign before this, right, if my x is less than -1, x is less than -1, if x is less than -1, then obviously this part is overall negative, right? This part is also negative because less than -1, -2 I can pick, which is negative, so this is also negative, and obviously this is negative anyways, we're subtracting, so this will be negative anyways. So these three, right, these three are negative anyways. So negative times negative times negative is what? Is a negative number itself. Okay, I'm getting a negative number itself. So I'm getting a negative number. That means that obviously for x lower than -1, right, I will get a negative. Right? Now for x higher than -1, what is happening over here? For x higher than -1, the sign will change. Okay, because I have got single factor, right? I have got single factor over here, the sign will change only once. Okay, if this was, let's say, x plus 1 whole square, then sign would remain same. Okay, that is important point. Obviously we have to check the overall sign also, that is also important, but if this one was x plus 1 whole square, the sign will change. But as this is e odd, right, only single element is present, only single factor is present, sign will change. So sign will change to this will be plus. Okay, and then what will happen? Then again we encounter at 0, again we encounter a root. Whenever we encounter a root, the sign again changes. Okay, the sign again changes. Again this will go on like this. Okay, this will go on like this, and again the sign will change as I encounter another root, and this time, right, sign will remain constant. Okay, sign won't change again, sign will remain constant. Okay, so yeah, this is the case. So basically this is -1, 0, 1, and these are my curves. So how will my graph look like? Roughly, right, roughly my graph will look something like this. I will explain. Roughly I can write it -1, this is 0, and this is +1, right? So roughly what will happen? Before -1, this will be negative, right? So this will be something like this. Just hold on a second. And around 0 it will remain positive. Okay, and after 0 again it goes to negative. Okay, and then again it is positive, right? It will go till infinity. So if it goes till infinity, it will be something like this. Okay, it will be something like this. And here also it comes back. It comes from negative infinity, so it will be something like this. Okay, as is the cubic equation, the graph will something look like this. Okay, now this is obviously a rough plot, this is not exact plot, but this is a good approximation what we can say, because in between this range, right, this will always be positive. Between this range 0 to 1, this will always be negative. Okay, and after this one, this will always be positive, and it will go to infinity, and before this -1, this will always be negative, and it will go to -infinity. Okay, so this is how my plot will be. So this is also another way to plot a graph. Okay, so yeah, this may not be that much needed, but this may be needed in signals and systems, also in some concept, right? This may be required. Okay, this skill may be required. So let's start with today's lecture. So first we'll start with functions and graphs. Whatever missing functions we couldn't cover in the previous lecture, we'll complete those, and obviously we'll end this with graphical transformations. So the first function is greatest integer function. So basically, what is a greatest integer function? Let's read the definition. Greatest integer less than or equal to x. So this is the symbol of greatest integer function. okay, they will always mention that it is a greatest integer function if x is written in square brackets. Most cases they will always mention this. Okay, this is known as GIF. They may write in short form GIF, and the definition of this is greatest integer less than or equal to x. What do we mean by this? We mean that immediate previous integer, if x is not an integer, okay, anything else than integer, x is not integer, then it will be the immediate previous integer. Immediate previous integer. What do you mean by that? Let's say I have 1.23. Is this an integer? This is not integer. If this is not integer, I will take the immediate previous integer of this. Okay, the integer less than this. Greatest integer less than or equal to s. What is the greatest integer less than or equal to this? What is the greatest integer less than or equal to this? This is 1, right? So our greatest integer of 1.23 will be 1 only. Okay, basically this is known as a floor function. Okay, floor function, right? Why is this called the floor function? Because I'm ignoring the floor parts, right? I'm ignoring the floor parts. I'm ignoring the fraction parts. I'm only taking the integer part. Okay, that's why this is known as a floor function. Let's take another example. 1.87. 1.87. What will be the greatest integer of this? The greatest integer of this will be 1. Okay, greatest integer will be of this one because I'm ignoring the floor. Okay, now let's take another great example. Minus 1.56. Now, what will be the greatest integer of this? You might say I will just ignore this floor and I will just take -1. You are wrong. The definition is this, right? Greatest integer less than or equal to x, or when immediate previous I will take the immediate previous integer if x is not equals to x, x is not equals to integer, and I will take x itself if x is equals to integer. Okay, so now the important point is here, is my x integer? No, x is not integer. So x is not integer, first point gone. So I will have to pick from this. I will have to pick the immediate previous integer. What is my immediate previous integer? My immediate previous integer is -2, not -1, right? -1 is ahead of me. So in the number line, if I check, this is -1, this is -2, and -1.56 is lying somewhere in between. So -1 is ahead of me and -2 is behind of me. So I will pick the previous integer, not the integer in front of me. So obviously this will be the greatest integer of this will be -2. Okay, -2. So yeah, this is the point where students tend to get confused with the negative numbers. So need to clear this one up. Now next is, let's say I have 2. What will be the greatest integer of 2? It will be 2 itself because it is an integer. If it is an integer, don't need to think anything. It will be directly x. Okay, so these two are the important points of the greatest integer function. So the graph of greatest integer function looks something like this. Okay, so you might see something like this is open circle, this is closed circle, this is closed circle, this is open circle, closed circle. So basically your open circle, right, these are denoted by open circles. And what do these represent? This represent This represents that it will be excluded. It will be excluded. And what about closed circle? So closed circle will be basically the points which will be included. What do we mean by those? Basically, if this is open circle, right, so this is not included in the curve. So this 0, right, is not included at x equals to 1. So this point is included. So I'm suddenly jumping, right? So this point is included, which is equals to 1. So 1 will be included at x equals to 1, and it will not be included as this is a function, right? This is a function, only 1 point. We should get only 1 point, that is with the vertical line test. That's why, right? That's why. Okay, so yeah, this is what we mean. This is included. So a closed circle means it is included, and an open circle means this is excluded. This point, this 1, right, y equals to 1 is not included. This point is not included. We are including this point. Okay, so basically what, let's analyze this graph. So here, right, if I'm lying between 0 to 1, you can see my greatest integer function is always equals to 0, always, and that was expected, right? As I'm lying between 0 and 0 is also equals to 0 itself. And if I'm lying between 0 to 1, it will just cancel out the floor part, right? Cancel out the floor part, and I'll be only remained with this 0. If I lie between 1 to 2, it will always push it down to 1. Okay, whatever the value is, it will always push it down to 1, except when my x is exactly equals to 2, then I will suddenly jump up to 2 itself. Okay, so this is what this greatest integer like graph of this greatest integer function is. I don't think there is much explanation needed. I've already explained this very well. So another similar thing like greatest integer function is the fractional part of x. So what is the fractional part of x? Basically this is denoted like this third brackets. I don't remember what brackets these are called. So this fractional part of x equals to x minus greatest integer of x. Basically whatever the fractional part is left, right, that is the fractional part of x. That is what this name suggests. So let us take few more examples, and from there we'll understand. So let's say I have this 1.6, right, 1.86. Now what will be my fractional part of x? My fractional part of x will be 0.86, right? My fractional part of x will be 0.86. Because why? What is my, like x is 1.86, what is my greatest integer function of 1.86? It is 1. It is 1. So 1.86 minus 1 is 0.86. That is what I am getting, right? Now let's take the negative example. From there you will understand this more better. 2.47. Okay. Now what will the fractional part of this? You will say 4.47. Then you will be wrong. The fractional part of this will be 0.53, and it is always positive. Okay, fractional part is always positive, and it always lies between 0 to 1. Okay, so fractional part always lies between 0 to 1. So this is one thing that lies between, because I am only taking the fractional part, right, and it can only lie between 0 to 1. Between, it is a fraction, right? Okay, so it always lies between 0 to 1. So it always lies between 0 to 1. What does that mean? So now I said you, right, it won't be 0.47. Why? Let's use this formula. So this is minus 2.47, and what is the greatest integer of minus 2.47? It is minus 3. So this becomes minus 3. Minus into minus, it becomes 3. 3 minus 2.47. 3 minus 2.47 is 0.53. Okay, 0.53. So that is why just be careful with negative numbers. Whenever there are negative numbers, just be careful with that. Okay, so it will lie somewhere around here, right? So if it is 2.47, it will lie somewhere around here. Okay, so no, it will lie somewhere around here. Okay, lie somewhere around 2.47 will lie somewhere around here, right? So yeah, I have got the point. It will always lie between 0 to 1, and this is the fractional part. There is nothing like fancy to this. Now next is modulus function. We already know this. We have already studied this previously, in our class. I mean in our school. So just giving you just a quite brief thing, that modulus function is represented like this: mod of x, okay, equals to this thing. So it will be equals to minus x when my x is lower than 0, so that it can make it positive. Okay, my modulus function will always lie above y-axis. Okay, if I take the mod of anything, it makes it positive. Basically absolute value, it makes it positive. Absolute value, it will make it above the x-axis, sorry, not y-axis, above the x-axis. So it multiplies a negative sign so that it can make this negative x positive. Then for 0 it is obviously equals to 0 itself. Then if my x is greater than 0, it will be x only. It will not change anything. So that is the definition of modulus x, right? So if y is equals to x, right? If y is equals to x, then the modulus of y equals to x will be this, because the negative portion becomes positive, symmetric about y axis, symmetric about it flips this to y axis, and my modulus function is always symmetric about y axis, because this is the even function. This is the even function. Okay, because if we simply do f of minus x, you will get the same function back again. Okay, f of minus x and f of x will be same, so that's why this will be even function. So this is an even function, and this is symmetric about y-axis. It will be symmetric about y-axis, right? So that is one thing. Also, any other things you can notice. You can notice that if my y is equals to x, right? Y is equals to x, then there is a very sharp turn around here. There is a very sharp turn around here. Okay, and this is important in the differentiability chapter, not here, in the differentiability chapter. Okay, sharp Okay, short term. So yeah, this is the case basically. So now right now your function short term. Okay, let's solve the quotient. Okay, like there is another definition for mod of x. Basically, mod of x can be written as maximum of plus x and minus x. So like whatever is inside this modulus function, I will keep this as it is and then multiply a minus 1 sign with it. Now whichever will be maximum out of those two. For a negative number, let's say minus 1. For minus 1, what is maximum? Minus 1 or minus 1 into minus 1 plus 1. So plus 1 will be maximum, so I will take plus 1, right? So basically it makes the negative value positive. Okay, that is what this does. So obviously here what will happen, these, right, these, like this is what, this is y equals to plus x and this is y equals to minus x. So basically this, right, this and this I can cancel out, this and this I can cancel out, right, this and this I can cancel out. If this and this I can cancel out, then obviously I will be only left with this, okay, which is I got in the previous case, okay, which is I got in the previous case. So yeah, let's like solve quotients of the modulus function, then I will come back to this. Okay, then I will come to the next part. So yeah, this one was the graph, right? So what do I have to do for negative values of y? So what do I want to do? Basically I want to plot the modulus of this, modulus of 2x minus 1. Okay, so you try to do it by yourself. Basically what does modulus function does? A modulus function basically makes the negative values positive. That is what the purpose of a modulus function is, right? So the positive values will remain as it is, will not do anything with them, but the negative values I will just multiply a minus 1 side with it, so that whatever the value, magnitude won't change, but the sign will change. It will become positive instead of negative. So I will just copy this graph. Okay, copy if I can. This whole day feeling very sleepy. Okay, so let me just color this differently. So here, right, so which portion is negative? This portion, right? Obviously what is the negative portion here? This portion, right, where my y is negative, this portion is negative. I just need to flip it from this point, so this also becomes positive. Okay, and all the points will remain same. So this will be something like this. It will flip it over, right? It will flip it over. Okay, so yeah, this is basically this point. These are basically these points, right? These are basically like this is the modulus of that. So this is how we plot this. Okay, I hope we got the point. Basically this is just flipping the negative portion in the positive portion. All the values, magnitude will remain same, just the sign will interchange. Now this, instead of being minus, will become plus, right? It will become plus 1. Okay, it will become plus 1. So yeah, that was the plot. So let's now continue with our functions. So next, what is next? Next is a key point to again define the ranges. So we can write the ranges using the closed interval, open interval, that format also, using this format also. How? Let's say if my x is lying between -1 to 1, x is lying between -1 to 1, how can we represent that? So basically I can represent it in a single format, that is my mod of x will be less than 1, not equals to less than 1. How can we say this? So this mod of x includes both -1 and 1. Okay, this mod of x includes both. How? Basically If I write mod of x equals less than minus 1, what does this represent? If I put x equals to minus 0.5, if I put x equals to minus 0.5, and x equals to 0.5, right? Are these two, the mod of x values for these two are same, right? These are satisfying. Okay, so this will satisfy. So again, this is lying in this range. Minus 0.5 and 0.5 is lying in this range, right? Now if I pick x equals to minus 1.5 and 1.5 plus 1.5 and minus 1.5, so again mod of x will be 1.5 itself, so which is not satisfying, which is okay, right? So like this you can understand, right? So this one single mod of x is including this minus 0.5 and 0.5 also, so negative and positive is including both. So if something like this is written, so we can write it like this, or something like this is written, this represent x, right? So you can go both ways. Now if I write x is varying from minus 1 to 1, okay, I have made a mistake, it should be equal over here, right? This should be equal over here. Now if this is equal, obviously the difference will be mod of x will be less than equals to 1. Okay, mod of x will be less than equals to 1, right? Now if x is greater than 1 and x is less than minus 1, if x is greater than 1 and x is less than minus 1, what does that mean? That means that here this is union. Okay, x greater than 1 or x less than minus 1. Okay, so what does this mean? This means that it is going towards minus infinity it is going, and this is going towards plus infinity, and it is greater than 1. Okay, so 1 to minus 1, this range, right? This range is not included here. This range is not included. This range was previously included. Now this range is not included. This range is excluded, right? So how can I write it? So basically what I can write, if my mod of x is written like this, that what do I have to think? So I have to exclude minus 1 to 1. I have to exclude this. Okay, everything else is included. So I will just do the opposite of this. So I can write mod of x greater than 1. So if I write mod of x greater than 1, what does happen over here? So if I write mod of x greater than 1, basically I'm including 2 points, minus 1, 1, minus 1.5, 1.5, minus 2.5, 2.5. So yeah, those are true. Okay, for x equal to minus 1.5, this equation is satisfying. For x equal to 1.5, this equation is satisfying. For x equal to minus 2.5, this inequality is satisfying. For x equal to minus 3.5, this inequality is satisfying. For x equal to 3.5, this inequality is satisfying, right? So for x equals to minus 0.5, this inequality is not satisfying. That's why my x can't be minus 0.5, which is fine because we are not including this range. Okay, so again you can write it like this, basically the opposite of this. Again, if we're including x and minus 1, the slight difference will be mod of x will be equals to 1. Okay, that is just the simple thing. I won't go much deeper into this. Okay, so next is the signum function. This is mainly used in signals and systems, and this is also known as sigmoid function, right? Sigmoid function. Okay, that is very important function in artificial intelligence. So if you study about that, you will understand. So it is also known as sigmoid function. Okay, also it is known as sine function. If I am able to write this, also it is known as sine function, right? So I have sigma, this is sigma of x, and this is like defined if x is positive. If x is positive, it is equals to plus 1. So here, right, if x is positive, it's equals to x itself. But if here x is positive, it is equals to plus 1. It just gives me the sign. If x is equals to 0, it will give me 0, so it has no sign. If x is negative, it will give me minus 1. So it will tell me the sign of the value whatever is inside this signum function, right? Whatever is inside this signum function. So if y is equal to signum of x, basically this is open circle, right? So at x equal to 0, it is not equals to 1, it is not equals to minus 1, it is equals to 0 itself. That's why these are open circle and this is closed circle. Okay, now if x is greater than 0, obviously it is positive number, so it will give me output as 1. If x is less than 0, obviously it is negative number, it will give me output as minus 1. Okay, minus 1. Okay, now what is the alternate definition of signum of x? Okay, so basically sigma of x equals to x by mod of x, right? X by mod of x. You can define it for yourself. Basically this, right? This modulus of x, what does this does? It makes it positive always. It always makes it positive. And here, right, if x is positive, this will be x only. If x is negative, this will be something minus 1. So let me give you example. So let me take minus 1. So if I take minus 1 over here, in the numerator there will be minus 1. In the denominator there will be plus 1 because it makes it positive. So minus 1 by plus 1 is 1. Then again, let me take another example. Minus 5. So if I take minus 5, in the numerator there will be minus 5. In the denominator there will be 5. So minus 5 upon 5 is minus 1. So we get the sign. Basically, we only need the sign. That's why I'm dividing by x itself. But the modulus function helps us in decoding the sign also. Okay. So you can use this. Obviously, if x is equals to 0, we can't divide by 0. Okay. Why? It is an undefined value. That's why x is not equal to 0. If x is equal to 0, we directly define sigma of x is 0 itself. And the same thing for this one. Okay. I won't go too much into the details of this. Okay. So these are the few questions. What I will recommend you to do is take this as homework. Plot the following functions. Okay. The sigma of x, the greatest integer function of this sin x, and the sigma of this, right? We have already plotted this previously. And sin x, we know, you know already, I hope. If you don't, we are just studying in the next few slides the trigonometric functions. You can see from there. I'm giving you all this as a homework, right? All this as a homework. Now let's understand the trigonometric functions. So what are the trigonometric functions? Trigonometric functions are the sine function, cosine function, tangent function, cotangent function, okay, sec function, cosec function. Then we'll study about the inverse trigonometric functions. Okay, so sine, everyone knows. Like all of you are mostly all of you are from electrical background. Our students are mostly from electrical background. So sine, I hope you already know this. Okay, sin x is something like this. Okay, it is not a polynomial function. And also, what type of function is this? Is this an odd function or even function? As you can observe, right, it is symmetrical about the origin. If it is symmetrical about the origin, this will be odd function. Okay, this is equals to sin x. Okay, and it is basically odd function, right? It is basically odd function. It is basically odd function. So this is a odd function, right? Okay. So also, like, what is the period of this? This is a periodic function. What does a periodic function mean? Periodic function means whichever repeat itself after a certain time. So let me just quickly write a few things. So periodic function, right? It repeats itself after a certain period. So all these, right, trigonometric functions are periodic functions. Here you can see that it is repeating after every 2 pi. So 2 pi is radians. This is in radians, right? So I hope we already know these basic things. So 2 pi is in radians, and this repeats itself after every 2 pi value, right? 2 pi value. Now, what are the points to note over here? The points to note over here is what are my zero crossing points? What are my zero crossing points? So my zero crossing points are this, right? Minus pi, 0, pi, 2 pi. All these are zero crossing points. Okay. So basically, it is an integer multiple of pi. It is an integer multiple of pi. So what are my zero crossing points? So zero crossing points are sin x equals to 0. So x equals to n pi, or for all n, right? X equals to n pi for all n. Okay, where basically my n has to be integer. Okay, I should write this for all, right? For all, I should write here for all x where my n is basically integer, right? N is integer. Integer is represented like z, and like basically it will be 0, 1, 2 and so on, right? It will be 0, 1, 2 and so on. Okay, So this is one of ns. And also another important one note here is that my sin x function will always lie between -1 to 1. Okay, it will always lie between -1 to 1. Okay, and it is oscillatory in nature. Okay, it is never settling, because as we increase x, there isn't any constant value. It is never settling, it is oscillatory in nature, right? So my sin x will always lie between -1 to 1. Okay, this is also another important point. Okay, next is cosine of x, basically cos x. If you remember cos x, now like this is equals to cos x, f of x is equals to cos x. And what type of function is this? What type of function is this? This is a even function, right? Even function, because this is symmetrical about the y axis, not about the origin. Symmetrical about the y axis, right? Like as you can see, right, if I split it into two parts, this and this part will be same, right? Same only. So this is symmetrical about the y axis, and obviously my cos x will also lie between -1 to 1. -1 to 1, right? My cos x will also lie between -1 to 1. Okay, so this is the case. Next is tangent of x. So what is tangent of x? So tangent of x can be written also as sine by cos, right? Sine by cos. So tangent of x, I can write, use some other pen. Okay, so my f of x is equals to tan of x. So again, right, what is this? Is this even or odd? You can see, right, if I break it this down about the y axis, this is not same again. But if I see about the origin, I can see this is going in this direction, this is going in this direction, and they are about symmetrical, right? So obviously this is an odd function. This is an odd function. You can prove it with the mathematical proof as well, whatever mathematical relationship I have given you, right? So but like we can observe from the graph itself, this is an odd function. Okay, this is an odd function, right? So this is an odd function. And what is the period of this? So this period, right, this has the period of 2 pi. This has the period of 2 pi. Again, what are the zero crossing points? The zero crossing point this time are not n pi anymore, they are n pi by 2. So I will explain those, just hold on a second. The period of this, right, two pi. The period of this is 2 pi. And what are the zero crossing points? This time the zero crossing points are different. Oh no, I wasn't able to copy. Cos x equals to 0. So if cos x equals to 0, that means basically my x has to be n pi by 2, right? So if my x is n pi by 2, okay, and also it can't be, okay, what am I missing over here? N plus 1 pi by 2. I can write yeah, n pi by 2. This is 3 pi by 2. Yeah, fine. But this can't be 2. Previously, did I do something wrong over here? No. These are only pi only, right? Yeah. Pi minus pi. Okay, it can be negative as well. Sorry. Okay, it can be negative as well. I missed this point. -1, and like from minus infinity to plus infinity, all of them are integers here, right? So yeah, that is this. And what about this? I can't simply use here integers. I have to use what? I have to use odd integers. I have to use odd integers, right? So how will I use odd integers? That is what I'm saying. So there will be 2n plus 1. So I should write this like this. So these are all odd numbers. So even if I pick something, right, like this, they will still be odd, because n equals to 1 is 3, n equals to 0 is 1, right? So all of this will be odd only. Okay, so x is 2n plus 1 pi by 2, n belongs to integer, this, right? N belongs to this. Okay, and like yeah, these are the zero crossing points for a cos function. So only the odd multiple of pi by 2, only the odd multiples of pi by 2. Like this is also another thing, these are basically the even multiples of pi by 2, even multiples of pi by 2, because 0, okay, or you can say pi, even multiple pi by 2, 2 times pi by 2 is pi only, right? So I can like see here in words, even multiples of, like I can further express this, right? I can further express this like this, 2n into pi by 2, the same thing, and like 2n will be always a even number. So this is known as even multiple of pi by 2, even multiple of pi by 2, and this is known as odd multiple of pi by 2. Okay, so this is how also you can say this in words. So let's come back to the tangent function. Basically, what are these? These are asymptotes, basically, plus infinity and minus infinity. So these are asymptotes. Asymptotes we have already learned in Bode plots, I hope. Like asymptotes we have already learned in Bode plots, right? So these are asymptotes, and this is f of x, and this is tan is equal to sin x by cos x. Okay, and this is odd function. All this we know, and this is a ratio between sin x upon cos x. So if you just put this pi by 2, right, at pi by 2, what happens? My cos x goes to 0. It is basically odd multiples of pi by 2. So cos x goes to 0. Now what is my value of my sin? For minus pi by 2, it is minus 1. So that's why it tends to go to minus infinity. Okay, minus infinity. But just here, right, just here if you observe, it tends to go to plus infinity. So let me take the zero example, x equal to 0. So not sorry, okay, we can take x equal to 0. We have to take this only. So if I just before minus pi by 2, it is going to plus infinity. Just after minus pi by 2, it is going to minus infinity. Why is this the case? This is the case because my cos pi by 2, my cos pi by 2 is what? So here, right, just before it is negative, just after it is positive, right? Sine is not changing its sign, basically. Sine at pi by 2, right, it is always negative. It is always negative. Sine pi by minus pi by 2 is always negative. So just after this becomes positive. So if this is become positive, so negative upon positive is something negative itself. So I'm getting negative just after minus pi by 2. Just before minus pi by 2, my sine is negative, but my cosine also becomes negative. So negative upon negative becomes positive, and cosine is very small number, very small number. So something constant divided by very small number tends to infinity. So this is tending to positive infinity. So just before this and just after this, in the neighborhood of minus pi by 2, the two values are not equal. Why am I stressing this much? Because this is important. This will come in handy. Okay, so yeah, this is one thing. And what is the period of this? The period of this is only pi. Okay, because this is repeating from pi by 2 to 3 pi by 2, you can say, or from this 0 to pi, you can say, right? So the period of this is pi, not 2 pi. That is important. The period of sine, like period of this, right, period of this is the period, this is the period cosine, and the period of tan is only pi itself. Okay, period of sine is pi itself. Okay, so yeah, this is the thing that I wanted to say. Now like these are the things we will learn more about this in the limits chapter, okay, in the limits chapter. But what are my zero crossing points? What are my zero crossing points? The zero crossing points will be basically whenever my sign crosses 0. Okay, so whenever my sign crosses 0, it will also have zero crossing points. So basically it will be ditto same as this, because cos x anyways at that point of time is non-zero, so it doesn't matter. The denominator 0 should not come. That is the most important part, right? So basically I'll just change one thing. My tan x has to be 0. For tan x has to be 0, sin x has to be equals to 0. Okay, so sin x has to be equal to 0, and like from there you can further solve this. Now let's come to the cosec function. Just hold on a second, I have to drink a bit of water. Yeah, sorry. So just a bit tired. So let's come to the cosec function. What is cosec function? Cosec is basically 1 over sine. It is 1 over sine x, right? So it is the like the inverse of this, reciprocal, not the inverse, reciprocal of sine x. So it is reciprocal of sine x. So what can we say? That if my sin x is odd function, then my cosec x will also be odd function, right? As we can observe from here also, because it is symmetrical about the origin, so it will be an odd function. Okay, it will be odd function. Okay, so my sin x varies from what to what? Sin x varies from -1 to 1. So it takes all of the points, at all of the points -1 to 1, that also includes 0. So if sin x is varying from -1 to 1, then what will my cos x vary? It will vary from -1 to infinity, because 0 is included, right? 0 is included. So -1 to -infinity, +1 to +infinity. So it can vary like that. So here this is +1 to infinity, +infinity. Then this is -1 to -infinity. I have got the point, right? So like I'm not explaining this further, this will just waste our time, so I'm not just wasting our time, right? So further these things you can do it for yourself, like observe for yourself. I'm just showing you the graphs. What is sec x? Now what is sec x? Sec x is 1 over cos x. 1 over cos x. Now if it is 1 over cos x, the period will remain same here, right? The period will still remain same, right? Period is still 2 pi, okay, because sin x has period this, and this also will have same period, right? This will also have 2 pi, okay, but as cos x is even, this will also be even function, symmetrical about the y-axis, okay, symmetrical about the y-axis. Further things you can like do it for yourself. Then what is cotangent of x? It is basically cot x, and cot x is basically equals to 1 by tan x. Cot x is basically equals to 1 by tan x, right? Cot x is basically equals to 1 by tan x. So it is equals to 1 by tan x. So basically, right? Basically, what is the period? Period for this will also be same only. It will be equals to pi only, right? It will be equals to pi. It will be equals to pi only. Okay, so f of x is cot x. Okay, so basically what next? So these are the asymptotes we already know, and like my tan x is varying from -infinity to +infinity, so cotangent will also vary from -infinity to +infinity, because 0 is also included, -infinity is also included, so 0 will also come along here. Okay, so I'm not like explaining these things, you can understand this by yourself, right? So let's go to next few things, right? Next few definitions. So what do you mean by undefined value? Undefined means we can't define those things. Can you define infinity? What is the value of infinity? What is infinity? Can you say? I might say infinity is 10 million, 10,000 of million, 10 billion, billion. Okay, so I can't define infinity. That's why it is called as undefined value. So how can I like express this undefined value? Can I express this? So like tan x, right? Tan x or cot x is going to infinity. So like if my f of x, if my example if my f of x is equals to tan x. Now, can you tell me what will be my f of pi by 2? What will be f of pi by 2? It is equals to positive infinity, if you recall correctly. If you recall correctly, you just put the value of pi by 2 in your calculator anywhere. Okay, anywhere you put pi by 2, tan of pi by 2, you will get undefined. Okay, so basically this is known as undefined value. But can we quantify this? So how can we quantify? We can quantify like this, that I have, let's say, anything at the numerator, 1 I can take anything I can take at the numerator, and below 0. Now this is not exactly equal to 0, this is tending towards 0. Okay, from the positive end, 0.001, 0.0001. okay, so if my 0 is very small, 0 is very small, right? If my 0 is very small, basically let's say this is 0.01, okay, or this is 0.000001, what will be the value? It will be very large, right? It will be very large, okay, because this is in the denominator. So you reduce it further, you try to go more closer towards 0, you will almost reach infinity, but you can never touch it. Okay, you can never feel it because it is undefined, it is not defined. Okay, so yeah, I have got the point about the undefined value, and this concept, right, this concept will be used in limits. We'll go to limits, and from there we'll understand. Now, what is oscillatory value? Oscillatory value means it is finite. Here that this was infinite, it is finite. We can quantify that 2, 3. We can quantify those things, but it is uncertain. What do you mean by that? So like, let's take an example. If f of x equals to cos of 1 by x minus 1. Okay, f of x equals to cos of 1 by x minus 1. Okay, then now what will be f of 1? So this, right, this will be cos of infinity with something very high value, which is never stopping. Now what is cos of infinity? Like this is x equals to 1, right? This is 1 over 0, which is tending towards very high. Now let me come back to the cos graph. Now this cos, right, this is the x-axis, and this, if I move more towards right, the more I move, that it will move closer towards infinity. Obviously I can never reach infinity, but it will move more closer towards infinity. Now I am moving more towards right, and this is also varying, right? This is keep on varying, right? So I don't know what is the value of that. I don't know where I will stop, because I'm moving more infinity and I can never touch the infinity. I'm moving on the right hand side, but I can never touch it. I will never stop, basically. I will never stop. So this is like this only, okay, and this graph is like this. So, but what is the important point? One thing sure I know, that it has to lie between +1 to -1. It will lie between +1 to -1, but I don't know where exactly it will lie. But I know, like, it will lie between these 2 points only, because I'm always moving on the right hand side. So I'm moving along this curve, right? So it cannot go beyond +1 or below -1. So that is what I know. So so from this expression, right, what I can conclude? I can conclude that this will lie between -1 to +1. That is for sure. But where it will lie, I don't know. So this is oscillatory nature. Okay, this is oscillated, right? So this is the case. Now let's like these 2 points I wanted to give you a quick feedback of. Now let's come to inverse trigonometric functions. Okay, so trigonometric functions are many to one, so the inverse cannot be determined. Okay, so basically what do you mean by this? So what is the point here? So like, let's say I have a y equals to sin x, right? Y equals sin x. What does inverse mean? Inverse means basically, if I take the inverse of this, my x will be equals to sin inverse y, right? Okay, x will be equals to sin inverse y. That is the main point of inverse. If I take the inverse, right, so x and y, I'm taking the inverse of sine, so I'm taking inverse trigonometry, so x will be equals to sin inverse y. So my x will be angles and y will be basically my output, input, right? Y will be input this time. So if I say y is equals to 1, what will you say to me? If I say y equals to 1, what will you say me? So what is sin inverse 1? Sin inverse 1 can be what? Let's go to the graph here again. So if I see, when is my sin 1? Sin is 1 here, minus 3 pi by 2. Sin is 1 here, pi by 2. Sin is 1 here at, 5 pi by 2. Okay. So sin is, sin is 1 so many times, right? So many times. So what will be your answer? Because if I want to say what will be sin inverse 1, what will be sin inverse 1, right? So what will be my sin inverse 1? So basically you can say it can be pi by 2, every 2 pi it is repeating, right? It can be 5 pi by 2, it also can be minus pi by 2, all those things it can be, right? But what is the problem over here? I can only get one output, right? But I need only one output, because for a valid function, for a particular input, this time, right, y has become input, right? So very important, don't get confused. So this is my output and this is my input, but as soon as I take the inverse, this becomes my output and this becomes my input. Okay, so here, right, I for a single input, I am getting multiple outputs, okay. So for a single input I am getting multiple outputs. That is very important, right? So this can't be function, because the definition of function was for a single input I should get a single output only. Okay, the output can be same for different inputs as well, that is fine, but I should get a single output only, not multiple outputs. So not function, can't be called a function. Can't be called a function, right? Can't be called a function. Okay, so yeah, this is the case basically. So that's why, hence we have to restrict our domain so that function is one to one within that domain. Okay, what do you mean by this? So if I restrict that, this, right, y, I can give only basically this x, right? If I restrict the domain of this x, like I'm talking about this function now, if I restrict this to 0 to 2 pi, if I restrict this to 0 to 2 pi, then what, or like minus pi by 2 to pi by 2, whatever you choose, like one period only you should choose, because this is repeating, right? This is every time repeating. So if I just choose one period, I'll be able to exactly have a one-to-one mapping. So right now, if I can say I'm restricting my domain from minus pi by 2 to pi by 2, so then what will be my value of sin inverse 1? You will say it will be equals to pi by 2 only, because I can only give pi by 2 input to this initial function, right? Initial function I can only give pi by 2. It will pi by 2. So if I say what will be my sin inverse 0, it will be 0 only, because I am restricting my domain to minus pi by 2 to pi by 2, right? Minus pi by 2 to pi by 2. Okay, here I explain this in short. Okay, you can see, right, I am restricting my domain. Okay, because as you can see, like if I just don't restrict my domain, then what will be sin inverse of 0? It will be even multiples of pi by 2 or integer multiples of pi. So at pi, 2 pi, 3 pi, 4 pi, these will be my solutions for sin inverse 0. But obviously that is not possible. There has to be like one input can only map to one single output. It cannot map to two outputs, right? That is not possible. That's why we are restricting our domain. Here we have restricted our domain so that when we take the inverse, we will get a one-to-one mapping. One-to-one mapping, right? One-to-one mapping. I hope you got the point. You just search one-to-many mapping. One-to-many means for a single input, I'm getting multiple outputs. Many-to-one, that means for many inputs, they may map to the same output. That is fine. Okay. For f of minus 1 equals to 1, f of plus 1 is also equals to 1. That is fine. That is not an issue. Okay. Vertical line test, right? Remember vertical line test. But for this one to many, that is a problem. For a single input, I am getting two outputs. That is a problem. So that for the to avoid that, we are restricting our domain. So these are the domains for the trigonometric functions. You can go through this, right? And yeah, that's why, like, obviously we know that x can vary from -1 to 1 only, because I am taking the inverse this time. So sin can only vary from, sin x can vary from -1 to 1. So like the inverse, the whatever we can vary from -1 to 1. Also we have restricted our output also from pi by 2 to -pi by 2. Here also it is restricted from 0 to pi. Okay, so you can just check the graphs. Okay, I won't go too much in depth to this graphs. You can just check the graphs for yourself, and this will help you quickly revise everything. You can understand that how is this coming, how is this coming, that you have to understand for yourself. Okay, next is the exponential functions. So exponential functions are there are two things. One is when, like, it is a raised to power x, when my a is between 0 to 1, and when my a is greater than 1, right? A is greater than 1. Okay, so basically if my a is between 0 to 1, what happens over here? So let's say I'm doing minus 0.1, right? 0.1, not -1, 0.1 whole square. So if it is 0.1 whole square, this is x, right? This is x. So if it is some positive value, this will reduce it further. So whatever my value of x is, right, it will try to reduce it further. So this raised to power 0 will be 1, and after this, right, after if I increase this raised to power 1, this is 0.1, this raised to power 2, this is 0.01. So this is reducing. So this will always be lower than 1. This will always be lower than 1. Okay, and up here what is happening? If I write 0.1 raised to power -1, this means 1 by 0.1, this is 10, right? So this is 10, this is always greater than 1. So that's why this left hand side will always be greater than 1. This is my x. Remember, this is my x, right? This is my x. Okay, so this left hand side will always be greater than 1, and this right hand side will always be lower than 1. If my x is, obviously, if x is positive and my a is lying between this range. Now for this case, right, for this case, what is happening? If my a is greater than 1, that means that let's say 2, right? Let's say 2. Now if x is positive, okay, if x is positive, let's say 2, it becomes 4. Fine. So it will be always greater than this 1, right? So basically when x is 0, it is 1. Okay, it is 1. When x is 2, it is 4. And if I further increase it, it will further increase, right? Now if I decrease my x, so if I decrease my x, what will happen over here? So this will be 2 raised to power -1. So this will be 1 by 2. So this will be 0.5, right? This will be 0.5. So this will be less than 1. So that's why on the left hand side, this is always below 1, and on the right hand side, this is always above 1. Like this, you can understand. Obviously, like this is going towards 0, okay, because this is less than 1, and if I increase it further, this will go towards 0, and this will go towards infinity. Okay, so these things you have to keep in mind. And for log, right? For log, these are just opposite of these things. Okay, these are just opposite of these things. What is the important point over here? What do you mean by log? So basically, this f of x is the power, right? Basically, if I want to write this in a more like accustomed manner, we can write it like this. So this is this a raised to power y equals to x. This is what this equation represents, right? This is what this equation represents. Now if my a is between 0 to 1, what will happen over here? So if my a is between 0 to 1, so a is between 0 to 1, so let me take one example of what time is it, of this 0.5, right? 0.5. And if my x is greater than 1, this is y, x is greater than 1. So obviously y has to be equals to 0 this time. Y has to be equal to 0, which is fine. Y is equals to 0. Now if my x is greater than 1, let's say this is equals to 4, right? If this is equals to 4, what can solve this equation? So my y has to be negative, right? Because this is 0.5, this 0.5, I have to make it reciprocal, so this becomes plus 2 or 2 square. So this has to be 2 square, right? So basically y here, right, will be equals to -2, right? -2, because I have to like make it reciprocal as well, because I have to make it more than 1, okay, to bring it back to 4. So that's why this graph is negative after y equals to 1, and that's why this graph is positive after y equals to before y equals to 1. Why? Because this value right here, if I write this 0.5 y equals to, let's say my output is 0.5 itself, Okay, not 0.5. I won't say 0.5 because y will become 1, which will be positive again, which is fine. I can say 0.25, right? So if I want to say this is 0.25, what will be this? This will be 2 y square, right? So this will be 0.5 square. So again, this is positive. So before 1, this is positive, after 1, this is negative. And similarly, like the same thing, you can decode it for this right hand side graph as well when a is greater than 1. Okay, I won't explain this again. So few definitions we have. Also, like this, right? Obviously I won't plot for negative value. So my domain, right? Domain of x will be only for positive values. Why is this the case? Why is this the case? Can you tell me? X belongs to 0 to infinity. Zero also I can touch because this is anyways 0, so 0 I can touch. Okay, 0 to infinity. Why is this the case? If you observe this here correctly, right? If I observe this here correctly, this time my y is the output. So what is my range? My range becomes domain here. What is my range? It is between 0 to infinity. 0 to infinity because it is going to 0 and infinity. So the range becomes domain here because log and exponential are just inverse of each other, kind of inverse of each other, right? That's why. So here, right, I will always get between 0 to infinity. That's why the domain becomes 0 to infinity here. I have got the point. Okay, so now let's read few key points. What are the key points? Key points is if I replace my y to minus y, and if the function remains same, it will be a symmetrical function, symmetrical about x-axis. So basically, so let me take an example. Let's say I have y square equals to 4x. I have y square equal to 4x. So if I have y square equals to 4x, now if I change my y to minus y, what will happen? Nothing will happen. Okay, nothing will happen. Equals to y square equals to 4x. I get the same equation again. So hence this will be a symmetrical function about x-axis. If you plot the graph, this will be symmetrical about x-axis. We know the graph was something like this, right? So it was symmetrical about the x-axis, even though it was not a proper function. Okay, but the graph was symmetrical about x-axis. That is more important to us. Okay, next is this, right? Next is this. If we replace x with minus x and the function remains same, it will be symmetrical about y-axis. Basically, this is a even function. So this will be symmetrical about the y-axis. This will be even function. Okay, and what else? Like, let me give you an example of even function. X square equals to 4ay, just like simple parabola, right? Like here, like this. So it was symmetrical about the y-axis. Next is if I interchange x and y, what will happen? If I interchange my x and y, what will happen? If the function remains same, then it will be symmetrical about the y equals to x line. So what is the example of this? The example of this, you can take y equals to 1 by x, the rectangular hyperbola. Okay, now the rectangular hyperbola was something like this, right? This and this. Now if you plot the y equals to x line, you can see that it is exactly cutting those into two halves, right? They are symmetrical to each other. So you can say that, yeah, it is symmetrical about y equals to x line. So these three key points you have to remember. These are not that heavy to remember. This you can understand intuitively as well. Okay, now what are graphical transformations? So what are graphical transformations? Graphical transformation is basically equals to y equals to, like y equals to fx is there. Now I am making some transformations with it. Okay, what type of transformations? Basically, if my y dash, like I'm changing my function, I'm adding the previous function with plus minus a, what will happen? It will either shift up or down by a units. Okay, with a units, right? The previous function. So if y is something like this, okay, if I add a units with it, it will become something like this. Just copy this and paste this, and it will either shift it up. Okay, and I will color this to different thing. Okay, or shift it down. Okay, so either it will shift it up or shift it down. Okay, next is another thing, the if I basically I'm not directly adding with the function, I'm changing the x value. I'm changing the x value, manipulating the x value. Now if I manipulate the x value, then it will shift left or right by a units. Basically it is a horizontal shift, right? So if I just copy this graph, it will either shift it here, okay, and either shift it here. So I should write this a units here. Okay, a units. So like here also I should change the color of these things. So let me mark this green, let me mark this, and this will shift, like this will shift, right? This and this again, a units. Okay, so yeah, left and right on the a units. Okay, so this is known as the horizontal shift. Now if I just directly multiply a -1 with this, obviously it will reflect around the x-axis, because whatever positive things were here, it will become negative, and whatever negative things were here, it will become positive. So it will simply reflect about x-axis. So basically what will happen, copy this, okay, so it will basically reflect, right? A reflection. Okay, it will be a reflection about the x-axis. Okay, so next is y is equals to f of minus x. Y is equals to f of minus x. So basically if I, like, now I am not multiplying -1 with the function, I'm just multiplying -1 with the x, right, with the independent variable. So it will reflect about the y-axis this time, because whatever for positive x values I was getting this graph, right, I will get the same thing for negative x values, and for negative x values whatever I was getting this, I will get for positive x values. So basically it will reflect around the about the y-axis. Okay, so I will just plot this thing. It will be same only. Okay, and what will this graph be called? This graph will be called y equals to e raised to power minus x. Instead of x I'm writing minus x, right? So yeah, it will be simply symmetrical about the y. Yeah, actually my storage got over, that's why I had to restart this thing. So this graphical transformation you understood, I hope. Next graphical transformation is basically scaling. So if I am simply scaling, right, with a, okay, I'm multiplying the function with a, either it can stretch or compress. If a is greater than 1, it will stretch. If a is less than 1, it will compress the thing. So let's say I have a sin x, right? This is equals to sin x. So this, right, this is equals to sin x. Now if this is equals to sin x, then what next will happen? Basically if my a is let's say 2, if my a is 2, so it will be 2 sin x, so it will stretch it. So what I will do is I will first write these things. Okay, so the graph will look something like this. Okay, I won't be able to exactly plot it. The graph will look something like this. Okay, and what about this? So here, right, this is simply 2 sin x. So my a is greater than 1. If my a is greater than 1, I am getting expansion, I'm getting stretch. Okay, I'm getting stretch. Now when will it's compress, So it will compress when my a is less than 1. Okay, obviously a has to be positive also, that is also important. So these things you already know, just quickly giving you quick revision. So here, right, this is, let's say, 0.5 sin x. So here, right, a is less than 1, but the important fact is a has to be greater than 0. A has to be positive. Okay, a has to be positive, right? So these are a few important points. So this is one graphical transformation. Now instead of directly scaling the function, I'm scaling the x, right? So basically I'm scaling the axis. So my axis will be scaled this time, stretched or compressed about the x axis. So my axis will be stretched. So what will happen, right? So if my, this is sin x, right? This is sin x. So if this was, this is sin x. So just hold on a second. This 0, this is pi, this is 2 pi, this is minus pi, and this is minus 2 pi, right? This is minus 2 pi. Now if I am simply stretching it, right? If I'm simply stretching it, so what will happen? So basically okay, I was just lost in few minds. If I'm stretching it, so I will make this sine of 2x. If I make this sine of 2x, what will happen? So for x equals to pi by 2, it will also give me pi. For x equals to pi, it will give me 2 pi. So I am getting more zero crossing points. So it will cross 0 twice as often as previously if my x is 2 pi. So if my x is 2x, so obviously my period will become pi instead of 2 pi. So what do I mean by this? So if I stretch this, right, this will be something like this. At pi by 4, it will get pi by 2. Let me draw this, then I will explain. And at pi by 2, it will be pi. And here, okay, this. Right, so the graph will be something like this. Same here also. Obviously the output range won't change this time. Okay, am I doing this correctly or not? So it will cross 0 at maximum point. Yeah, it will cross 0 at maximum point. Then again here, okay. So what is this graph? Basically this graph is sine of 2x. Okay, basically the period becomes pi instead of 2 pi, because if I put x equals to pi by 2, what will happen? If I put x equals to pi by 2, this will be sine of pi, which is 0. If I put x equals to pi by 2, it will be sine of pi by 2, which is 1. So it is basically compressing, right? It is compressing. So it is compressing about x-axis, compressing about x-axis. Okay, and if I make this now x by 2, if I make this x by 2, this will elongate this much further. Okay, so what do I mean by this? Basically it will be something like this. You tell me why it will be something like this. So pi by, this is pi by 2 to maximum here, right? It will maximum, and here it will be maximum. Okay, so what is this graph? This graph is sine of x by 2. So you try to explain me why the graph will look something like this. Obviously this is not like the exact graph because I'm really bad at drawing, but you tell me why this will be something like this. Okay, next is graphical transformation. So I have y equals to f of x, y equals to f of x. So if y is equals to f of x, now I want to make it modulus, right? Modulus. I want to make it mod. So whatever I have to make it positive. So reflect only the portion below the x-axis above the x-axis. So the portion below the x-axis will be reflected up here, right? Will be reflected up here. Okay. So basically, I just want to make all the negative things positive. Okay, I just make all the negative things positive. Okay. So this will be my modulus of x, right? This will be my modulus of x. Now, if I make x as mod, instead of the whole f of x mod, I just want to make the x mod. So this thing is very interesting. You have to notice to me right now. You have to focus on me. So basically, for this, right, what am I doing? I am ignoring all the negative values of x. That is what mod x does, right? So whatever, like if x is -1, mod x will be +1. If x is -0.1, mod x will be +0.1. So inside this function, only positive values can go. Okay. Inside, let me write this. Inside f of x, inside function, we can only give positive values. Okay, we can only give positive values. Okay, so we can never give negative values. So this information about the negative, right, values of x is lost. Information about the negative values of x is lost. So we can remove this portion, and like, what does this -1 will represent now? If I give my x as -1, it will give me output for x equals to 1, because mod of x, I am giving this -1, feeding this -1. This makes it +1. So I will get the output as f of 1. And what is f of 1? F of 1 is somewhere around here. F of -2 is somewhere around here, because this gets back to +2 only. So obviously these things will be same only. Okay, so obviously I can copy this. Okay, I can delete this part. Okay, this negative portion only, and delete this part. And what I will do, I will just copy this thing. Okay, and this, right, if I can somehow paste. Okay, my battery has been gone. I have been talking too long. Just hold on a second. Yeah, so if I just paste this part, this will be something like this, right? This will be something like this. Yeah. Okay, this has to touch the negative -3. Just hold on a second. This writing. Okay, so this is -1 and -3. Okay, so this is basically the reflection, right? Reflection around y-axis. So this makes it a even function. Here, right, this makes everything positive, this makes everything positive, and this makes it a even function, because the information for negative of x is simply lost. I don't have any information about the negative side of x. So that is what this thing is telling, that remove the left portion of the curve. So I just remove the left portion of the curve, keep only the portion of the right of y-axis, and reflect it about the y-axis, keeping the original position intact. So I just kept the positive portion of the x-axis and I reflect it around the y-axis to keep everything intact, right? So that will be my answer. So this is my f of mod of x, right? Okay, so yeah, this is how we solve this. So another way what you can do is basically you can write this in terms of function, right? So your y dash will become basically mod of x square minus mod of x plus 3, right? So like you can observe from here also, like mathematically, that you will only get this for positive values of x can never be negative, right? X can never be negative. Now another type of graphical transformations are there, which are envelopes. So basically, if when I'm multiplying two functions, so when y is equals to x sin x, when y is equals to x sin x, basically there will be envelopes, like two functions. One is x and another one is sin x. So sin x can be positive or negative. That's why I have to plot for both plus x and negative x. So this will be simply f of x equals to x and f of x equals to minus x, because x sin x, right, can be positive and negative. That's why I have to plot the two things. So I just my g of x is x, but I have to plot the two things. Now obviously this can always lie in this range only. This can always lie in this range only. This can never go out of this range. That's why these two are called envelopes. These two are called envelopes. So x is my envelope right now, and sin x, right, can only be between those two things, right? As I'm multiplying these two. Okay, here also e raised to power minus x. Okay, so this will be, as sin x is both positive and negative, that's why the two envelopes are, this envelope is basically f of x. This is, let me write this as g of x, not f of x. G of x equals to e raised to power minus x, and g of x equals to minus e raised to power minus x, right? So like these are the envelopes, and in between these, right, this will remain. Okay, that's how we plot these type of function. Okay, this is a method to plot these types of function. When we have two functions in multiplication, one function is oscillatory, so this will be something like this, and I will first draw the envelope of this, the outside one. Okay, outside one, and the oscillatory function will lie between these. Okay, so this is another type of transformation. So I will give you a few homeworks. Okay, MSQ, as this lecture has already gone long, and the next lecture will do all the problems, all the solutions, right, of this thing. So just read the question and try to answer this question. Okay, then this is also another question. Just this is actually multiplication. People might get confused with convolution. This is multiplication, simply multiplication. Okay, now this, right, what is this? This is a composite function. This is a composite function. So you have to understand that composite function, which we learned in the previous lecture. Okay, then here, right, I have given you all the graphical transformations. The graph is given to you, and you apply all the transformations, and then you match your solutions. Okay, this is important. So another assignment homework question I've given you, so where this includes most of the transformations. Okay, so yeah, that is it for this lecture, and in the next lecture I will come with the solutions. Okay, thank you for watching. Hey everyone, and welcome back to PrepFusion. So this is basically the extra part of the lecture 1. Basically, I mean lecture 1A and B has been finished. So in this lecture we'll basically solve the questions. Okay, so yeah, basically this was the question that I gave you, like before, like after studying the greatest integer function and the signum function, right? So we have to plot this, right? With plot this function. So to plot the greatest integer of sin x, plot the greatest integer of sin x. So basically, what is sin x? So if I copy sin x, right, sin x, okay, sin x is just after this here, right? Sin x is just after this here. So if I just copy this graph, right, just copy this graph. If I just copy this graph, now what is the important point? So what was the greatest integer function? Basically, greatest integer function means greatest integer less than or equal to x. Okay, so here, right, my x is sin x this time. X has changed to sin x. So at this point, what is the greatest integer function? This is something lower than 1. If this is something lower than 1, so obviously my greatest integer function is very brutal. It will directly drop it off to 0. Directly drop it off to 0. So this, right, this is also something less than 1. So this will directly drop it off to 0. So in this, right, in this whole region, it will be 0 only. But in this point, at this particular, when my x is pi by 2, when my x is pi by 2, it is exactly equals to 1. And the definition of greatest integer function is greatest integer less than or equal to x. So at this point my x is sin x is 1, so it is an integer, so it will be exactly equals to 1. For this particular single point it will be 1, and for the rest of this point it will be 0. So from 0 to pi we got our waveform, right? And it will be obviously periodic because my sin x is periodic, so greatest integer of sin x will also be periodic in nature. So now let's come to this pi to 2 pi. So what is happening to pi to 2 pi? So at this point, right, at this point, at sin pi is 0, and greatest integer function of 0 is 0, so this will not shift anywhere, right? Now at this point what is happening? This is just below 0, just below 0. If something is just lower than 0, my greatest integer function will directly shift it down to -1, directly shift it down to -1, because it searches the lowest integer, like next lowest integer after this, right? So the lowest integer after this is not integer, obviously this is something -0.1, -0.001, right? This will shift it down to -1. Okay, this will shift it down to -1, so this is -1. Okay, so if this is -1, so suddenly just after pi this is -1, okay, and this will go on till -1 until here, and suddenly like here, right, here, what is this point? This is -1, right? So sine of 3 pi by 2 is -1, and what will be the greatest integer function of that? That will also be -1. Okay, that will also be -1. Let me check if I'm just talking, and if it is not recording I'll be mad. Okay, yeah, it is recording. So the greatest integer of -1 will be -1, so that is fine, it will not shift anywhere. Then again, if I'm again my value is increasing again, right, this will be again, this will shift this back to -1, so this will not shift anywhere else. Now again I come to this point, just at 2 pi, just at 2 pi. When I am at 2 pi, just below 2 pi, this will shift it down to -1. When I am at 2 pi, the greatest integer of 2 sin 2 pi is 0, because sin 2 pi is 0, so greatest integer function of 0 will be 0 itself. Okay, so that was the analysis, and this will keep on repeating. So let's plot the graph. Okay, let's plot the graph. So if I just draw the axes, okay, this is x and this is greatest integer function of sin x, right? So what did I tell you? What did I explain right now? So I explained that here, right, this is just above 0. If this is just above 0, but this is below 1, so this is this point, right? This part is between 0 to 1, so this will always be equals to 0 itself. So here, right, this will be always equals to 0. But one interesting fact is that just at pi by 2, this is equals to 1, this is equals to 1, right? So if this is equals to 1, that means the greatest integer function will be 1, not 0, so it will suddenly jump to 1 only. Okay, so at this point, this will be open circle because it excludes 0 and it includes 1. So this part, right, this part is 1. Okay, this part is 1. Now then, just after this, what is this point? This point is pi by 2, x equals to pi by 2. Just after this, my sin x is something lower than 1. So if it is something lower than 1, greatest integer function will directly pull it down to 0. Okay, so hence again we'll restart with 0 until pi. So this is the first half cycle. Now what happens? Just after pi, this goes to something -0.1, -0.001, right? So greatest integer function will directly pull it down to -1. So again, this point is included here. Okay, this point is included, but this point, this -1 point is not included over here. Okay, but this will continue till 2 pi. Continue till 2 pi, and again at 2 pi, right? At 2 pi, again I will go to 0. Okay, again I will go to 0. Again I will go to 0, and this will continue again like this. Okay, again I will have an open circle. Let me just copy this thing. And again I will have an open circle. So what I can do is I can actually do one thing. I can actually delete this thing. can copy this thing actually. If I copy and paste this over here, then delete this thing, right? If I delete this thing, okay, this is the important part for me. Now again, if I paste this over here, if I copy this again, again for negative half cycle, right? Negative half cycle also the same only, so it will again be somewhere around here. Okay, here, yeah. So okay, I need to okay, so this will be this only. Okay, so yeah, this is how my plots will look like. Okay, let me delete this. This is what my plot graph will look like, right? So this is basically this is basically 2 pi, one complete cycle. Again, this is 5 pi by 2, not this is 3 pi only, and this is 5 pi by 2. Okay, so now this is minus pi, this is minus 2 pi. Okay, am I correct? Yeah, am I correct? So okay. Am I correct? Only a sine graph is like this. Yeah, sine graph is asymmetrical. Yeah, this is minus pi and this will be minus 2 pi, and this will be 3 pi by 2, right? So yeah, this will be my answer to the first question. Let's go to the next question. Let's go to the next question. So next question is a signum function of x into x plus 1, x minus 1. So this, right, this thing we have already done. Okay, just the difference is we have done this, we have plotted the exact plot for this, right? Okay, we haven't plotted signum of this. So where is the exact plot? The exact plot is okay, where did I do? Yeah, here, right? So exact plot is here only. Or we can take this, right? We can copy this same analysis. Okay, because I know where my function is positive and where my function is negative. So I know the locations of where my function is positive and negative. Just signum function tells that only. Okay, it tells that only, that if it is positive it will give me plus 1, if it is negative it will give me minus 1, if it is 0 it will give me 0. Okay, so pretty simple. Okay, wait. So graph will also look something like this only, right? So graph will also look something like this. If I just try to make the graph. Okay, if I try to make the graph, this is something x and this is something y. Okay, and currently what we can say, so basically this part, right, after 0 this is negative. So for a negative value, like at this particular 0, right, it is 0 only. This at this 0, if I make x equal to 0, this is 0, so signum of 0 will be 0, so that is fine. Signum of 0 will be 0, fine. And let me mark this point, signum of 0 will be 0. And here also at x equals to plus 1, right, again this whole thing is 0, so hence again this will be again 0. This is x equals to plus 1, and again at minus 1 also this will be again 0. So I marked the 3 points. Now after, just after this 0, right, my function is negative. So my function is negative, I will get minus 1 point. So I will get minus 1. So I will start somewhere from here and until x equals to 1 I will remain at minus 1. Until x equals to 1 I will remain at minus 1, right? So this will be minus 1. Now just after x equals to 1, what is happening? this is becoming +1, this is becoming +1, right? So if this is becoming +1, so what will happen? So this is also not included over here, and I can write from here, right? This is becoming +1, and this will go on, this will go on, this will not end, right? This will not end, because it is always positive after x equals to 1. It is always positive after x equals to 1. Okay, and what is happening in the negative side? So when x is lower than 0, so for between -1 to 0 it is positive. So up until -1 to 0 it is positive. So if it is positive, the graph will look something like this, right? Just hold on. Oh no. So it will be something like this. Okay, and obviously there will be open circles here and here, because at like x equals to -1 it is 0, and then again less than x equals to -1 it is going negative. So if it is going negative, it will be somewhere around here, right? Somewhere around here. And it will keep on going, it will keep on going. Okay, so yeah, this is what this is, right? Let me just put this in here. Okay, I hope you understood the graph. This open circles, right? This open circles means they are excluded. This closed circle means they are included. Okay, so this is the graph of signum of x into x plus 1. So wherever this is positive, this is positive, right? Before 0, and after 0 this is slightly negative, then again this becomes positive, and wherever this is negative, this is also -1, -1. Okay, that is what signum tells. Signum tells us about the sign of the signal, right? So yeah, this is basically it basically. So now let's go to the next question. Let's go to the next question, right? So what is the next question? So I gave you a few homeworks, right? I gave you a few homeworks. So this was the first homework, right? So first thing what you notice is this a function? Is this a proper function? No, this is not a proper function, right? Because this is equation of circle. Equation, fine, but this is not a function, because for a function, for a this equation to be a function, right, it has to have many to one mapping, but one to many can't happen. Basically a single value of x can give multiple outputs, it can only give single output. That is possible. Okay, so the curve by this equation is symmetrical about x-axis. How, when will it be symmetrical about x-axis? Okay, just try to recall. I gave you a few short notes, right? I gave you a few short notes. When it is symmetrical about x-axis, that means I'm replacing y to -y, and they should be same. Just I think I gave you a few key points, right? Give you a few key points here. If I replace y to -1, it should be symmetrical about x-axis. You can remember like this, that if I am replacing y to minus y, then it should be symmetrical about x-axis, yx. Okay, if I am replacing x to -x, then it should be symmetrical about y-axis, xy. Okay, opposite thing, right? And if I am interchanging x and y, then it should be symmetrical about the y equals to x line. Okay, you can recall it like the rectangular hyperbola. Okay, and even odd functions, though, you already know, like odd function is symmetrical about the origin, even function is symmetrical about the y-axis. From here itself we do the same thing, right? We for us to check whether the function is even or not, we simply replace by x to -x, and then we check whether that condition follows or not, that f of x equals to f of -x. That is what this thing is also saying to us. Okay, so is it symmetrical about x-axis? So for x-axis I have to check, I have to change y to -y. It is symmetrical, because if I change y to -y whole square will be y square only, so it will be same only, so it doesn't matter. So again, this is correct. Which of the following options are correct? I should have written which of the following options are correct. I forgot to write that, sorry for that. I'm really sorry. Which of the, oh no, options is /r correct? Okay, so here, right, it is symmetrical about x-axis, symmetrical about x-axis, so which is true, which is true. Okay, next is it is symmetrical about the y-axis. Is it really? So again, if I replace x with minus x, it will be same only. Minus x whole square is x square only. So again, this is true again, right? Again, it is symmetrical about the xy line. Now if I replace the x equals to y, if I replace the x equals to if I replace x with y and y with x, what will happen? This will be same only, right? This equation won't change. So again, this is also symmetrical about the line y equals to x. So I will just write few things, that replace y to minus y, then replace x to minus x, replace, like not replace, exchange, interchange x and y. Okay, then the last one is this neither even neither odd? No, this is the even function, right? This is the even function, that we know because this condition is satisfying. So this is the even function, even function. So this can't be neither even neither odd, it is a even function. This option is incorrect, right? So ABC is our answer. ABC is our answer. Okay, so let's go to the next question. So the next question is again interesting. It is a question of composite functions, right? So here g of x is given and h of x is given. We have to find g of x into h of x, which is simply a new function. Let's name this a new function as u of x. Okay, so I haven't written the options. So options, something like options come up. Okay, I have written the options. So basically how you solve this, so what you want to do, you want to put this g of x in the h of x, right? And but be careful that while putting this, right, is there any domain constraint over here? There isn't any domain constraint. X can take any real value, right? So like this portion can take any value, that is h of x can be anything, h of x can be anything, so that is fine. So basically this will be 2 minus h of x, u of x equals 2 minus h of x into what, h of g of x. So simply, is there any domain constraint over here? Yes, there is, right? This x can't be equals to 2, this x can't be equals to 2, so this g of x can't be equals to 2. So that is very important, that g of x can't be equals to 2. Okay, hence if this is equals to 2, that means x minus x will be equals to 0. So x can't be equals to 0, right? X can't be equals to 0. That is a very important domain over here, right? So this is basically g of x divided by g of x minus 2. Okay, g of x divided by g of x minus 2. Okay, so now how you want to solve this? What you can do, you can directly replace h of x and g of x with their particular relations, right? Equations of x. So here this will be 2 minus h of x. H of x is x minus 2, and this is simply what is this? This is, let me like take this arrow to the bottom side. G of x is 2 minus x again, so this is 2 minus x divided by 2 minus x minus 2. Okay, so this will simply be, if I just take this common, so this will be 2x minus 4 minus x. This is x minus 4 divided by x minus 2. This is into 2 minus x divided by, this is minus x, right? So basically this becomes x minus 4 divided by x minus 4 divided by x, okay, which is equals to 1 minus 4 by x, where my x cannot be equals to 4. Okay, so u of x I can write, sorry, where my x cannot be equals to 0, where my x cannot be equals to 0, so u of x I can write 1 minus 4 by x. Okay, basically my x can take any real values except x equals to 0. Okay, except 0 it can take any real values, which I already proven here, Okay, so yeah, this is how you solve composite functions. Pretty simple. Now let's solve few transformation questions. So like I have already given you transformation, so this will like quickly give you a revision of what transformations we have done. So this is a graph, okay, and first thing what I am doing is adding 1 with this graph. What will happen? This will basically shift up. Okay, so let me just copy this over here. Okay, and let me do one more thing. Let me again copy this and let me delete the axes. Okay, so it will be easier for me to do everything. Okay, but not for you. Okay, what I will do, I will just delete these markings. Okay, and I will just copy the graph itself. Okay, so everything will be easier for me, not for you. Okay, you have to do it by hand. Okay, and please do it by hand, it will be helpful for you. Okay, so I will copy this. I will simply copy this. I will keep this aside. So what is happening, this will get shifted, okay, by 1 units above, right, above the x-axis, because I am adding 1 with this. So basically if I may delete this, how can I delete this? So this can be deleted like this. Okay, yeah, so if everything gets shifted above by 1, right, so this will be something like this. This will be something like this, because this point, right, this point, the lowest point was at -1, so the lowest point will reach to 0. Right now. If I can, lowest point will be 0. Okay, so yeah, like nothing fancy over here. This is the highest point will become 2 this time instead of it being 1. So let me extend this graph further actually, and let me make this more. Okay, so yeah, this is this thing. So now let's go to the next one. This is the first transformation, so let's now go to the next transformation. And yeah, now coming to this, right, this is 2f of x, y equals to 2f of x. So if y is equals to f of x, then simply we are scaling this, right, we are expanding this. So what will happen is that, let me paste this over here only. Let me copy the axes only, if I may. Can I copy that? Okay, I can copy the whole. Okay. This is really okay. What I can do is, I can do this, then this. Okay, not this actually. I have to do this. I can simply copy this whole graph, right? So simply what I will do, I will just change the y values, because y values are getting changed, right? They are getting scaled. Okay, the shape of the graph will remain same, just the y value are getting scaled. So this, I'm multiplying 2 with this, so this will become 2 and this will become -2. Okay, everything else will be same, because shape is same, just the maximum upper and lower limits are changing, because I'm multiplying the y values, right? So then next what I am doing, I am simply multiplying a -1 with this. If I multiply -1 with this, whatever was here, right, whatever was positive here, it will become negative. Whatever was negative, it will become positive. Okay, so let me just cut and copy this in the next page. So what I will do, I'll again copy and paste this thing only. Okay, not this only. So this will be negative and this will also be negative. Okay, and this will also become negative and this will become positive. This will become positive and this will be negative. Basically I'm multiplying -1 with this. I'm changing the sign of this graph. All right, I'm changing the sign of this graph. So yeah, this is one thing, and let's go to the next thing. So next is this, right? If I am multiplying minus with the x, what will happen? It will just flip about the y-axis, right? About the y-axis, because whatever was negative, whatever like was minus x, it will become plus x, and whatever was plus x, it will become minus x. So like these values will be same and they will become different. So what I'm telling, basically x equals to minus 2, my value is let's say here, right? X equals to minus 2, x equals to minus 2, my value is 1. So if I multiply minus with my x, so it will become, now at x equals to minus 2, it is f of plus 2. So what is f of plus 2? It is 0. So it will become 0. So this will flip over here and this will flip over here. Basically I'm multiplying the negative sign. Okay, so nothing fancy over here. So what I can do is so basically this will be somewhere around here. Okay, what will this become? So I can simply draw this actually. Let me draw this. So okay, this axis will get shifted on this hand side, right hand side. This will get cramped over here. Okay, okay, so basically they will get swapped. So this, right, what did I have? This was a sine wave, right? Like a sine wave thing. So this will be something like this only. Okay, and this will be minus 1. And then again, this, what will this will be something like this triangular, and this will be this. Okay, and this is x equals to 2, right? Yeah, this is x equals to 2. Okay, so minus 1 plus 1, x equals to 2. Great, fine. So this is done. So this is how you flip about the y-axis. Okay, what is the next transformation? So we are doing the mod of x. So whatever is positive will remain positive. Not mod of x, we are doing the mod of f of x. So whatever is positive will remain positive, but whatever was negative, it will be just flipped along the x-axis. So that will become positive only. So this thing will remain same only. Okay, just the negative part will become positive right now. Okay, this had no use actually. So this is the 5th one, right? Everything is recording, right? I have to sometimes check everything is recording or not. Yeah, this is recording. So this will become positive only, right? This will become positive only. So that is what this will change to, right? So this is simple only. Now next is mod of x. Now mod of x, what will happen? So I told you, right, the negative values of x will be deleted. The information will be deleted because this f of inside it, this can never go to negative. Okay, at minimum this can go to 0. Okay, so this f of inside can never go to negative. So this part is of no use to us. So this part is of use to us. So whatever is in the 0 plus 1 2, that will be in the minus 1 2, because this is mod of x. So minus 1, mod of minus 1 is 1 itself, mod of 1 is 1 itself. So those two things are same only. Okay, so basically the right hand side will be copied. Okay, right hand side will be copied basically. Let me copy this. and then obviously it will be symmetrical about the y-axis, right? Because whatever is mod of minus x minus mod of minus 1 is 1, mod of, sorry, I am talking about, yeah, minus 1 mod is 1, 1 mod is 1. Okay, so those two things are same, so that's why it will be same symmetrical about the y-axis. So this also, let me just copy these points, paste this over here. Okay, what I will do is, okay, this can't be flipped. What I can do is, this thing is of no use, I can just simply replace this 1 and 2, right? Replace this 1 and 2, and yeah, this will be somewhere around here. If I just copy this thing somewhere around here. Okay, so I hope we got the point. So this, right, this mod of f of x will always be a even function. This will always be a even function. Okay, so yeah, we did all the transformations basically. Now let's do the final one, the homework one. So what I think is, I think you should do this for yourself. Okay, and like I will put this in the notes or solutions or somewhere. I may not. Some things you have to do by yourself. So this is pretty easy. You can do it for yourself, right? So that you can use your brain also. Your brain needs to keep on working, right? So yeah, this is for you to solve. So in the next lecture, we'll start with limits, which will be very interesting. Okay, from there questions mostly start coming from the calculus chapter. From there, right? This is the basics part. If someone has skipped their basics during class 11 and 12, they can watch this. Okay, limits also I will start from basics, then I will go to the next level. Okay, so yeah, thank you for watching, and I'll see you in the next video. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 2A of calculus chapter. Basically, up until now we have done the basic things, basically functions, what are functions, what are different standard functions, and what are the graphs of those functions. We have understood the functions part very well. Now what we'll do, we'll study about the limits. What do we mean by limits? What is the physical significance of limits? Okay, and after that we'll move on to few more next things. So like, why are the limits used? First we'll understand what are limits, then we'll understand the methods to solve limits, and then we'll understand why is limits so important to us. So let's start off with a question. So here we have been given a function like this, x minus 1 divided by 3 into x minus 1. Okay, what you can do, you can simply cancel this, right? You can simply cancel this and you will get 1 by 3, right? You will get 1 by 3, because x minus 1 and x minus 1 are the same only on the numerator denominator. If two things are same on numerator and denominator, you can simply cancel those things out, right? So like, but what is the question asking us? The question is asking us to find the value of the function at x equals to minus 1, 0 and 1. But you know, like it will be always 1 by 3. So you will say that f of minus 1 equals to f of 0 equals to f of 1 equals to 1 by 3. Okay, equals to 1 by 3. Okay, it is equals to 1 by 3. So basically it is equals to 1 by 3. So is this correct? No, right? All of this, whatever we have done is wrong. Whatever we have done is wrong. Why? Because you can't simply cancel these things out, because when there is something, right, in the denominator, you can't simply cancel that out. Okay, you have to check whether this is 0 or not, whether this becomes 0 or not. So if it becomes 0, so something by 0 is undefined, which we have studied in the previous lecture, right? So we'll also explain this further in the next few slides. So here we can't simply cancel it. When you can cancel it, when my x is not equals to my this one, right? So we can simply cancel it. So this, right, this 1 by 3 is valid for x when x belongs to all the real numbers except the x equals to 1, right? I cannot put x equals to 1. For that it is not valid. For every other values of x, this I can simply cancel out. Okay, they will be same only. But for x equals to 1, I cannot, because 0 by 0 is undetermined. Okay, undetermined. We will understand this in the next few slides. So how to solve this? So basically what you can see is x of, if I do f of minus 1, f of minus 1 is correct. If I do f of minus 1, it is equals to minus 2 by 3 into minus 2, so which is equals to 1 by 3 itself. If I do f of 0, which is 0 minus 1 into 3 into 0 minus 1, which is equals to 1 by 3 again. Now if I do f of 1, right, if I do f of 1, so this is 0 divided by 3 into 0. Now can I cancel 0 by 0? No, I cannot cancel 0 by 0. Okay, I cannot do that. Okay, I cannot do that. So this becomes 0 by 0. We can't simply cancel 0 by 0. Okay, this is undefined. Why? I will explain the next few slides. Okay, so what is the value of this? We don't know. Currently we don't know what is the value of this. Okay, anyways, I cannot put 1 equals to here because this is not in the domain. This is not in the domain, right? Okay, so like this already I have explained. I cannot put x equals to 1. Okay, so we don't know what is the value of the function at x equals to 1. Okay, so at x equals to 1 we don't know what is the value of the function, hence this is open circle. I have plotted the function and hence this is open circle, right? So this 1 by 3 is somewhere around here. Okay, and I don't know what is the value, right? I don't know. The function is undefined at x equals to 1. Okay, it is undefined at x equals to 1. Now it is undefined. Now is there any method so that we can know what is x equals to 1? Is there any method to that? So let me give you one analogy here. So let's say like the police has come. Okay, this is a very bad analogy, but let's say the police has come to get information about a certain person, right? He has come to his home. Okay, he has came to his home to get the information. Now he just knocks the door and he sees that there isn't anyone inside the home right now. Okay, so what is the next thing you will do to find information about the person, right? What do you do? You will go to his neighbors, right? You'll go to his neighbors and ask the neighbors about that guy. Whatever information he needs, you will ask that same thing about the from the neighbors about this guy. Okay, so here also what we'll do the same thing. We don't know what is the value of this function at x equals to 1. We don't know. It is undefined right now. Okay, I will explain also what is undefined, but for now just assume that 0 by 0 is undefined, right? 0 by 0 is undefined. We don't know what is 0 by 0. 1 by 0 is also undefined. Okay, so now I don't know the value, but we are in mathematics, right? We are studying mathematics. So we want to know what is the value at x equals to 1. We want to know. Okay, we want to know what is the value of x equals to 1. Even though we know that x equals to 1, the value of the function at x equals to 1 is undefined. We want to know what can be the value. Can we guess something? Can we give a good approximation? Okay, so here what do? We use the concept of limits. So as I told you, right, we go from the neighbors. So what is the value of the function of its neighbors in its neighborhood region? What is the value of the function? So if its neighborhood region, okay, has the same values, then I can assume that this also can have same value. Okay, but I will give you warning. This is just an analogy. Okay, we'll go to the more formal definition later on. Okay, just giving you an analogy right now. So I'm talking about neighbors. So if I'm coming from the left hand side, then this is known as the left hand limit. So what I will do is I will approach this point at x equals to 1 from the left hand side. Okay, let's say first I start from x equals to 0.5, then x equals to 0.7, 0.8, 0.9, 0.99, 0.9999, 0.999999. Okay, it is going on. So I'm reaching very close to this point, not exactly close to 1. So what is the value of that function at very close to that x equals to 1? Not exactly close to 1, but very close, 0.999999. Okay, so it is 1 by 3. If I'm approaching from left hand side, it is 1 by 3. Good. Okay, so if I'm approaching from left hand side, so this, right, approaching from left hand side and right hand side, basically neighborhood. Okay, I have forgotten the spelling, that is my bad. Neighborhood, but I think this will be the spelling only. So I'm approaching the neighbor. So from the left hand side I'm seeing that the value is 1 by 3. Okay, so left hand side value is 1 by 3. From the right hand side, what is the value? So basically currently my x is 1.5. What is the value of the function? 1 by 3. I'm going to 1.1, then 1.01, then 1.001, 1.00001, 1.0000001. Okay, so I'm reaching very close to this point, not exactly equals to 1, but very close to this point. So I am very close to this point. Okay, but not exactly close to 1. I'm just at the neighbor of this point, but on the right hand neighbor of this point this time, not on the left hand side, on the right hand. So on the right hand also, this is always equals to 1 by 3 only. Okay, so basically the right hand side, right hand neighbor and the left hand neighbor. So let me write left hand neighbor is equals to left hand neighbor is equals to 1 by 3, and similarly right hand neighbor is equals to 1 by 3. Hence we can assume that both of the neighbors are saying the same thing. So we say that the behavior of the person, or whatever question that police officer asked, right, the answer to that will be that only. But that is not sure. We're not sure about that. That is not exactly equals to 1. Okay, so basically we say that the value of the limit will be defined at x equals to 1, and the value of the limit will be 1 by 3 if left hand neighbor and right hand neighbor are same. So what we'll say is basically, I've already written this on the left hand side. So here I've already written this. So left neighborhood of x equals to 1 is 1 by 3, and right neighborhood is 1 by 3. Just I have explained it visually, right? So value of limit at x equals to 1, okay, is what? It is equals to 1 by 3 itself, as these two are same only. Left neighborhood and the right neighborhood are same only. Okay, now is this the value of the function at x equals to 1? This is not value of the function. The first warning that I want to give is this is not value of the function. Value of the function at x equals to 1 does not exist. Value of the function at x equals to 1 does not exist. Okay, because it is undefined. So this is not value of the function. So value of, let me copy, value of function does not exist. Okay, value of the function at x equal to 1 does not exist. So that is that thing is not changed, but we are defining a new term, that is limit. Okay, and this is useful in finding other things. What things this is useful, we'll understand this later. Okay, limit is defined, but value of the function is not defined. It is does not exist. So what do you mean by limits? So limit in maths are defined as the value that a function approaches the output for the given input value. So I'm approaching this, right, from the left hand side, from the right hand side, for a given input value. So I'm approaching this output. Okay, but I'm just approaching it. I'm not getting exactly equals to that value. Okay, that is very important. Now you can read all this. I've already explained this with visually, so I won't explain this. So here also I'm again explaining this. So let's say we have a function, right? Let's say we have a function. Very important point. We have a function. Now if you observe one thing, let's say I'm approaching this from the left hand side, on the right hand side, from the left hand side and the right hand side. So I will name 2 points. I will name 2 points. What are the 2 points? One point is a minus h and a plus h. Okay, a minus h and a plus h. So basically this hold on a second. So h, right, h is a very positive small quantity. Okay, h is a positive small quantity. H is a positive small quantity, right? So h is a positive small quantity, very small, but h is a positive small quantity, almost equals to 0, but it is some positive value. Okay, so here it is asking us 2 things. What is limit x as x? This is I forgot you to tell that. Okay, one thing I forgot you to tell is that how we write the limit, right? How if the question is asking us to find the limit at certain point, how is the representation? So representation is something like this, that limit as x tends to a, like limit at x equals to a for the function f of x. Okay, and if the limit exists, then like we can equate this with L, right? Let's say L is the limit. L can be any real number. L can be any real number. Okay, it can be infinite also. It can be infinite also. It doesn't matter, right? So so this is how we represent the limits. So here, right, it is asking us the limit of the function, right, at x equals to a. Okay, and what is this? These two things are saying the different thing. This is asking us what is the value of the function at x equals to a, and this is asking us to find what is the limit of the function at x equals to a. Okay, limit and value are different. Limit means I'm going very close to that point, but not exactly equals to that. But this means exactly equals to a, exactly equals to a. So these two things are different over here. So now as I'm moving from this left hand side, right, so this a, as the h tends to go more lower, so this, right, this difference, I'm moving from left hand side, this difference will go more closer to this a, but this will never reach a, okay. So this point, right, is L. Like if I move very near to this, you can see that this point is L only from the left hand side. So left hand side, what I can say, from the left hand side I'm approaching L only, right? I'm approaching L only. Okay, and from the right hand side, what again if my h reduces, very small, h goes to very small value, right? So it is some positive value, that's why it is on the right hand side, but it is approaching very near to e. So if I'm approaching very near to a, again, right, what is happening over here? This is again almost equals to L itself, So I can write that these two things, right? So this left hand neighborhood and right hand neighborhood are L, right? So my limit will be that L only. So I can say my limit, so I can write LT also. So there is few people write LIM and few people write LT, right? So both of them are same only, it doesn't matter. X tending to a, f of x is L, right? Okay, and what is the value of the function? What do you observe? Exactly at x equals to a, what is happening? This is open interval, open circle, right? Open circle, and this is closed circle. So obviously this is suddenly going to this point, right? So exactly at x equals to a, the value of the actual value of the function is c. Actual value of the function. This is also known as functional value, which we will study. So f of a is actually equals to c itself. Is actually equals to c, right? F of a is actually equal to c. Okay, so this is the thing. So like this, right, this a minus h is called known as the left hand limit. So this is known as the left hand limit. We will study this formally in next few slides, just giving you few heads up. This is known as the left hand limit, and this is known as the right hand limit. Okay, left hand limit and right hand limit. So basically these are the things. Okay, so what do you see the difference, right? You see the difference, right? The limit of that function and the actual value of the function, these two things are different. These two things aren't same. Okay, so they may be same or they may not be equal. They can be. So here what thing I can write is that they can be equal or they or cannot be equal. Okay, cannot be equal. Okay, there is no particular relation between these two, right? Relationship, there is no particular relationship between these two. Cannot be equal. Okay, there is no particular relationship, there is no any function value. Okay, so what is a visual representation of limit? So like how is it? It is said that it is read as the limit of f of x as x approaches a equals L. Okay, here, right, as I'm approaching this a, it is equals to L. Okay, it is shown by arrow. Okay, and C described by right arrow. So basically let's say this point, right, this point is my a. Okay, and this point is my L. So I can approach from two sides. So how I can write like this, right? I can write that if limit exists, if limit exists, then I can write limit as x tends to a minus f of x will be equals to limit as x tends to a plus f of x. I'm just talking about the right neighborhood and the left neighborhood. Okay, will be equals to L, right? Will be equals to L. Okay, not capital L, will be equals to small l. Okay, so this is about the right hand limit and the left hand limit, right? So if this a plus, right, instead of a plus, sometimes what they do is they write simply x tends to a. Okay, these two things are same only, because a is assumed to, like, this is assumed to be positive only. For positive we don't write any sign, right? For negative we write the same thing applies over here also. Okay, so these and these are same thing. Okay, so like I just give you a brief about the left hand and the right hand limit. Now let's study the definition, right? So a function may approach two different limits. Until now what we have been studying, that it is approaching the same value from the left and the right. But I told you, right? I told you during the tan x graph or some other graphs, right, that sometimes I'm approaching plus infinity from the right and sometimes I'm approaching minus infinity from the left. So there, right, the limits are different over there. The limits are different. So slowly we'll do questions and from there we'll understand. So a function may approach two different limits. One where the variable approaches its limit through values larger than the limit, and the other where the variable approaches its limit values smaller than the limit. So I'm approaching larger than the limit, that is, it's talking about the right hand limit. So I'm larger and I'm going towards the smaller one. I am smaller going towards the larger one. Okay, left hand and right hand limit. Now in such a case the limit is not defined, but the right hand and left hand limit exist. Basically, if it approaches two different limits, okay, from left and right hand, then limit will not exist. Okay, limit will not exist, but the right hand and left hand limit will be defined. Okay, right hand and limit will be defined. So what does this mean? Basically, this is LHL and RHL, which is the left hand limit and the right hand limit. So this is H, right? So I have given you two formats. This is the one format. This is the left hand limit. This is the right hand limit. Okay, and this is also another format. So here H is small positive quantity. This is written 0. 0 means positive. No sign is given. So this is positive. Small positive. So if this is positive, so this will be something very something smaller than a, but the difference will be very low. Something smaller than a. Okay, and this will be something greater than a. Okay, that's why this is called as right hand limit. I'm approaching from the right, greater than a. Something smaller than a, I'm approaching from the left. Okay, so this, right, this also I can write like this, that limit x tending to a minus, okay, I've already written this in the previous slide, still f of x, and this we can write limit x tending to a plus f of x. Okay, f of x. Okay, so basically now what are the important points I want to tell you? What are the important points? The important points is that just hold on a second. So if my LHL is not equals to RHL, okay, even if those two exist, obviously they have to be some real number, right? They have to be some real number. Those two will exist. If that is, those are not equal, then limit does not exist. For that function at that point. Okay, now if LHL equals to RHL, then limit exists for that function at that point. So that is what is written on those English words. Okay, those are very complex English words, that's why we tend to avoid those. So then limit exist for that particular point. Limit exists for that particular point. Okay, so for existence of limit, this is the main important criteria. The left hand limit and the right hand limit has to be equal. Okay, so we're just talking about limits, we're talking about the approach, we're not talking about the value of that function. Okay, we're talking about the approach. Okay, so let's do few of these questions and from here we'll understand. Okay, so here f of x, we have to find the limit f of x at x equals to 0 and 1.5, where my f of x is the greatest integer function. The graph is also given. Okay, so we know what is greatest integer function. So you have to find the limit at x equals to 0. So if you want to find the limit at x equals to 0, how you find? What you will do? You will calculate the left hand limit and the right hand limit. So obviously I will talk about the steps in the detailed manner in like next few slides, but we know the rough method, right? We have to approach from the left and approach from the right, neighborhood. Okay, so if I approach from the left, what do we see? I'm approaching from the left, my function is lying over here. I'm approaching from the left, my function is lying over here. So just below this 0, right? Just below this 0, my function will always be this -1. Always be this -1. So what I can say? I can say that limit, okay, is there limit as x tends to 0 minus f of x equals to what? This is -1, right? Because something greatest integer function is very brutal. Anything lower than 0, 0.0, no, minus 0.00001, okay, it will directly pull it down to -1. Okay, so greatest integer function is very brutal, so it will directly pull it down to -1. So this will be -1 only. This will be -1. Okay, next, what is happening? Next, I am approaching from the right hand side. If I am approaching from the right hand side, my value is 0.0001. 0.001 greatest integer function will pull it down to the lesser integer value, which is 0. In this case, it was -0.001. The lower integer value will be -1. The next lower integer value will be -1. Here it is 0.0001. So the integer value will be lower integer value. Next lower integer value will be 0. So it is 0 in this case. It is 0 in this case. So right hand limit is 0. Hence, what I can say that let me take another page actually. That my right hand, like my limit of f of x does not exist at x equals to 0. Okay, limit does not exist at x equal to 0 because left hand limit is not equals to right hand limit. Okay, that is one thing. Now let's try it for 1.5. Okay, x equals to 1.5. So x equals to 1.5 is somewhere around here. If I approach from left and if I approach from right, I can see that these two are same only. What is the value? This is 1, right? Okay, this is 1. So you can do it for yourself. So basically I will copy this and paste this over here again. And what I'll do, this is 1.5 minus and this is 1.5 plus, and this is plus 1 and this is also plus 1. This is 1.5 plus and this will be 1 itself. Okay, so limit exists at x equals to 1.5 as right hand limit is equals to left hand limit. So limit exists okay. So yeah, this is the case basically. So limit exists at x equals to 1.5, left hand limit equals right hand limit. Okay, so yeah, this is the thing. Just hold on a second. And the value of the limit is 1. Value of the limit, so value of the limit is 1 itself, and which is equals to 1, right? It's equals to 1. Okay, so yeah, this was it for the greatest integer function. Let's now solve for the signum function. So for the signum function, again we have to find the limit. Or so what do we notice over here? So it may so happen for the same function, limit can exist at a certain point and limit cannot exist at a certain point. That is possible, right? That's probable. So next is find limit of f of x at x equal to 0. What will the limit of f of x at x equal to 0 for mod of signum of x? I'm not talking about signum of x, I'm talking about the mod of signum of x. So we have to plot the mod of signum of x. So this is given signum of x, okay, or sigmoid, you can say sigmoid function. So what we can do, we can, like, what do we do in mod, right? What do we do in the modulus function? We simply this is x, this is signum of x, okay, and basically we simply, like, whatever negative is there, we simply make it positive, right? So simply make it positive, whatever negative value we had, we simply make it positive, okay. So this is plus 1 only, and this one is also plus 1, right? Okay, so this is equals to 1, this is equals to 1, right? Okay, so basically now what can you do? So we have to find the limit, right? And obviously don't forget this dot over here, this dot is also present over here, right? So this 0 is mod of 0 is 0 only, okay, because x signum of 0 is 0 only, so don't forget this dot, okay, this dot is here. So now let's calculate the left hand limit, okay. If I'm approaching from the left hand side, what can I observe? If I'm approaching from the left hand side, I can observe that if I am approaching very near to this 0, right, minus 0.001, this is equals to 1 itself, this is equals to 1 itself. Now if I am approaching from the right hand side, if I am approaching from the right hand side, 0.001 again, right, this will be 1 again, this value is not changing. At x equals to 0, this is 0, that is fine, but I'm not talking about x equal to 0, I'm talking very near to this x equal to 0, okay. That's why I can say that limit x tending to 0 minus of f of x equals to 1, and the same thing limit x tending to 0 plus f of x equals to 1 itself. So limit does exist, okay. So limit exists, and value of limit is which is equals to 1 itself, okay, which is equals to 1, okay. So these two things, like solutions, were just a warm up for you. These two questions were just a warm up for you, right? So let's now first understand the difference between functional and limiting value. I already told you, like, just by explanation I already told you, but formally I haven't written anything. So let's first understand this. So the limit describes the behavior of the function as it approaches a specific point. Basically it describes the neighborhood around that specific point, while the function value is the actual output of the function at that specific point. I already told this in the first slide itself, right? So functional value is the exact value of the function at that specific point, and the limit tells us about the neighborhood, just very near to that critical point. What is the value of the function? That is what limit tells us, very near, as it approaches that critical point, Functional value at a point has no relation with the limiting value at that point. We have done this already, like through this example we already understood this point. They may be or they may not be equal, okay. I hope you got this point. So basically, how can we represent the functional value? Functional value can be represented where no limit is written. So I can represent my functional value x like this, f of x at x equals 0, or f of 0. So these are the representation for functional value. Functional value. Okay, and next is about limits. So what is limiting value? Limiting value is limit as x tends to 0 f of x. This is called as my limiting value. limiting value. Okay, so yeah, this is the difference between limiting value and functional value. Now let's first understand few determinant and indeterminate format. So what is 6 by 2? Very like silly question, right? What is 6 by 2? It is 3, right? So what we can do is like doing very childish thing, that I'm assuming I don't know what is 6 by 2. I can assume this as x. Now if I multiply 2 on both sides, 6 should be equals to 2x. So what should be my x, so that if I multiply 2 with it, I will get 6. It will be 3, right? And it is a unique value. It is a unique value. X equals to 3. Unique value. Okay. It is a unique value. As it is a unique value, it is a what? It is a determinate value. We can determine the value of x. Hence, it is also known as determinate form, because we can determine the value of x. Okay. Now let's go to this next. This is known as undefined form. Why is this called undefined form? Let's understand. So again, I will apply the same process. Even though doing this is legal, but this is illegal, right? This is not recommended. Okay, but just to understand the core concept behind this is not recommended, and like obviously this is not we can't do this because this is against the rules, but just to understand the concept, we're doing this. Okay, so I will also write this over here. So what I will do is, this is 6 over 0. So what I can assume, 6 over 0 is equals to x, right? 6 over 0 is equals to x. So again, I can multiply 0 on both sides. Okay, I can multiply 0 on both sides. This will be, I will write it here over here, that this is not recommended. Okay, not this step, this step, right? Multiplying 0 on both sides, this is not recommended. Okay, so 0 times x, this step is not recommended. Just to understand, we are doing all this. Understand the concept. Okay, so now what can I put my value of x, so that I can multiply 0 times it and I will get back 6? Is there any value? There is no such value. No such value for x exists, right? Which can satisfy this equation. No, I can write this in some. No such value for x exist. Okay, no such value for x exists. So basically that's why this is known as undefined. X is not defined. Okay, we cannot define x for this equation. Okay, we cannot define. So that's why this is called as undefined format. Okay, that's what is called as undefined form. Okay, so now let's understand another type of form, which is the indeterminate form. So what is indeterminate form? So basically it is 0 by 0. So again I will do the same thing. That I will extend this 0 by 0 equals to x. 0 equals to 0 times x, right? 0 times x. Now 0 times x. Now for what values of x will this equation satisfy? This will satisfy for any value of x, any real value of x. Any real value of x. Okay, any real value of x, this will satisfy. Obviously this will not satisfy if x equals to 1 by 0. You can say, sir, x is equals to 1 by 0. I will cancel 0 0 and it will be 0 equals to 1. But I already told you that we cannot do that. Okay, I've already abandoned that. We cannot do 6 by 0, 1 by 0, all those things we cannot do. Okay, we cannot do that. That's why, okay, that thing is out of the window. But x can be 1, 2, 3, 4, 5, 6, 7, 8, 1.11, minus 1.11, 2.3, 5.4, anything. This equation will always be satisfied. Now that's why I will not be able to determine the value of x. Okay, that's why this is called a indeterminate form. Okay, not able to determine value of x. That's why this is called as indeterminate form. So 0 by 0 is called as indeterminate form. Okay, as I'm not able to identify the value of x. Okay, so I'm just a bit thirsty right now, so I will just drink a bottle of water, then I will again come back. Okay, so let's restart basically. So let's understand what is the concept of infinity. Just hold on a second, let me check if I am recording or not. Yeah, this is recording, this is recording, this is recording. So what is the concept of infinity? So infinity, okay, where am I going? Where was I? Here, right? So infinity is a symbol, not a number. It is not a single number, right? It is tending. It is a very high value, very high value. We cannot never reach to it. Infinity means it is never ending, right? Our universe is always expanding. Our universe is infinity because it is it is never stopping expanding, right? It is always expanding, okay, along all directions. So we will never be able to reach the end. It is infinity. Okay, so that is also a very interesting fact. So positive infinity is a symbol for the behavior of a variable that continuously increases and passes through all the limits. Okay, it passes through all the limits and it is continuously increasing. Every time it is increasing, like our universe. And negative infinity is a symbol for the behavior of a variable that continuously decreases and passes through all the limits. Okay, black hole might have something to do with negative infinity. I don't know exactly, but it is always continuously decreasing. Okay, it is going in the negative direction. That is why it is known as negative infinity. It is always continuously decreasing. Now, infinity does not follow the rules of algebra. What are the rules of algebra? So I cannot say like that my x will be equals to. I can assume that x is some variable and it can be equals to infinity, because infinity is not stable, right? It is always increasing. Okay, so it can't be equal to something. Because if I say x is equal to infinity, next second I will say it is increasing. Infinity has become something else, always increasing, right? So it can't be equal to anything, right? X can't be equal to anything. So I will do one thing. I will just write this over here and I will make a cross mark. Okay, and what else we cannot do? What we can say is, we can say x is tending towards infinity. This we can say. Okay, tending, it is going towards infinity. That is good, because x is also increasing. That is fine. Okay, but x cannot be equals to infinity. What else? You cannot simply say that your infinity minus infinity will be 0. You cannot say this, right? This does not follow the rules of algebra. Okay, also you cannot say that infinity plus infinity is equals to infinity. There is nothing, no concept like to infinity. What you can say is infinity plus infinity. Okay, infinity plus infinity will be equals to infinity itself. Okay, it is infinity itself because it is also ever increasing. Okay, so this is what you can say. Okay, so these are the few things you have to remember about infinity. So I hope you got the point about infinity. Now let's try to understand few indeterminate forms. So first, indeterminate form, I have already explained it to you. Anything here, right? And this was undefined form. So there exists no values for x for me to satisfy this equation. But this was indeterminate because all the values of x will satisfy. So I have no choice. I don't know what will the value of x. I don't know what will be the value of x. Okay, because all the values of x satisfy this equation. Okay, so it will always satisfy. Okay, so 0 by 0 is an indeterminate format. Now what about my infinity by infinity? Basically what you can do is you can convert this into 0 by 0 itself. So basically, how is infinity by infinity indeterminate? So what you can do, 1 by 0, 1 by 0, 1 by 0. Okay, what is 1 by 0? 1 by 0 is almost tending towards infinity. Just remember this thing. All these things, right? All these things are tending, exactly not equal to 0. So here, right, 1 by 0, 0 is tending towards infinity, not exactly equal to 0. Just remember, this is tending towards 0, right? Not exactly equal to 0. So this is within our defined manner. So basically, if you write 1 by 0.01, it is 10. 1 by 0.001, 100. 1 by 0.00001, much higher, right? So it is tending towards 0, but exactly not equal to 0. So this is also infinity and this is also infinity. Okay, so now I can write this like, again I can rearrange this in terms of 0 by 0. Okay, so this is how also we will solve the questions also. We'll convert this into 0 by 0. So again, this is also a indeterminate format. So I got back to this same format again. Now what is 0 times infinity? Again, right, what you can say that what you're doing, this is 0, right, and this I can write as 1 by 0. I can write, now again this is tending towards 0. So all of this, right, all of these values are tending, okay, not exact values. I will write this point. Tending towards, oh shit, tending towards 0/infinity. Okay, not exactly equals to 0/infinity. Okay, not exactly equals to 0/infinity. Okay, so yeah, this is the thing. Now what about my infinity minus infinity? So again, right, I told you this is again indeterminate format, because I won't be like simple algebra is not like, it's not possible over here. Simple algebra is not possible. So infinity minus infinity will also be a format. Okay, so it is also an indeterminate format. Okay, what is the value? I don't know. What is the value? I don't know. Okay, infinity minus infinity, can you say me what is the value? No, right? So that's why this is indeterminate. Now infinity to the power 0. So you might say, sir, this is 1, right? So anything to the power 0 is 1. You are wrong again. So this is infinity, this is going like always increasing, and this 0, right? This 0 is not exactly equals to 0. Okay, so this is, let's say, some tending towards 0, right? Tending towards 0. Tending towards 0. Okay, let me make the size smaller. Okay, so this is tending towards 0. So yeah, like you can say that very high number, right? 10,000 to the power 0.0001, 1 million to the power 0.000001. Okay, so we won't be able to like say what is the value, okay, that's why this is indeterminate. Okay, indeterminate. Then 0 raised to power 0 again, right? 0.001 raised to power 0.001. Okay, again all of these are tending towards 0, not exactly equals to 0. That's why these are indeterminate. You can try it for yourself. Right? You can put examples in the calculator. You can try it for yourself. Okay, these are tending towards 0 again, right? You can say that, sir, 1 raised to power anything will be 1 itself, but this is tending towards 0, tending towards 1, tending towards 1. Okay, 0.99999 raised to the power 1 million. Okay, what is it? 0.99 raised to the power 1 billion. What is it? Okay, like that. So this is not exactly equals to 1. If you say me exactly 1 raised to power anything will be 1 always. Okay, so this is tending to 1. Okay, like 0.99, 0.9999, okay, and etc. So here this is 0.001, 0.0001 dot. Okay, so these are the things. Now these are the basic things that I wanted to explain. So yeah, so I hope I have explained everything over here. So like for this, right, for this what you can do, again you can do the simple algebra trick, right? What you can do is, I will explain it to you. So basically what you can do, let me take this on the next page. So here I have infinity minus infinity, you might say that, sir, I couldn't understand why is this indeterminate. Okay, so how can I write infinity minus infinity? This is tending, remember, this is tending, right? So 1 by 0 I can write 0 is tending to this denominator is tending towards 0, not exactly equals to 0, else it will become undefined. Okay, so now this is again 1 minus 0. Okay, infinity minus infinity, so this will become 0 by 0. So yeah, again we get back our this indeterminate format. Okay, this indeterminate format. So I hope you got the point that this is also a indeterminate format, right? Indeterminate format. Okay, so here, right, if you want explanation, I can explain it to you. So let's take this infinity raised to power 0. Okay, infinity raised to power 0. So if I write infinity raised to power 0, whenever there is power, right, what you can do, we can use the log formula. So what I will do, everything I will convert to 0 by 0 format. 0 by 0 format is a fundamental indeterminate format. So I will write y equals to infinity raised to power 0, and then what I can do, I can take the log, right? I can take the log ln of infinity. Now if you recall the graph correctly, ln of infinity is also infinity, right? If you recall the graph, so ln of infinity is also infinity. Okay, so this y, right, ln of y equals to 0 times infinity. Okay, and again, right, so your ln of y is equals to 0 by 0, because this is what, this is 1 by 0, and I can again convert this back. Okay, I can take the exponential on both sides. Okay, and this will be equals to e raised to power, or what you can do, this, right, e raised to power your y, right, your y will be e raised to power 0 by 0. Okay, e raised to power 0 by 0, which is a indeterminate format. Okay, which is indeterminate format, we don't know. So from here also you can understand this is indeterminate, right? So like this also, do the 0 by 0 format by yourself. Okay, try to prove the 0 by 0 format by yourself and send it to me. Okay, I will put this down here. I will write this down. Okay, try a few things you should try. Okay, you try 0 by 0 and 0 raised to power 0 and 1 raised to power infinity. These two you try. Now what are not indeterminate forms? What are not indeterminate forms? 0 by infinity, right? Is this an indeterminate form? Can you say me? 0 by 1000, 0 by 1 million, 0 by 1 billion. It is always going towards 0, right? It is always going towards 0. So this is not indeterminate. It is going to a 0. It is going to a 0. Okay. Anyways, if I write 1, 2, anything over here, this will always go to a 0. Okay. So this is going towards 0. 0 into 0 is 0 itself, right? Because 1 by infinity is 0. Okay, because infinity is every time increasing, and it is almost equals to 0 itself. Okay, like this. Now what is infinity by 0? Is this a indeterminate format? Is this an indeterminate format? Now here what I can say, that 0 by 0 was in indeterminate format, but what about infinity by 0? So this 0, right, is tending towards almost tending towards 0, almost tending, but not exactly equals to 0, not exactly equals to 0. So this is tending towards 0. What I can say, this will only increase this. This will only increase this infinity. Okay, but previously I don't know what this could have done. 0 by 0, I don't know what this could have done. Okay, or what you can do. Yeah, sorry for the interruption. Again, the light got cut off. So I was explaining that this will only help it increase. This is tending towards 0, so this will only help it increase, right? This will be also equals to infinity itself, because this is only helping it increase. Okay. Again, infinity plus infinity, there, right, it was infinity minus infinity. That's why we couldn't understand. But here, right, infinity plus infinity will be again infinity itself, because this is also always increasing. The resultant is also always increasing. Okay, now infinity to the power infinity is again always increasing. 2 raised to power 2, 4 raised to power 4, 5 raised to power 7. Okay, always increasing, always increasing. So this is also infinity. Now this is interesting. 0 raised to power infinity. What will happen over here? Now this is, right, always going towards 0 itself, always going towards 0. Okay, here, right, in this case I won't be able to tell 1 raised to power infinity. I won't be able to say why, because 1.0001 raised to power 1 million can be something, right? Can be something else than 1. Can be something else than 1. It is not tending towards 1. not tending towards 1. You put these things in the calculator, you will understand. You put 1.0001 raised to power 1000, 1.00001 raised to power 1 million. Okay, you see that it is not tending towards anything. That's why it is indeterminate, because it is not tending towards anything. Like, we are not getting a final value. We're not getting any final value here, right? Here, all these equations, if you put, okay, you put 0 by anything, right? You put 0 by anything, 0 by 1000, 0 by 1 million, 0 by 1 billion, it will always be 0 itself. It is always tending towards, or like this 0, right? This 0 is also tending, right? So I can say 0.001 divided by 1000, 0.0001 divided by 1 million, always tending towards 0. Okay, now this infinity, 1000 divided by 0.001, 1 million divided by 0.0001. Okay, again, this is every time increasing, right? So that's why I can say this is tending towards infinity. This infinity plus infinity, 1 million plus 1 million, 2 million, 1 million, 1 billion plus 1 billion, 2 billion, right? This is always again increasing. So this is also tending towards infinity. Infinity raised to power infinity, I just gave you the example, and 0 raised to power infinity. Now, what is this tending to? So I can write 0.01 raised to power 1000. Okay, then 0.001 raised to power 10,000, right? What you will observe, this will go towards 0, right? This will go towards 0. So that's why we are getting a finite value for this. Okay, that's why these are non-determinate. Like, these are not indeterminate form, these are determinate, because we are getting some values, right? We're getting, like, not for this, like we're able to understand where this is tending towards, Okay, I hope we got the example. Okay, so like, let's now understand what are the steps to calculate limit at a point C, right? If there is limit, so I have already told you the steps. Now let's formally understand this. So to find the limit as x tending to C not equals to C, f of x, we have to first calculate the right hand and the left hand limits. Okay, so what is right hand limit? Generally, whenever this positive sign is not present, we assume that by default we are calculating the right hand limit. So right hand limit is equals to limit as x tends to C plus, just ahead of the neighborhood. I'm coming from right hand side of the neighborhood I'm coming from right hand side towards that particular point, right? So on the right neighborhood, okay, of the number line, okay, of that particular point. So it will be equals to simply f of x. Now I can rewrite this. Wait a second. Yeah, sorry, this was coming for a long time. So I can rewrite this as limit h tends to 0. As limit h tends to 0, I can write f of c plus h. Right? Okay. So how is this meaningful? This represents h is a very small quantity, positive small quantity, as nothing is mentioned, right? It is going to us from right hand side. So h is a very small positive quantity. It is written also here. Okay. So c plus h means just at the right hand side of c. Okay, that means I'm coming from the right hand side. Right? It is reducing. Like, if I again write the number line, okay, so this is c, this is h, c plus h, and this is c minus h, right? So I'm coming from this end, coming from the right hand side. Okay, now what about c minus h? So this is the left hand limit. So either you can write this x is tending to from minus c, like c minus, or you can write it like this. So if you are solving it graphically, you will use this. If you are solving it algebraically, you will use this. Like, you don't want to plot the graph, you directly want to solve it through the equations. Okay, so you will use this. Okay, and if you want to solve it graphically, you will use this. So graphically, you can just see the graph, right? And from there you can directly calculate the limits. So this method, right? This method is generally used graphically. You can write this graphically. Just hold on a second. And this method is used when we want to solve it algebraically. Okay, so these two are the things that is the most important thing to us. Okay, so The right hand side is called R, L. You can name it whatever you wish to. Okay, so yeah, these are the things that I wanted to explain over here. Let's go to the next step. So what is the next step? Next step is basically check if limit exists or not. So how can we check if limit exists? So limit should exist only if L is equals to R. So limit will exist only if L is equals to R, then only limit will exist. Okay, so uh, if L is equals to R, limit will exist, and limit of that function, right, will be equals to L equals to R, because both of them are same only. And there can be three cases. Okay, limit can be anything, right? It can be infinite also, it can be minus infinite also, it can be zero also. Okay, it can be finite also. Okay, so yeah, anything is possible for limit. But for limit to exist, both of these, the left hand limit and the right hand limit, have to be same, then only limit will exist. The value of limit can be anything, value of limit can be anything, right? Now, condition when limit does not exist, there can be two conditions. Okay, so when L is not equals to R, I forgot to write the not equal to. So when L is not equals to R, the left hand limit is not equals to right hand limit, then limit will not exist. We have already established this in the previous slides. Or either L or R or both are oscillatory at x equals to A. Okay, what do you mean by oscillatory? What do you mean by oscillatory? We'll understand this oscillatory behavior in the next question, right? In the next question. Okay. So yeah, let's go to the next question. So this is the next question. Okay, so what do you mean by oscillatory? Oscillatory means basically it is oscillating between two values. It is not infinity, but it is always oscillating. There is no stable value, like as your pendulum, right? Pendulum always oscillates. There isn't any stable value to it. That's how oscillatory means. Okay, so if you watch my time response control system video, sorry for the sound, if you watch my control systems lectures time response, you will understand what does oscillations mean. Okay, so like through this question also you will understand. Let's solve this question. So let's first solve this first one. We have to find the limit of f of x at x equals to 0. At x equals to 0, we have to find this f of x limit, right? So you can solve it using two ways. Okay, using the graphical method, using the algebraic method. I will solve it both ways. Okay, so let's first solve it using the graphical method. So 1 by x square, what was the graph for it? If you recall, I have given you few standard graphs, right? What was the graph for 1 by x square? 1 by x has the graph something like this, right? Just hold on a second. One by x has a graph something like this. Okay, so 1 by x square will be what? 1 by x square will be simply like this, right? Because like the negative part will be positive, because this is an even function, and anyways there is x square, so it will always give me positive values. Okay, so if you don't understand this graphically, don't worry, we will solve this algebraically also. But if you try to put this 0 over here from the negative side or from the positive side, if you try to put something very close to 0 which is negative, it will also be positive. If you try to give something very close to 0 which is also positive, it will try to go to infinity itself, right? So anyways, it is always trying to go into infinity, and x equals to infinity, okay, it is going to 0, positive 0. Okay, because anyways minus infinity square is plus infinity anyways, and 1 by plus infinity is 0 itself. Again, plus infinity square is plus infinity anyways. Okay, so yeah, that is the thing. So this is my graph. Okay, so now we have to calculate the limit at x equal to 0. So obviously at x equal to 0 it is not defined, right? So we are talking about the neighborhood of 0. So what about my left hand limit? So left hand limit, if I can observe from here, okay, from the graph, if I may observe, it is equals to positive infinity. If I am coming from the left hand side, it is going towards positive infinity. So left hand limit is positive infinity, and right hand limit, okay, right hand limit again, right? If I am coming from the right hand side towards this again, right, this is going towards positive infinity. So this is positive infinity. Okay, so like both of them are same only, and both of them are infinity, that is fine. Okay, that is fine. So it will be simply like limit exists, okay, and the value of limit is infinity. Now let's solve it algebraically. So how can I solve it algebraically? So here, right, so this was okay. Let me take this to the next page. This is the one. Okay, and I'm solving it using graphically, right? I'm solving it using graphically. Okay, if I'm solving it using graphically, so basically I can write that my shell equals to infinity, limit exist. Okay, limit exist. Okay, next is algebraically, right? Algebra is not method 2. I am to write this as method 1. Okay, so basically what will happen over here? So like what has been asked to us, we have to find limit as like x tends to 0, right? So this is 0 plus. I will first calculate the right hand limit, and what is f of x? F of x is 1 by x square. Okay, so what I can replace? I can replace my this x to h, right? H tending to 0, and I can replace my x as 0 plus h, right? Whole square. Okay, so this will be limit as h tends to 0 1 by h square. So 1 by h square, I'm not exactly putting 0 over here, I'm exactly putting a very small number, okay, and positive small number, right? Very small positive number. So this will obviously tends to 0, right? This will obviously not 0, sorry, this will tend to infinity. Right? Now what about my left hand limit? So this is right, this is my right hand limit. One by x square. Now limit as h tends to again 0. This time I will replace my x as 0 minus h, right? So again h is very small positive quantity, so anyways I'm taking the minus whole square. This will be 1 by h square only. Okay, so again if I'm like h tending to 0, 0.001, 0.0001, okay, this will also tend to positive infinity, right? So again from here also we can say the same statement, that limit exists, left hand limit equals to right hand limit equals to positive infinity. Okay, so we solved it using the both methods, that is the algebraic method and the graphical method, right? Graphical method. So now let's solve the second question. So let me solve the second question. So if I see this, right, if I see this, now like let me solve it algebraically only, let me not solve it graphically. Okay, graphically solving it will be a bit difficult for me to plot this complex function. That's why we generally tend to prefer the algebraic method. So when the graphical, like plotting the graphical method is difficult for me. Okay, so what we can do, we can calculate the right hand limit, right? We can calculate the right hand limit, which is equals to limit as x tends to 0 plus, okay, x tends to 0 plus now what is happening at sine of 1 by x. Okay, now what I can change this to as limit as h tending to 0 sine of 1 by 0 plus h. Okay, anyways, like when you are calculating the right hand limit, you just replace x with h, right, when they are tending to 0. Obviously, if this was tending to 1 or something else, then we wouldn't be able to simply replace x with h. Okay, so now what is the interesting fact? This, right, this h is a very small number. 1 by a very small number will tend to infinity. This is tending to infinity, right? So h tending to 0, sine of infinity. Now, can you tell me what is sine of infinity? Can you say it to me? What is sine of infinity? Like we will obviously, I think we have already covered this, like few oscillatory values, like what are oscillatory values. So what is sine of infinity? Infinity is all ever increasing, and sine graph is like this, right? Sine graph is something like this, if you recall correctly. And like, what do you understand by infinity? Infinity means basically I'm always increasing in this x direction, right? And it is always between this plus minus 1. Okay, so it is always between this plus minus 1. So obviously this is oscillatory. Okay, so this is oscillatory. So that is what I meant over here, right? Over here, either L or R or both are oscillatory at x equals to a. Basically L, right? L can be anything. Like for same case for R as well. Same case for R as well. For R, this will be minus sin x. This will be minus sin x. Okay, minus sin infinity. Okay, basically I can say for left LHL, left hand side, it will be minus sin x. You try to solve it by yourself, and it will be minus sin x. Basically, you will get sine of 1 by minus h. So minus I can take outside, right? For sine is a odd function. So minus of sine infinity again, right? This will vary. Our right hand limit is varying between minus 1 to 1. Okay, there is no stable value for it because x is always increasing. So my y is always changing. It is oscillatory, right? Like this, it is oscillatory. Okay, this is never stopping. This is going from minus 1 to plus 1, right? So this is oscillatory. So this also same thing only. I'm just multiplying minus sign, which won't change anything. Okay, won't change anything. This will also be oscillatory, minus 1 to plus 1. Okay, so obviously both my LHL and RHL are oscillatory. Are oscillatory, hence limit does not exist at x equals to 0. Okay, so this is very important point. So now first let's understand what are the different methods of solving limits. So the first method is direct substitution. Okay, so the most famous method is I will tell you is the L'Hopital's method. Okay, that I will teach you at the end. Why? Because sometimes using these are easier than that. Most cases you will use that method only. Okay, that method only. I will be honest, I also use that method only. Most cases, as this is an objective paper, but sometimes these methods, right, are much quicker and efficient sometimes. Okay, so you have to understand when to use these and when to use L'Hopital, because L'Hopital, like you already know, I think, uses differentiation, and the expression can become complex and tedious to solve. Okay, that's why sometimes this is preferred. So we'll learn this. Okay, then obviously L'Hopital, you already know, you will use L'Hopital only in most cases, right? So what are direct substitutions? So basically I'm directly substituting the value of that point, right? So whatever I have doing here, right, same thing I'm doing. Okay, basically directly substituting this h in the limit, directly I'm substituting. Okay, so that is already what we have been doing until now, but for this to happen, what conditions must be matched? Okay, what conditions must be met. What conditions must be met. So limit should exist. I can only directly substitute the value of that limit, right? Whatever it has asked us for that to limits to exist, and no 0 by 0 forms after substitution. If you are getting 0 by 0 form, then we have to think of some other way. Okay, what do you mean by this? I will explain. Okay, now if let's say we are getting after substitution, right? I see that I am getting a 0 by 0 format. If I see a 0 by 0 format on that particular limit, then I have two weapons with me. One is factorization, another is rationalization. So with the help of factorization, I can factor out the 0 by 0 format, and no 0 by 0 format will be left. How? We'll see, solve questions, and from there we'll understand. Now with the rationalization, basically I'm multiplying the conjugate with it. Okay, conjugate root you can say with it to rationalize it. So if I rationalize it, then also the 0 by 0 format will be vanished. So if the 0 by 0 format is vanished, then again I can use my direct substitution. Okay, so yeah, these are the flow chart of this method. Okay, so basically there were three methods. One is direct substitution, factorization, and rationalization, but basically they are doing the same thing only, because first I try to directly substitute the value of x. I see a 0 by 0 format. If I don't see, then obviously I will solve. Okay, if I see a 0 by 0 format, I will choose these two weapons with me. Then again I will remove the 0 by 0 format, and then again directly substitute the values of x. Okay, so let me solve this question, and from there we'll understand. So first things first is that they're asking us to find the limit of this particular f of x, right? And it is an NAT type. So you have to take the hint. It is not possible that limit cannot exist, as this is the NAT type, right? Limit has to exist. So you only calculate either the left hand limit or the right hand limit. You don't have to calculate both. Or even if the options, 4 options are given, and none of the options have written that limit does not exist, so limit will exist. Okay, so that is also a hint. You don't have to calculate the two limits, only calculate one of the limits, either the left hand limit or the right hand limit. So here I will write hint limit as NAT limit must exist. Okay, limit must exist. So if limit exists, then definitely like we don't have to calculate both, right? Only calculate right hand limit or left hand limit, right? Only calculate right hand limit or left hand limit. Okay, so I will calculate the right hand limit only. So now let's directly substitute this value, x tending to what? 1. So I will substitute directly x tending to 1. So if I substitute 1 over here, what happens? 1 square minus under root of 1, which is 1. 1 minus 1 is 0 again. 1 minus 1 is 0 again. So by substituting like f of x at x equals to 1, I'm getting a 0 by 0 format. 0 by 0 format, right? Okay, 0 by 0 format. So this is a problem for me. So what can I do? I can either do the factorization or I can do the rationalization. Okay, whichever suits you the best. Okay, so like what I'm observing is that this is x square, right? 3 by 2. I can do rationalization also. Okay, so I can simply multiply under root x plus 1. Okay, I can do that. So either way you can do, right? So let's do that. Let's like factorization, what you can do, I will solve this using two methods. Okay, so first I will solve this using the rationalization. So if I rationalize, right, what will happen? So this is limit this so this becomes simply what does this become? So this, okay, actually I won't be able to do rationalization because again, right, in the denominator this will anyways be 0 only. So sorry for that, we won't be able to do rationalization. that was my mistake. So we retreat, right? We retreat. So we should do the factorization. So basically what I can do, I can take common x raised to power 1 by 2 over here, right? X raised to power 1 by 2. So this is x raised to power 3 by 2 minus 1. Okay, 3 by 2 minus 1. And this is x raised to power half again. Now if you recall correctly something, that we had a formula, like for factorization you have to remember all these formulas, right? A cube minus b cube, this was a simple only a minus b into a square minus ab plus b square, right? A square minus ab plus b square. Okay, so this will be equals to simply I can write this x raised to power half into x cube. So this is x, like in this case, right, what is a is x raised to power half, because x raised to power half whole cube is x raised to power 3 by 2. Okay, that is what this is doing. So this is x raised to power half minus 1, and 1 cube is 1 only. So, and this is x raised to power half, x raised to power half whole square. So this will be 2 by 2 minus x raised to power half into 1 itself plus 1 square divide by x raised to power half minus 1. So conveniently this and this gets cancelled. Okay, so yeah, let me, like generally what happens is in objective you can do, but I can't. Okay, I am a teacher, so obviously I tend to forget to write the limit as x tending to 1. This is very important. Okay, you shouldn't forget this. Okay, so now, right, so the like the term in the denominator has vanished, the 0 term has vanished. Now I can simply substitute the values. So this will be simply limit as x tending to 1, I can simply substitute, right, directly. So this will be 1 raised to power 1 by 2 into 1 minus 1 plus 1. Okay, so again, right, in the denominator I have 1 only because this has been cancelled. So it will be simply equals to 1 only, right? So my answer to this question would be okay, am I doing this correctly? Am I doing this correctly or not? Thinking of something. Okay, I think I have messed up a formula over here. Okay, like this happens with myself also. So I have messed up a formula, so this will be plus only. You can always cross verify, right? Okay, that's what I'm thinking, because like the answer was 3 to this and I messed up the formula, right? So this is a cube, this is a square b, this is ab square, this is minus b a square b, and this is minus ab square. Okay, that is getting cancelled, so both of them can be negative. So yeah, this happens with me also. So yeah, just try to remember these formulas. So this will be plus, so here, right, this will be plus, this will be plus. So that is what I was thinking, that my this answer, right, this answer should be 3, not 1. Okay, yeah, so this is 3, not 1. Almost going to mess it up. So in the exam also, just be careful. If you have solved this question, right, just for 1 second you just go through your rough note again. Okay, whatever you solve. So it must happen that you may have made some mistake over there. So it is important to understand. So next what I'll do is I will give you this as homework. Okay? This you have to rationalize. Okay, you can see under root. Whenever you see under root, you rationalize. Okay, so this is what I'm giving you homework. This also I'm giving you as homework. Okay, this you can solve it using factorization, not rationalization, because here I have no square terms over here, no square root. This is cube root, right? Cube root. So just be careful. You have to solve this using factorization. Okay, so there is another method. Another method is like using standard limits. So before studying the standard limits, let's first understand the fundamental theorem of limits. So there are a few fundamental theorems which are fundamental. So they are very easy to understand. Okay, you don't have to remember anything. Just let's go through this. You already know all this, right? So if we have a limit as x tends to a f of x, which is equals to L, and a limit x tends to a g of x, which is tending to m. Okay, so we have two different functions. both are function of x, okay, and they are tending to some L and M, okay. So what will be the combined effect of those two? So if I add these two functions, right, f plus minus g of x, like it is written over here, right, and they are tending to same value, like x is tending to same value only, so I can also add and subtract the limits. Pretty like intuitive, right? Pretty intuitive, okay, not that difficult to understand. Again, if I multiply these two limits, right, if I multiply these two limits, like these two functions and the limits, their limits will also get multiplied. Obviously the limits has to exist as written over here, right? Next, if I divide the two functions, okay, and find the limit, obviously I can individually divide those two limits, okay, given that m cannot be equal to 0. M cannot be equal to 0, right? If m is equal to 0, this will be undefined, which you don't want, okay, which you don't want. So we have another thing, right? Like next fundamental theorems. What are the next fundamental theorems? Now here, if like I have a constant multiplied with f of x, I can take the constant outside the limit and I can solve my limit, right? It will be simply k times L, okay. I can take the constant outside because constant isn't doing anything, right? We can simply take it outside. Next is, this is interesting. If I have a power over here, right? So if I have a power over here, so basically I can also like convert this into the limit itself. So limit as x tending to a will be L only, and it will be raised to power m. Now what is the important point over here is, the given fact is this f of x has to be greater than 0. This base has to be greater than 0. Why is this the case? So basically we derive this, right? We derive this using logs, okay. So I will write, we derive this using logs. Derive this using logs, okay. And what do you know about logarithms? We know that if I have something log of f of x, right, this has to be positive quantity, right? Log of negative doesn't exist, okay. Hence that's why you can relate it with that this has to be positive quantity. Next we have f of g of x, basically the composite function. So for composite function, you can obviously take this limit right inside this g of x, so it will be f of m, okay. It will be f of m, provided that your f of x is continuous at g of x equals to m. It has to be continuous, right? It has to be continuous at m. What do you mean by continuous? We'll understand this later on. So if you don't want to solve, remember this fundamental theorem, it is fine, because this is a bit difficult to understand, okay. So obviously all the domain conditions for the function should be met, right? So like I'm putting f of n, basically f of x at x equals to m. So if my x equals to m is not lying in the domain of this f of x, then obviously I won't be able to write this, right? Because it is not lying in the domain. So that is what this is telling, and obviously the first statement is telling the same thing only, because this m has to lie in the domain. If the m isn't lying in the domain, I won't be able to substitute the m value. So let's say m is 0 and my f of x is 1 by x. Can I do limit as x tends to 0 f of x g of x, f of g of x? Can I do that? No, right? So it will tell me to find the f of 0 value. Is there a possibility? No. F of 0 is undefined, okay. So that's why these two conditions have to be met. So I hope you got the basic idea. Don't worry if you didn't got the idea. In continuity chapter, there will understand this better, okay. So I think we have to end this lecture now. In the next lecture, we'll start with standard limits, more methods for solving limits, and whatever questions I gave you as homeworks, right? So what you can do is that what I was thinking, can I give you a few homeworks? Okay, let's just take 5 minutes and solve this standard limits, right? So these are standard limits. These can be proved with the L'Hopital method, which we will learn at the last. So if you remember, very good. If you forget, you can prove it in 1 second, right? So as x tending to 0, sin x upon x will be 1, okay, because x will also become a linear function, okay. X will also become a linear function. How? When we'll do the series expansion, there we'll understand, okay. Then this, right, limit as x tending to 0 tan x by x. This the numerator will also become a linear function almost equals to x when x is very small. So x by x will be 1 again, same thing only, right? Sin inverse x upon x, same thing. Tan inverse x upon x, same. So these four you have to remember no matter what. Okay. Next is this exponential function. So here, right, another important fact is x is measured in radian, not in degrees. Okay, so you have to keep this in mind. Gate will give you easy constant on limits. Okay, they will play with units. Okay, they will give this value sine of 10 degree by something, some value, right? And you have to convert that back into radians. Then only you will be able to calculate your limits, right? Very important. X is in radians. Now, what is another standard limit? So another standard limit is e raised to power this exponential function, which is e raised to power x minus 1 by x, which is equals to log e. Just hold on a second. I will drink a bit of water. Yeah, actually, I was dry in lot. That's why, like, I was like exhausted. So yeah, let's restart again. As I was saying, right here, like this limit is a raised to power x minus 1 by x. Okay, so the value of this limit is log e of a, log base e of a, right? So just hold on a second. This is the standard result you have to remember. Now in place of a, right, if you put e, it will be simply a e. So log e is 1. That's why this becomes 1 as x tends to 0. Okay, so like how can you use this? Basically they won't obviously give you this simple thing, right? What they will give you is something like this. That they will give you some format like this, that limit as f of x, if any function of x is tending to 0, instead of x I am just replacing everything with f of x, e raised to power f of x minus 1 divided by x equals to 1. Okay, so this is not, this is also f of x, sorry. Okay, so basically as limit f of x is tending to 0, so this will be e raised to power f of x minus 1 by f of x equals to 1 itself, right? So they will give some function like this. So like what can be f of x? It can be x square minus 3x plus 1. Okay, so x square minus 3x plus 1 tending to 0, that means x will, here they will write x only. Okay, but that value x square minus 3x plus 1 will tend to 0. Okay, when will this x square minus 3x plus 1 will tend to 0? When it will tend to 0? X equals to 1? No, x equals to 1 multiplication. Okay, it will tend to 0 some value. Okay, and in that particular value this also will tend to 0 and this also will tend to 0, then only my limit value will be 1. So they will give you some form like this. We'll do this in questions, from there you will understand. Okay, again this is another log formula, like log of 1 plus x by x equals to 1. All of this, right, you can solve using L'Hospital. So if you are getting scared a bit that I have to remember all this, don't worry. If you can, very well. If you can't, then there is L'Hospital with you, L'Hospital method with you, right? So we'll learn that at the end. So like here also, what will be the format? Simply the format will be limit as f of x tending to 0. Just hold on a second. F of x tending to 0. Log of 1 plus f of x divided by f of x equals to 1. Okay, so it will be simply equals to 1. Okay, so next this, right, this is like a power formula more or less. So this becomes n a raised to power n minus 1. This you can recall like n x raised to power n minus 1, right? The differentiation of x to raised to power n. Okay, so somewhat more like that only. Okay, and this one, like I will write the analogy over here. You already know this from your class 11 12, I think. Okay, so like that only. Okay, then what about this? This is also another interesting formula, which is 1 minus cos by x square should be equals to 1 by 2. Okay, so how can you solve this basically? So what you can do is you can again rationalize this, right? So like you can solve this using L'Hopital method. Again, I'm saying repeating the same thing, but like, is there any other way? There is method of rationalization or factorization, whatever you want to say. So what I can do, limit as x tend to 0, because if I put 0 over here, what will happen? 1 minus cos of 0, which is 1 minus 1 0, and this is anyway 0 by 0 format. Okay, so what I will do, I will multiply and divide by 1 plus cos x. Okay, so if I multiply and divide by 1 plus cos x, this will become 1 minus cos square x divided by x square to 1 plus cos x, which is equals to, okay, which I don't know, right? So now what will be the interesting fact over here is, so this, right, this I can change to sine square x, right? 1 minus cos square x sine square x. So this I can change to sine square x, and this is x square, and this is 1 plus cos x. I can simply substitute this value, right? Is there any problem with this? No, right? No, there isn't any problem. So if I put x equals to 0 in this, so it will be 1 plus cos of 0, which is 1. So 1 by 2. This will be 1 by 2. Okay. And here, right, what is happening over here? So if I observe this carefully, this is sin x upon x whole square. So sin x upon x whole square. What is the limit as sin x upon x? X as x tends to 0. It is 1. So 1 whole square is 1 itself. So it will be 1 by 2 only. Okay, so from here we can understand that we are getting 1 by 2. Okay, so now I will just give you few homeworks, and this you will solve. I'll solve in the next lecture. Okay, so this is one question, this is another question. Just remember, this is in degrees, and this is also another question. Here we have power terms, right? We have power terms. So what standard limit will be used? Just try to think about that. Okay, this is also another question. Okay, here the trigonometric functions will be used. This is also another question. Okay, the power term is here, so again, right, that will be used. So this is some f of x, right? As I told, the format a raised to power f of x minus 1 divided by x, like that. So I think that's it for this lecture. I will try to solve all these questions in the next lecture, and after that we'll learn more methods to solve limits. Okay, so thank you for watching. I'll see you in the next lecture. Hey everyone, and welcome back to PrepFusion. So today we'll start the lecture 2B of engineering mathematics from the calculus chapter, right? So we were studying about the limits. In the previous lecture, we learned the basic meaning of limits, what do we understand by limits. Then we solved few questions, and we were in the continuation of how to solve limits, right? There were a few methods. I told you few methods, and in this lecture, right, I also tell you more methods, right? But before going into more methods for solving limits, I gave you homeworks, few questions. So let us solve those first, then we will we'll come back, right? We'll come back to this lecture. So I solved this question, and after this I stopped solving, right? So like whenever these type of questions are given, any type are given, that means limit exists. So either you calculate a right hand limit or left hand limit. You don't need to calculate both limits, right? That is the first point. Like I told you in the previous lecture also, but I just wanted to repeat it again. Limit exists, NAT, limit exists. So either you calculate, don't need to calculate both, right? That will just save time. Calculate left hand limit or right hand limit. Okay, so this is the first point to notice. Now next point is, we are seeing under root, right? We are seeing under root at the denominator. Obviously this is going to 0, because 1 plus 0 minus 1 minus 0, 1 minus 1 is 0, so 0 by 0. Like we have under root at the denominator. Now if I have under root at the denominator, that means that we have to rationalize this. Like whenever we have under root, like we have to either do rationalization, or what we have to do? We have to like factorize either of those two things, right? And under root present, that's why rationalize. So under root, I have forgotten the spelling of under root, I don't know. Rationalize, right? Okay, so yeah, let's rationalize basically. So let me copy this, and what I will do is I'll multiply with the conjugate of this, like real conjugate, not the complex conjugate. Like there isn't any complex number anyways. So this, right, this will be multiplied by the same thing only, but with a plus sign, right? So this will be multiplied with a plus sign, plus, right? So like what will this become in the numerator? This is still limit as x tending to 0, like this is x tending to 0 plus. We are not writing it, but like if nothing is set, then it is 0 plus only. X cube into this, right? I can copy and paste this again. And in the denominator, what does this become? This becomes like 1 plus x cube whole square. Like under root is there. Okay, under root is there. I am squaring it, so this will be 1 plus x cube minus 1 minus x cube. Okay, so this will become, okay, let me like use white because question is in x tending to 0. So this becomes like this becomes, right, this 1 gets cancelled and we have 2x cube in the denominator, and in the numerator we have this thing only, 1 plus x cube plus under root 1 minus x cube divided by 2x cube. So now if I like, sorry, 2x cube is getting cancelled because we have x cube at the top and x cube in the 2x cube in the bottom. So x cube will get cancelled and I'll be left with only 2. So if I now do limit as x tends to 0, I can substitute, right? There is no issue with that. So we are using the method 1 only. Okay, just we had to rationalize start at the start. 1 plus 0 under root plus 1 plus 0 under root minus, it is actually divided by 2, which is equals to 1 itself, right? So your answer will be 1 for this question. So pretty simple. You can calculate the left hand limit, that will be same only. Okay, now this like how will you solve this? So this, right, I don't have any under root here. Okay, I don't have any under root, so I won't be able to rationalize right now. I won't be able to rationalize. I have cubic, so I remember some formula like a cube minus b cube. I just use that formula, right? But this is not cubic. This is like this raised to power 1 by 3, not 3. So what I will do in this, what I will do, so here, right, like cubic is there, so that is the first hint. Okay, so what thing I know, that a cube minus b cube, I just derived, like not derived, I just wrote the formula in the previous lecture. So that is a minus b into a square plus ab plus b square, right? Whenever there is a minus sign over, one minus sign will be here and one plus sign will be here. Okay, so now this is a minus b, a square plus ab plus b square, right? Plus b square. So what is this? Now if I replace, right, if I replace this a and b with 1 by 3, so a is 1 only, and this b is b, let me replace this b as t raised to the power 1 by 3. And what is t? What is t? T is simply equals to because I want some form like this, right? Some form like this, and here I am getting this form. Okay, like t is under root 1 plus x square. Then like these this much difficult question may not come, but it's my duty to solve all of the difficult questions. Generally, like simple questions come, right, in examination. Like for GATE I am talking about. Mathematics is pretty simple, but 1-2 questions can come difficult. Now it's up to them which topic they choose. Okay, they may choose this limits, they may choose complex variable, they may choose vector calculus, anything they can choose, right? And linear algebra. Okay, that depends on them. So 1-2 questions comes difficult and other rest will come simple only. Okay, so now a is equals to 1, b is equals to this t raised to power 1 by 3. Okay, not under root, only 1 plus x square only. So like I am getting this form over here, right? I am getting this form over here. Okay, so what I can write right now. What I can write. So I can write that this is a cube 1 cube minus t by 1 by 3 whole cube, okay, equals to 1 minus t by 1 by 3, and we have to multiply this as well. This is 1 plus t by 1 by 3 plus t square by 3, right? So this is what we are getting. Okay, so now what I can do, I can replace this, like, anyways, if I put 0 over here, I am getting 1 minus 1, which is 0, and 0 over 0 form. So obviously I won't be able to continue with that with direct substitution. So I have to think about something else. So that is why I'm thinking about something else. Now this is this and this is this. So I can replace this 1 minus t raised to power 1 by 3 with these and this, right? With this and this. So basically I can write 1 by t, okay, divided by 1 plus 1 by 3t plus t two by 3. Now one more interesting fact, like I want to tell you this method, is that if your x is tending to 0, then what will t tend to? Here if you put x equal to 0, what will t tend to? T is tending to 1 itself. Right? So t will be 1. T will tend to 1. If x is tending to 0, t will tend to 1. Okay. So like what I will do is, just hold on a second. I can replace this everything with x also. That isn't a problem. So what I will do, this, right? This is equals to 1 minus t raised to power 1 by 3, which is basically this. Okay. So I will replace this denominator with this directly. Okay. So just hold on a second. So this will become, now what is my x square? Can you tell me what is my x square? So x square, right? X square is t minus 1. From here I can substitute, right? X square is t minus 1. Okay. So I can replace my x square like this. I can replace this variable. You have done this in your class 11, 12, I think. So I can replace this whole thing, right, with in terms of t. That will be easier for me to solve. I will just do that. So limit will change right now as x was tending to 0. So t will now tend to what? T will now tend to 1. Okay. Now this x square has become t minus 1. And in the denominator, what is this? This is 1 minus t. And we have in division 1 plus t raised to power 1 by 3 plus t raised to power 2 by 3. Okay. So this becomes so now this and this gets cancelled, right? I have a minus 1 over here. So this will be minus 1 into am I doing this right? Yeah, this is minus plus only, yeah. And t is tending to 1, so this goes above. So I'm replacing 1. Okay, just hold on a second. Yeah, this is correct only. 1 plus x cube. I'm thinking about something else. If I replace this, right? Yeah. So this will become minus 3. Basically I have just replaced t with 1 because this has got cancelled, right? So this 0 by 0 form has gone. So I'll be only left with this. Okay, and there is always obviously a minus sign over here. So this will be minus 3. Answer for this question, right? So yeah, this is the answer for this question. So now basically we'll start the okay, we have also this question also. Basically the fundamental theorems we use, right? Those also we have right now. So yeah, let's solve this. So this is pretty easy, this one, first one. So basically here what you have to do, so like what was the standard limit? If you recall correctly, it was sin x upon x, limit as x tends to 0 equals to 1. It was this, right? Sin x upon x. But this, right, this is something different. This is sin 4x upon x. So what we have to do, we have to make this this, right? Whatever inside the sin x and in the denominator, both of them same. Okay, so basically you have to remember this thing, that sin mx upon mx equals to 1, right? Limit x tends to 0. Okay, so we have to somehow get a 4 over here. How can I get a 4? So if I get a 4 over here, to make this whole function same, I have to again like multiply 4 in the numerator also. This 4 will cancel, I will remain with 1. Okay, so basically what you can do is you can divide and multiply 4 from the numerator and the denominator. So this will be 1 times 4, because this whole thing has become 1 and this is 4 only, so this will be 4 only. So answer to this question will be 4 only. Pretty simple. Now this, right, this is very interesting because this x, right, x is in degrees, x degree. So obviously the formula that I gave you, sin x upon x, limit as x tends to 0, sin x upon x equals to 1, that is for a what? That is for when the x is in radians. So now, like, I have to convert this, right? So x degrees in radians, what will it be? So 180 degrees is pi radians. 1 degree is 1 by 1 degree is pi by 180. X degrees will be pi by 180 into x. So pi by 180 into x. Simple unitary method, right? So yeah, this will be my conversion. Okay, this will be my conversion. So I will just replace this x degree, right, with this. Okay, so limit as x tends to 0, sine of pi by 180 into x. Now again, right, I don't have pi by 180 in the denominator, so I have to produce that and I will multiply that in the top. Okay, so that they get cancelled. But this form, right, this form will be 1 and this will be pi by 180 because this is a constant. I can take this out. This has already been taught in the fundamental limits, right? Fundamental limits part. So this is 1 times pi by 180, which is pi by 180 itself. Okay, so pi by 180 will be answer to this question. Okay, so let's go to the next question. So here, right, like, what is this next question, like, what is the expression? So what things I can observe? So like, whenever you're trying to solve with standard limits or substitution, right, you always try to take focus on the expressions. We have sin x over here, so I may have to use that sin x over x formula. I have 15 raised to power x, 5 raised to power x, 3 raised to power x, so I may have to use that exponential formula, right, this power formula. Okay, you have to remember this. So a raised to power x minus 1 divided by x is log a, or ln a, you can say. Okay, so we may have to use this. So like, what other things I can observe? That this 15, right, is a multiple of 5 and 3. Okay, so I can do some common business over here in the numerator, and in the denominator I have to produce, like, I have sin x, I have to produce x also, but I have to produce 2x, like x square, because this is sin square x. What do you mean by that? So basically, if I say that sin x limit as x tends to 0, sin x upon x equals to 0, right? So what another thing I can say is that limit as x tends to 0, sin square x, okay, sin square x by x square, right? I can rewrite this as like this, limit as x tends to 0. I can take the limit inside this square function, right? Sin x upon x whole square. I can do this. Okay, so that's how you calculate this, right? So yeah, basically that is what exactly I will do. I will try to produce x square over here. So how can I write this? So this will be, right, this is 3 15, no, not 15, sorry, 5 into 3 raised to power x minus 5 raised to power x minus 3 raised to power x plus 1. Okay, sin square x limit as x tends to 0. Okay, so now what I can do, I can take common either 5 raised to power x or 3 raised to power x. I will take common 5 raised to power x from these two, right? So I will be left with 3 raised to power x minus 1 minus, I can take common again, 3 raised to power x minus 1 sin square x. Okay, so now what I can take common? I can take common 3 raised to power x minus 1, 5 raised to power x minus 1. Okay, because like I can take common 3 raised to power x, right, from both of this. So this will 5 raised to power x minus 1, 3 raised to power minus 1, and I have a sine square x here. So I forgot, like it may so happen sometime I may forgot to write the limit, right? That may happen. Limit x tending to 0. Here also limit x tending to 0. Okay, now what is the interesting fact? Now I have to produce x square, right? And also in the denominator also I have to produce x for each of this. So it gets sorted out by itself only. So that is how they give you the questions mostly. So this, right, I have to separate, I can separate the limits out. So this will be limit as x tends to 0. This is the first bracket, which is 3 raised to power x by x, okay, times 5 raised to power, I can write this in the denominator, not here, minus x by x, okay, then this, right, I have produced 2 x's over here, I need 2 x's over here also, okay. So what I will do, I will just write this whole square. So this x square and x square gets cancelled, nothing is changed in this whole equation, right? Nothing is changed, just that the way I write this equation has changed, okay. So limit as x tends to 0 is this. What will this produce? This will produce what? Log e3, right? ln3 this will produce. And what will this produce? This will produce ln5 this will produce into what? This is 1 square, right? 1 by 1 square, because this is in denominator, anyways that is 1 only. So this will produce 1 square. So my answer will be ln3 into ln5. Is there any formula for this? No, right, there isn't any formula for this. You can't say that I am multiplying or adding these two logs. Like multiplication of log doesn't have any formula, addition of logs have formula, okay. So this next one, right, next one is interesting. You have to find the limit as x tends to 0 tan x minus sin x by x cube. So you have to use that sin x upon x formula or something else, some trigonometric standard limit, right? So like we can solve this using the method of L'Hopital, okay. That is very you don't have to use much brain with that, but that will be lengthy. When we'll solve, you will see, okay. So here, right, what we'll do, first I will try to like make all the like terms. So whatever, like I have to get tan x upon x, I don't have. I have to get sin x upon x, I don't have. I have x cube, right? So what I will try to do, I will convert this into like sine by cos, because I know one formula, that 1 minus cos square x is divided by x square is half, right? That standard formula I know, so I have to find that, okay. So that is why I am dividing this into sin x upon cos x. So this, right, limit as x tends to 0. Like whenever you don't find your way, you just go ahead with whatever you're thinking and something might click, right? So sin x upon cos x minus sin x divided by x cube, okay. So next what I can do, limit as x tends to 0, this will be sin x minus sin x cos x divided by x cube, okay. So what else can I do? Like there was this formula, right? 1 minus cos x by x square. So yeah, now what I am observing something, that if I take the sin x common, right, I have 1 minus cos x and I have x square also, extra x is there. What I'll do with that x, I will say. So this, right, limit as x tends to 0. Now if I take the sin x common, okay, 1 minus cos x divided by x square, extra x is there, I can write this x like here. And what we're seeing something familiar, right? We're seeing sin x over here and 1 minus cos x by x square. So this, right, this will give me 1 by 2 and this will give me 1 only, right? So this is 1 times 1 by 2. I can break the limits, right? Fundamental theorem limits, there are two products, okay. I can individually calculate the limits. So this will be 1 by 2, okay. So let's go to the next question. Now this next question is very interesting. Why? Because like this is like exponential only, but at the exponential, right, we have a function itself, not a constant, not x, we have a function of x, okay. So this is not in the standard format. Also what you remember is this is not going to pi by 2, Okay, like sorry, this is not going to 0, x is not going to 0. Okay, it is going to pi by 2, right? So what you can do, like either there are two ways. Either you solve it using like the mathematical approach, right? You convert this into h and from there you solve, or you can change the variables. You can change the variables. So we'll try to solve it using two ways, right? Two ways. First, using the mathematical approach. Okay, so using mathematical method 1, mathematical approach. Okay, so what you will do, basically, as limit x is tending to pi by 2, like it is talking about the right hand limit only. So or you can do left hand limit also, both will be same. So what you can say is h is tending to 0, h is a small positive quantity, and I will replace my this cos, right, with x plus h, right, x plus h. Okay, and this will be minus 1 only, not x, sorry, 0 plus h. I forgot myself. This will be 0 plus, because I am replacing 0 with 0 plus h, very small quantity. Okay, this is 0 plus h minus pi by 2. Okay, so next what happens over here? So this, right, I can write limit as h tends to 0. This is 2 raised to power minus cos of h minus 1 divided by h into h minus pi by 2. Okay, so next what I can do, this minus cos h, right, I can replace this, right? If you recall correctly, this minus h I can replace something. Okay, what I'm okay, sorry, I made a blender over here. This will be pi by 2, right? X is not tending to 0, x is tending to pi by 2. So like we are also in that same zone again, like we always assume that x is tending to 0. My bad. So this will be pi by 2, this will be pi by 2, and this will be pi by 2. Okay, so yeah, this whole thing will get changed right now. So what is cos pi by 2? So like if you want to, like I also tend to forget this, like cos pi by 2 plus x or sine pi by 2 minus x. I also tend to forget this. How you can remember this is, like I've taught this in my network theory class. So your cos, right, is in the x-axis. If you know the equation circle, like your cos theta was in the x-axis, if you remember correctly. So this is my cos x, and sine, right, will be always in the below of this. Sine x will be always in the below of this, right? Sine x. So I have to go 90 degrees in the clockwise direction, which is negative angle. If you remember correctly, in a coordinate system, if I go in the anti-clockwise direction, it is positive angle, and if I go in the clockwise direction, it is negative angle. So this is talking about pi by 2 plus h. So I have to go in the anti-clockwise direction. So what will be this? This will be minus of sine h. Okay, this will be minus of sine x, right? So this will be minus. So I will replace this, right, with simple minus of sine x. Okay, so this will be 2 raised to power minus of sine x. So this is anyways I will replace minus 1 pi by 2 plus h, and this is h only. Okay, so yeah, this is the case. Now how to solve this? So basically what you can do right now is, now if I make, okay, this is not sin x, actually this is h. Okay, so let me rewrite these things. So here, right, like I have something exponential like here, okay, and this pi by 2. So what the main thing is this, right, I can simply replace this h with 0. There is no issue with this, because this is not producing any 0 over here. So I can take this outside of the limit and like without h. So this will be 1 by pi by 2. Okay, limit as h tends to 0, then I have 2 raised to power sine h minus 1 by h. Now this is sine h and this is h. So can I use that formula of ln2? No, right, I can't use that formula. Why? Because the simple funda is this and this has to be same. Okay, this is, if this is signage, this has to also be signage, so I have to produce an extra signage. So what I will do, I will just multiply and divide by sin h itself, right? Sorry, sin h. Okay, so next what will happen? So this, right? So this is 2 by pi limit as h tends to 0 to raised to power sin h divided by sin h into sin h by h. Okay, so like now I can individually solve the limits. This is same and this is also sin h by h is solvable, right? So this will be 2 by pi into e raised to power x, ln a, which is ln 2 times sin h by h, which is 1. Okay, so my answer would be 2 ln 2 divided by pi. Okay, so this will be my answer to this question. So now we'll start the topic of this lecture. Okay, so let's first understand how we can solve infinite limits. So beforehand I was solving for all of those limits where my x was tending to 0, but this time, right, my x is tending to infinity. So this is an issue. Like we generally tend to find for 0 by 0 format, right? 0 by 0 format, but now I have infinity by infinity format. Basically this, right? If my x is tending to infinity, this numerator will tend to infinity overall, and if my denominator is like this, x is tending to infinity, my denominator will also tend to infinity. But previously, like while showing you the indeterminate formats, I told you that infinity by infinity can be converted into 0 by 0. How? What you can do, you can simply assume that x is tending to infinity, right? X is tending to infinity. That means what? That means 1 by x will simply tend to 0. If x is tending to infinity, 1 by x, like very large number in the denominator, will tend to 0. Okay, so this, right, 1 by x I can assume as h. Okay, h tending to 0. So I can replace this x, okay, with 1 by h, and from there I can totally solve this limit. That is the 0 by 0 formula. Now what is the other method? Like this is one of the methods. This is method 1. Okay, basically the method 2 is simply the like the refined version of this. Okay, so basically what we do, we divide, like this is what we'll do generally when we have been given a infinity by infinity format. So we'll divide the numerator and denominator by the highest power of x. So let's say it was x square, highest power was x square over here, and here it was x. So we'll divide the numerator denominator by x square, the highest power between the numerator denominator, right? Okay, highest power of x. Now the thing is, if my m is greater than n, what do you mean by m and n? So L is this, right? L is the limit as x tending to infinity f of x. Okay, and x is tending to infinity over here, and like I can say like m and m. M is the highest power of numerator of x, and n is the highest power of denominator of x. Okay, so here, right, here it will be not defined. Why? Let us take an example. So limit x tending to infinity x square plus x plus 1 plus x plus 1. Now if I divide the numerator and denominator by the highest power of x, which is the highest power over here, it is x square. So if I divide by x square, what will happen? Limit as x tends to infinity, this will be 1 plus 1 by x plus 1 by x square. This will be 1 by x plus 1 by x square. Now in this case, right, if I tend my x to infinity, this will tend to 0, this will tend to 0, so this will remain constant 1. Okay, and in the denominator this will tend to 0 and this will tend to 0, so I will get something like this 1 by 0 format, and I won't be able to further reduce this. Okay, I won't be able to further change this, so this will be not defined, or you can say undefined, or you can say infinity. Okay, like after seeing the next two cases we will understand, like if you are not able to grasp this concept. So here, right, now if my m is equals to n, if the order of the numerator is same as the order of the denominator, so m is equals to 1, that means this I can say that it is something like this, right? X square minus x plus 1 divided by x square plus x plus 1. Okay, hence the order of the numerator and denominator are same. Okay, so if I divide by x square on both numerator and denominator, what will happen right now? So obviously I forgot to write the limit thing, so let me just reduce the size of this and do this. This is limit as x tending to 0. Okay, then what do you do? Then we divide by x square. So then if you divide by x square, this is 1 minus 1 by x plus 1 by x square divide by 1 plus 1 by x plus 1 by x square. Now sorry, this is not 0, this is infinity. Now if you observe this one thing, right, if you observe this one thing, that if I now like say that my x is tending to infinity, if I now say x is tending to infinity, what will happen? So basically this, right, this will tend to 0, 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 but this, right, are constants, so that it will be simply 1 by 1. I can replace my x equals to infinity, very high number, so it will be simply 1 by 1, which is equals to 1. So I am getting a finite number over here, and if you just simply calculate the left hand limit also, you will see the same thing only. Okay, you will just replace like with minus h and you will see the same thing only. Okay, so yeah, this will be your answer. Basically limit will exist and limit will be a naught by b naught, which is the coefficient of the highest powers. Okay, and it will be non-zero. Okay, it will not equal to 0. Okay, now next, if my power of denominator is greater than numerator. So intuitively, how you can understand, like intuitively, if you want to understand, right, if my power of numerator is higher than the denominator, so this is increasing at a higher rate. So x square infinity, like infinity square, will be higher than normal infinity. That's why numerator will be increasing at a higher rate than the denominator. That's why it becomes undefined or not defined. Okay, in the first case, as the power of numerator is higher. Next, here power of both numerator and denominator are same, so it depends on the coefficients itself. Next, here the power of denominator is more than the power of numerator, hence denominator is increasing at a higher rate than the numerator, hence this will tend to 0 because denominator is increasing at higher rate, right? So if denominator is increasing and numerator is, let's say, constant, then obviously it will tend towards 0, right? That's why this is tending towards 0. Intuitively you can understand. Or let us take an example again. So here again I will take, right, limit as x tending to 0, x plus 1 x square minus x plus 1. Okay, not 0, like this is the bad habit, right? We always tend limit to 0. It is not tending to 0, it is tending to infinity. So now if I divide by highest power from both numerator and denominator, this will be 1 by x square, so not 1 by x, 1 by x only, plus 1 by x square, 1 minus 1 by x plus 1 by x square. Okay, and now if I replace like x with infinity, right? If I replace x with infinity, what will happen? If I replace x with infinity, this will be 0, like this will be 0, right? Everything will be 0 in the top. 0 plus 0 divided by 1 minus 0 plus 0, right? So overall it will be 0 only, right? Overall it will be 0. So that is what I was saying, as the denominator is increasing at a much faster rate than the numerator, hence overall the limit will be 0. Limit will exist and it will be equals to 0 itself. Okay, so yeah, this is the case. Okay, so next, right, let's do a few questions about infinity by infinity format, and like we'll like get along with this, right? To get along with this method. So here, right, n is tending to infinity. This time x isn't variable, like it may so happen x isn't always variable. So n is tending to infinity, and at the numerator I have n square, and at denominator I have n. So you might say, sir, this is a linear, right? N is a linear thing. So like this power like the power of the numerator is higher than the denominator, hence it will be undefined. Limit should not exist. But here we haven't given NT, so limit should exist, right? So what is wrong here? So if you observe this carefully, right, this is simply not that polynomial equation. Okay, this is right. This is a series. This is series of n numbers. Okay, n natural numbers. And I hope you have learned this in aptitude. If you have studied from Himanshu, that the summation of series of natural numbers, okay, will be what? In natural numbers will be n square, or you can say n into n plus 1 divided by 2. You have to remember this. This is like pretty standard, and I hope you all of you already know this. N into n plus 1 divided by 2, right? So I will just replace this over here. Then I will compare it with a polynomial equation. So previously it wasn't in the polynomial form. It was in the series form. Now it is in the polynomial form. Okay. So yeah. So this is n into n plus 1 divided by 2. Now if you observe this carefully, right, if you observe this carefully, that basically the power of the denominator and the numerator are same. The power of the denominator and numerator are same, right? So like we will get some finite value over here. So if I divide by n square on both sides, what will happen? So this will be simply 1 divided by, I'm divided by n square. So 1 n has been cancelled over here, and 1 n will be cancelled over here, right? So this will be, if I divide, this will be 1 by 2 plus 1 by n. Okay. So simply, if I now tend like this to infinity, right, n to infinity, this will go to a 0. This will be finite, half only. So 1 by half is 2 only, right? So my answer will be 2 in this case. Okay. Answer will be simply 2. Okay. Pretty simple, but these types of formula based question comes up, right? So you have to remember the like the series formula. Now let's solve the next question. So here, right, the interesting fact is this time instead of positive infinity, it is tending towards negative infinity. So what should you do? You can do one thing, that you can transform this variable, right, to positive infinity. How you can transform? So you can assume a variable like it is tending towards negative infinity. I want, like, my standard form is this, right? My standard form is this. Okay, it should tend towards positive infinity. That is my standard format. So what I will do, I will just take a variable which is of opposite sign. Let's say y equals to minus x. Now in this case, if x is tending towards minus infinity, then can you tell me what is y tending to? What is y tending to? Y will tend to positive infinity. If x is tending towards minus 5, y will tend to plus 5, because it is the negation of the other, right? The negation of the other. So it will be plus infinity. Okay, so now, right, now so let us replace this. So I will replace everything x with minus y. So limit, I will x, so what is my x equals to? X will be equals to minus y, right? If I multiply negative sign on both sides, x will be equals to minus y. So this will be like x is replaced to minus y. This will be minus 3y. Basically, what is the crux? Crux is that I will replace like the coefficient, change the sign of the coefficient of the odd powers, right? Odd powers, because even powers anyways they are getting squared. So negative infinity square and positive infinity square are same only. But for odd powers, the coefficient are getting changed. So to not do that manually, I'm just replacing this with minus x. Okay, to do that automatically, to not take much pressure in your brain, right? So yeah, that is what happened. You might observe that the odd powers, the coefficient, sign of the coefficient will get changed. This, right, this become minus 3. Okay, you might observe this. So this is minus 1, and this is now this minus 1, right? This is 0 power, x to the power 0, that is even power. And again, right, under root we have minus y whole square, which is again even power, right? So this is equals to, so limit as y tending to infinity minus 3y. So now, right, now I can divide. Okay, let me just do this first. This is y square plus 1. Now I can divide by highest power. What is the highest power this time? If you like observe this carefully, the highest power is y raised to power 1 only, because we are taking the under root, right? So here if I take the under root of y square, it will be y raised to power 1. So highest power on both numerator and denominator is y raised to power 1. Or you can, what you can do, you can take this y square common, and in the outside what you'll get, y raised to power 1 only. So the highest power in numerator and denominator is y raised to power 1. So this will be minus 3 minus 1 by y divided by if I take this under root, right, this will be 1 plus 1 by y square. Now if I like say limit as y tending to infinity, okay, now if I do that, what will happen? Like this, right, this will go to a 0, this will go to a 0, and this will be minus 3 divided by under root 1, which is minus 3 itself. So minus 3 minus 0, 1 plus 0 minus 3. Okay, so this will be the answer to this question. Pretty simple. Okay, like these limits question, right, you will be solving in seconds, but this limit concept will be used in continuity. There mainly you will use the limits concept. Okay, so here, right, this is also another thing. It is like our x is tending to infinity, so this is something like infinity, infinity minus infinity. So this format is infinity minus infinity. This is a new format, right? Infinity minus infinity. And I told you, right, how we solve that format. It was basically 1 by 0 minus 1 by 0, 0 by 0. Okay, so like here what you can do, you can again rationalize this. Generally what is the tendency to rationalize the denominator, right? Now we are rationalizing the numerator. So what you can do, like here we have under root, right? So from there you should take the hint, right, whenever we have under root. So we will rationalize it. Anyways, this is not in 0 by 0 format, so you won't be able to solve with that L'Hopital method, which you will learn in the next lecture. Okay, so yeah, that is also a heads up. So this is x square I'm rationalizing it, right? So I will just multiply with the conjugate x. This will be so this, right? So what will the numerator become? Numerator will become this x square plus x, like this will be whole square minus this x square, right? This whole square minus x square. So x square gets cancelled. Okay, x square gets cancelled, and I'm remained with this, right? X square plus x plus x. Now, okay, just hold on a second. I always forget the limits. Always forget the limits. So this, right? if I take x like x square common from inside, so outside it will be x only. 1 plus 1 by x plus x only. So I can take x common from this whole thing, plus 1. Okay, so this x will get cancelled out, this x will get cancelled out, and I can simply replace my x with infinity. So this will go to 0. Okay, so I can cancel these ones out. So limit as x tend into not 0 anymore, we are directly tending into 0. So this is simply 1 divided by under root 1 plus 0 plus 1, which is 1 only. Okay, which is 1. So answer to this question will be 1. Okay, so like these were few ways to solve infinity minus infinity limits. You with more questions, right? With more questions you will be able to solve. So your task is you have to solve more questions, right? So I'm not solving every question. Okay, you have to solve yourself. That's how you will be able to clear your concepts. So what is the next method? So next method is series expansion method. So in this, right, you have to remember few series, okay, new few expansions of important functions. What are the important functions? Like 1 plus x raised to power n. This is like a binomial function, right? So like a binomial function, like if you remember correctly, it was like this 1 raised to power 1 into this nc0, then this nc1, then nc2, nc3, like this it was going on, right? It was going on. Okay, so if you recall correctly everything, so this 1, right, anything raised to power 1 is 1 itself, so it doesn't matter. So if you remember like binomial function, then you will be able to recall this formula. Okay, this is like that only. Like if you recall the formula, it was like, yeah, sorry, just the iPad got crashed that moment. So like as I was explaining, right, so what you can take the analogy from was this binomial expansion, where we used to write nc0, then nc1, right, nc1 into x, okay, plus nc2 into x square plus nc3 into x cube. But what is the difference with this and that, like with this formula and the written in the top like this, right? This is valid for n as a fraction also, okay, n as a real number. Okay, so this is valid only for integers, okay, for integers, and this is valid for fractions. Okay, this is valid for fractions. So yeah, this is the difference. So here you can put any real number, and this series will follow. So this you have to remember, right? 1 plus x to power n is this. Now next, what is next? Next is e raised to power x. So this is again pretty like simple to remember, like 1 plus x 1 plus x square by 2 factorial plus x cube by 3 factorial. Pretty easy to remember. Like all summation, all addition, right? How to remember? All addition will be there, right? All addition will be there. Anyways, you know that e raised to power infinity is infinity, so there has to be addition, there can't be subtraction, right? Then what else? What are the key pointers? Next pointer is, you can remember like this: 1 by 0 factorial plus x raised to power 1 by 1 factorial plus x raised to power 2 by 2 factorial plus x raised to power 3 by 3 factorial, and so on. Okay, you can remember it like this. Now can you tell me, if you know this formula, right? If you know this formula, can you tell me what will be e raised to power minus x? Okay, what will be e raised to power minus x? Because it will help us to derive the other formulas, okay, with exponential function. So you just need to remember this, okay, and remembering this is pretty easy, I know, because I myself have remembered only this, and the other ones if I tend to forget those, right, I used to derive from here. Okay, I used to derive from here. So they said I will replace x with minus x, nothing else, right? I'll just replace x with minus x. That is what has been changed from this top equation and the bottom equation. Okay, so this will be minus x plus minus x whole square by 2. So just replacing x with minus x. Then minus x whole cube divided by 3 factorial. So this will be 1 minus x, and this is minus x whole square, so this will be x square by 2 factorial minus x cube by 3 factorial and right. So this is this, and this is my e raised to power minus x. So this, right, you don't have to remember, you just remember this, and like just by observation you can see that if I replace my x with minus x, this will become like the even powers will remain same, the odd powers will change their sign. That will happen. So yeah, this is also another very important formula, and from this, right, we'll derive the other things. Oh no, shit, just hold on a second. Yeah, so let's go to the next formula, that is a raised to power x. So how can we represent our a raised to power x? The difference is like here, right, this exponential function is easier to remember. The difference is with this x an extra term is coming. Okay, with this x an extra term is coming, extra term, like previously this was 1. Why? Because log e of e is 1, because ln e is 1, right? 1, because base and the this uh, base and this log base e and e, both of them are same, right? So if they both of them are same, then obviously it will be 1 only. So this is extra term, and you can take the analogy from log base e, right? So you can take the analogy from here. Previously this was 1 over here, it was hidden, it was 1, right? So yeah, you just remember this, and from here you will be able to remember this, right? So yeah, like this is pretty simple. Or what you can do, there is a formula, if you remember correctly. Okay, I have taught this like in border plots, I have taught about logarithms, I have basics of logarithms. I don't have time to go over those. So you can replace this, right, with the exponential like this. Okay, e raised to power ln a raised to power x. Okay, this you can replace, and this x, right, will come in front. This x will come in front because e and ln will get cancelled, and I will be remained with a raised to power x only, and this x will come in front. So if this x comes in front, this will be x only, and then, right, so my power this time, my power instead of being x has been changed to x ln a, and that is what exactly what I'm writing over here, right? So yeah, you can remember it like this also. So from x my power has become to x ln a. So that is what exactly what I'm doing, right? I'm simply writing x ln a over here, then x square ln a square, then all of these things, right? So yeah, that is it. Next is log of 1 plus x. So what is the expansion of log of 1 plus x? This is very interesting. Okay, now this one, right, like this one is pretty interesting because this has alternating signs with it. This has alternating signs. So what will happen over here? So you just have to remember this, that logarithm has alternating signs because something has to be different, right, with exponential. So alternating signs. Okay, so this, right, so x minus x square by 2, this is x minus x square by 2. Okay, what I was saying, yeah, this is alternating sign, right? Fine, if this is 1 plus x, now if I change this to 1 minus x, so there is no other option. You just have to remember like x by x square by 2, similar to exponential only, but instead of factorial in the denominator we have simple numbers. Okay, simple natural numbers, right? So like that you can remember. Next is log of 1 minus x. Don't worry, I used to tend to forget this many times, so I had put this in short notes and I used to revise this like constantly, right? So yeah, I also don't like wasn't able to remember all this, right? I used to put those in short notes and then like again revise again and again and again, right? So this is again x. Now x, right, I will replace with minus x. X will be replaced with minus x. So this will be minus x. This is minus, like odd powers won't change its sign obviously. Okay, so minus x square by 2 minus x cube by 3 minus x raised to power 4 by 4. Okay, so yeah, this will be the expansion of log of 1 minus x. Now can you tell me what will be the expansion of log of 1 log of x simply? What will the expansion of log of x? So simply what you can do, you can write log of x, right? Log of x you can write, like you have to convert this into this form because the series is beautiful for this format only. Okay, that's why we remember this format, and from this format you can obviously go to the other formats. So this will be simply I can write, like, I have to put a 1 over here. If I put a 1 over here, I will obviously have to remove this one. So how will I remove this one? So what I will do, I will subtract 1 minus x. Okay, then this, right here it is minus x only, but x, instead of x I will replace 1 minus x. So everywhere I will replace 1 minus x instead of x. So replace in this, right, in this above formula, x to 1 minus x. Okay, replace x to 1 minus x, and that's how you will get your formula for log of x. Okay, you don't really remember, you just need to remember this, and like if you're in a crunch, okay, then you will derive there, right, in the examination. I also don't used to remember, I used to derive, right. Now next, sin x. So sin x has this particular series, so everyone will tell you to remember this, but if you are not able to remember, you can remember this, right. This is the basic format of sin x. So this is e raised to power ix minus e raised to power minus ix by 2i. How you remember? Basically, what is like polar form of exponential, if you remember correctly, complex number polar form, right? E raised to power I theta was equals to cos theta plus I sin theta, right? I sin theta. Now e raised to power I theta is cos theta plus I sin theta, then minus e raised to power I theta, right? Sorry, e raised to power minus I theta, which is cos of minus theta, which is cos theta only, and minus I theta, and I'm subtracting this, so the cos theta gets cancelled, and I get 2 sin I theta in the numerator. Okay, 2i sin theta, right, in the numerator, and obviously I need only sin theta, sin x, so I need to divide by 2i. That's why I'm dividing by 2i. Okay, I hope you got this point. If you don't, just revise that. What is e raised to power I? I write this, and the task for you is derive for yourself. E raised to power I theta is equals to cos theta plus I sin theta. Okay, so this is what e raised to power I theta is. So now, right, you can you can write this exponential as a series function, which we have already learned over here. Now if you write this, okay, and then subtract this, what will happen? The thing is that we are writing e raised to power minus ix, right? So what are the common things between e raised to power ix and e raised to power minus ix? What are the common things? The common things are, if you observe this carefully, common things are the odd powers, because odd powers won't change their sign, even powers will change their sign. Okay, so sorry, I'm telling the opposite. Even powers will not change their sign, but odd powers will change their sign. So if odd powers are changing their sign, what will happen over here? So basically the common terms are the odd even terms. Okay, even terms are common terms. That's why you don't see any even terms over here. All the even terms get vanished, because here, right, this is also x square by 2 factorial, this is also x square by 2 factorial. They get vanished. Okay, so they get vanished. And next is what? Next this is x minus like the odd powers remain. So x cube by 3i, x to the power 5 by 5i, all those things will remain. And what will the interesting fact over here? The interesting fact over here will be it will be of negative sign. Why it will be of negative sign? Because I have a I in division as well. That's why it will be of alternating sign. Okay, alternating sign. So how will you remember? Point 1, odd power, point 2, alternating sign, right? So yeah, this is how we remember, and you just derive and you will understand. You will get back to this series. Now we have another function, sine hyperbolic of x. So sine hyperbolic of x, the difference is just this imaginary terms, right? They are vanished, they are not present. Okay, so it will be only plus. Due to this imaginary term, we are getting negative. Now due to this non-imaginary term, we will always get positive, right? So for this, how you remember? Don't need to remember anything. If you just remember this, that is good enough. So no imaginary terms. Anyways, here also we don't have imaginary terms, because this is magically getting vanished because I'm dividing by imaginary number. But just to understand these two things, right? Okay, and again, right, sine always has odd powers. Sine is an odd function, Sine is a odd function. Sine is a odd function, right? That's why it will have odd powers. Okay. Next, let's understand cos x. So what is cos x? So cos x is basically I'm adding these two again, right? You just like write in terms of this, and you will see you are getting back cos x only if you replace e raised to power ix in polar format. So here, right, again the sign is alternating, but we have only even powers. Because this time, right, what are getting cancelled? The like common terms will be remain because I'm adding these two, and the uncommon terms like the negation, right, negative things will get cancelled because I'm adding, right, plus minus I'm adding, so they will get cancelled. So this, right, simply you can remember like this will be even powers. Okay, so again, right, sign change, alternating sign. Okay, so again, right, hyperbolic, the powers will be same, the sign will not change. Okay, sign won't change. Okay, imagine there won't be any imaginary term over here. If you observe, there won't be any imaginary term. Okay, now let's come to tan x. Now unfortunately for this I don't have any choice. You have to remember. If you don't want to remember, right, like then also you have to remember. I have no other choice, because like what you can do, what is tan x? Tan x is sin x upon cos x, right? Sin x upon cos x. What you can write? Sin x e raised to power ix minus e raised to power minus ix divided by 2y, and cos x is e raised to power ix plus e raised to power minus ix divided by 2y. 2y gets cancelled, and you are remained with only this. Okay, so after this, like we can't go any further, right? We can't go any further. So this you have to remember, there isn't any term, there isn't any choice. But what you should remember is that these three terms, right? Just remember these three terms. Okay, just remember these three terms. I also tend to forget these three terms, but that's fine. Okay, I can forget sometimes, but you are preparing it, you have to put this in short notes, and you have to remember these three terms. So remember, okay. So like I want to go into few points which I told you earlier, right? I told you that like standard limits. I told you that limit as x tends to 0, sin x upon x is 1 itself. You can visually understand that like as like I go from both neighborhoods, right? Like it will be 1 only. Okay, because why will it be 1? If you observe here, sin x as a series is written like this. Now if I divide by x, okay, then this will be 1, this will be x square by 3i, x to the power 4 by, not I, sorry, x to the power 2 by 3 factorial, x to the power 4 by 5 factorial, right, sorry. Now if I make my x equals to 0, if I make my x equals to 10 to 0, so all of these terms, right, will get vanished. I'll be only remain with this one. So I have only this term left. So obviously my answer to this limit will be 1. But what is the catch over here? The catch over here is I'm not, like when I'm calculating the limit, right? When I'm calculating the limit, I'm not exactly putting 0. I'm putting near about 0, in the neighborhood of 0. So something very small to 0, or something slightly higher than 0. And this is x square, right? Now this is x square, and I'm subtracting over here. So there is subtraction over here. Okay, now if there is subtraction over here, what happens? This will be something smaller than 1, something like very minuscule, but something smaller than 1, right? So this will be something smaller than 1. So That is the interesting fact you have to note over here. So this, right, this will not be exactly equals to 1, this will be something smaller than 1. Okay, and why is this important? Why is this important? Because this is important because I'm talking about the greatest integer function. Because if this was exactly equals to 1, the greatest integer function will be 1, right, of this one. But as it is something smaller than 1, okay, I write this. Okay, so as this is something smaller than 1, so the greatest integer function, right, the greatest integer function will directly pull it down to 0 itself. The greatest integer function will directly pull it down to 0, right? So yeah, that is the thing. So you have to take notice whenever greatest integer function is involved. You have to take note of that. Next, about tan x. So tan x, right, tan x has all positive terms. So I forgot to write over here all positive terms, right? So it will have all positive terms, positive and odd power. Okay, this you have to remember, all positive and odd power. So tan x are all positive. Now here, right, if I divide by x, what happens? I initially told you tan x by x is 1 only, but now if I divide by x, this will be x squared by 3, and this is something adding up. So if this is adding up, this will be somewhat higher than 1, right? Just in the neighborhood of x equals to 0. So minus 0.001, minus 0.001 or plus 0.0001, right? It will be something higher than 1, because this is square term, right? You do minus or plus, it doesn't matter. Okay, so after this I'm ignoring this because this is higher order term, and anyways this will be tending towards 0 only. Okay, so here I have addition, and like this is somewhat higher than 1. Okay, so yeah, this was the key point that I want to tell you. Like here I have summarized these things, right? That now for sine inverse, right, it's quite the opposite. So inverse will be opposite. Okay, so this is how you like remember. I will tell you the analogy. Like you just remember for sine x, and for tan x it will be the opposite. Okay, and for sine inverse of x it will be again opposite. Okay, now for tan x, you know, it is 1 plus, so tan inverse of x it will be again opposite. That is how you remember. You just remember sin x and that's it. Okay, or you can directly derive it from the formula, right, from the series expansion. Inverse, opposite. Okay, so yeah, this is how you remember all this. Like I told you, right, tan inverse x by x was also equals to 1. Previously I told you when x is tending to 0, but this time somewhat less than 1, because it's like this, right? This is somewhat higher than 1. So if this is somewhat higher than 1, so okay, one thing may have happened over here, somewhat lower than 1. So this, right, this will be somewhat higher than 1, right? Because this is somewhat lower than 0.09999. If I take the inverse of that, that will be something higher. So yeah, that's my fault. This will be something plus, right? Not be minus, this will be plus, and this will also be minus, because let's say this is 1.011. So if I take the reciprocal, it will be something 0.99999, something like that. So this will be somewhat lower than 1, and this will be somewhat higher than 1. So I hope you got the short like the key points, right? So like I will give you few questions as homeworks, and in the next lecture we'll solve this question, and in the next lecture we'll understand the main method of solving limits, that is the L'Hopital method, and that is the most important one, and through that you will be able to solve questions very easily. But like sometimes why I explain these methods at the starting, because sometimes solving with that method will take you much longer time. Okay, and if you solve with this method, you will be able to solve within seconds. Okay, so you have to identify by just seeing the questions. After seeing the question, you have to identify which method to use, whether to use series expansion, whether to use substitution, rationalization, factorization, or L'Hopital method. first thing you should do is L'Hopital. Okay, but if you see that the question may go lengthy with L'Hopital, then you can do series expansion, because series expansion has like generally what happens if you solve with series expansion, you will be able to solve it in a very fast manner. Okay, when we solve questions, we will understand like this, right? Try to solve this with series expansion. Try to solve this also with series expansion, because cos x and sin x are series expansion. So like this is basically the end of this lecture, and the next lecture I'll solve these questions and we'll study the most important method, that is the L'Hopital method. Thank you for watching, and I will see you in the next lecture. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 2C of calculus chapter, right? So before starting, I want to say that I have caught a cold, so my voice is a bit different. That's why apologies for that. So in this lecture we'll continue with our topic, that is methods of solving limits. So we had different indeterminate formats, and we are solving different indeterminate formats. The methods for solving different types of indeterminate formats are different, so we have to go along with the process. So before starting this lecture, I gave you homeworks, 2 questions, right? So let's solve those 2 questions using whatever we have learned till now, and then again we'll try to solve those same questions using a different method, which is the most used method, and you must have used that method, because in competitive examinations we only use that method. But sometimes the method that I am using right now, that I will use right now, expansion of series, is also useful in certain cases, because the number of steps will be greatly reduced, if you use this expansion of series instead of the L'Hopital's method, right? L'Hopital's rule. So we'll learn that just after this solving this question, right? So let's first solve this question. So here we have been given that we have to find the limit as x tends to 0, tan x minus sin x divided by x cube. So the first thing that should come into your mind is, like I have told this previously also, that this is a NAT type question, so there isn't any question of limit does not exist. So we don't need to find right hand limit or left hand limit, just find only one, and we know that will be my answer, because it has some valid answer to it. So obviously left hand limit and right hand limit will be same. Okay, so that is the first thing. And now we're using series expansion. So if you're using series expansion, like these are basically series, like these can be represented as series of polynomials, right? Polynomials, powers of x. Now how far should I write? I should write, because if I try to put x equal to 0, I can't, right? Because in the denominator I'm getting x equal to 0, which is not suitable for me. So I want to vanish this x cube in the denominator. I want to vanish whatever is there in the denominator, right? To vanish it, it would be so much convenient if I have x cube at the top also, right? And I can easily eliminate that. I can easily cancel that x cube. Okay, that will be much simpler for me. So yeah, let's try to expand this sin x and tan x. Until how much power will I expand? Until x cube I will expand, because that will just cancel the powers of x, right? That will just cancel the powers of x. Okay, let's expand, then we'll understand more like thorough manner what is happening. So like I know, like it is difficult for you to remember the expansions, right? Sin x it is easy, for tan x it is difficult, but you have to you just write those in short notes, and you have to go through those daily, okay, to remember. Okay, so the up until x cube, the first 2 terms of tan x are there in the expansion, that is x plus x cube by 3, and this is the tan x expansion. And sin x expansion is x minus x cube by 3 factorial, like it is an odd function, right, if you remember correctly. Okay, then in bottom I have x cube, and obviously I won't change this is still limit as x tends to 0. Okay, limit as x tends to 0. Now if I subtract these, right, if I subtract this, what I am left with this, like x cube by 3 plus x cube by 3 factorial. So this is x cube into 1 by 3 plus 1 by 6, right? 1 by 6 divided by x cube. So this is 1 by 3 plus 1 by 6. So what is this? 2. So this, like conveniently what is happening is that, like I told earlier, right, that x cube is getting cancelled. If limit exists, this x cube has to get cancelled, else limit won't exist. Denominator has to be non-zero. That's why this x cube is like conveniently getting cancelled. So yeah, now as limit x tends to 0, I can easily cancel this x cube, and I'll be left with this 2 by 6 plus 1 by 6, that is 3 by 6, that is 1 by 2, right? 1 by 2. Okay, so my answer to this question will be 1 by 2 simply. So yeah, that is the answer to this question. Okay, so yeah, now let's solve the next question. Next question is again like the same process we will follow. We'll just expand this, right? And they have told us that limit already exists, so we don't need to find left and right hand, just find any one side limit, and that is good enough, right? That is good enough. Then a plus b plus c, we have to find a plus b plus c. Okay, how will you proceed? So we have x cube here, right? So we'll expand until x square. So here also I will write here expand until x cube, expand until x square. Okay, expand until x cube, expand until x square. So here what we'll do, so just let me write the expansions, right? So this is limit as x tending to 0, a is as it is, plus b into, now what is the expansion of cos? Cos is an even function. So if cos is an even function, it will be something like this. It will have even powers, 1 plus x square by 2 factorial, and I will go until only highest power should be x square. I should not go above that, right? So this is x square by 2 factorial plus c into, this has odd powers. So I have x, then I have minus x cube by 3 factorial. So that is more than x square, like more power than x square. So I will obviously skip that. Divided by x square, okay, equals to 2. Now like I told you right earlier, that for the limit to exist, this bottom term, right, this has to get cancelled. Here also this has to get cancelled over here. So obviously this x cube somehow has to get cancelled. Okay, so basically this a plus cx, just hold on a second. So if I write some things, a plus b and plus cx, I'm just writing like the constant terms individually together. Okay, then the coefficient of x individually here, then I will write the coefficient of x square. Okay, then I will write the coefficient of x square. So this will be b into x square by 2 divided by x square. Now what is the interesting fact? The interesting fact is, for limit to exist, this x square has to get cancelled with this x square, right? And these terms has to get cancelled. Like why these term has to get cancelled? Why this term has to be equal to 0? Why? Because if I divide each of them by x square, here in the bottom there will still remain some term of x, and that will be undefined, right? I can't put x equal to 0 on those terms, on those individual terms. Let me expand this and you will understand better. Limit x tends to 0, a plus b divided by x square plus c, x is cancelled, but still there is one x in the bottom, right? And this is b plus 2. Okay, so obviously in these two, right, in these two terms I won't be able to put x equal to 0, because in the bottom I have a x term. So obviously what will happen over here? Obviously these terms, right, these terms has to be equals to 0. The numerator has to be equal to 0. Okay, so a plus b has to be equal to 0, c has to be equal to 0. Okay, and if these two are equal to 0, then what do we know? Like what is my answer? Answer is half, right? Answer is half. Only what I am remained with. So in this simple thing here, right, here there is no x involved, so obviously b by 2 will be equals to half. All these terms are vanished, these are gone, this is 0. So b by 2 equals to 1 by 2, so b equals to 1 simply. Okay, so b is equals to, wait, sorry, this is not equals to 1 by 2, sorry, this is equals to 2, this is equals to 2, so b will be equals to 4. B will be equals to 4, and So if b is equals to 4, now I can put the value of b over here. So a will be equals to minus 4. Okay, and obviously c, I have already found out c is equal to 0 itself. C is equals to 0 itself, right? Okay, so from here you can find the value of a, b, and c. Okay, what am I doing something wrong? Okay, I have done something wrong actually, sorry for that. Like I was thinking b should be negative of this, so here, right, I expanded it wrong. I also tend to forget sometimes the expansion, I'm sorry for that. This should be 1 minus x squared by 2. So here this will become minus, this will become minus, and obviously this, okay, this is not again half, this is again minus equals to 2. So this b will be equals to minus 4, and a will be equals to plus 4. Okay, a will be equals to plus 4. So this is the answer for this question. A equals to 4, b equals to minus 4, c equals to 0. So yeah, that is how you solve these types of question in series expansion. Now these types of question we will solve using L'Hopital's method also, which we will study right now. So basically, what is L'Hopital's rule? So there is a rule, like L'Hopital has like made a rule for us to solve the limits really easy. Okay, really easy. So basically, L'Hopital's rule states that the limit of the ratio of two functions where the denominator is not equals to 0, that results in an indeterminate form by direct application of limit is equals to the limit of the ratio of the derivatives. Okay, I know you didn't understand anything, so let's just with examples and with visualization we will try to understand this. So basically, for you to apply the L'Hopital rule, what should be the first things to keep in mind? The first thing to keep in mind is that the format, right, the format of the limit should be something like this. Indeterminate format should be something like this: 0 by 0 format or infinity by infinity format. How did I got infinity by infinity? Because getting infinity by infinity is really easy. Simply, it is like 0 by 0 only. It is like 1 by 0 and 1 by 0. Okay, if you do 1 by 0 by 1 by 0, like it is simply 0 by 0 only, and which is infinity. 1 by 0 is infinity, tending to infinity. 1 by 0 is also tending here, right? Everything is tending, not exactly equals to 0. Everything is tending. I hope you remember the things. Okay, so this is the thing. Okay, so here, right, I have like a limit question which I have to solve, and I have a function of x in the numerator and a function of x in the denominator. Now if I put x tending to a, the both the numerator and denominator are going to 0, or both the numerator and denominator are going to infinity. Okay, basically it is an indeterminate format. If it is an indeterminate format, then what I can do, I can solve the limit using this formula. I will take the derivative of both the numerator and the denominator with respect to x individually. Okay, and like we haven't studied derivative yet, but like in 11 12 we have already studied derivative. So I like these are basic things, so you will know that. Okay, so after like finding the derivative, what will happen is that if now the denominator you're getting is non-zero after putting the value of x, if you're getting denominator as non-zero, then obviously you got your answer. That is your answer. Okay, and if it is again 0, then you have to repeat this process again. Take the derivative of the numerator and the denominator individually. Okay, so while solving these questions we'll understand this further. Just hold on a second, I want to check the noise of something. Yeah, sorry, actually I forgot to turn off the fan. That's why I think there might have been a bit of noise up until now. So I have turned off the fan, but the problem is like I have to face the heat. That's fine in summers, but still we'll do anything for you guys. So yeah, basically like which like when is this method useful? So when you are like absolutely out of ideas, and in general in competitive examination, this is the best method to use. Okay, best method to use. Best method to use in competitive exams. Okay, competitive exams, this is the best method to use. Sometimes what happens, sometimes the number of steps becomes higher. Okay, so may become lengthy sometimes, may become may become lengthy sometimes. So like what I was explaining previously is that if you have a rational function, right, like you have to find the limit for it, x tending to a, f of x divided by g of x. Now what you do, you can take the derivative, and if you're getting 0 by 0 format, what you can do, you can take the derivative of it, limit as x tending to a, f dash of x by g dash of x, if, very important point, if both f dash of, not f dash, f of x equals to g of x equals to 0 or infinity at x equals to a. Okay, this point is very important. So now if, like, again, right, if these two are also 0 or tending to infinity, again we'll repeat this process. What we'll do, again I will say this will be equals to limit as x tending to a, f double dash of x divided by g double dash of x. Okay, and if the derivatives of 0, previous derivatives were 0, that's why we took this further step, right, f dash of x and g dash of x equals to 0. Okay, so yeah, this is the case, and we'll proceed further. We'll again proceed further again if these two are 0. Okay, again if these two are 0, we'll proceed further, or infinity. Okay, this is how it works. So before using this method, I want you to like see few standard formulas, right, standard derivatives, just to have these things in mind. I know you already know all this, just a quick refresher of all this derivatives. So you know, like, what is the derivative of constant x, all this ln x, sin kx, all these things, you know, right? Tan x, sec square x, it is tan kx is k sec square kx. Then cosec x, basically it is like cosec x is equal to 1 by sin x. From there you can derive the formula for cosec x, okay, from quotient rule and sin x. Okay, like quotient rule, you already know, I hope. Then sec x is simply 1 by cos x, then cot x is cos x by sin x. Okay, like this, right, sin inverse of x, this you have to remember, 1 by 1 minus x square under root 1 minus x square. This is very important, this will be helpful in the integration chapter as well, so this is very important. Then cos inverse x, tan inverse x, hyperbolic. Now what you can do, like these hyperbolic functions, right, these you can derive. Okay, if you tend to forget this, like any sine cos, you can, if you tend to forget this, you can derive using exponential, because already like that you have to remember what is cos hyperbolic x in exponential format, that you have to remember anyhow. So cos hyperbolic x is equals to e raised to power x plus e raised to power minus x divided by 2. Okay, that's how you remember. Then sin hyperbolic x equals to e raised to power x minus e raised to power minus x divided by 2. Okay, that is like you remember that, and you can take the derivative of exponential. It is very easy to take the derivative of exponentials, and from there you can derive these formulas. Okay, if you tend to forget these things. Okay, anything else if you want to remember? Okay, I think I've missed. Okay, no, these formulas are here only. These formulas are here only, right? So basically now let's these formulas, I hope you know, like this is like a raised to power x, the derivative of this will be a raised to power x ln a. E raised to power x is simply e raised to power x log ax. Now that base isn't exponential here, natural log, this is not natural logarithm. Okay, that's why the base will come here, 1 over x with an extra term ln a. Okay, this ln a is just a constant. Why? Like you can write this, right, like ln x divided by ln a. Okay, now ln a is still here, and this ln x, derivative of ln x is 1 by x. That's how you write this. Then ln x is simply 1 by x, that we already know. Okay, so like these if you want to remember, that's fine. If you don't want to remember, just put it down in the formula notes and go through this every day, and somehow this will get into your brain. Okay, so cot inverse of x is simply minus 1 by x square. Why is this the case? If you recall correctly, like how can I write my cot inverse of x? So cot inverse of x you can write like this, right? Cot inverse of x you can write equals to pi by 2 minus tan inverse of x, because tan inverse of x plus cot inverse of x equals to pi by 2. Tan inverse of x plus cot inverse of x cot inverse of x plus tan inverse of x equals to pi by 2. So this will be simply equals to if I take the derivative of this, what will happen? This is constant, right? Derivative of constant is 0, and this is what? This is 1 by x square. Derivative of tan x is 1 by x square, so this will be 1 by x square. Okay, so this is minus 1 by 1 plus x square. Okay, so this is the derivative of this. Yeah, as I was saying, that if you are able to identify like the derivative of sine inverse of x, which is 1 by under root 1 minus x square, then it's very easy to find the derivative of cos inverse of x. Basically, sine inverse of x plus cos inverse of x equals to pi by 2. Okay, equals to pi by 2. So from here also you can derive, right, the cos inverse of x. You don't have to remember, but like it is very easy to remember because it is just negative sign. Okay, from that you can take the hint. So basically cos inverse of x equals to pi by 2 minus sine inverse of x, and basically ddx of cos inverse of x equals to minus ddx of sine inverse of x. Okay, so this is how you see this. So like this is how you try to remember, and like this I have no other option but to remember. Okay, the other one, cosec one, you can remember because again the same thing, that cosec 1 will be simply equals to pi by 2 minus sec inverse of x, and from there you can take the derivative and you can easily find it out, right? So yeah, ddx okay. So like there are a few fundamental theorem of derivatives, like I hope you know all this, but if you don't, like let's just go through this quickly. Okay, so if f of x and g of x are both derivable functions, that is their derivative exists, then obviously it will follow the property of what? Homogeneity. Like if there is a constant multiplied, I can take this constant out. Okay, this derivative, right, it is a linear operator, and if I like use the superposition, if I add two functions and take the derivative, and if I individually take the derivative and add those two, those will be again same. So again these, right, follow homogeneity and superposition, hence our derivative, right, ddx is a linear function. Okay, this more about this you will learn in second lesson system. So yeah, this is the case. Okay, now next is ddx f of x into g of x, f of x into g of x. So like this is basically the chain rule or product rule, you can say. Now derivative one, simply other function multiplied, then derivative of the other and simply other function multiplied. So this is the okay, chain rule or product rule. Now here, right, if they are in fraction, so this is known as the quotient rule. I hope you know all this, but if you don't know, just try to quickly get a definition. Okay, this I won't go through much further. So again, right, let's come back to that quotient which we solved previously. So can we solve this using L'Hopital? So here if I put x tending to 0, this is 0, sine tan of 0 is 0, sine of 0 is 0, 0 minus 0 0, 0 by 0. So this is 0 by 0 format, so we can apply the L'Hopital rule. But what is the problem here? This is x cube. So like from starting itself I'm telling you that we have to apply differentiation thrice. Why? Because first time the differentiation will be 3x square, second time the differentiation will be 6x, third time the differentiation will be 6. So after that only the bottom term, right, bottom term, the 0 from the bottom will be vanished. Then only we can put x equal to 0. Then only we will be able to reach our answer. So that is the issue with this. So this is a lengthy process. So with series you will see how fast we solve. With this, right, it will take us time, but at least when you are stuck, right, in the examination, you don't know anything, you can apply this method. No worries, but you have to have time and your calculation needs to be good. That is an important thing, right? So here I will say power is 3, so this will be we have to differentiate thrice, right? Okay, so basically this will be limit as x tending to 0, and what will be the differentiation of tan x? It is sec square x. Okay, and sin x differentiation is cos x divided by 3x square, basically 0 by 0 format. So that's why I'm differentiating both numerator and denominator. Here if I put sec square x of 0, what is it? It is simply 1 over cos square x, which is 1. So 1 by 1 is 1, 1 minus 1. Okay, this is 0, and anyways denominator is again 0, so it is 0 by 0 format again. So again, right, we'll differentiate it further. So again this is becoming 0 by 0. Okay, hence we'll differentiate it further. This will be 2 sec x into what is the differentiation of sec x. This is I'm applying the chain rule, right? So differentiation of sec x is sec x tan x. Okay, minus what is the differentiation of cos x? It is minus sin x, so it will be plus sin x. Okay, divided by 6x, and obviously we have limit as x tending to 0. That we cannot forget. So now if I again put x equal to 0, so this, right, tan x is going to 0, sin x is going to 0, so this is numerator is 0, anyways denominator is 0. Again we have to differentiate. Okay, one thing we can do, this is 1 by cos x. Okay, can we do anything? No, we can't do anything. Okay, so this, right, this will be limit as x tending to 0. If I now differentiate it further, so this is 2 sec square x, so again I will apply the product rule. So this will be 4 into sec x into tan x into sec x tan x. Okay, now why is this not that important to me? Because if I differentiate this and keep this function as it is, anyways this is going to 0 if I put x equal to 0, so this term anyways will get vanished. That's why don't put too much emphasis in this differentiation. Anyways I know, I'm applying the product rule. First I will differentiate these term and then I will differentiate this. Okay, now anyways this is going to 0, so anyways whatever the differentiation of this, I don't care. Okay, because this term, any constant term with multiplication with 0 is 0, 0 times 0 is 0, so I don't care about this. Okay, but still I have done this. Okay, and also obviously I have a tan x present over here. Okay, so this, right, this part is the differentiation, this is the differentiation of this part, and I'm keeping this as it is. Next is the differentiation of tan x. It's 6 square x, so this will be 2 plus sec raised to power 4x. Now differentiation of sin x is cos x. Okay, and differentiation of this 6x is simply 6. Okay, simply 6. So this, right, now I can simply put x equal to 0 because I have no boundation right now. So my denominator is simply 6, so I have no boundation. So if I put x equal to 0, this is totally 0. Okay, this is 2 because sec 0 is 1. 2 plus 1 cos 0 is 1. 3 by 6 is equals to 1 by 2. Okay, same answer as we got earlier, but the steps were more here. We got to answer much earlier. So you can use the same example for the second question as well, which we did earlier. Okay, so yeah, let's start by solving different type of limit, that is the 1 raised to power infinity limit. Okay, obviously you might say, sir, 1 raised to power anything is 1 itself, right? The problem here is this 1, right? I'm tending to 1. Not exactly equals to 1. I'm tending to 1. Infinity is also tending to infinity, right? Very high value. So how, like, what are the few methods of solving 1 is to power 1 here, right? This is one of the type, one of the definition of 1 is to power 1, and this is also another definition. Simply there is just difference of how we write the x. Here, if limit as x tends to 0, this bracket term is tending to 1, bracket term is tending to 1, and this side 1 by 0 is tending to infinity. Okay, so this, right, the solution of this will be e. Okay, the solution of this will be, you can solve this. Okay, you can solve this, like there are various methods to solve this. I'm not proving it right now. Okay, next, these, right, if my x is tending to infinity, so 1 by infinity is 0, 1 by infinity is 0, 1 plus 0 is like almost equals to 1, and here, right, if I like raise this to the power of infinity, this will be again e, the same result, right? Same thing, 1 raised to power infinity, 1 raised to infinity, the answer will be. Okay, now how will they give you, like they will give you in some different format. They will not give you this easy format. What will they give you? They will give you this format, right? So limit, let me write this, limit as f of x, not x tending to 0, f of x tending to 0, 1 plus f of x divided by 1 by f of x. Okay, so they will give you some format like this. What do you mean by f of x? Like, it can be x square, it can be x cube, it can be x square plus 1, it can be ln x, whatever, like ln x tending to 0 also. But here, right, instead of f of x, they will write x tending to a. Okay, just to trick you, they will not write f of x, then it will become more simpler. Like, anyways, these are, what is the difference? Just a simple difference of f of x. But the trick part will be, they will write here x tending to a. Okay, not x square tending to a, x square tending to 0 or something. X square will tend to 0 as x is tending to a. Okay, like that. We'll solve question, there you will understand. Okay, and these, right, these will be in the format of f of x. Here also the same thing will happen. Here I can write that, just hold on a second, my pen is dead, just hold on a second, let me come more closer to the mic. Okay, yeah, so here I can write that limit as f of x tending to infinity it will be 1 plus 1 by f of x equals to e. Okay, so as my f of x is tending to infinity, this will be the result. Now, instead of writing f of x tending to infinity, what they will write is x tending to a again. Slowly we'll solve questions, and from there you'll get a good grasp of this. Okay, there is another format which may come. Okay, so like format 2. What is the format 2? So basically, if I have limit as x tending to this 0, if I have limit this x tending to 0 and not 0, let me say x tending to any e, right? Okay, and I have 1 plus f of x, and I have g of x over here, not this. And what we know that as my, like this a, right, as my a is x is tending to a, I know my f of x will x tending to a will tend to 0. Okay, will tend to 0, that I know. If my x is tending to a, f of x will tend to 0, that I know. So what I can do is simply I can convert this further. I can write limit as x tending to a 1 plus f of x, and I can write here 1 by f of x into f of x into g of x. G of x is still over here. I'm just multiplying and dividing by f of x. Okay, just doing that. Nothing illegal over here. So these, right, these I can write internally, these I can write internally. So this is limit as x tending to a, I can write this in bracket 1 plus f of x into 1 by f of x, okay, and these are further different, f of x into g of x. Now I know this whole thing, right, this whole thing is e raised to power 1, this whole thing is e raised to power 1, okay, I know, because this is tending to infinity and this is tending to 0, so 1 raised to 1 infinity is e. Now what I can do, I can take this limit, right, inside here, inside to the power of exponential to solve this further, so what I will do, basically, right, this g of x is also tending to infinity, that also has to satisfy over here, else we will not be able to find the answer, okay, at x as x tends to 0, so x tends to a, okay. So limit, now limit, right, limit I can take inside, this will be a e raised to power limit x tending to a f of x into g of x. So this is very important formula, this you have to like understand, which will solve questions, and from there also will understand this, okay. But this, right, these type of question can come. These type of question can come. This is very important format, okay. Now what is another format? So what is another format? Format 3. Another format is there isn't any 1, there isn't any 1, okay. What is that? Like it is simply limit x tending to simply a, and I have f of x raised to power g of x, and I know f of x is tending to 0 and g of x is tending to infinity as x tends to a, okay. These two things are very important. Now what is happening is that I don't have my standard format, so what I will do, I'll try to convert this into my standard format. So I will try to convert this into standard format. So this will be simple, right? Now what I can say, this is my new function, okay, this is my new function f of x minus 1, and this is the old function, okay. So again what you can do, again you can apply the same thing what we applied over here, whatever we applied over here we can apply the same thing. So again limit as x tends to a 1 plus f of x minus 1, so like this will be f of x minus 1 divided by, okay, sorry, one thing I meant wrong, this shouldn't be 0, this should be 1, f of x tending to 1, not 0, okay. So yeah, then only this whole thing, right, this whole thing will tend to 1, okay, or else this whole thing will tend to 0, that is very important. So f of x minus 1 into g of x we have still over here, and simply after converting, I'm skipping few steps, so after converting this will become e, and this will be limit as x tends to a, this will be simply f of x minus 1 into g of x. Now whatever the solution of this limit, right, will be my answer, e raised to power my answer, okay. So what I will give you is just I'll pause the video, you try to solve this question, and I will come back with the solution, and then we'll solve different types again, some other types of limits. So let's start with this question. At first glance this question may seem different, right? Here we have this tending to infinity, so and this is raised to a power x. How will you solve this question? Like if you have studied this limits chapter previously, what you will think of as taking logs. But generally when there is infinity to the power, right, we don't take logs. When there is raised to the power 0, then only we take logs. Here, like, what is this tending to? We have already solved for infinity by infinity. So what we know, that this, right, here the powers of the numerator and the denominator are the same, the maximum power, that is, which is x square. So the powers are same. Okay, other, like, as they are same, what will happen? It will be simply the ratio of the coefficients as x tends to infinity. We have already solved this. I won't explain this further here. So this will be 1 by 1. So this will be simply, this is tending to 1 raised to power x. Okay, 1 raised to power x, or 1 raised to power infinity. This is tending to 1 raised to power infinity. Okay, so this I can say is tending to 1 raised to power infinity. Okay, so how to solve this right now? So this, right, this is my f of x. Okay, if you recall correctly, here I have just solved it. F of x raised to power infinity. Okay, so same format only. So what I will do, I will just write this, right, 1 minus f of x minus 1 and raised to power g of x, which is x in our case, right? So, like, what is the solution of this? The solution of this limit as x tend to a. The solution of this will be e raised to power limit as x tending to infinity f of x minus 1 divided by, into g of x. Into g of x. Exactly what we just derived in the just previous section, right? We just derived it. Okay, I won't go like much in details to this. So here what will happen? Limit as x tending to a, not a, infinity. Okay, then f of x minus 1. F of x minus 1, I have to subtract 1 from this. What will happen? That this x square will get cancelled. This 4x will remain. 4x I will write here. So this will be e raised to power x square plus 5x plus 3 minus x square plus x plus 3 divided by x square plus x plus 3. Okay, limit as x tends to infinity e raised to power this is getting cancelled, this is getting cancelled. We have 4x over here, so 4x divided by this is still over here, right? And we have obviously into x square plus x plus 3 into g of x. G of x is simply x. Okay, so the interesting fact over here is this again, right, becomes x square. You would have thought that, yeah, we have x over here and x is tending to infinity, hence what will happen? This will go to 0 and this will be e raised to power 0, which is 1. No, right? No, that is the interesting fact over here. That's why you have to obviously solve this. This limit will come inside this exponential, okay, in the power. So here, right, now if this is g of x, if I multiply x with this, what will happen? This will become 4x square. Now infinity by infinity, and the highest power term, I will take the ratio. Here, like, they are equal, right? Highest power terms are equal. This is x square, this is x square. So it will be 4 by 1, which is 4 itself. So this will be equals to e raised to power 4 by 1, which is equals to e raised to power 4. Okay, so this will be equals to e raised to power 4. So my answer to this question would be e raised to power 4. Okay, so this is how you solve this question. So let's go to the next question. So here, like, this is again the format of the previous case, where I have tan raised to power pi by 4 plus x as x is tending to 0 and raised to the power 1 by x. Here what I observe is, if I put x equal to 0, this will tend to 1. If I put x equal to 0, this will tend to infinity. Again 1 raised to power infinity, same format. So obviously I won't use logs. In the next format I will show you why I am talking about logs. Okay, so I won't use logs over here. What I will do, I will just use that simple formula, right, whatever I have told you right here, this one this format, right? I have this format right now. So obviously this is directly going to 1 instead of this going to 0, right? So I have to again convert this. So they won't directly give you that format, that 1 plus x raised to power 1 by x. They won't directly give you. You have to make it. So here again, after putting this x tending to 0, I am observing that this is going to 1 raised to power infinity format. So what I will do, again I will write the formula directly over here right now. So this is my like g of x right now. This is my g of x, okay, and this is my f of x. So I have to write f of x minus 1. So here limit as x tending to 0, this is tan pi by 4 plus x minus 1 into 1 by x, right? So this is how my format will be. This is my simple g of x and this is my f of x, and the other thing, right, other thing got converted into this e, right? E here I have already told you this thing, right? This thing, not this right, this thing has already been converted to e. That's why I write e over here, and the other rest of the part has been remained. We have to evaluate that, further evaluate that. So here what can I observe? I hope you know the simple formula for tan a plus b. That this you have to obviously remember, okay? So what is tan a plus b? Tan a plus b is tan a plus tan b divided by 1 minus tan a tan b. So like this gives us a beautiful expression for tan pi by 4 plus x, which is equals to tan pi by 4 is 1 plus tan x divided by 1 minus tan x. Okay, and this is minus 1 divided by x I have already over here, and obviously this is exponential limit as x tend to 0. Like x is here 0, right, in denominator. That's why I won't be able to simply put x equal to 0 over here. I won't be able to put simply x equal to 0. Then what will it become? This is limit as x tending to 0. Okay, I am subtracting 1 with this, so this will become 2 tan x. 1 will cancel, 2 tan x by x. Okay, now if you recall that sin x upon x is 1, tan x upon x is also 1. I mean as limit as x tends to 0. So this will be simply 2, right? Because like this 2 times 1, this is 1, and I have 2 outside. Okay, outside, so 2 will get multiplied. So my answer will be e square. Okay, so obviously you have to evaluate. So that's why so that is what I was trying to get at, right? You have to further evaluate this, right? You can't simply put x equals to 0 over here right now. You can't. Here also you can't simply put x equals to this f of x here, right? Simply equals to 0, else this will go to infinity. This will go to 0 only. 0 into x is 0. It will be e raised to 0. It will be 1. No, you have to evaluate this, right? This multiplication, you have to evaluate this. That's why it is limit, because it is tending to something. It is not exactly here. This is not exactly equals to 1. This is tending to something. That's why we have to evaluate further to understand exactly what it is tending to. Okay, so that's why like we want to know where it is heading towards. Okay, we like this is not exactly equals to 1. That is the most important part over here, right? So yeah, let's go to the next question and the next format basically. So this format will like use logarithms. Here we have to solve 0 raised to power 0 format and infinity raised to power 0. Again, write this 0, this tending towards 0, not exactly equals to 0. That's why we don't know the answer. Can you tell me what is 0 raised to power anything? We know 0, right? So it's simply 0, because 0 times 0 is 0. Okay, but this 0 is not exactly equals to 0. This is tending towards 0, and this power in the power 0 also is not exactly equals to 0. Okay, that's why we have to solve it further, evaluate it further. Anything raised to power 0 is also 1. 5 raised to power 0 1, 6 raised to power 0 1, e raised to power 0 is 1. But here this is not exactly equals to 0. So that's why the confusion lies. This infinity, can we quantify infinity? No. This is always increasing, always increasing. So infinity raised to power 0, you might say, sir, anything raised to power 0 is 1. So infinity raised to power 0 should also be 1. No. This is tending towards infinity. I mean, it is always increasing. This 0 is not exactly equal to 0. Okay. These two things you have to keep in mind. Now, let's understand with a question how to solve these types of problems. So here I have a question where I have to solve limit as cot x raised to power x as x tends to 0. Now what do we observe? Previously it was 1 raised to power infinity format. Now this, right, cot 0 is what? Tending towards infinity. As my I hope you know the graph, or if you tend to forget the graph, what you can do, you can break this down. Break this down to cos x upon sin x. Now cos x as x tends to 0 is 1. Sin x as x tends to 0 is 0. So denominator is tending towards 0. So obviously this whole thing will increase. So this is tending towards infinity. So that's how you can also remember. I also tend to forget what is the graph of cot x. So I remember it by breaking it down to sin x and cos x. Okay, then this x, simple, x is 10 to 0, so this will also 10 to 0. So this is the second format, infinity raised to power 0. So how to solve this? Now we can solve this using the basic method. What is the basic method? Using the right hand and the left hand limits. So first let us solve using that. Obviously, we'll use logarithms also. So here what we can do, we can replace our x with 0 plus h. Okay, so what I can write is my right hand limit will be simply equals to limit as x tending, not x, as h tending to 0, cot of h raised to power h. Okay, this is the answer of my question. So like first let me write that this will obviously be 0 raised to power infinity. Okay, this will obviously be 0 raised to power infinity. This is the first case. Okay, so here now how to solve this? So here I can name this as r. Okay, I can as they have given me nat, I know limit will exist. I will get some value, some finite value, or some zero value. Okay, some finite value of this answer of this limit. So I can name this limit as r. Okay, the value of this limit as r. Now what I will do, I will take log on both sides. If I take log on both sides, what I will write, log of r. Okay, I can take the natural logarithm, ln of r equals to this. Now what can happen is, if I am taking log on both sides, right, this log can go inside this limit. There is no issue with that. Okay, log of this limit will be same answer. Okay, no issue with this limit. So what I will write, limit as h tends to 0, ln cot h raised to power h. So this will be limit as h tends to 0, h, okay, this is whole raised to power, whole log, right? So this will be h can come outside. This is the property of logarithms. Cot h. Okay, so this is my lnr. So now what I can write, I can do a very interesting fact over here. So this h, right, I can do a good manipulation. So here h is tending to 0, this is going to 0, and this is going to what? Cot of 0 is going to infinity. So log of infinity is going to infinity itself. Log of infinity is infinity itself. So I'm getting this is 0 times infinity. Okay, now what do I know? 0 times infinity. 0 times infinity, and I can convert it into infinity by infinity format. So this, right, 0 times infinity, I can convert it into infinity by infinity format, right? So if I convert it into infinity by infinity format, what will happen? Basically, how I can I'm just rearranging terms over here. This will be h tending to 0, ln cot of h will remain as it is, and this will be 1 by h. So now what do you observe? This is going to 0, so this is infinity again, this is again infinity. Okay, this is again infinity by infinity format. So now what I can do, I can use the L'Hopital rule. Okay, so sometimes L'Hopital rule is really useful when I have to just use one step. Okay, so here L'Hopital rule is really useful. So like I forgot to write okay, this lnr. So this is simply infinity by infinity format. So this will be, I can use the L'Hopital rule. So this will be 1 by cot h into what? Minus cosec square x. Okay, the differentiation of cot h. Okay, divided by, this time x is not my variable, h is my variable. H is tending towards 0. That's why I'm differentiating with respect to h on both numerator and denominator. So this will be minus 1 by h square. Okay, so what else? So now this cottage is going to, so here, right? So what I can observe is cottage is what? Limit as h tends to 0. Cottage is cos h upon sin h. So this is sin h upon cos h into cosec square h. So this is 1 minus sin square h divided by minus 1 by h square. Okay, so here this is limit as h tends to 0. Okay, and like one sin h will get cancelled. Okay, I will be remained with another sin h. This I can just hold on a second. So this, right, I can write here minus sign also gets cancelled over here. Okay, so here I can write 1 by cos h into 1 by sin h into h square is still there, right? H square is still there. Okay, so okay, am I missing something? Just hold on a second. By sin h, this is cottage, sin h, yeah, this is 1. Okay, okay, yeah, h square. So now what I can do is I can write that limit as h tends to 0. I can take this h here cos h and this h over here sin h, right? So this, right, if I like h tending to 0, this will go to what? 1. This will tend to 1. This will tend to 1. I can solve the limits individually. This will tend to 1. Now this, in the denominator I have a 1 only, and in the numerator I have a 0. The 0 by 1 is like we can write 0 by 1, right? No issues to write 0 by 1. So I can simply write 0 by 1 over here. So this will be limit h tends to 0. This is 0 by 1, okay, into 1, and I have ln r over here, right? So I'm solving this slowly, that's why it is taking me so much time. Now now what I can do, I can again get back my r. What I will do, I will take the exponential on both sides, okay, inverse of logarithm. So this will be r only, and this will be e raised to power 0. So this will be equals to 1 itself. So my right hand limit is 1. Okay, so let's now go to the next question. So what is like this question asking us? Here we have a inverse function. So we have to find as x tends to 0 cot inverse of cos x, and this box, right, this square brackets, it has mentioned that this is a greatest integer function. So this is a greatest integer function. Now if I tend my x tend to 0, what will happen? So basically x is tending to 0, so cos x will tend to 1. So cos x will tend to 1. Okay, now if cos x is tending towards 1, this greatest integer function will be 1, but it won't be exactly equals to 1. What will happen? Like let's now plot the graph of cos x very closely. Okay, very closely, let's plot the graph of cos x. Like whenever greatest integer function comes up, right, you have to plot some graphs or check something, right? Very important. So here what do you observe? This is 1. Okay, this is 1, this is x, this is cos of x. So as I'm approaching x tending to 0, as I'm approaching x tending to 0, what is happening? I'm almost equals to 1, but not exactly. Okay, somewhat lower, right? Somewhat lower than 1, And what does greatest integer function do? Greatest integer function is very strict. Okay, if it is not exactly equal to integer, if it is not exactly equals to 1, it will directly bring it down to 0, the previous integer. So here, as this is not exactly equals to 1, this will bring it down to 0. And what is cot inverse of 0? Cot inverse of 0 is again infinity. Okay, so sorry, cot inverse of 0 is what? It is pi by 2, right? It is pi by 2. Why is it? Because cot of pi by 2 is what? Cot of pi by 2 is cos pi by 2 upon sin pi by 2. Sin pi by 2 is 1, cos pi by 2 is 0. So the numerator has to be 0. So when is the numerator 0? Okay, like this is 0. So when is the numerator 0? Numerator 0 when x is equals to pi by 2. Okay, that's why my answer will be pi by 2 over here. Now obviously let's solve this. Like we can observe, right, either way, if we come from the left hand side or from the right hand side, either way this will be somewhat less than 1. Okay, as this is somewhat less than 1, this will be equals to like 0. So cohort inverse 0 is anyways from the left hand side, right hand side, anyways this will be 0 only. Okay, and cohort inverse 0 is pi by 2 only. So my answer will be E. Directly with graphical observation we can solve this question. But if you don't want to solve this question, like now this question is different than this one. Okay, this is some different question, some random question, right, with greatest integer function. You have to solve these type of question also. Okay, not they will not always give you in specific formats. That is very important. So here like I told you how to solve this intuitively. Let's now solve it like with proper explanations. Why do we need to solve it proper explanations? Because here what you observe, all options are given. Okay, this option is given. Okay, so obviously we have to check both right hand limit and left hand limit, as limit does not exist is also given, right hand limit and left hand limit. But anyways, I have already checked that, because from the right or the left, either way this function will give me same answer, that is 0. Okay, now let's apply this. Okay, let's write this down. So basically let's calculate the left hand limit. How to calculate the left hand limit? Basically, what do we mean by left hand limit? I'm approaching my point 0 from the left hand side, from this left hand side, right? Okay, and what is my like this function? This is cohort inverse into cos x, cohort inverse into cos x. So now if I approach from the left hand side like this, I can replace this with minus h. So I will write limit as h tends to 0, this will be cohort inverse into cos of h. Okay, so not cos of h, cos of minus h. So from here also we can understand that cos is a even function, so cos of minus h will be cos of h itself. Okay, cohort inverse into cos of h itself. So again, can I put h equal to 0? Yes, this will give me 1. Okay, it is not any indeterminate format, so I can simply put h equals to 0. So this will be limit, not limit only, so this will become cohort inverse of 0. Okay, because what is happening over here, you have to be very careful over here. You have to be very careful, because you simply can't put 1. Cos 0 you simply can't, because it will be somewhat less than 1. Why? Because it will be 0 point, like h is tending to not exactly close 0, h will be equal to 0.00000000001. Okay, and even if it is 0.0001, so I am lying somewhere around here, and it will directly, greatest integer function directly will bring it down to 0. Okay, that's why like the definition of greatest integer function, if this, right, this is not exactly equal to the integer, it will be the previous integer. That's why it exactly brings it down. Okay, we already have studied like many properties about greatest integer function. So obviously we're lying somewhere around here, right, lying somewhere around here. This is h, this is cos of h, so obviously this will directly bring it down to 0 itself. Okay, so this, right, wait a second. So this will be equals to cohort inverse of 0 is pi by 2. Okay, cohort inverse of 0 is pi by 2. I hope you recall all these things. Okay, now again, right, simple, you can do the right hand limit, the same thing only. Okay, so like here I can further, like better manner can understand this. I can better oh shit, so I can write this. Just hold on a second, my pen is not working. Yeah, I can write this like this, that this, right, so this I can write cohort inverse of greatest integer function 1 minus something less than 1. As it is something less than 1, obviously what will happen, this will go to 0 itself, right, 0 itself. Okay, sometimes my pen is not working, sorry for that. So again, right hand limit x tending to plus 0. Okay, 0 plus same function, 10 to 0, and again, right? So this time the age is 10 to 0, and this time this is positive, so we don't need to make any changes. Again, the same thing, cot inverse of 1 minus equals to cot inverse of 0, which is I don't have space, just hold on a second. Cot inverse 0 equals to pi by 2. Okay, equals to pi by 2. So the answer will be same only, right? So like left hand limit equals to right hand limit, so my answer will be pi by 2. Okay, from there also you can understand. So left hand limit equals to right hand limit equals to pi by 2, actual limit. Okay, so again let's solve another question. So these type of questions are very interesting because here the greatest integer function is getting involved. So here, right, you sometimes have to draw the graphs. Okay, have to draw the graphs. So I will mention have to draw graphs. I've already told you what happens, like sine, what the sine extends to, what does cos extends to, but all those, right, all those are not that useful because how many things will you remember? Okay, try to remember as little as possible. Try to do those things in exam halls. Okay, try to do the derivations in exam halls, the smaller ones, because I also tend to forget everything, right? It's very difficult for me to remember these many things. That's why I also tend to derive on the examination hall, or I'm deriving it in front of you, like drawing the graph and then doing the greatest integer function. Or I could have simply told you, right, simply told you that yeah, this greatest integer function as x tends to 0, this, right, will be simply 0, not equals to 1. Okay, but I draw on the graph, so you also try to draw it, so that you can get the assurance that yes, whatever I am trying to solve, I am solving it correctly. So we have to draw the graph. Okay, again, as limit does not exist has been given, we have to check the both the right hand and the left hand limit. So let's check the right hand limit this time first. So let me do this a bit quickly. So my right RHL equals to limit as x tends to 0 plus tan inverse sin x. Okay, this is the greatest integer function, they have already told us, sin x. Okay, which is equals to limit as h tends to 0 tan inverse of sine of plus h, right, positive h. Now as h is tending to 0, sin h is tending towards 0, but is it exactly equals to 0? Let's check. So graph of sin x, if you recall correctly, is something like this. Okay, so I'm in coming from this end, right, positive end. Okay, this is h, this is sin h. Okay, I'm coming from positive end. So as I'm coming from positive end, what is happening? This is going towards 0, but this is somewhat higher than 0. Okay, somewhat higher than 0. So this is somewhat higher than 0. So this will be limit as h tends to 0 tan inverse of 0 plus, which doesn't matter to us. This will directly bring it down to 0. Anything like this is not equal to integer, right? If it is what equal to integer, it would have been integer itself, 1 itself, but it is something like just higher than 0. This will directly bring it down to 0 itself. So this will be tan inverse of 0 tan inverse of 0. Okay, let me write this on the here, right? Let me get this graph here. Tan inverse of 0, okay, which is equals to 0 itself. Tan inverse 0 is 0 itself. Now let's solve for the left hand limit, which will be interesting here. So left hand limit is, I am coming from x tending to 0 minus, from the left hand side. Okay, from the left hand side I am coming. So this will be tan inverse of sin x. I can further write this down as x tending to not x, h tending towards 0, but this is 0 minus h. So I'll replace x with 0 minus h. So this will be tan inverse of sine to 0 minus h. Okay, so this will be limit as h tends to 0 tan inverse 0 minus h, which is sign of minus sign of h. Sign of minus h is minus sign of h. Okay, again the same thing, this, right, this h is changed to positive, this is something 0 plus, this is something 0 plus. Okay, but these are negative. So here, let me again like draw the graph. Now I'll draw the graph of minus signage and not plus signage. There you will understand this better. Okay, or you could understand a different manner also. I will tell you both manners. This is a minus signage. So minus signage will just be the inversion about the x axis. So here this will be positive. Just hold on a second. This will be positive and this will be negative, right? Because it is just the inversion. Okay, I am just multiplying a minus 1 with it, so it will invert around the x axis, or this is around the h axis. So here my h is tending to positive, from positive side, positive 0, right? So I'm coming from this end, right? Coming from this end, what I'm observing, I'm some small negative number which is around 0, somewhat less than 0. Now what does greatest integer function does? If it is somewhat less than 0, okay, it is a fractional part and which is somewhat less than 0, it will directly bring it down to the previous integer, which is minus 1. Okay, so I can write here, this is limit h tends to 0 tan inverse of 0 minus. So this is somewhat less than 0, somewhat less than 0. Okay, I can tell you, for example, minus 0.000001. Okay, somewhat less than 0. Okay, somewhat less than 0. So this is minus 0.0001 and our greatest integer function will directly bring it down to minus 1. Okay, it is very harsh, very strict, just like our girlfriends, or if you have boyfriend, they are very strict, right? They don't allow you anything. So this will be almost equals to 1. So limit, not 1, minus 1, h tends to 0 tan inverse minus 1. Okay, so tan inverse minus 1. So now what is tan inverse minus 1? Tan inverse minus 1 is simply equals to minus pi by 4, and take the minus outside. Okay, simply equals to minus pi by 4. Okay, now what do I observe? I observe that my LHL and RHL are not equal. So my LHL is not equals to my RHL, hence limit does not exist. Limit does not exist. So this time my answer will be D, right? So you have to be careful. You have to be careful always when solving MCQ type questions of limit. If there is an option limit does not exist, you have to check for both right hand limit and left hand limit. If there isn't any option that limit does not exist, then you can blindly just do one of the limits, that is either right hand limit or left hand limit. You don't have to do the work twice. Okay, it will save you time. So here now how to solve this? So you might say, sir, if I put this x tend to 0, this is 0 minus 0 and this is 0 minus 0, so this is 0 by 0 format, I can use the L'Hopital rule. I will say no. Why? Till now we don't know about differentiability, but like few students, like I think most of you know, few students may not know, but we know that mod of x is not differentiable. Why? Because there is a sharp turn around x equal to 0. It is not differentiable at x equal to 0. Okay, that's why we cannot use L'Hopital's rule. Okay, so first of all, like we can say 0 by 0 format, we will use L'Hopital's rule. Like you will be very happy, I will use L'Hopital rule, right? L'Hopital's rule. Okay, I actually forgot to write h on some place, I think. What did I forgot to write? I think I just wrote like LOP. I forgot the spelling previously. Just hold on a second, let me check. What did I forgot? Somewhere I wrote L'Hopital rule. Okay, leave that then. Okay, previously I think I wrote, not here actually. Okay, here, yeah. This spelling, I tend to forget the spelling sometimes. Okay, So here this is also okay. So L'Hopital rule. So you will be very happy. Yes, I will apply L'Hopital, very easy. But then what you will see is that mod of x is not differentiable. Seeable at x equals to 0. Okay, hence again you will become sad. I can't use L'Hopital because function has to be obviously differentiable, else how will you find the value of the differentiation? We will understand more about differentiability in next few lectures. Okay, so for now just you try to take my word that this function is not differentiable. We can't differentiate numerator and denominator, so we have to solve using basics. Okay, so if you have to solve using basics, so we have to again find the LHL and RHL. Okay, because again we have the option of limit does not exist. So for LHL, what I'll do, limit as x tends to 0 minus 2x minus mod of x 3 of mod of x minus 2x equals to, I can replace this h as h tends to 0. This will be replaced with 0 minus h minus mod of 0 minus h, and this is mod of 0 minus h minus 2 0 minus h. So this will become limit as h tends to 0. This is minus h, and mod of minus is h because h is a small positive quantity. Okay, h is a small positive quantity. Small positive quantity. Okay, so this is h itself, and this is 3 of h minus 2 into minus of h. So this will be tending to 0 minus h minus 3 of h divided by plus to 5h, right? So this will be now I can cancel h, and this will be minus 3 by 5. Okay, so I am getting minus 0.6 as my left hand limit. Now let us calculate the right hand limit, which will be very easier for us to calculate. So I will write this directly now. Limit as h tends to 0, and I will replace x with 0 plus h minus mod of 0 plus h divided by 3 into mod of 0 plus h minus 2 into 0 plus h. Okay, limit as h tends to 0. This is 2 minus h, so this will be 2h minus h divided by 3h minus 2h. So this is limit as h tends to 0, h by h, so which is equals to 1, right? So what we can observe is our left hand limit is not equals to my right hand limit. So obviously I will say that limit does not exist. Okay, limit does not exist. So option D will be my answer. Okay, so yeah, this is how you solve like this modulus type of question, right? You have to solve with basics. You can't use a L'Hopital's rule. That is very important. This is another type of question. Now let's solve the next type, that is solving double limits. So one question came from gate. Okay, I think for double limits a simple question will only come. Okay, so just a very short topic. We'll finish this, and then in the next lecture we'll start with continuity. So basically here, right, what we can say that if I have a double limits, so if I have a function of xy, okay, xy function, which is like a function which is a function of two variables x and y, x is tending to a, y is tending to b, okay, and I have to find the limit of this particular function. What I can do is, like, this can be written in this format. What I can do is that I can individually find the limits. First I will make my y tending to b put in this function. Okay, then I will put x equals to a. Okay, then I will find some value L. Then I will do the opposite. I will put first in this function x equals to a. Okay, and then put y equals to b. Okay, and then I will find some value m. So you might say, sir, won't this be the same? Yes, this will be the same when limit exists, and that will be the value of the limit. This L will be equals to m when limit exists, and limit will be equals to this L or m. Okay, but this may not be same always, and when this is not same, we say that limit does not exist. Okay, I won't go to the visual details of this because that will make the lecture very lengthy. We don't have time. Okay, just they will give you some question to find limits of double variables. Okay, two variables, and you will just simply solve it. You don't need to go into the too much details. Okay, too much detail visualization you don't need to. Okay, so this is how you go. So basically, from one question we'll be able to understand this much better manner. So here, first what you have to check whether I am getting some 0 by 0 format or not, whether I can simply put this value of x and y or not. So first simply put x and y. Okay, so you put x and y, then what do you see? So if you put x equals to 2 and y equals to minus 1, this is 8 minus plus 3, which is 11. Okay, 8 plus 3 is 11. 8 plus 3 is 11. Okay, so which is not equal to 0. Not equal to 0. So anyways, you don't need to do that much of hard work right now. Don't need to do that much of hard work. You can simply say that limit will exist. Limit will exist because either way this is not going to 0. Okay, you put x y equals to minus 1 first or x equal to 2 first, it doesn't matter. It doesn't matter. Okay, so simply you can simply put the values. So this will be 2 times 2 plus 3 times minus 1 divided by 4 times 2 minus 3 times minus 1. Okay, this will be 4 minus 3 divided by 8 plus 3. So this is 1 by 11. So 1 by 11 will be your answer. 1 by 11 will be your answer. Okay, but what if my, okay, wait a second, what if my denominator goes to 0? Here this is a gate question, gate production engineering question. Okay, mathematics. This time, right, root 0 minus root 0 equals to 0. So now be careful. Now you have to use those steps. What steps you will use? So now first what we will do, limit, I will write this x tends to 0 and I will write limit as y tends to 0 x square. I will assume my x as treat x as a constant number. Okay, y x under root x minus under root y. Now what I will do, this is the first case. So this will become, if I put y equals 0, this will go 0, this will go 0, this will be x square upon under root x. Okay, so limit x tend to 0 x square upon under root x. Okay, so limit as x tend to 0, this will be x three by 2. Okay, so this will be equals to simply 0. Now let us calculate the right hand side. Okay, I mean not the right hand side, the other way around, right? Other way around. So this time what I will do, case 2. So this is, let's say this is L. Let me calculate for M. This time I will put the value of y later on. Okay, and then what I will put? I will put limit as x tending to 0, this function, right, x square minus xy divided by under root x. Anyways, this was 0 by 0 format. You will be able to observe this is 0 by 0 format. So this is also like, right, 0 square minus 0 into 0 equal to 0. So 0 by 0 format, right? So under root x minus under root y. So this will simply be this is going to 0, this is 0, 0. So this only this is remaining, right? Okay, this is also going to 0. This is also going to 0. So overall, anyways, this is totally going to 0. So what I will write, limit as y tend to 0, this whole thing, right? 0 minus 0 divided by 0 minus under root y. So anyways, something 0 by under root y is 0 itself. So this is 0 irrespective of the value of under y, right? So this will be anyway 0. So obviously L equals to M equals to 0. So my answer will be 0 itself. Answer will be 0 itself, right? So here option A will be correct. So let me just give you a quick recap of what we did in this lecture, and then in the next lecture we'll study continuity. Okay, so these are basic lectures. You can go through this very fast. Okay, just the last few questions, right? Question solving part you have to be more attentive, right? Because like concepts you may know, okay, concept you may know, but you may have forgotten how to solve the questions. That is more important, how to solve the questions. So what we did, we basically solved few different types of limit. We solved the questions that I gave you as homework. Then we learned about the L'Hopital's rule. So how to solve the L'Hopital's rule? If I have a 0 by 0 format or an infinity by infinity format, I can solve using L'Hopital's rule, but it has to have like the function must be differentiable. If the function isn't differentiable, obviously I won't be able to differentiate it, right? What do you mean by differentiation? We'll understand in the next few lectures after continuity. Okay, so like if the first differentiation does not work, even after differentiating for one time both numerator and denominator with respect to this variable x, if again I'm getting 0 by 0 format, again I will differentiate. Okay, again I will differentiate share. Okay, so next, this function I have, derivative I have. Okay, so next, right, so I told you few standard derivatives, okay, differentiation of functions, and how to solve those, also how to sometimes derive those, because I also tend to forget all of them. Okay, and now also I tend to forget all of them, but when the examinations come, I tend to put them in short notes, or sometimes I try to revise them. Okay, daily try to study those daily. Okay, very important to study this daily. And how to, like, if you tend to forget, how to find it out. Okay, I told you few basic things, cos inverse formulas. Okay, like you can put the tan as sine by cos, cot as cos by sine, all those things you can do, right? So these formulas you have to remember. Okay, then I told you like basic properties about differentiation, and then we solve. Okay, why, like I told you, right, this may be lengthy. Why? Because I have x cube, I have to differentiate it thrice to cancel the x in the bottom, so that I am left with a constant term in the bottom, non-zero constant term in the bottom. Okay, then I will be able to find my value of limit. After that we solved few formats. 1:1 infinity, okay, it has mainly two formats. The answer will be E only. 1:1 infinity, the answer will be 0:1 infinity. Okay, I don't know what is 0:1 infinity or 0:0. I will always try to take logarithm. Whenever I have 0, I will try to take logarithm. Here I won't be able to take logarithm. Okay, so these formats I told you how to solve these questions. I hope you know. This is the most important format, right? This and this format is the most important format. Okay, like the basic simple bacho wala question they won't give you, right? So next, I told you 0 by 0 format, you have to take logs. Okay, to take logs, we solve few questions, how to solve this type of question, and we are finished, right? Next is greatest integer function. Whenever greatest integer function is present, you have to take the help of graphs. Okay, and write it down, right? Very small number. I have written it down, 1 minus 1 z plus. Okay, that quantify something. 1 minus is somewhat smaller than 1. Okay, and if it is somewhat smaller than 1, greatest integer function will directly pull it down to 0. That is why it is very important to write. If there wasn't any greatest integer function, 1 minus is okay, it is 1, no issues. Okay, but here greatest integer function is present. That's why I have to be more emphatic here. Okay, I have to be more emphatic. So we solve few questions about greatest integer. Sometimes limit does not exist. Okay, if option is there for limit does not exist, we have to be careful. And like for modulus, we can't use the L'Hopital's, we have to go with basics. We solve this question, and I solved two questions for double limits. When like simply 0 by 0 format is not present, anyways you will get the answer. Okay, but 0 by 0 format is present, you will solve using this method what I told you. First, limit as x tends to 0, then limit as y tends to 0, or other way around. And if both L and M are equal, then limit exists and the value of the limit will be L equals to M. Okay, So yeah, that is basically it for this lecture, and in the next lecture we'll start with continuity. Hey everyone, and welcome back to PrepFusion. So today we'll start the third lecture of calculus chapter. So previously we have been studying about limits and functions. So right now in this lecture we'll study about continuity. What do you mean by a continuous function? Okay, and what will the previous knowledge, right, that we learned from limits, that will be utilized here. Okay, what does actually continuity mean? All those things we learn in this lecture, and in 3b 3 and 3b we'll cover continuity, then we'll cover differentiability, and then we'll cover the next few topics. So let's first understand what do you mean by continuity. What are you talking about when we're talking about continuity? Okay, we're talking about, in calculus chapter, we're talking about continuity of graph. Continuity of what? Continuity of what? We're talking about continuity of graph. Okay, our graph must be continuous. What do you mean by that? Slowly, when you will go through this lecture, you will understand. Okay, I will explain you everything. So let's read the definition. Very simple definition, that continuity can be simply defined for a graph y equals to f of x. Like whatever graphs we have been plotting, those are y equals to f of x only. So that is what we're talking about as continuous if we are able to draw the graph easily without lifting the pencil at a point. So this is the broad definition, or you might say the practical definition of continuity. So basically, if I'm able to draw a graph, right, where this is my x-axis and this is my y-axis, y equals to a function of x, y is a function of x, and I'm able to draw this graph without lifting the pen even once, or pen or pencil. Okay, now if I like draw some graph like this, I had to leave the pen. Right here there is a gap here, so I had to leave the pen, okay, and then start from here. Okay, then we might say that this function won't be continuous function. This is the what do you say, practical definition of continuity. Now, like, how can we define it mathematically? We have to talk about continuity mathematically, because in practical sense it doesn't, we won't be able to evaluate whether the function is continuity or not just by looking, right, just by looking. Okay, and by this definition we won't be able to evaluate, so we have to think about different ways. So mathematically, what they tell us is that let f of x be a real valued function on the subset of real numbers, like the x is all real numbers, and let c be a point existing in the domain of f of x. So we have already understood the meaning of domain and range, all those things, right? I won't explain over here, of f of x. Okay, then we say that the function f of x is continuous at the point x equal to c if we have limit, left hand limit, that is limit as x tends to c minus just before c, and right hand limit, that is limit as x tends to c plus just after c, f of x equals to f of c. Okay, so this point is very interesting. Here we're talking about continuity at a point. You have to note this point, right? Very important. We can only talk about continuity at a point. Okay, we can't talk the continuity of the whole function at all the points. No, we can't. We can say that at x equals to 1 this is continuous, at x equals to 1.1 this is continuous, at x equals to 1.2 this is continuous, but I won't be able to say between x equals to 1 to 2 this is continuous. Okay, from this definition I won't be able to say that. From this definition I will only be able to say that the function is continuous at a point. Okay, I will come back to this, don't worry. Okay, so continuity at a point, like we are talking about continuity at a point, we are not talking about range right now. Okay, just keep this in mind. So continuity of what? Continuity of the amplitude of the y-axis, because in signals and systems there you will study continuous time system, discrete time system. That thing is different. So I will write here, this is amplitude of y-axis. Also I will write here that signals and systems like continuous time and discrete time, they are different, right? They are different. Okay, so these are different. So like, don't get confused. When you will study signal system, there you will understand what does a continuous time signal mean and what does a discrete time signal mean. Those things are different. Here we're talking about continuity of the amplitude of the axis. I plotted, right, y is a function of x, so we're talking about the amplitude. Now let us define few things. So here, like, let me just write down few things, jot down that these, right, this is known as the left hand limit. Just hold on a second, let me check everything is recording or not. Yeah, this is recording, everything is recording, fine. So this, right, this is known as the left hand limit. We already know this. This is known as the right hand limit. Now what do we call this? F of c. What do you call this? Is the value of the function, right? This is the value of the function at x equals to c. So this is known as the a functional value. Like, if you want to formally name it, this is known as the functional value. Functional value. Okay, so if this condition is made true, if this condition is true, so then we can say if this condition is true, then this condition is true, then we can say amplitude is continuous. We just write this properly. Continuous at x equals to c. Okay, so amplitude will be continuous if the functional value is equals to the left hand limit is equals to the right hand limit at that particular point. Then we will say that the function is continuous at that point. So previously what we learned, we only learned until this part, right? We learned that limit for a function, limit for limit to exist for a function of a function at x equal to c, the left hand limit and the right hand limit must be same. But right now what we studied that for the function to be continuous at that point, an extra condition is added, that is these two things must be equal, that is limit must exist, that is the first condition. Then it should also be equal to the value of the function at that point. Then only we might say that the function will be continuous. So these condition is very important, and this is how you will solve the questions of continuity. Okay, so let's start with the example, and from there we'll understand this better. So in example, they are asking us to check the continuity of f of x. Okay, f of x is this old function which we have taken previously, I think. So first let's clear our domain. So obviously we have to like make sure that we are not plugging in any values that can make the function undefined. Okay, so what is the domain? Domain is all real numbers except which can make this denominator 0. So domain can't be equals to x equals to 1. Okay, so this, right, here my domain equals to all real numbers minus 1, right? X can't be equals to 1, so it is equals to all real numbers. Let me just note, this is like all real numbers and x equals to 1. So let's first calculate the left hand limit. So left hand limit will basically be like around 1. I am only talking about the continuity because every other point it may be continuous. Why? I will explain later. I am more interested in 1. Okay, so generally this denominator is the most interesting part, right? So I'm more interested in 1 right now. So around x equals to 1. So I will calculate the limit for around x equals to 1, right? So here let me just check. So if I do limit as x tending to 1 minus x square minus 1 by x minus 1. Okay, so what I can replace this can be replaced with 0 minus h, right? 0 sorry, not 0, 1 minus h. I can replace my x with 1 minus h. Okay, so as h tends to 0,
this will be 1 minus h whole square minus 1 divided by minus 1 and yeah, this is it basically. So now, right, h is tending to 0. What I can do, I can simply break this down. 1 minus h minus 1 into 1 minus h plus 1 divided by 1 minus h minus 1, right? So these can get cancelled out. Okay, this can simply get cancelled out, and this will be simply now limit as h tends to 0. I can simply put h is tending to 0. This will be simply 2. Okay, so this will be simply 2, right? And what about the right hand limit? What about the right hand limit? Limit as x tending to 1 plus. Okay, so again the same thing. Okay, I will just put one thing I will do. I will take another page actually. This will be x square minus 1 x plus 1 equals to limit as h tends to 0 1 plus h whole square minus 1 divided by 1 plus h. This is not minus, this is plus 1, this is minus 1. Okay, so yeah, this is the case. So like I hope you are able to catch up this thing, right? Why, how am I replacing this with 1 plus h? All these things we have studied in limits. Generally we used to replace 0 plus h because this, right, x was anyways tending to 0. That's why now we are replacing 1 plus h because h is a small positive quantity and this is something greater than just 1. Okay, that's why this is 1 plus h, because x is tending to 1 plus. Here this is 1 minus h. H is something small positive quantity and this is something lower than 1, just something very closer to 1 but something lower than 1. Okay, so I hope you are grasping that concept. So now, right, again the same thing, this will get cancelled. 1 plus h plus 1 into 1 plus h minus 1. So now this is 1 plus h minus 1, so this will get cancelled. Okay, and this is 1 plus h plus 1, so this will only remain 1 plus h, and obviously we have the limit over here, limit as h tends to 0, so this will get cancelled. So only 1 plus h 1 will remain and this will be 2 again. 0 plus 1, so this will be 2 again, right? So this is equals to 2. Now this is equals to 2. That means my left hand limit equals to my right hand limit. Now what about my f of 1, right? What about my f of 1? So can you tell me what is f of 1? We might say the function is undefined at f of 1. Function is not defined at f of 1, right? So obviously as it's not in the domain itself. Okay, so that is the reason our graph will look something like this. We'll put a hollow circle over here to represent broadly that x equals to 1 function is not defined. So at x equals to 1, function is not defined. Okay, this point is very important. This point is very important. Okay, so at x equal to 1 function is not defined, right? So like you might say, sir, but this is like telling us that like this has more number of points because this circle is so big. This circle is so big, but we can't just simply represent a point, right? The point will be so minuscule, small, right? So minuscule. Even here, if I mark this, you might say that so many points are included over here. So to represent, like this is just a single point, we mark it as a hollow circle. So hollow circle represent that the function is not defined at this point. Okay, the value of the function is not equal to this, except the left, just at the left the value of function is almost going towards 2, just at the right the value of the function is almost going towards like 2. If I come from the left, if I come from the right, it is going towards 2. Perfect example of limits. the perfect example of neighborhood. If I am on the neighbor of this one, x equals to 1, go from the left hand side and go from the right hand side, it is tending towards 2. Okay, but exactly at x equals to 1 the function is not defined. Okay, you might say like in Hindi I might say उसके एकदम पास पहुंच गया मैं, एकदम पास, लेकिन उसके साथ मतलब हाथ नहीं पकड़ पाया उसका, ठीक है, हाथ नहीं पकड़ पाया लेकिन एकदम पास पहुंच गया, ठीक है। इसका मतलब आप लेफ्ट हैंड साइड पे हो, मतलब एकदम नेबरहुड पे हो, या राइट हैंड साइड पे हो, नेबरहुड पे हो, उसके राइट हैंड पकड़ा या लेफ्ट हैंड पकड़ा, ठीक है, लेकिन हाथ मतलब पकड़ नहीं पाए, हम हाथ पकड़ नहीं पाए, देन दैट इज नोन एज द नेबरहुड, राइट। अगर हाथ पकड़ लिए तो एग्जैक्टली दैट इज इक्वल टू द फंक्शन। सो फॉर द पीपल लाइक हु आर इंग्लिश व्यूअर्स, आई एम लाइक apologizing a bit because I'm like speaking Hindi with them, so like Hindi people can understand my feelings, that's why. So yeah, that is what I am trying to explain, right? So आप एकदम पास पहुंच गए, हाथ नहीं पकड़ पाए, ठीक है, तो इसका मतलब आप नेबरहुड पे हो। आप हाथ पकड़ लिए, इसका मतलब आप एग्जैक्टली उस वैल्यू पे हो। यहाँ पे हम हाथ पकड़ नहीं सकते क्योंकि लाइक फंक्शन का वैल्यू एग्जिस्ट नहीं करता। Okay, so yeah, let's come back to English. We can't obviously put the value of x equals to 1 because the value of the function is not defined at x equals to 1. Okay, so this point is very important. So that's why we will say that the function is not continuous. Function is not continuous. Function is not continuous because it doesn't satisfy my previous definition. I told you, right? Limit should exist, left hand limit, right hand limit should be equal, and also the value of the function at that exact point should also be equal. Here the value of function is not defined at that point. Okay, so function is not continuous. And what else? Like let's go with the first definition. So if I draw this graph, okay, then can I pass through this point? No, function is not defined, right? I have to pick up my pen again, start from here. So I had to pick up my pen just before x equals to 1 and just after x equals to 1 I again start. Okay, hence I had to pick up, right? My function wasn't continuous. If my function was continuous, I didn't have to pick up my pen, then sorry, as my function is not continuous, I had to pick up the pen. If the function was continuous, then I didn't have to pick up the pen, right? I would have simply gone through this x equals to point, x equals to 1 point, then I didn't have to raise the pen. Okay, so that is the thing, right? So from the first definition also you can get a brief intuition. Okay, what does continuity mean? Either I had to pick up the pen and then again restart, or I don't pick up the pen, again go smoothly. Okay, so in the next example I will tell you like what is happening in this case. So I slightly change the definition of the function. So this, right, these makes the function continuous. Makes these makes the function continuous. Okay, so what is happening, I am defining that my function values is this for x not equals to 1. Now if my x is equals to 1, then my function value becomes 2. Okay, function value becomes 2, which is just equals to the limit, left hand and right hand limit. Very strategically I have done this. So now what will happen, here I won't have a hollow circle anymore, no hollow circle anymore. Okay, the value of the function will be exactly equals to 2. Now if I go draw with my pen, what is happening, do I need to lift my pen at x equals to 1? Do I need to lift it? No, I can go through this, right? I can go through this point, so I don't need to lift my pen anymore. So if I don't need to lift my pen, obviously like this function will be continuous. Okay, from x equals to minus infinity to plus infinity. Okay, throughout the whole range I can say that LHL RHL equals to LHL equals to f of 1. Okay, equals to f of 1, equals to f of 1, right? So yeah, then the function will be continuous because I have made the function continuous. I've changed the definition of the function. Okay, so let's do a question. From there also we'll understand that how to find continuity of function. So basically like finding continuity is basically division of limits. So you have to be thorough with the limits thing. Okay, I hope you have learned limits previously, like from the previous lectures. So right, how to check the continuity? Basically what we have learned, continuity at a point. So what we can do, at max we can check continuity at a point. So what we will do, we will check check continuity at breakpoints. Okay, we'll learn this more later on, how to check continuity over a range, over a interval, right? We'll learn this more in the next lecture, but for now just I'm explaining you this, that just check the continuity at the breakpoints, right? What are my breakpoints? One of the breakpoints is this, right? At x equal to 0, the definition of function is changing. What do you mean by breakpoint? Where the definition is changing. Where definition is changing. By definition is changing, right? So here, right, here definition is changing. So like here we have to check around x equal to 0, then after x equal to 0, 0 minus and 0 plus we have to check, and obviously at x equals to 0, this is. So they have already told us that the function is continuous. The function is already continuous. They have already told us this, right? So what we have to do? We have to determine the value of a, right? So if the function is continuous, it will be continuous here, it will be continuous here, it will be also continuous at the break points also. It will be also continuous at the break points. So what was the mathematical definition of continuity? Left hand limit and right hand limit should be equal. So exactly that we'll do around the breakpoint. So as they have told us the function is continuous, hence the left hand limit and the right hand limit equals to the value of the function, right? All these conditions must be met. So what is my left hand limit? Left hand limit is basically as limit as x tends to 0 minus f of x. What is f of x? 0 minus the definition of function is here, right? Just before 0 the definition of function is this. So this will be 1 minus 4a divided by x square. Okay, so this will be equals to basically if I replace this with h, I can do that, right? So or like this is simple definition only, 1 minus cos 4, okay, this is not a, this is x actually, 1 minus cos x divided by x square. I hope you know, but what we have to change over here is limit as x tends to 0 minus, this should be 1 minus cos 4x divided by 2x, not 2x, sorry, yeah, 2x whole square, not 2, sorry, 4x whole square. Okay, like I have put extra 4 square here, I have to multiply extra 4 square at the top. Why do you want to make this same? So we have to make this whatever inside this cos, right? We have to make this thing same. I hope you are able to recall the formula. 1 minus cos x divided by x square, limit as x tends to 0 minus or 0 plus 1 minus cos x divided by x square is equals to 1 by 2. Okay, so here you can apply the L'Hopital rule, that also you can do whatever it suits you. If you tend to forget this formula, right, 1 minus cos x divided by x square, you are free to apply the L'Hopital rule, no worries, right? If you differentiate, this will become sin x, this will become 2x. Okay, then sin x by x is limit as x tends to 0, sin x by x is 1, and 1 by 2 is there anyways, so 1 by 2 is remaining. Okay, so you can derive from L'Hopital also few properties, okay, few limits, which standard limits. Okay, so now this is 4 square, so this whole thing will become half, right? This whole thing will become half, so this will be half times 4 square, which is 16, so this will be 8, this will be simply 8. Okay, so this will be simply 8. So now what is the right hand limit? What is the right hand limit? So let's calculate the right hand limit. Right hand limit is this, right? The definition of function just after x equal to 0 is this, so hence we will use this as our f of x. So limit as x tends to 0 plus under root x divided by under root 16 plus under root x minus 4. Okay, so now here, right, if I put x equals to 0, this is 4 minus 4 is 0. Okay, and this is 0, 0 by 0 format. So what I can do, I can rationalize, right? So anyways, under root is like you're obviously seeing under root, so it is obvious to rationalize. Next step, it is obvious to rationalize. So basically what we're doing, we're just simply doing the revision of limits. Okay, that is what we're doing. So if I rationalize this, this will be x tends to 0 plus divided by under root 16 plus under root this and minus 4, like this is this whole square into 4 square. I'm multiplying and dividing by 16 plus under root x plus 4. Limit as x tends to 0 plus this is under root x 16 plus 4 divided by 16 gets cancelled. This is only x, right? Sorry, this is only under root x, right? So like this is whole square, this is only under root x because this 16, right? This 16 and this 16 gets cancelled. Simple manipulation. So now this under root x gets cancelled. We're only we're only left with 16 plus under root x plus 4. So simply we can put x equals to 0 here, no worries, because this is not a indeterminate format. So if I put x equal to 0, this will be 16 under root 16 plus 4. So 4 plus 4 is 8. Okay, so what do you observe is that the right hand limit is equals to the left hand limit. So obviously it has to be equal because they have told in the question the function must be continuous. Okay, so we don't need to find out this right hand limit. Like after finding the left hand limit, we don't need to continue again, as they have told this function is continuous. This value for a function to be continuous, what is the definition? Mathematical definition. Mathematical definition is LHL equals to RHL equals to f of a. Okay, equals to f of 0 in our case for a function for a function to be continuous, right? For a function to be continuous, LHL equals to RHL equals to f of 0. Okay, so this is the case. So basically what we can say is that anyways, like if you have already found out LHL, we don't need to find RHL because they have told in the question the function is continuous. We don't need to again proceed, right? But I have to teach everything, so I will show you everything, right? So but in the examination hall, if you find out LHL, you don't need to find RHL. As the function is continuous, it will be automatically equals to RHL as we have observed over here. Okay, we just have to equate it with f of 0. So what is f of 0? F of 0 is simply equals to a. F of 0 is simply equals to a. So this, right, this will be 8 equals to a. So my answer will be a is equals to a. This is the answer. Okay, this is the answer. So yeah, this is the answer for this question. Now let us try to understand the continuity at the end points. So if a function is defined within a certain range, okay, x belongs to a comma b. Let's say x, like the domain they have provided is x belongs to 1 comma 2. Between 1 to 2 the function is valid. Okay, definition of function is given. Now the function f of x is said to be left continuous at x equals to a, because like if this condition is satisfied, because let's say like I have a function like this. Okay, x y, this is my function and this is a and this is b. Okay, so the important point is the function is defined at x equals to a and at x equals to b, but before x equals to a and after x equals to b it is not defined. It is not defined. So I won't be able to find the value of the limit just before x equals to a, because the function itself isn't defined. The function itself, it isn't defined. It is not tending to anything. Just if I come from the left hand side, it is not tending to anything. Okay, that's why the left hand limit does not exist. So I will say at x equals to a, the left hand limit does not exist. F of x is defined at f of x is defined from x equals to a. Okay, from x equals to a. Just at x equals to a, the definition of the function starts. Before x equals to a, we don't know what is the value of the function. Okay, because it is not defined. So that's why limit, only the right hand limit exists. And then you might say, sir, then how will I talk about continuity? So this is how you will talk about continuity. We'll ignore the left hand limit. We'll only take the case of right hand limit and the value of the function at that point. So we'll only talk about the just at the right hand side of x equals to a and the value of the function at that point. We'll equate these two things, and then we will say the function f of x is said to be continuous at the left hand. Okay, yeah, it is said to be left continuous. Yeah, you can say it is said to be left continuous. Okay, so here again, about what about b? So just after b, function is not defined. Function is not defined. Okay, the function is defined just at b and before b. Okay, function is defined for this case. Just after b, it is not defined. Okay, so now f of x is said to be continuous at right hand x equals to a. Okay, f of x is said to be continuous at right hand x equals to a. So as we are not able to identify the value of the function just after b, we ignore the right hand limit this time. Previously we ignored the left hand limit, now we are ignoring the right hand limit, and we will only equate the value of the function at that point and the left hand limit. And if these two are equal, then the function is said to be continuous at the right hand x equals to, this is not x equals to a, this is x equals to b. Basically it is said to be right continuous. Okay, right continuous and left continuous. Left continuous and right continuous. So basically the same thing again. Right hand limit does not exist at f of x is defined until x equals to b. Right hand limit defined until x equals to b, right? So yeah, that is the definition basically about continuity at endpoints. Now let's study about different cases for continuity. Okay, there might be different cases. What are the different cases? One case I already showed you in one of the examples. We'll learn about them step by step. So what is the case one? The case one is if the limit, left hand limit, is equals to the right hand limit is equals to the function. Okay, all of them are equal, but it is equals to the infinity. It is equals to infinity. So if it is equals to infinity, then the function is said to be discontinuous. Obviously limit will exist because the left hand limit and right hand limit are equal, but function is said to be discontinuous. So the previous definition, whatever I told you, right, mathematical definition, okay, I have to make slight changes that this cannot be equals to. I will make slight changes over here. This cannot be equals to plus minus infinity. Okay, because infinity, right, I won't be able to plot that on the graph. Okay, this definition is always true. You have to plot that on the graph. Can I plot infinity on the graph? This screen will be very small for that. Okay, anyways, everything will be small because I have to go out of earth everywhere to plot infinity, because it is ever increasing, so we can never plot infinity. So that's why obviously it won't be continuous. Okay, if the value of the function is infinity at that point. So like, this is the perfect definition. It should not be equals to infinity. I have done not equal to, right? Just let me check once. Yeah, not equal to. So that is the thing. So yeah, this is the first case, right? This is the first case that limit will exist but function will be discontinuous at point C. Let's go to the second case. Now the left hand limit and the right hand limit is equals to L. Okay, and the value of the function is finite value, but it is equals to M, and M is not equals to L. Okay, same case again, limit will exist but function will be discontinuous, because obviously all of these three has to be equal. If even one of them is not equal, then it will be discontinuous. Okay, let's go to the next case. So next case is left hand limit is equals to right hand limit is equals to f of c, value of the function is equals to finite. Then only the function will be continuous. Obviously, if the function is continuous, obviously limit has to exist, because the left hand limit and the right hand limit has to be equal. So limit will obviously exist and the function will also be continuous, as this f of c equals to finite. Okay, as this f of c is equals to finite. Now let's talk about case 4. So if we are talking about case 4, this limit as x tending to minus, like the left hand limit and the right hand limit are not equal to each other. The left hand limit and the right hand limit are not equal to each other. If they are not equal to each other, then obviously limit does not exist at x equals to c. Limit does not exist at x equals to c. Obviously, if limit doesn't exist, obviously function is discontinuous. So obviously, if the left hand limit and right hand limit are not equal, sure shot function will be discontinuous. Okay, if the left hand limit and right hand limit are equal, the function might be continuous, may not be continuous, just as we saw in these two cases. Okay, these two cases we saw. But if the function is continuous, sure shot the limit must exist. The left hand limit must be equal to right hand limit. If the function is continuous, I am 100% sure that the left hand limit will be equal to the right hand limit. Okay, so there is another case. Okay, this is also a very interesting case. If the left hand limit is oscillatory, just like sine over 1 by x. Okay, as x tends to 0, minus or 0 plus, it is oscillatory. The left hand limit will be oscillatory, the right hand limit will be oscillatory, the value of the function at x equals 0 will also be oscillatory. It is finite but oscillatory. So all these three, right? All these three are finite. All these three are finite. Okay, all these three are finite. So if these three finite, then obviously we will say these are oscillatory, right? So I mean these are not infinite, but like obviously we can't quantify, right? Are they equal, are they not equal? We can't quantify. Hence we say limit does not exist. Obviously limit won't exist, and if limit doesn't exist, obviously function won't be continuous, it will be discontinuous. Okay, so function will be discontinuous and limit does not exist. Okay, so these two, like these are the 5 cases, and only in one case the function is continuous, where 3 of them are equal and obviously it is equals to finite. Okay, so these are 3 cases. Now what is the key point? I just told the key point just in the previous slides, that if limit of a function at a point does not exist, then function is discontinuous. 100% function will be discontinuous if limit of a function at a point does not exist. But if limit exists, then function may or may not be continuous. So if limit exists, function may or may not be continuous, right? But if the function is continuous, the limit must exist. Okay, I will also write a second point. If function is continuous, then limit must exist at that point. Okay, then limit must exist at that point. So yeah, these are the few key points that I wanted to mention. So next, right, we'll try to see how we can remove discontinuity. If we have a discontinuous function, can we make that continuous function? Because sometimes it's very useful to us. Okay, we want to make the function continuous because we want to make things simpler, we want to make things more beautiful. Okay, so basically there are two types of discontinuity. One is removable discontinuity and another one is non-removable discontinuity. So basically what is the thing? Previously I showed you one example, right? Here we did one example. Here my function was discontinuous. Okay, my function was discontinuous, but I made few modifications to make the function continuous. I made some modification to make the function continuous. That is what exactly we learn in this topic, right? So here where did I go? Yeah, here, right? So value, if the value of the limits are finite, okay, and my RHL and LHL is not equals to my function, okay, obviously have to be finite. So what case are you talking about? We're talking about this case 2, right? Case 2, talking about case 2. So we're talking about this case 2. My LHL is equals to RHL, but it is not equals to f of c, right? So now let's discuss continuity of f of x at x equals to 1. So like again that question, right? That question again. So here can we discuss about the continuity at x equals to 1? So again the same thing. What is the LHL? We've already done this question. LHL equals to at x equals to 1 it is equals to 2. My RHL at x equals to 1 it is equals to 2, but my value of the function at x equals to 1 is equals to 0, right? So hence this is not continuous because my RHL equals to LHL, we have already solved this, so I'm not solving it, are equal, but it is not equals to my value of the function at that point. Okay, it is not equals to the value of the function at the point. So this is the thing. So what do we do to remove the discontinuity? We redefine the function. So here to remove the discontinuity we redefine the function, given function. So what do? I take the function, copy and paste, and I try to like make all of them equal. So already the left hand limit and the right hand limit are equal. Just I need to make the value of the function at that point equal. So what I will do, I will make this 2. Okay, I'll change this to 2. Okay, so I'll redefine the function. So what I will do, I will write this as g of x. Okay, put the function so that you can understand this clearly, that f of x has been changed to g of x. F of x has been changed to g of x, right? So basically f of x is not continuous, but g of x will be continuous at x equals to a. G of x okay, sorry, not x equals to x equals to 1. Okay, g of x is continuous at x equals to 1. So next is like this is the removable type discontinuity, but obviously there are non-removable type discontinuity. What are the non-removable type? Where the value of the limits are finite, but that is the left hand limit and the right hand limit, the values are finite but they are not equal to each other. Can I make the limits equal? If I try to make the limits equal, I have to change the function totally. Okay, and that I don't want to make. Okay, that we won't do. So these, right, I just change this point here, but I won't change this right here. That I won't do. Like I won't change totally the definition of the function. I can change a particular point, but totally the definition of the function I don't want to change. Okay, that will obviously change the function. So here you can see I have one example which is signum of x. So if I have signum of x, then what do you see? The right hand limit, like if I come from the right hand side, the value of the function is x like 1. If I come from the left hand side around 0, if I come from the left hand side around 0, the value of function is -1. They are not equal. Left hand limit is -1, right hand limit is 1. You try to solve this mathematically. You try to tend x 0 minus, then you try to tend like put x equals to 0 minus h, and you solve those mathematically. All those things you do, we have done this multiple times. Okay, you can solve these things. Okay, so here, right, left hand limit and right hand limit are not equal, so I won't be able to make this function continuous. This is not removable type discontinuity. So here I will write my left hand limit is equals to -1, my right hand limit is equals to +1. Hence left hand limit is not equals to my right hand limit, hence they are non-removable type discontinuity. Okay, so yeah, this is one case. Okay, there is also another type of discontinuity, but these functions are not discontinuous, what I am talking about. So here signum of x is discontinuous. Okay, but sorry, signum of x is not equal to discontinuous. It is known as piecewise continuous function. Why? I will explain. Let's read this definition, and from there, just hold on. From there we'll understand this better. So the piecewise continuous function is generally defined as a function that has a finite number of breaks / jumps in the function and doesn't blow up to infinity anywhere. Okay, so basically the piecewise continuous function is generally defined as a function that has a finite number of breaks / jumps in the function. Okay, so and doesn't blow up to infinity anywhere. So what does it mean? So it is basically talking about this. So it has jumps, it has discontinuity. Okay, finite number of breaks or jumps that doesn't blow to infinity anywhere. What do we mean by break? This is known as a break, right? Suddenly from this at around x equal to 0, from -1 I'm suddenly going to 1, so I'm suddenly going to 0. Then from this 0, right, I'm suddenly jumping to 1. Okay, but this is a finite jump. Okay, how much distance did I move? 1 unit. How much distance did I move? 1 unit. Is this infinity? Okay, no, this is not infinity, right? This is finite jump, so this doesn't cause us issue. Okay, so that is the thing. Now the non-negative difference between two limits is called as jump of discontinuity, right? So basically what can I say, that here, right, like this is a definition of jump. The non-negative difference between the two limits is called as jump of discontinuity. So here, right, between two limits, how much total distance I'm covering? Non-negative means distance. Total how much covering? Distance 2 units distance I'm covering. Okay, that is finite, that is not infinite. Hence here, right, if I have finite number of jumps and the jumps also are finite, okay, and the jumps also are finite, then it is called as piecewise continuous function. Okay, piecewise continuous function. Yeah, so that is the case. So basically what are the example of piecewise continuous function? Basically our signum of x, signum function is piecewise continuous function. Okay, so because there is jump at only one jump at x equals to 0. We have only one jump at x equals to 0. Okay, next is this fractional part of x, greatest integer function. Okay, so you might, if you recall correctly, there were infinite number of jumps, right? Here, this is not stopping anywhere. Like the jumps between this exactly at the integer values, like the number of jumps are infinite at x equals to 1, x equals to 2, x equals to 3, x equals to 4, x equals to 5. Infinite number of jumps, it is never stopping. Okay, hence these are not piecewise continuous function. So not piecewise continuous function. Okay, why? Because infinite number of jumps. Infinite number of jumps. Okay, infinite number of jumps. So yeah, this is about the piecewise, because the signum of x, few people may get confused that this is a discontinuous function. Yes, this is discontinuous around x equals to a, x equals 0, but you can also say that signum of x is a piecewise continuous function, and I have told you the definition of piecewise continuous function. So this may come up in examination. Okay, so let's come to the type 2 of non-removable type discontinuity. Now here, right, if either our left hand limit or right hand limit or functional value tends to infinity, okay, plus minus infinity or oscillatory, obviously we won't be able to redefine one function. Okay, that we won't be able to do. Only when my limits are finite, okay, when my limits are finite, then only I can change like the value of the function at that particular point to make the function continuous. Okay, here, right, limits are finite, I can do that. But here, and also they have to be equal, limits have to be equal, so that I don't change the function totally, I'm just putting a value of that function at that particular point, right, just making that equal. That much modification I can do. Okay, that much modification I'm allowed to do. But these type of modification, right, I am not allowed to do. The left hand limit and right hand limit are not equal, obviously I won't be able to change the definition of the function. That I'm not allowed to do. Okay, that much power I don't have. Okay, so yeah, those are things. Here also the limits are not finite. The left hand limit is tending to infinity or minus infinity, or they're oscillatory, then also I won't be able to do, right, that also I won't be able to do. So basically one example is sine of 1 over x. So if you observe this carefully, around x equal to 0, what is it tending to? So my left hand limit, right, left hand limit as x tends to 0 minus sine of 1 by x. So this is almost around, I can change this to limit as h tends to 0 sine of 1 by 0 minus h. So this is basically limit basically sine of minus infinity, right, I won't be able to eliminate the 0 in the denominator, so this will be simply minus infinity. Okay, now what is sine of minus infinity? I don't know. This is something oscillatory. And let's talk about the right hand limit. So this is limit as h tends to 0 sine of 1 by 0 plus h. So this will be limit as h tends to 0 sine of infinity. So this will be simply oscillatory again, right? This will be simply oscillatory again. And obviously the value of the function at x equals to 0 is anyways again oscillatory, right? Same thing again, oscillatory. Okay, so hence I will say function is discontinuous, f of x is discontinuous, and I won't be able to make the function continuous. Okay, so this is the case. So what I will do is I will give you few homeworks, okay, and in the next lecture we'll solve these questions. So this is the first question. You try to discuss continuity at x equals to a. Basically this is helping you revising your limits concept, right? We have this question also. Just try to identify the format. What format is this? Okay, what is this e raised to power format? What is this 1 plus sine mod of sine x format, right? All this you try to identify. Okay, my pen is not working. Yeah, this, right, this format you try to identify this format. And okay, that's the end of this lecture. And in the next lecture we'll solve these questions and we'll understand how to find continuity over interval, open interval and closed interval. Okay, and we'll also talk about different things, right, about continuity. So I will see you in the next lecture. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the second part of lecture 3, that is about the continuity of a function. So in the previous lecture we learned what is a continuity, how to check continuity at a point. Okay, in this lecture we'll understand how to check continuity in open and closed interval and what are the properties of continuous function. So basically this, right, we won't like do anything different, we will do the same thing only, but we'll apply few common sense to find the continuity over a range. Okay, this we'll do, and then we'll understand the properties of continuous function. But before going to this lecture, we have to obviously solve the previous questions that I gave you as homeworks. So here this one was the first question, right? So yeah, so here we had to discuss the continuity of f of x at x equals to 0. At x equals to 0 we have to discuss about continuity because around x equals to 0 there is some change in the function, right? The definition of the function is changing. In general, wherever the definition of the function is changing, we will find the limits, okay, left hand limit and the right hand limit, and we'll check for continuity at that point. So yeah, let's find the LHL and RHL. Okay, so here what we'll do, limit as, now this is, right, this is something like 1 raised to power infinity format, right? 1 raised to power infinity format. So this will be something like e. Okay, but here I have 2x, but here I don't have 2x, I have x only, so I will multiply and divide by 2 to bring a 2 over here, right? So this limit as x tends to 0. Okay, the left and right hand limit will be same because we have already the standard result for this. So I will calculate only limit once. Okay, and we know that the left and right hand limit will be same, into 2x, not x, yeah, into 2 equals to, what is this? So this whole thing, right, this whole thing will be e raised to power 2. So it is e raised to power 2, and at x equals to 0. Okay, so this is the value of RHL, and LHL will also be same. Okay, and the value of the function at x equals to 0, it is directly given that the value of the function at x equal to 0 is e raised to power 2, e square. So what we are observing, that our RHL equals to LHL equals to f of x at x equals to 0. Okay, so we can say that function is continuous. Okay, function is continuous at x equals to 0. At x equal to 0, right? So yeah, so this is how we solve this like a question. And anyways, these two are finite. Obviously the left hand limits and the right hand limits are finite. Obviously we'll say that the function is continuous. Okay, so yeah, this was the solution of this question. Let's go to the next question. So here also we had to find the value of a and b if function f of x is continuous at x equals to 0. Now it is reverse. So in general these type of question can come. Okay, that previous question won't come. This type of question may come, that they will tell you that the function is continuous around x equal to 0. Now you have to evaluate some other parameters of the function, like in this case b and a. Okay, so first what you'll do, you will calculate the left hand limit and right hand limit, and you will calculate the value of the function at x equal to 0. And you know all these three things will be finite and they will be equal, because it is already mentioned in the question that the function is continuous. Okay, so first what you can do, you can calculate the LHL, right? So for LHL, just before x equal to 0, what is the definition of the function? Definition of the function is this, right? So LHL is this. So limit as x tends to 0 minus f of x, which is equals to limit as x tends to I can say 0 minus e raised to power tan 3x by tan 2x. Okay, now this, right, this is simple formula, we will know all these things. Okay, so limit as x tends to 0 minus e raised to power tx by 3x into 2x by tan 2x. Now we have multiplied 2x and 3x, right? So we have to obviously like make this one also. Obviously we can't like bring numbers from heaven and put them here and just do as it is. We have to finally keep this expression intact. So what we will multiply? We will multiply 3x by 2x. So this 3x will get cancelled here and these 2x will get cancelled here. But these, right, these individual terms are what? This is tan 3x upon 3x. What is this? This is 1 as limit x tending to 0. Okay, and this is tan 2x upon 2x, right? This is also 1 as x tends to 0. So overall my value will be this e raised to power 2 by 3. Okay, so yeah, just hold on a second. This will be e raised to power 2 by 3. So this is 2 by 3, or sorry, 3 by 2. Okay, so this will be e raised to power 3 by 2, right? Now let's go to the right hand limit. So if I go to the right hand limit as x tends to 0 plus f of x, which is equals to 1 plus mod of sin x. Mod of sin x, like it is tending to 0 anyways, like 0 plus like sin 0 is almost 0. So this is again 1 raised to power infinity. So we have mod of sin x over here, we have also mod of sin x over here. Okay, so this thing is intact, but this a is extra. So how I can write like this, right? Mod of sin x 1 by sin x mod of this. Obviously we have limits also. Raised to power a, right? This raised to power a. Okay, so now, right, 0 plus. So again this whole thing, right, this whole bracket thing is e only. So this is e raised to power a. Okay, and the value of the function at x equals to 0 is what? It is equals to b. So at the end all these three should be equal. So e raised to power 3 by 2 should be equals to b, should be equals to e raised to power a. So obviously from this, right, we will be able to evaluate a and b. So my b will be simply e raised to power 3 by 2 and a will be simply 3 by 2, right, because this is in the power. So these powers must be same as the base is same, and this b will be e raised to power 3 by 2. So this is my answer to this question. Okay, so yeah, this is the end of this lecture basically. I mean, not this this questions basically. So let's start our lecture. Okay, so here we have to talk about continuity in an interval. So there are two types of interval. One is open interval and another one is closed interval. So I hope you remember, like, what does open interval mean? Open interval means it doesn't include a and b. Okay, like in between a and b all the points are included, but exactly a and exactly b are excluded. Okay, so this is the case. And what about closed interval? A comma b. Okay, closed interval means all the points between a and b will be included obviously, but the points a and b will also be included in this case, not excluded. Okay, so this is the difference between open and closed interval. So let's read about what does this mention about continuity of a function in open interval. A function f is said to be continuous in open interval a comma b if and only if. This IFF means if and only if. If and only if the function is, okay, I should, if and only if the function if and only if the function is continuous at each and every point. Okay, so obviously excluding a and b, it has to be continuous at each and every point, then only we can say that the function is continuous in that open interval. Like, this is so basic thing. Like, what you might say, sir, why are you mentioning this? Okay, yeah, like there isn't any point to mention this, but still sometimes basic things also become very difficult when you study too many things, right? So yeah, let's study about closed interval. A function f is said to be continuous in a closed interval if the following conditions are met. F of x is continuous in the open interval. So first condition, this condition has to be met, right? It has to obviously be continuous in the open interval. Then f of s has to be right continuous. I was mentioning this in the previous lecture, right? When we find the limits for not minus infinity to positive infinity, we find limits for ranges, right? Ranges. So here, as a is included, so for f of x at x equals to a, we won't be able to calculate the left hand limit. Why is this the case? Because the function doesn't exist in the left hand side of a, right? So there is no concept of LHL, because at the left hand side, like in no value of x is in the domain for that function, right? At the left hand side. That's why, okay, we will ignore the left hand limit. We will only equate with the right hand limit, and we will say that the function is right continuous at x equals to a. Okay, and if this condition is met, we will say function is right continuous. Similarly, for left the endpoint, right, x equals to b, on the right hand side the function doesn't exist, okay, around x equals to b. On the left hand side the function exists, okay, the function exists. So what we'll do, we'll only compute the left hand limit and we'll equate it with the function value of the function at f of v, okay, and if that is finite, then we'll say that the function is left continuous, okay, and then we will say the function is continuous over the closed interval. So function has to be right continuous, function has to be left continuous, and then only we can say the continuity about the closed interval, okay. So let's solve this question, very basic question. You try to solve this, and then I will come back with a solution and more questions. Okay, so what is this question asking us? We have to find whether the function is continuous, and if it is discontinuous, then tell which points are discontinuous. We have to talk about the continuity of the function. Okay, so the range has been given, x belongs to 0, 1, okay, for the first case, and for the second case x belongs to 0, 1, and 0 and 1 is included in the second case, and in the first case 0 and 1 are excluded. Okay, just hold on a second. Let me check if everything is recording. Yeah, everything is recording. So this, right, the function is greatest integer function, and it is also mentioned that the square brackets means greatest integer function for this case. Okay, so here let me just try to plot the greatest integer function around like 0 to 1. Okay, so if I plot this greatest integer function, this is x-axis, this is y-axis, okay, and like around 0, exactly at x equals to 0, it is 0. Okay, just above it, it is again 0 because greatest integer function brings it down. Okay, so just below 1, it will still remain 0. Okay, then just at x equals to 1, it will suddenly jump to 1. Okay, then again it will remain at 1, and just at x equals to 2, it will suddenly jump to 2. We won't put that over here. Okay, this is at x equals to 1, and this is at x equals to 0, and just before x equals to 0, this will pull it down to this minus 1, right? But exactly at x equal to 0, this will exactly go to 0. Okay, so this is equals to minus 1. Okay, so this is the case. Basically we are seeing sudden jumps, right? So there must be some discontinuity. We have to talk about this thing. Okay, so what we observe, as my x is not included, 0 and 1, is the function continuous between 0 and what is the value of the function between 0 and 1? Okay, so f of x equals to 1 for not 1, sorry, equals to 0 as x lies between 0 and 1, not equals to 1. Okay, so like the value doesn't change, so function is continuous. For the first case, function f of x is continuous as x belongs to 0, 1. Now let's talk about this square bracket, right? Okay, when 0 and 1 are included. So now let's talk about the second case. In this case, 1 and 0 are also included. So what do you observe here? Like, can I draw this graph? without lifting the pen. Okay, I'm coming from this left hand side, I'm just at equals to 0. Suddenly there is certain jump. Okay, then there is certain jump. Okay, so obviously I have to lift up my pen, then again put this point over here. So from the graph we can see the function is not continuous. So whenever this greatest integer type function is given, okay, you try to solve using graphs, that would be better. Okay, if you try to solve using equations, you can, obviously there is no issue with that, but with graphs it is more visually appealing and it is more intuitive to understand. Okay, so here, right, f of x is not okay, because 0 and 1 are not continuous. X equal to 0 and 1, there is discontinuity, sudden jump. Whenever there is sudden jump, discontinuity, because what continuity, what do you observe? We observe that, okay, where did it go? Okay, we observe that the left hand limit is 0, the right hand limit is 1. They are not equal. That is one thing. Okay, anyways we're talking about the left hand limit only. Okay, anyways we're talking about the left hand limit, because at x equals to 1 we will only talk about left continuous function. Okay, so the left hand limit is 0, and exactly at x equals to 1, what is the value of the function? It is 1. Okay, which are not equal. So again, this condition is not satisfied, even though they are finite, but they are not equal for this x equal to 0. At x equals to 0, the value of the function is 0. Okay, and just at the right hand side, the right hand limit is also 0. So this condition is satisfied. Okay, but this condition is not satisfied, hence we can say that the function is not continuous. Okay, x equal to 0, sorry, x equal to 0 there is no discontinuity, I'm sorry for that. X equal to 1 there is discontinuity. Okay, okay, so yeah, this is the case. So basically, how do you calculate continuity in an interval? What is the procedure? So here you have to look for possible points of discontinuity, as I mentioned earlier also. Okay, so like when graph is given, it is very simple to calculate, right? When graph is given, okay, you can easily directly identify that x equals to 1 is a point of discontinuity, and x equals to, like, if I ignore this point, then obviously x equals to 0 is a point of continuity, like it is continuous. But if I also include from -1 to x equals to 1, then you might say x equals to 0 also is a point of discontinuity, because the left hand limit and the right hand limit are not equal to each other. Okay, so here, right, when graph is not given, okay, when graph is not given, so obviously it is not possible to find, like, up until now, what we know how to find limits at a point, and with the help of limits we know how to find continuity at a point, but it is impossible to find, like, check infinite points. So it is impossible to check infinite point, because we only know how to find continuity at a point. So what do? We just check continuity, just hold on a second, we just check continuity at possible points of discontinuity. Now what are the possible points of discontinuity? We'll talk about that. Okay, but before that, like in general, we have to understand few things, that few functions are continuous within some range, and we will remember those. Okay, else obviously you won't be able to calculate the continuity around a range and calculate the calculate all the points, right? It is impossible for us to calculate all the points, continuity of all the points. I mean, to find the continuity of all the points, what we do is we understand this fact that all polynomials, trigonometric functions exponentials and logarithm functions are continuous but within the domains. Okay, this is very important. This point is very important. They are continuous. Okay, this is an information based fact that all of these functions are always continuous, but only if the value of the input, right, the value of the variable is kept within their domain. Okay, then only they will be continuous. Here you might say, sir, this is what this graph of what this tan inverse of x, right? So not tan inverse, this is tan of x. Okay, so you might say, sir, tan of pi by 2 is going to infinity. Okay, then how is it continuous? Pi by 2 is not included in the domain. Okay, pi by 2 is not included in the domain, it is excluded. Okay, it is an open interval. So here this is tan x, and here what we say, that x equals to pi by 2, like or odd multiples of pi by 2 is not included in the domain. Odd multiples of pi by 2 is not included in the domain. Okay, so now this is the thing. Now how to find the so-called possible points of discontinuity? We're talking about that, right? So this is a information based fact. Whenever these type of functions are given, right, we'll solve an example, and from there we'll understand this better. You will say that within that range this function must be continuous, but there can be a few possible points of discontinuity. We'll talk about that. Here first point is, if you have been given a rational function, okay, and the numerator denominator are functions of x. Now what do you do? Okay, like f of x, g of x can be anything, polynomial, sinusoidal, exponential. Okay, can be anything. I should try it here. Or okay, now what are possible points of discontinuity? Now if there is a common factor in numerator denominator, we solved this at the start, right? X square minus 1 divided by x minus 1. So x minus 1 was the common factor. Then x equals to 1 is a possible point of discontinuity, right? Because 0 by 0, like they are getting cancelled, right? And x equals to 1, the denominator is going to 0. Okay, but you are cancelling it, then you are putting x equals to 1. That is not valid. Okay, that is not valid. Okay, that may be possible point of discontinuity. Then the roots of g of x. Okay, if the roots of g of x are real, those roots will be also possible points of discontinuity, because x is only real. The domain which we are working with is real numbers. Okay, so obviously the roots of g of x. So I'll say roots of g of x which are real. Okay, and the common factor in numerator and denominator, right? So this is the case. Now let's understand what are the roots of g of x. Roots of g of x can be complex, they can be real, right? I mentioned over here, right? So these are the possible points of discontinuity if there is a common factor between numerator and denominator, which we have already done. X square minus 1 divided by x minus 1, that we have already solved, and this, right, we'll solve in the next question. We'll solve this. Okay, wherever the value of the x, like the roots of the g of x, the denominator are real, then those will be my possible points of discontinuity. Okay, possible, I am saying possible, very important. So here obviously what you do, what does real roots mean? Real roots mean I equate my g of x equals to 0. Okay, I equate my g of x equals to 0. Now if my x comes out to be real, right? If my x comes out to be real, so this, right, this x can be possible point of discontinuity. Okay, and if my x is not x is complex, right? X is complex. Okay, x is complex, then what I'll say, I will say obviously I have complex root. Important fact is g of x cannot be equals to 0 for real values of x. G of x cannot be equals to 0 for real values of x. Okay, so hence in the domain of x, like our domain is real values. Okay, it will always be continuous. That is our there will be no discontinuity. discontinuity. Okay, so this is the case. Now let's do this question, right? Let's do this question. You have to find the possible points of discontinuity for the given function. You try to, what do you do? You try to find any common factors, if you have common factors between numerator and denominator, and also you try to find the roots of the denominator. Okay, and if those are real, they can be possible points of discontinuity. Else they may not be. Also. Okay, because here the definition of function isn't changing, but what I may do, I may change the definition of function and make the function continuous. That is also important. Okay, at that particular possible point of discontinuity. So you try to solve this and then you again play this video. So I will start. Basically this, right, denominator is x square plus 2x plus 1. This is like x plus 1 whole square. Okay, so this means for the first case, x equals to minus 1 minus 1. Okay, so x equals to minus 1 are possible points of discontinuity, but in this case they are not possible. They are points of discontinuity because x equals to minus 1, obviously it is going finite upon 0, so obviously it is discontinuous. Finite upon 0 is undefined. So this is point discontinuity, right? Now let's talk about x equal x plus 1 whole square. Now the second case, right, how do you find the roots basically? So this I will say sorry, I'm feeling very sleepy. This is some finite upon 1 upon 0, right? Hence this is the possible point of discontinuity. Now let's solve for the second case. Solve it here. So basically this is x square plus x minus 1 divided by x square minus 2x plus 2, right? So g of x equals to x square plus x minus 1 divided by x square minus 2x plus 2. Okay, now here what you can do, you can use the Sridhar Acharya formula. So can equate x square minus 2x plus 2 equals to 0. So basically I can write plus 2 plus minus b square minus 4ac, which is 8 divided by 2a. Okay, so this is basically 1. Now this, right, this is imaginary number 1 plus minus I. So we'll say for x equals to real, for x belonging to real, function is always continuous. Function is always continuous. Okay, next is the second factor. I mean the third question, that is this one, right? This one I can copy. H of x. I'm very sorry, like my health is not that good, that's why I'm feeling a bit sleepy. So now here what do we do? Again, like I can see from the outside itself that minus 3 and minus 2 will be, like I can break this down into minus 3 and minus 2, and minus 3 times minus 2 is 6, right? So product and sum. So I can factorize this x square minus 1. So this is x minus 1 whole square in the top, and this is x minus 1, sorry, not minus 1, x minus 2 into x minus 3. Okay, so this is the case. So basically what we can say is, like around x equals to 2 and x equals to 3, the function is discontinuous, right? So at x equals to 2 and x equals to 3, function is discontinuous. Okay, so this is the case. So let's study few key points. So continuity of fractional part of x and greatest integer of f of x should be checked at all points where f of x becomes integer, because you might see that around the integer points, right, around the integer points there is certain jumps. So whenever the inside of greatest integer or inside of fractional part, okay, it becomes integer, there we should obviously check for continuity. So this is another tip for continuity. I will give you the question, and like from there we will understand this better. So whenever f of x is integer, we have to check at that point whether the function is continuous or not whenever greatest integer function is given. Okay, without graph I will solve. This is how you will solve. Okay, now continuity of signum of f of x should be checked at the points where f of x equals to 0. So the inside value of signum of x, whenever it goes to 0, we have to check the continuity at that point. Why? Because around x equals like signum of 0, there is a certain jump, right? It goes from -1 to 0, then to 0. Scroll from -1 to 0, then to +1. Okay, so there is a certain jump, you know, signum function. Okay, then continuity of function should be checked at the points where definition of function changes. So these three things you have to keep in mind for greatest integer function and function in general, that wherever the definition of function changes, I have already mentioned this previously, that wherever the definition of function changes, okay, there also you have to check for continuity. So these are the possible points of discontinuity that you need to check. So these was a theory part, right? This was a theory part where you have to check for discontinuity. So we were discussing about the possible point of discontinuity. First one was about the roots, okay, about the cancellation of a rational function. Another one, this, right, this is for greatest integer function, fractional part of x, then function in general, wherever there is multiple definitions. Okay, there is breaks, I will talk about those, okay, later on. So let's first solve this question. So here we have to talk about the possible points of discontinuity for the given function between 0 to 2. Okay, we have to talk about that. So f of x equals to sine pi x, f of x equals to sine pi x, and this, right, this is equals to the function definition of function changes around x equals to 1. Just above x equals to 1, the function is this. Just below x equals to 1, the function is this. Okay, so this is greatest integer function, and this is signum of x. Okay, so definition changes. So obviously, what are the possible points of discontinuity between 0 to 2? So the possible point of discontinuity, basically what we can say is sine pi x. So first things first, 0, x equal to 0, x equal to 1, x equal to 2, the endpoints and the point where the definition of the function changes, because they have told us to include the endpoints also. So 0, 1, 2, these are points. Now are there additional points here? So what we can say is that this, right, I told you just wherever my greatest integer function equals integer, okay, there we have to also check for continuity. So here sin x equals to 0 is included, and x equal to now x equals, what is sin pi by 2? Sin pi by 2 is 1. So x equals to half is also another possible point of discontinuity. So x equals to half means sin pi by 2. Okay, so this is also another possible points of discontinuity. Now at x equals to 1, this is sin pi, which is again 0, okay, which is anyways included, but between x equals to half and 1, my sin pi x never goes to any integer. Okay, that's why that part is done. So this part is done. Now let's come to this part, the signum part. Now here wherever my signum of x goes to 0, okay, this will be included. So I forgot one thing to write, that this, right, this is the fractional part of x. This is the fractional part of x. So I forgot to write this. Just hold on a second. Okay, this is the fractional part of x, right? So this is one thing. So now let's solve. And also I forgot to mention that another thing, that this top one is the greatest integer function, even though you are able to understand, but still. Okay, greatest integer function. So this, right? So basically at x equals to half there is a point of discontinuity here. Wherever my signum inside goes to 0, that is also a possible point of discontinuity. So at x equals to 5 by 4, signum this, right, this goes to 0. And is this included in this range? Yes. So definition of function is included in this range, so obviously this will be a possible point of discontinuity. Here x equals to 2 by 3. So x equals to 2 by 3, like is also integer, because 0 is also integer. Okay, so x equals to 2 by 3 for this part, right, fractional part of x. This is not in the range, not in range, because this is 0.66 and the definition of function is between 1 to 2. Okay, so obviously not in range, so exclude. Okay, now let's talk about x equals to this what do you say, next integer. Next integer is 1. Okay, inside this fractional part of x, negative 1 is there, but anyways if I keep on reducing the value of x, this is anyways not included in the range. Okay, I will increase 1, so I will add 1 with this. Okay, that will be inside will be 1. So if I add 1 with this will become 5 by 3. Okay, and 5 by 3 is what? 5 by 3 is 1.67, right? 1.67. Is this included in the range? Yes, 1.67 is between 1 to 2, so it is included in the range. So this is also another possible point of discontinuity, right? So obviously what are the possible points of discontinuity overall, what I can say? So if I copy this, the modified one will be this. So 0 will be included, just hold on a second, 0 will be included, and this before this one, right, before this one, half will get included. Okay, due to this greatest integer function. Next we have this, right? Okay, 5 by 4 is here. 5 by 4 is here because signum of x is going to 0, which is 1.25. So 5 by 4 will also be included. Okay, next is 5 by 3. 5 by 3 will also be included. Okay, so 5 by 3 will also be included. So total, so what find the total number of possible, like the question should be find the total number of possible points of discontinuity. Find the number of, so here what are the total number? So here this is 1 2 3 4 5 6. So total number of possible points of discontinuity is equals to 6, right? So answer will be 6 in this case. Now let's solve the next question. So we have to find the values of a and b so that the function is continuous. Okay, I forgot to write is continuous. Okay, so obviously we know it is continuous, so around the breakpoints our main focus would be around the breakpoints. Continuity is nothing but division of limits. So what are the possible points of discontinuity at x equals to pi by 4, x equals to pi by 2? Okay, and nothing else, because it is continuous, so endpoints will be anyways continuous. That is already given. So possible points of discontinuity, x equals to 0, pi by 4, pi by 2 and pi. But mainly we'll focus on these 2 points, okay, because we have 2 unknowns. Just by solving the limits we will be able to find the unknowns, right? So basically what we know, as sin x and cos 2x will be always continuous, okay, between these range, okay, hence we can safely say that this whole thing will be continuous in this range. Good. Cot x also is continuous within this range, right? Within this range cot x is also continuous, so we will say this is continuous, okay. And this, right, again sin x is continuous within this range, so this will be anyways continuous, okay. So we won't stress about continuity in the intervals, okay. I told you a few information based facts. So basically now what we should do, we should find the continuity, okay, around x equals to pi by 4 to find the values of a, okay. We already know that the function is left continuous and right continuous, that we already know, okay. So yeah, let's solve. So basically around x equals to pi by 4, if I solve for x equals to pi by 4, what do we get? So basically I have to solve for limit as x tends to, just I am solving on the left hand side of pi by 4, right? So pi by 4 minus, function definition is this, right, a sin x plus b cos x, okay. This is a function definition. So what you can do, either you can replace this with h tends to 0 and then that with 0 minus pi by 4, or simply you can put pi by 4 here, because this is the definition of pi like the function just before x equals to pi by 4, and here we are not getting any indeterminate format, okay. So we can simply put the value of x equals to pi by 4 in this limit. So if I put the value of x equals to pi by 4, this will be a by root 2 plus b by root 2, right? A by root 2 plus b by root 2, okay. So now let's solve for x equals to exactly x equals to pi by 4, okay. Exactly x equals to pi by 4, what is the value of the function? The right hand limit and this right will be same, because within the range pi by 4 to pi by 2 it is continuous. So x equal to pi by 4 plus and x equals to pi by 4, both of these will be same, okay, because cot x is continuous. So f of pi by 4 is simply 2 into pi by 4 into cot of pi by 4, which is 1 plus a, okay. So this equals to a plus pi by 2, right? Yeah, this is the case, okay. Sorry, once my mistake, this is not simply cos x, this is cos 2x. So this is cos 2x, this is cos pi by 2, so cos pi by 2 is 0, right? Cos pi by 2 is 0, okay. So this will be simply a by root 2, okay. So yeah, this is the thing. So now what we should do is, we should equate these two things, right? Equate these two things, a by root 2 and a plus pi by 2. So if I equate these two things, what will I get? What will I observe? So basically my a will be something like this, right? I'm not calculating the pi by 4 right hand limit, pi by 4 plus, because they will be equal, because it is a continuous function, okay. The answer will be same. The homework task for you is calculate RHL, basically limit as x tends to pi by 4 plus, okay. This is the value of the function exactly equals to x equals to pi by 4. The homework for you is calculate x equals to pi by 4 plus, okay. So this these two, right, for function to be continuous, these two has to be equal, okay. So a by root 2 equals to a plus pi by 2. So a, okay, this will be 1 minus root 2 by root 2 equals to pi by 2. So a will be equals to, simply this is root 2 and this is gone, pi by 1 minus root 2 into root 2, okay. So this will be my answer for a, Okay, so can we solve for b? So again, right, we'll calculate the around x equals to pi by 2. So if I solve around x equals to pi by 2, first I will calculate the compute the left hand limit. Okay, so limit as x tends to pi by 2 minus, what is the definition of function just before pi by 2? The definition of function is again this, and at x equals to pi by 2, what is the value of cot x? Cot x is equals to cos pi by 2 by sin pi by 2, and sin pi by 2 is 1, cos pi by 2 is 0, so it will be 0 simply. So let me write 2 cot x plus a, so this will be 0 plus a, which is equals to a itself. Okay, and basically now let's calculate for x equals to pi by 2, and pi by 2 plus is same only because this function is continuous within this range. I'm not solving for the x equal to pi by 2 plus, the answer will be same, limit value will be same. So f of pi by 2 is equals to simply this x minus b root 2 sin x at x equals to pi by 2. So pi by 2, sin pi by 2 is 1, and this is pi by 2, so pi by 2 minus b root 2 into 1. Okay, so as the function is continuous, these two have to be equal, these two have to be equal. So what is a? A is equals to simply this, right? A is equals to pi, very weird answer, pi into 1 minus root 2 into root 2 now this should be equals to pi by 2 minus b root 2. Okay, very like the answers are very weird. Okay, so yeah, let's solve this basically. So if I try to solve this, what will I get? So I will get something like this, that pi by 2 root, am I doing this correctly? Let me just check once. Pi by 2 is this, yeah, pi by 2 is this, zero, okay, so okay, there is also b, another b, 0 should be equals to, so here, right, what will be the answer? So basically what I can say is b root 2 equals to pi by 2, pi can take pi common, 1 by 2 minus, I can say 1 plus root 2 minus 1 into root 2. Okay, so this is equals to root 2 minus 1 into root 2 plus 2 divided by 2 into this root 2 minus 1 into root 2, right? So very weird answer this is actually. So this will be my if I divide by root 2 again, this is b root 2, so b will be equals to pi by 4. Okay, this is root 2 minus 1 actually. Pi by 4, like this root 2 has gone down, and this is 2 minus root 2 plus 2. Okay, this will anyways come out weird, I won't break this down further. This will be root 2 minus 1 into root 2 plus 2, then 2 into, no, not 2, only root 2 minus 1. Okay, can I take common root 2 over here? I can actually take common root 2 over here, but that won't be any fruitful to us. Okay, so this will be the answer for this a and b, right? So yeah, we'll talk about the properties of continuous function just in a bit. Okay, I will just have some dinner, then I will talk about properties of continuous function. So let's start with properties of continuous functions. So let's read this statement that if two functions f of x and g of x are real valued functions and are continuous at a point x equal to c, then the following properties will be satisfied. If I multiply a scalar with that function, or I like with the g of x or f of x, then it will still remain continuous at x equal to c. If I add the two functions or subtract the two functions, then also the overall function, right, will still remain continuous at that particular point. If I multiply the two functions, then also the function will remain continuous at that particular point. All these are self-explanatory. But here the fourth point is a bit different, because here g of x is in the denominator. Now it will be continuous at that particular point, okay, at x equal to c, actually not a, x equal to c, provided that g of x is not equals to 0. Okay, obviously if the denominator goes to 0, we will get a indeterminate format. Okay, hence this won't be continuous anymore, the overall function won't be continuous anymore. That's why this g of x has to be non-zero at that particular point of x, right, particular value of x. If it is non-zero, then obviously this whole thing will be continuous. Okay, this whole thing will be continuous. Okay, so these are few basic properties. Now there is also another properties for composite functions. Now if we have two real value functions, okay, this is actually real valued, this will be real valued. Yeah, sorry, my ipad got crashed. I was talking that if we have two real valued functions, okay, my ipad is recently like not giving me support right now, I don't know why. Yeah, two real valued functions f of x and g of x, such that the composite function f of g of x is defined at x equal to c. It is defined at x equal to c if and only if g of x is continuous at that particular value, and the function f of x is also continuous at g of c. Okay, then f of g of c will be continuous. Okay, what do you mean by that? We'll solve questions and from there we'll understand this better manner. So we have this example of two functions. Okay, these two functions, obviously this is not continuous throughout the range, but this is continuous at some particular range. Okay, so let me further explain this thing, that let's say if your f of x, like I will tell you the converse statement, that if your f of x is discontinuous at x equal to c, then what does that mean? Now what I am interested in, I'm interested in the continuity of f of g of x. So here f of x is discontinuous at x equals to c, so the inside bracket, when the inside bracket is equals to c, it is discontinued. I have to equate this inside bracket equal to c, so hence it will be discontinuous at g of x equals to c. Okay, so this is the case. Now if we equate g of x equals to c, now for what value of x my g of x is equals to c, let's say for x equals to d, for x equals to d, just hold on a second. X equals to d, this, right, this function is what do you say, x equals to d, my g of x equals to c. Okay, so I will say that f of x is discontinuous at x equals to c, but f of g of x is discontinuous at x equals to d, right, not c, because that was for f of x, not f of g of x. These two things are different. Okay, so I hope you get the point, that how can we measure discontinuity. We'll solve this example and from there we'll understand this better. So here we have to find the points of discontinuity in f of g of x and g of f of x. Okay, so let's first solve for f of g of x. So let's first solve for f of g of x. So here what do I see? I see that this f of g of x, okay, like when is this f of x discontinuous? Can you tell me when is this? Let me write this. When is this f of x discontinuous? F of x is discontinuous, you can blindly see that x at x equals to 5 it is discontinuous at x equals to 5. Okay, and if it is discontinuous at x equals to 5, I am more interested in f of g of x. So what I will do, I will equate g of x equals to 5, and obviously here, right, we have to also check for discontinuity of g of x also. That also we have to check. So f of x is discontinuous at x equals to 5, g of x is continuous for all real values of x. Okay, g of x is continuous for all real values of x. I forgot to mention that here, right, whatever x the value of x, it is for all real values. So here my x, okay, my iPad is going crazy, my x should belong to real values only. So x belongs to real. Okay, so basically what I can say is that f of x is discontinuous at x equals to 5, but my g of x is always continuous. Okay, it is always continuous because it is simply a polynomial linear equation. Okay, so now what we have to do, we have to equate g of x equals to 5 because we are talking about the continuity of f of g of x. So x plus 5 equals to 5, x equals to 0. So at x equals to 0, this f of g of x will be discontinuous, right? Can we do this with another method? So this is method 1. Okay, this is a standard method that we use. We can use also another method. Okay, that is also many people tend to prefer. Okay, so what is method 2? Direct substitution. Okay, so here what do? We have to find f of g of x, right? We'll directly substitute the value of x with g of x. So what is g of x? G of x is x plus 5, f of x plus 5. So I will replace this x with x plus 5 simply. Okay, because my x is changed to g of x and g of x is equals to x plus 5. So this will be x plus 5 minus 5, 1 by x. Okay, 1 by x. So basically this, right? So I can clearly observe that at x equals to 0, function will be discontinuous, right? Function will be discontinuous. Okay, so let's solve for the second case where I am talking about g of f of x. So in this case, right, I will copy the same statement that g of x is always continuous. Okay, g of x is always continuous, but f of x is discontinuous at x equals to 5. Okay, f of x is discontinuous at x equals to 5. That means that basically g of f of x will also be discontinuous at x equals to 5. Why is this the case? Because when x is equals to 5, this f of x like doesn't have any value, right? F of x doesn't have any value because it has 2-3 values or something. It has a certain jump. Okay, I don't know what is the value at x equals to 5 because it is discontinuous. Okay, hence that's why I won't be able to put any particular value over here. Okay, any particular value over here. If I am not able to put any particular value over here, how will I able to evaluate g of question mark? So how will I able to evaluate? Because it is not continuous, I don't know the value of that point. Okay, I don't know the value of the function at that point. So how do I calculate g of question mark? Okay, how do I calculate g of question mark? I can't, right? I can't. That's why it will be discontinuous. Okay, that's why it will be discontinuous. Okay, so obviously at x equals to 5, g of f of x is discontinuous. Okay, so let's now solve another question. This is a bit on the higher level side. So here, right, they are asking us to comment about continuity of f of g of x and g of f of x, okay, at x equals to 1, at x equals to 1. Okay, so f of x is this, g of x is this, right? So how will you find the point of continuity, whether this is continuous at x equals to 1? So what you do in this case, right, what you do in this case, you first go inside this function. So first we're talking about the f of g of x. Okay, f of g of x. Now if you're talking about f of g of x, what does that mean? That means instead of directly talking about f of x, I'll talk about first g of x. Okay, I'll talk about first g of x. So here I have to talk about x equals to 1. So at x equals to 1, what is the value of g of x? X equals to 1. Okay, there is no break over here, because at x equals to 0, like the definition of the function is changing. But at x equals to 1, I am lying around here. There is no issue, because this x minus 1 under root 1 by 3 is continuous in that range, right? Left hand limit and right hand limit will be same. You can compute, right? So here at x equals to 1, so first, right, what we'll do, we will try to compute the left hand and right hand limit, okay, of f of g of x. So compute the left hand limit and right hand limit. Okay, so basically we will do this thing twice. So here 1 plus x equals to 1 plus, still I am in this x greater than 0. X equal to 1 minus, still I am in this x greater than 0. 0.999, it is greater than 0. 1.00001, still it is greater than 0. So this g of x definition won't change. Okay, g of x definition won't change according to RHL and LHL. So g of x will be always be equals to x minus 1 by 3. Okay, g of x will always remain this, right? So now what you do, basically so what will be the value? So if I compute the value, right, if I compute the value, this will be, for our assurance, I will replace this with h. So what I will do, I have to compute limit as x tends to 1 plus f of g of x. What I will do, limit as x tends to 1 plus f of, I will replace my g of x with this, right? Also I will replace this x with h0, and this will be 0 plus h minus 1 1 by 3 cube. Okay, and yeah, that is it. Yeah, that is basically it. So this is 1 plus, so this will not be 0 plus 1, this will be 1 plus h, right? 1 plus h. Okay, so this is equals to limit as h tends to 0, f of h 1 by 3. Okay, f of h 1 by 3. So now basically h is tending to 0, right? H is tending to 0. So this is something positive, because h is a small positive quantity. I will write here, h is a small positive quantity. Positive quantity. So basically what you do, you you are in this range, right? Because h is a small positive quantity. Now if h is a small positive quantity, what you do? You will replace this with limit as h tends to 0 f of h cube, right? So this will be x cube minus h is a small positive quantity. Okay, so as h is a small positive quantity, we're lying in the positive, right? This is positive, so f of x will be replaced with this function, sorry, will be replaced with h 1 by 3 whole cube minus 1. Okay, so it will be limit as h tends to 0 h minus 1, and h is a small positive quantity, it will be almost equals to minus 1. It will be almost equals to minus 1. Okay, so this is my right hand limit of f of g of x. Now let's compute the left hand limit of f of g of x. So again we'll do the same thing. Okay, anyways the g of x definition won't change. Okay, but this time what will happen, this will become 1 minus h whole okay, wait, yeah, 1 minus h 1 by 3, right? Just hold on a second. Yeah, 1 minus h, and we have minus 1 also, right? Just remember that h is a small positive quantity. So if h is a small positive quantity, okay, under root of something negative will be negative itself, right? This minus 1 by 3. Okay, so this whole thing is something negative, right? So this whole thing is something negative. So this is negative, obviously. Where we are lying in this range, right? X less than 0, because for the inside value, when the inside value is less than 0, then the definition of function will be this 1 plus x square. So I will replace this. Okay, limit as h tends to 0, this will be minus h 2 by 3 plus 1. Okay, now what is the thing over here is like this, right? This thing is negative and I'm squaring the negative. Negative square is something positive. Negative square is something positive. Now if negative square is something positive, that means there's some small number but which is positive, which is getting added with 1. So I can say that this is equals to 1, almost equals to 1, right? So what we observe is that the left hand limit is 1 and the right hand limit is minus 1, right? So this is the right hand limit. So my left hand limit is not equals to right hand limit. Okay, so this is not equals to, so obviously function is discontinuous. Anyways, limit does not exist, so anyways the function was discontinuous. Function is discontinuous. Now let's talk about g of f of x, right? Let's talk about g of f of x. So if I talk about that, then what will happen? So I'm talking about the second case. So here, now let's talk about x equals to 1. What is happening at x equals to 1? Again, right? X equals to 1, the definition of the function is not changing over here. The definition of the function at x equals to 1 is this x cube minus 1 only. This x cube minus 1 only. The definition of the function is not changing over here, right? So what we can do, we can say that, again, copy paste this statement that my f of x will be always x x minus x cube minus 1. It will always be x cube minus 1. Okay, so just hold on a second, let me check everything is recording or not. Yeah, everything is recording. So here what you do, you just simply put this value, right? Now you calculate the right hand limit, whichever you find suitable. You first calculate that x tends to 1 plus f of, not f of, g of f of x, which is equals to x. So this, right? So what I'll do, my definition is this, so I'll replace this with h. So 1 plus h, so 1 plus h whole cube minus 1, right? So what I can do is that I can expand this thing, limit as h tends to 0, g of 1 plus h cube plus 3h, just hold on a second, okay, 3h square plus 3h minus 1. Okay, so this will become simply limit as h is a small positive quantity, g of, I can take h common, h into h square plus 3h plus 3. Okay, now as h is a small positive quantity, this means this whole thing is positive, this is also positive, so positive times positive is obviously what? Positive and positive will obviously be something positive, right? So this whole thing is something positive. Now if this whole thing is positive, whenever inside of g something is positive, the definition of the function is this, x minus 1 whole cube, right? So okay, the definition will be this. So this will be simply, this is my x, right? This is my x, and the definition of the function will be this, this whole thing, right? So just hold on a second. So what I will do, I will just write this as it is, that okay, this will be difficult for me to write. Minus 1 by 3. Okay, so this is how you will replace, right, x. This is how you replace x. So here what I can do, I can say that x is a small positive quantity. If x is a small positive quantity, this is very small number and this almost equals to 3. It's like 0.0001 times 3 will be equals to 0 itself, almost equals to 0. Like 0 only, right? So this will almost be equals to minus 1 by 3, which is equals to minus 1. Okay, this is also minus 1. Now let's compute the left hand limit. If I compute the left hand limit, h is tending to not h, I will say x is tending to 1 minus g of f of x. Okay, okay, so 1 minus g of f of x. So this will be something like this. So this, right? So now I will replace limit as h tends to 0, 1 minus h. This will be g of 1 minus h. So 1 minus h will be replaced over here. So this will be 1 minus h whole cube minus 1. Okay, so this will become limit as h tends to 0, g of 1 minus h cube minus 3h square. Okay, and wait a second, this will be minus, yeah, just let me, I sometimes tend to forget the formula, right? So it was 1 minus h cube, so it is 1 minus h into minus 3. So this will be something like this, if I remember it correctly. Minus 3 times h into 1 minus h, minus 1 is there. So limit as h tends to 0, this is g, and this is 1 gets cancelled, and this is minus h cube, this is minus 3h plus 3h square. Okay, so now what I can do, I can take the h as common. Okay, if I take the h as common, what will happen? G of, I take minus h as common. Oh no, I can't take, I can only take h as common. So if I take h as common, this will become minus h square minus 3, let me write the higher order term first, plus 3h and minus 3. Okay, so if my h is tending towards 0, okay, this will anyway tend towards 0. This is something negative, this is something negative, so this overall thing is negative. Okay, this is something negative, and this is obviously something positive, because h is something small positive quantity, h is small positive quantity. So this overall thing is going to negative, this overall thing is going to positive. So obviously what will happen overall, right, this will be something negative. Okay, previously if you observe correctly, this will be something positive, this is something negative. I might say this is something less than 0. Okay, now the definition of the function changes. Okay, if the definition of the function changes, obviously it would be discontinuous, we'll see that. So here negative, so it is equals to x plus 1 under root x plus 1. So this, right, we can replace this with limit as h tends to 0, h into minus h square plus 3h minus 3 minus 1, or it was plus 1, I forgot, it was plus 1 under root, right, plus 1 whole under root, right? So this is plus 1 whole under root. So obviously now if you put x tending to 0, what will happen? This will be something almost equals to 0. Okay, this will be something, wait, just hold on a second, this will be something almost equals to 0. Like this one is far greater than this. Like you take an example, 0 0.001, 0 0.001, this is almost equals to 0 and minus 3. So minus 3 into 0 0.001 is almost minus 0 0.003, something like that, and plus 1, like this part is negligible in terms of this. So this will be replaced with 1 only, 1 raised to power half will be 1 only. So now what we observe is that the right hand limit was minus 1 and the left hand limit is 1. So obviously again I will say the same thing, right hand limit is not equals to left hand limit. Obviously f of g of x, no sorry, g of f of x not continuous at x equals to 1, right? Okay, this is the like this is very beautiful question actually. So like just what I want you to do is, okay, you just try to understand what I did in this question, just don't go to the solution. Okay, the solution is not important here. What is important is the procedure, what procedure I followed over here. First, obviously I thought of that, let's first think about the inside function, whether the definition of the function is changing, okay, or not, within where I have to find the limit. Okay, within the point which I have to find the limit, just 1 positive 1 plus, I mean 1 plus just greater than 1 and just lower than 1. Okay, so I have to check about the definition of the inside function, whether it is changing or not. I saw it is not changing, so obviously this will remain same. Okay, then I will compute my limit. I will see what is happening in this bracket term. Okay, what is happening inside f. Okay, whether for this, right, the definition of the function is changing or not. We observed that yes, the definition of the function is changing. Okay, this was positive, something positive, and if it is positive, then the definition will be this. If it is negative, the definition will be this, and that is exactly what happened in the left hand limit. Okay, for the second case also, where we are calculating g of f of x, that was the same case. The definition of the function was changing for g of x, but f of x, right, it was remaining same, because I have to compute the continuity about x equals to 1, and at x equals to 1 there is no discontinuity, right? There is no discontinuity. But as for negative and positive values, there is discontinuity. That is the more important part. Okay, that is the more important part. Okay, so let's study about the intermediate value theorem. What do we mean by intermediate value theorem? So here, let's read the statement. Very simple only, very straightforward. The intermediate value theorem says that if a function f of x is continuous on an interval, okay, we know that the function is continuous on an interval, it has already been given, okay, and if f of a and f of b possess opposite signs, they have opposite signs, I mean the endpoints, right, they have opposite sign, one is positive and one is negative. So what do I mean by this? So basically, this is my graph. X, f of x, okay, this is a, this is b, okay. So basically, let's say my f of a is positive, so my f of a is somewhere around here, okay, and f of b is somewhere around here, okay. So basically my f of a and f of b are of opposite signs. I have taken an example where my f of a and f of b, f of a is positive, f of b is negative. So what will happen in between these 2 points? It must cut the x-axis at least once. It will cut the x-axis. So it will cut the x-axis at least one if this condition is satisfied. If the function is continuous between a and b, and the signs of f of a and f of b are opposite, then it must cut the x-axis at least once, okay. It must cut the x-axis at least once. What do you mean? Like in other words, you can also say, then there exists at least one solution of the equation. F of x equals to 0 in the open interval, okay. Then there exists at least one solution of the equation, f of x equals to 0 in the open interval, right? So, or you might say, then f of like one solution means this f of x will be equal to 0. That is also known as solution or roots. You can say then there exists at least one root, okay. That also you can say between the range a and b. All these things you can say, right? This x f of x equals to 0 has many names, okay, many different names. So there is also another theorem, okay. The intermediate value theorem says that if a function is continuous on an interval a and b, and if k is any real number between f of a and f of b, then there exists at least one solution where f of x is equals to k in the open interval a and b. Just notice one point, that this is open interval, right? Okay, because we are not including the a and b, okay. A and b we are not including, okay. In a and b they may be exactly equals to k, right? They may be exactly equals to k. That may be also another solution, but we're not including that. We're excluding that. Excluding the a and b points, in between a and b there must exist a point where my function passes through this value k again. Because why? Because the function is continuous, right? If the function is continuous, this is f of a and this is f of b. Okay, so if it is continuous, then what will happen? Then basically this, right, then will say that it must pass through this k, right? It must pass through this k, because without passing through I won't be able to complete this graph. I won't be able to plot this graph, because this graph is continuous. I won't be able to say, okay, I stop here, then I pick up my pen and then I start from here again. I won't be able to do that, okay. I stop here, then pick up my pen and then I start from here. That is not possible for me. That is not possible for me, right? So I have to pass through this because my function is continuous, okay. So it is very important. So yeah, these are the few things that I wanted to say about intermediate value theorem. Let's solve a question and from there we'll understand this even better. So given that basically this condition is given that a is less than b is less than c is less than d, then comment on nature of the roots of the equation. Comment on nature of the roots of the equation. Okay, 2 into x minus a into x minus c plus 5 into x minus b into x minus d equals to 0. Okay, we have to comment about the nature of the roots. You might say, sir, this is like 4 x's are here in multiplication, how can I solve? This is not order 4. If you observe this carefully, this is order 2. Okay, order 2 function. Okay, this is quadratic equation because 2 multiplications and there is addition. Okay, quadratic equation, right? Quadratic equation. Okay, now if this is quadratic equation, then like the roots can be in this 4 format, right? Real, distinct, real, equal, complex, conjugates, or imaginary roots. Okay, so what we should do first is, like, this is the intermediate value question, but you won't be able to understand that. Okay, you won't be able to realize that unless you solve it using the theorem. Okay, that is the beauty of this theorem sometimes. So like when question will come from this, you will not be able to understand that you have to apply the intermediate value theorem. Okay, you can apply your simple brains also. Okay, intermediate value theorem is just simple common sense, right? So let's plot this in the number line a, b, c and d. Okay, a, b, c, d. Now this is a, b, c, d. Okay, now basically what you do, you just think of one thing, that if my x is greater than a, okay, now a is less than, so that's how I plotted it, right? A is less than b, c, all those things. Now if x is, let's do this, right? Let's do this. Okay, this is the positive side and this is the negative side. Okay, so this is, let's say this is x, this is positive infinity and negative infinity. Now if I say that my x is greater than d, if my x is greater than d, okay, then obviously these will also be positive and this will also be positive. This overall thing will be positive, hence this is positive and this is also anyways positive because x is greater than like d is greater than a also, d is greater than c also, d is greater than b also. Okay, and like this is also already greater than d because I am mentioning for the fact x is greater than d. So everything is positive, so this will be positive, right? Just hold on a second. Shit, this will be something positive. My pen is not working. What is happening? This will be something positive, right? So now what is happening, if I put my x equals to d, this goes to 0. Okay, this goes to 0, but this still is positive because d is greater than a, d is greater than c, so this will still be positive. Okay, around x equals to d, this will still be positive. Now what about my x equals to c? Now here the interesting fact is happening, right? What is the interesting fact? At x equals to c, this whole thing is going to 0. Fine, c is greater than b. It has told in this condition, c is greater than b. This is positive, but c is less than d. So this thing is negative. This is negative, this is positive. So this overall multiplication becomes negative, right? This overall multiplication becomes negative. So if this overall multiplication becomes negative, this is anyway 0. So what will happen? This will be something negative. So around c, just before c, we will go to 0, right? We will go to 0. So around c we will be negative. We will be negative. Okay. So let's go to the next point, that is at b. Okay, so at b, what is happening? This whole thing will go to 0 because exactly at b this whole thing will go to 0 anyways. Okay, b minus b is 0. Now here, right, I will say that b is greater than a, so this is positive, but b is less than c, so this is negative. Again, positive and negative is negative, so anyways around b also it will be negative only. Okay, now what about a? So at x equals to a, this is vanished, this is gone to 0. At x equals to a, this is negative because a is less than b, and this is also negative, a is less than d. Okay, so negative and negative is positive, so obviously around x equals to a, this will be positive. So just before x equals to a, this will go to somewhat positive. So just keep in mind, this is not the exact graphical plot, I'm just approximating it. I'm just trying to understand where my function will be positive, where my function will be negative. That is more important to me. Okay, the exact values are not important to me right now. Okay, that is how we approximate it. Okay, so this will be around a, this will be something positive, right? So it will be something like this. Okay, positive and negative. So what is the important fact over here? So if I say f of a and f of b, right, so we will say that my function is crossing the x-axis at two distinct points, right? It is crossing the x-axis at two distinct points, like this y value is going to 0 at two distinct points. Okay, or you might say that at x equals to this is positive, and then again at x equals to A, this is positive again. So here what was the condition? Or you might say that if you say x equals to b, okay, x equals to b, this is negative, and x equals to a, this is positive. So I will say f of a is greater than 0, f of b is less than 0, hence at least one root will lie between a comma b according to intermediate value theorem. Okay, then again, right, again what I can say, x equal to c and x equals to d. So f of d is greater than 0, f of c is less than 0. Again the same statement, at least it has to lie, right? At least one root has to lie between c comma d, okay. So at least one root has to lie between c comma d. So if one root is lying between c comma d, what does that means? That means that at least one, at max how many root I can have? I can have two roots, right? So some one root is lying between this and one root is lying, okay, my pen is not working suddenly, I don't know sometimes what is happening. I have to buy a pen, I think. So one root is lying between this and one root is lying between this. So what I can say, at least, but at max I can have two roots. So the two roots are distinct, okay, two roots are distinct, hence I will say roots are distinct and real, because obviously they're crossing the x equal to 0, right? And for real values of x, because a b c d all of them are real. So real and distinct will be my answer, because at least one root should lie between a and b, and at least one root should lie between c and d. So they are real and distinct, hence obviously hence obviously the answer will be real and distinct. So this is how you solve using intermediate value theorem. The concept of intermediate value theorem is very important, okay. So yeah, that's it for this lecture, and in the next lecture we'll start with differentiability. That will also be very like a good topic, okay. You just watch it in 2x, okay, because all these things I hope you have already studied in your 11th and 12th. This you watch with the revision purpose, right? You are revising your concept so that you can attempt the good questions, okay. That is more important to you, and just get a good grip of the concepts that you studied in 11 or 12, or you may have skipped in 11 and 12 due to some reason, okay. So thank you for watching, and I will see you in the next video. Hey everyone, and welcome back to PrepFusion. So today we'll be starting the fourth lecture of calculus chapter. So previously we studied about limits, before that we studied about functions, then limits, then we studied about continuity. What does a continuous function mean? We apply, like, what are the properties of continuous function, okay. Now how to find the continuity at a point, and how to find the continuity over a range. Then we also solve a few questions. Now we'll study about the next topic, that's the differentiability. Now this is a fundamental topic, so if you already know about this, you can either watch it in 2x or just watch the notes. That's enough, okay. Because it may so happen the people or the students who have studied already 11th and 12th very well, they will already know all these concepts, okay. They just need to just have a quick revision, okay. So that thing you can do. For the people who are coming from diploma, or they haven't studied 11th and 12th that well, they will obviously watch this lecture completely, okay, according to their own pace, okay. So yeah, what is differentiability? Again, right, we'll talk about differentiability at a point this time, okay. Differentiability at a point, we're not talking about a range, okay. We can only, that is our limitation, we can only find the differentiability at a point. Now differentiability of a function can be understood both graphically and algebraically, okay. It can be understood in both graphically and algebraically, just like continuity. Then geometrically, the differentiation of a function is the slope of the graph of the function y equals to f of x at x equals to a in the domain of the function. So like, I hope you already know what does differentiation mean. It means the slope of the graph at that point, right, at x equals to a. What is slope? We'll talk about slope later on, okay. If you don't know, we'll talk about that. Slope is this right, f of x2 minus f of x1 divided by x2 minus x1, simply equation of line, okay. We'll talk about that. Function is differentiable if the graph is continuous and smooth, okay. Continuous, we already know. What is continuous? We already know. But what about smoothness? What does it mean for a graph to be smooth? We'll learn that in the next few slides. So one thing I can observe here, that if the function is differentiable, then surely the graph will be continuous. For a function to differentiable, the graph has to be continuous. So the first criteria is the graph has to be continuous anyhow. Okay, then algebraically the differentiation of the function is a change of the value of the function y equals to f of x from f of x1 to f of x2 with reference to change in the domain value of x from x1 to x2. Okay, so it is a ratio of y2 minus y1 divided by x2 minus x1, just the slope. I hope you already know all these things, right? So this is also known as the tangent, right? Or slope is also known as the tangent. Why is it known as a tangent? Like here, right, if you see, I have a graph, okay, and this, right, this line is just touching one point of this graph, okay, and that's why this is known as tangent, as this is a perpendicular to this point. Okay, you learn more about this, like when you solve question, you learn more about this, right? So this is the visual representation or graphical representation of differentiation of a function. Okay, so here you can see that my tangent will obviously keep on changing as I move along in the graph. Okay, so we are talking about the tangent here. Differentiability is mainly focused toward tangent. Okay, so at each point the tangent is changing. Like what are the repercussions of that, we'll understand later on. Okay, but here we understood the differentiation of a function at point p equals to dy upon dx. So let's move to this quadratic function, and from here we will also understand about slopes. So here what you see, what is the slope here? Okay, like the slope is something like this, right? Then slope at this point is like this, then slope at this point is like this, slope at this point is like this. Okay, it will only touch at a single point of the graph, right? It will only touch at a single point of the graph. That is what a tangent means, right? This, right, will only touch here. Okay, if it is like this, then straight line, this will touch 2 points, which is not possible. Only like this it will touch 1 point. Again, if my like line is like this, it will touch 2 points. So tangent means it will only touch at a single point, just touching, just tangent to the curve, so touching, okay, touching, all these things, right? So here I am coming from the left hand side and then going towards the right hand side. Okay, so like I can trace this tangent from both ends, right? Either if I come from the left hand side, or either if I come from the right hand side, right? I can come from this end and trace this tangent, I can come from this end and trace this tangent, right? So like it's similar to continuity, right? I can come from the LHL, left hand side, or the right hand side. I can check for the left hand side limit and the right hand side limit. So tangent also I can come from the, okay, I don't have straight line, come from left hand side, and this tangent also come from right hand side, right? Come from left hand side and right hand side. Okay, so we already know this is a differentiable function because the differentiation for this function exists, because like that's very simple, right? We already know all these things. F of x, in this case it is a quadratic function, is simply x square, and f dash of x will be 2x. Okay, basically the differentiation exists. Obviously if the differentiation exists, then the function will be differentiable. For few functions the differentiation doesn't exist, or you don't know the formula of differentiation for that function. That means the differentiation doesn't exist for that function. We'll see with examples. So another example is sine function. So like sine f of x is what? Sine x, in this case we got x of 0 is 0. Now what is the differentiation of this? F dash of x simply equals to cos of x, right? F dash of x simply equals to cos of x. Now in these functions, right, what do we observe? We observe that first of all this function itself is continuous. This function itself is continuous. And what else we observe? We observe this is smooth. Why this is smooth? The slope doesn't abruptly change. Okay, we'll see with one example where the slope changes abruptly, and that will be called not a smooth graph. Continuous and smooth. Here in this case also the graph is continuous and smooth. Okay, because the slope doesn't change abruptly, it changes slowly. or this smooth, right, definition of this smooth can be set from here, that the differentiation is continuous. Okay, like the difference after differentiating this, right, this function is again continuous. If I name this g of x, this is continuous. That is also another definition of differentiability. If I differentiate it and it is like this new function is continuous, then obviously this function, right, f of x, will be differentiable. That we will understand later on. Okay, so here we see that this is continuous and smooth. Let's come to the next example. Okay, here what do we see? We see that this function is not continuous. This function is not continuous. I'm not talking about smoothness. Okay, I'm not talking about the smoothness, because here, right, the slope is 0 0 0 0. Again, at just at here the slope is again 0. The slope is again 0, and here also the slope is again 0. Okay, slope is not abruptly changing, but this function is discontinuous. We have already proved this. So this is discontinuous, right? Discontinuous. Okay, so this function is discontinuous, but like slope is not abruptly changing in this case for the greatest integer function. Okay, so let's go to the next example. Here the modulus function, right, modulus function f of x equals to mod of x. What do you observe? That the function itself is continuous, because I don't have to lift my pen up, okay, to draw this graph. I don't have to lift my pen up. But what is the interesting fact over here? If I come from the left hand side, the tangent is this straight line only, this straight line only. Just before this, right, the tangent is like this. Just after this, just after 0, the tangent suddenly becomes this, right? It suddenly becomes this. It was this, suddenly becomes this, then this. My hand will break, right? My hand will break if I do like this. So this also abruptly changes. There is sudden change of the tangent. Okay, so I will write the tangent, like I will just show you. This is a tangent of, if I come from the left hand side, and this is a tangent if I come from the, okay, just hold on a second. This man. So this is a tangent if I come from the right hand side. Okay, so basically like tangent from right hand side, tangent from left hand side. So what do you observe around x equal to 0 is, around x equal to 0 here, right, the tangent changes abruptly. My hand will break, right? Tangent changes abruptly. Okay, changes abruptly. Okay, tangent changes abruptly. So if there is abrupt change in tangent, then obviously that differentiation won't exist. So not continuous, this is continuous, but not smooth. Okay, but not smooth. Okay, so again let's come to another function. This is what this is, f of 1 over x, sorry, f of x equals to 1 by x. But is this differentiable? If this is differentiable, okay, this is, you might say, sir, x equals to 0, it is going towards positive infinity, negative infinity, but this is differentiable and continuous. Why? Because x equal to 0 is not included in its domain. Okay, as x equal to 0 is not included in its domain, hence we can say any other point, at any other point there isn't any abrupt change in the slope, also the function is continuous, okay, in this domain. Okay, so what I will say is that f of x is differentiable and continuous in its domain. Okay, f of x is differentiable and continuous in its domain. Okay, so basically let's like read these key points what I have told you previously. These are the summary, okay, what I have told you. So if differentiation of function is known, it does not mean that the function is differentiable at all points, okay. So why is this the case? Why is this the case? Because like if you differentiate, like you take ln x, right, ln x, if you take ln x, the differentiation will not exist at all point, okay. The differentiation will not exist at all point, because at one ln x, if you write the differentiation is 1 by x, so x can't be equals to 0, okay. X can't be equals to 0, that is not in the domain, okay. All the results of the differentiation are valid in the domain of the function, okay. So obviously I cannot put any point on that function, they have to be valid in the domain of the function. That these two are very important points. So I will take the example of f of x, right, ln x, okay. And what is the domain? X can't be equals to 0 or less than 0, okay. Negative number it can't be, x can't take negative numbers because base can't be negative, right. I mean the result cannot be negative, whatever power output power I am getting, that cannot be negative, okay. Also like it cannot be 0, it cannot be 0, right, it cannot be 0. If it is 0, then what does that mean? That the like this also has to be 0, but this is in 0, right. The base of this logarithm has to be 0, this can't be 0, right, okay. So that is the case. So this is e, so that is not possible. So that's why x has to be greater than 0. Now if I differentiate this, this will be 1 by x. Now if this is 1 by x, this is x greater than 0, okay, x greater than 0. So this x is greater than 0 right now. So basically what can we say? So here, right, we can't put x equal to 0. X equal to 0 is not in its domain, that's why, except that it's differentiable everywhere, right. So that is more important to us, okay. So like I have already told you about like tangents, but not in detail. For the people who don't know, we'll talk about them here, right. So basically let's take a secant. What does secant mean? Secant means it is cutting the graph at 2 points, okay. Now I'm talking about x equals to a, okay, x equals to a. So if for some reason I try to, like this is a minus h and this is h, a plus h, I try to bring this more closer, these 2 points, right, this point is fixed, I try to bring this more closer. So this will be something like this will be something like this, this touching 2 points, still touching 2 points, and somewhat here this will like not somewhat here, so this will touching like this, then somewhat here this will directly become tangent to that curve, okay. So that is not a tangent. I am reducing this distance, right, from this is known as secant, okay. This AP is known as secant, and AQ is also known as secant, right. AP and AQ is also known as secant up over here. What I am doing, I am converting from secant to tangent, okay. Secant means it touches the graph at 2 points, right, cuts the graph at 2 points. Now this tangent, right, if I extend this, okay, if this is, let's say this is the tangent at x equals to a, if I extend this, and the angle that it makes with the x-axis, okay, is also related with the slope. So basically what we can say, so tan theta equals to dy upon dx at x equals to a, very important, at x equals to a. So this slope, right, this is the slope at x equals to a. Now we have angle, like this means angle with respect to x axis and theta, that is theta. Definition of theta is okay, this is the definition of theta, that theta is angle with respect to x axis, okay. As I reduce my h, this becomes tangent. So this is the basic concept, okay. I'm just coming more closer to this point A, okay, from the left hand side, from the right hand side. Now these two, right, these two secants actually mean the left hand derivative and the right hand derivative, okay. So these two, right, these two are the same meaning only. So basically what I can say right now, if I am coming from the left hand side, okay, I will say like this has also some angle, right, this has also some angle, Okay, this is also same angle, and this angle will keep on changing. So let me write that. So let's talk about ep secant. Sorry, yeah, ep sec. Yeah, I have written, yeah, ep secant. So if I talk about ep secant, what will be this? This is a slope, okay, and I will try to find the tangent. How will I try to find the tangent? Tangent will be, I will talk about that. Let's first try to find the slope of the secant. What does slope mean? Slope means difference of 2 points divided by x2 minus x1. Okay, those 2 points. So it will be simply y of p minus y of a divided by x of p minus x of a. Okay, so what is y of p? Y of a is fine. This is I can write this as a f of a plus a, not plus, a minus h minus f of a divided by a minus h. Okay, so yeah, f of, okay, did I do something wrong, or it should be something like, sorry, I actually rearrange these things. This will be something like this. Okay, or what we can do, you can, yeah, this is the left hand side, right? This is the left hand side. Okay, so this will be simply equals to f of a minus f of a minus h divided by h. Now what about the tangent? Okay, if I'm coming from the left hand side, what about the tangent? So this is the slope of the secant, and this is the slope of the tangent, right? This is the slope of the tangent. Okay, so what will the slope of the tangent? It will be same only, but as I am more closer to this, as the difference between these 2 points is minuscule, that means h is tending to 0. So what I will do, I will apply limits concept. So everything is limits only, so if I apply limits concept over here, this will be limit as h tending to 0, f of a minus f of a minus h divided by h, right? Okay, so this will be my left hand differentiation. Okay, left hand differentiability, I'm talking about left hand differentiability. Okay, now this is slope at point a. Okay, so now let's talk about slope at point a coming from, like, this is ap. Let's do the same thing for the right hand side. From, if I am coming from the right hand side, so if I am coming from the right hand side, now this will become aq secant, right? aq secant. Okay, so this is aq secant. What will this become? This will be okay, I actually did something wrong. This should be okay, did something wrong here. Actually this should be right. This should be y of a minus y of p. So y, okay, y of a is this only, and y of p is, that's fine, so here what will happen, this will be y of q minus y of a. What is y of q? Y of q is a plus h. Okay, y of q is a plus h, and this is simply x of q minus x of a. Okay, this one I also have to replace, right? This one also I have to replace. minus a. So this will be h and this will be f of a plus h minus f of a. Okay, so a, this is q qa, and this is h tends to 0. RST. Okay, so a plus h minus f of a, and as this is 10 to 0, this is my right hand derivative. Okay, this is my right hand derivative. Now what is the condition for differentiability? Like this is a tangent and this is the slope of the secant, right? And this is a tangent. Now what is the condition for differentiability? The condition of differentiability is that the left hand derivative, okay, whatever we've computed here, right, we're just applying limits. Okay, we'll solve one question from there, you will understand this better. Okay, so the left hand derivative and the right hand derivative. So basically whatever tangent or this tan theta I'm computing from the left hand side, okay, this tan theta whatever I'm computing from the left hand side, coming from the left hand side, and whatever the tan theta I'm computing coming from the right hand side, they should both match, and obviously they should be finite. Then only the function will be differentiable. Okay, so LHD equals to RHD equals to finite. Okay, so this is the condition for differentiability, okay, at point A. Okay, at point A. So this is the condition for differentiability. So here, like I have written this, that the function should be continuous at that point, which we have already discussed starting of the lecture, and the left hand derivative should be equals to right hand derivative should be equals to finite. Okay, so here I have slightly made a small Venn diagram where I'm talking about that if function is continuous, okay, then it can be differentiable. Okay, but it is not necessary that it must be differentiable. But if the function is differentiable, then it already lies inside this continuous circle, right? So if it is differentiable, it has to be obviously continuous, then only it can be differentiable, because this is already lying inside the continuous circle. Okay, so if the function is differentiable, then it has to be continuous. But if the function is continuous, then it may or may not be differentiable. We're not sure, we have to check. Okay, so always when the differentiation comes up, okay, so you don't need to check for continuity back again. Okay, in the question if they have asked for continuity and differentiability, which is rare, but if they ask for both of those things, then you don't have to check two things, right? You just check for one, that is the differentiability, and continuity will be taken care of, no worries. Okay, so here what I can say that basically if k is the derivative of function, so let's name this finite number as k. Okay, let's name this finite number as k. So k is equals to derivative of f of x, okay, at x equals to c. Then what can I write? I can write k equals to f dash of c. I can write k equals to f dash of c, basically k equals to that tan theta angle, right? So function is already differentiable. So if function is differentiable, then just from this statement I can say function will be continuous at x equals to c. Okay, just from this statement, if the function is differentiable, it must be continuous at x equals to c. But if the function is not differentiable, then what we can say? We can say we can't say anything. It can be continuous, it cannot be continuous, right? We can't comment about that. Okay, but if it is continuous, it must be differentiable. That is for sure. Okay, so that is the thing. So let's first solve a question over here. From there we'll clear our concepts more. If the function is differentiable in its domain, then the value of m plus k. Okay, so basically if it is differentiable, then it must be continuous. Okay, so we'll solve this using two methods. Okay, first one is simply simple method, that is a limits method. Second one we'll solve using the derivative method. Okay, so what we can do, basically, not the derivative method, second method is something different, I'll talk about it later on. Okay, so here first, if the function like is, they have told us the function is differentiable in its domain. Okay, in its domain it is differentiable, then what is the first thing I can conclude? It must be continuous. So if it is continuous, around x equals to 3 we have a breakpoint. Any other place this is anyways continuous, right? Around x equals to 3 we have a like breakpoint, that is basically the definition of the function is changing. If the definition of the function is changing, what we can say, this is k, like left hand limit, okay, is equals to limit as x tends to 3 minus k x plus 1. So I can simply put here 3 over here, this will be k under root 4, which is 2k. Okay, and what about my right hand limit? X tends to this 3 plus this will be mx plus 2. Okay, so this will be simply 3m plus 2, right? I can simply put 3 over here, no issue, and these two should be equal to each other. So 2k is equals to 3m plus 2, but I have only found out one relation. I need to find out another relation to find, okay, m and k individually. Okay, I am not able to find m plus k. So what is another condition? Another condition is simply your that left hand derivative and the right hand derivative. Okay, so left hand derivative, we can compute what is the left hand derivative. If you recall correctly, limit as h tends to 0, just hold on a second. Okay, f of, what was this, f of a minus h divided by h, right? The most important part is people tend to forget this, right? People tend to forget this. Will not forget this. Okay, will not forget this. So what is f of a? F of a in our case, like it has to be differentiable around this like this breakpoint, right? Every other like square root of x is discontinuous, and this is a simple linear equation is, sorry, square root of x is differentiable. Okay, and this linear equation in itself is differentiable, but around x equals to 3 there is a break, right? There is a change, right? Okay, hence what we can say, basically we can say that definition changing, hence we will only talk around x equals to 3, right? So here limit as h tends to 0, and in our case a equals to 3. Okay, so f of 3 minus f of 3 minus h divided by h. So f of 3 is what? F of 3 is this, right? It follows this definition. So it will be k under root 3 plus 1 minus f of 3 minus h. Just before 3 is again this definition again. So just before 3, this is like h is some positive, small positive quantity. So it will be something lower than, like 3 minus h will be something lower than 3. So obviously we will again fall under this category, this definition. So I'll replace with this. So this will not be f, this will be k into under root 3 minus h plus 1 h tends to 0. Okay, so limit as h tends to 0, this will be k into under root 4 minus h by h. What I can do is I can simply rationalize, right? I can simply rationalize. So I will rationalize this time. So anyways, I can keep this under root 4 also, that is not an issue, but okay, let's take common k over here. Okay, and this will be 2 square minus 4 minus k. I'm just dividing and multiplying by dividing and multiplying by 2 plus under root 4 minus k. Okay, no, sorry, not k, this is h. Okay, so this is not k, this is h actually. So now what will happen, this is my left hand derivative, so this will be limit as h tends to 0, this k. What is interesting over here is this 4 and this 4 gets cancelled, and I have a positive h at the top, and also I have a positive h at the denominator. I can cancel those out, they will get cancelled. I will be remained with k upon this 2 plus under root 4 minus h. Okay, so this will be k upon 4, 2 plus 2 is 4, so we'll get k upon 4. So this is my left hand derivative. But like, what is the more important point is, people tend to forget this, right? People tend to forget to write this. Okay, so that's why I write this one first. That is my formula. Okay, so that is what I observe in most people, so don't forget this, don't forget. Okay, that's why I'm warning you guys, because many students tend to forget this thing. Okay, so let's compute the right hand derivative. What is the right hand derivative? So the right hand derivative is simply this limit as h tends to 0 f of a plus h minus f of a divided by h, right? So again, right, you will forget this, don't forget this, write this first. So again, I will talk about a equals to 3. Obviously there is a break point around 3. Now f of a plus h, this is somewhat greater than 3. If it is somewhat greater than 3, this will be mx plus 2, this will be mx plus 2. Okay, so this will be mx plus 2, and x is 3, so this will be mx plus m into 3 plus 2 minus f of a. Exactly at x equals to 3, the value of the function is this, right? K under root this, right? So this will be k under root 3 plus 1 divided by h. Sorry, this is not into 3, this will be 3 plus h, I'm sorry. And obviously we have limits. So obviously what will this become? This will be I can write this, so this will be 3m plus 2 minus 2k, and this is plus m into h, and we have a divide by h. So the interesting fact should be that this, right, this whole thing should be equal to 0, and that is what we have already observed over here. Okay, if I take this to the this left hand side, this whole thing, right, this whole thing is equal to 0. This has already been, like, we have already taken into consideration this property, but this whole thing is 0, we already know this. Okay, from anyways, for it to be continuous, this has to be 0, because this will be something finite upon 0, which is again indeterminate, which is not possible, because the function is, they told us the function is already differentiable. So this has to go to 0 from continuity, right? Continuity. So we're only left with this, and if we're only left with this, this is limit as h tends to 0. So this will be h cancels out, and we are left with m. So m, the left hand derivative should be equals to right hand derivative, and should be equals to finite. Okay, so this is basically, this means that k by 4 equals to m. Okay, k by 4 equals to m. So k by 4 equals to m, we can replace this m right here and find out our value. So 2k minus 3m, that is 3k by 4 equals to 2. So this will be 8. 5k by 4 equals to 2. K equals to 8 by 5. Okay, so k is equals to 8 by 5. So this is the answer. And what is m equals to? M will be equals to k by 4. So it will be 2 by 5. Okay, and m plus k will be equals to 10 by 5, which is equals to 2. So answer will be 2. Okay, so this is the answer of the question. Simply this is how you solve a differentiability question. This is basically what is it? This is basically the pattern that comes right in like JE. The pattern, this pattern comes up, but this is the overall use of overall question that can come in gate. A bit part can come from like come in gate, right, from this question. So what is the method 2? Method 2 is direct differentiation. Method 1 was basically basics, right? Method 1 basics. Method 2 is differentiation. Okay, method 2 is differentiation. So my LHD will be equals to RHD will be equals to my f dash of A. Okay, f dash of A. Okay, at that point, because at that point is where I'm most interested in. If it is differentiable, we can actually differentiate it, right? So we already know like function is differentiable. Function is differentiable. Differentiable. So if the function is differentiable, then obviously it has to follow this step. I forgot to write one thing over here, that it is equals to finite, and this is equals to f dash of C, right? I already told you, right? If the differentiation exists, the value of the differentiation will be f dash of C. Okay, the finite value, that finite value will be the differentiation itself. So here this is what, this is equals to f dash of 3, right? So what we can do, we can equate these two things. What we can do, we can differentiate the left hand side and the right hand side and directly equate these two. Okay, so what will be in my LHD? My LHD will be simply the differentiation, right? So if I differentiate, okay, here, if I differentiate here, what is this? This is k upon, I hope you know how to differentiate a square root function. This will be k into 1 by 2 upon under root x plus 1. Okay, so this is how you differentiate a square root function, and obviously it will be at x equals to 3. So this will be k upon 4. Okay, and what about my RHD? RHD is simply this, right? If I differentiate this function and put the value of x at that point, that will be my RHD. If I differentiate this function and put the value of x at that point, that will be my LHD. Okay, so that is how this differentiability concept works. Okay, if it is differentiation, if the function is differentiable, they've already mentioned, we can simply differentiate it and put the value of that x, right? So we can do that. So this RHD will be, if I differentiate mx plus 3, this will be simply be m. Okay, and it is irrespective of any x value, irrespective of any x value. So this will be equals to m only. So m will be equals to k by 4. And another, what is another like relation we have, directly f dash of 3. Okay, so these, right, these I was putting for like the right hand side and the left hand side, right? These I was putting for the right hand side and left hand side. Okay, so and what is f dash of 3? F dash of 3 also is also equals to m in our case, because that thing is included in the range. Okay, that thing is included in the range. And I will move this, because anyways you have to solve for continuity, that you have to do. Okay, that is the part, but the differentiability part you can ignore. So LHD, right, you can directly find the differentiation with this, with the help of this. Okay, directly find the differentiation with the help of this. So this will be what? This will be simply equals to f dash of a minus, and this will be simply f dash of a plus, f dash of a minus and f dash of a plus. Okay, so this is the thing about these two things. So now what we can do, so continuity you have to anyway say, if the function is differentiable, it must be continuous. So from these two equations, right, from these equation and these equation, what you can say is that my m like same equation only, my k will be equals to 8 by 5 and my m will be equals to 2 by 5. So my m plus k will be equals to 2 itself. Okay, so this will be my answer to this question. M plus k will be 2. So m will be 2 by 5 and k will be 8 by 5. So similar way you solve this question. So next we'll like learn about the reasons of non-differentiability at a point. So what are reasons of discontinuity? So the first reason is the most obvious one, which is the function is discontinuous. Sorry, I meant what are the reasons of non-differentiability. The first reason is the most obvious one, is that, okay, again this pen is not open. Most obvious reason is that the function is discontinuous. If the function is discontinuous, obviously there will be non-differentiability, right? There will be non-differentiability. This is a case one. Okay, and like the next cases we have already seen this, when there is a corner abrupt change in the differentiability. Basically this is known as the one-sided derivative. So this is some negative differentiation. Like if I do the tan theta of this angle, this like minus angle, right? So there is negative and this is positive, right? Negative and positive. Okay, so basically like this is known as a corner where the derivatives are one-sided on both ends, right? Okay, so this can be another reason for non-differentiability. So like let's further elaborate this, okay, in terms of key points. So mod of x is non-differentiable at x equals to 0. Now you will obviously not be given simple mod of x, you will be given a more complicated function. So if you have been given mod of ax plus b, then where is it not differentiable? It is not differentiable at ax equals to b. It was x equals to 0, now it is ax plus b equals to 0. Okay, now if I have been given summation of this, okay, this is I have missed arrow over here. If I have given mod of ax plus b plus mod of px plus q plus mod of mx plus n equals to, like this is a function, right? Then where is it differentiable? Why is it not differentiable? It is not differentiable at when my ax plus b equals to 0 individually. When my ax plus b equals to 0, px plus q equals to 0, lx plus m equals to 0. So this is not pq mn. I should write this m actually. Mx plus n equals to 0. So this I can say that this is x equals to minus b upon a, and here I can say x1 equals to minus b upon a, q upon p, x3 equals to minus n upon m. Okay, x1, x2, x3. Okay, these are the three things. So like let's like what is the like these are the few key points that you have to keep in mind, right, while calculating the non-differentiability of mod function. Now let's calculate the non-differentiability of another case, right? So this, right, similar only that the left hand derivative and the right hand derivative are not same. So this, what is this tending towards? Is tending towards minus infinity, and this, right, right hand derivative, it is tending towards plus infinity. So here like this is a name for this, no need to remember this, don't worry. Just the left hand derivative and right hand derivative are not equal. Also they should not be infinity, okay, they should be finite. So here they are not finite and obviously they are not equal. One is tending to minus infinity, another one is tending to plus infinity. I'm just showing you the example, don't need to remember curves for all these things, okay, don't worry. Okay, just showing you the examples. Case 4 is, in this case the left hand derivative and the right hand derivative are same. Okay, they are same. This function is x raised to power 1 by 3. They are same, but what is the problem? The problem is at x equals to 0, it is tending towards positive infinity, okay, so which is again against the rule. Okay, so our derivative has to be finite for it to be differentiable at that point. At x equals to 0, this is not finite. If you differentiate this, okay, what will you get? You will get 1 by 3 by x raised to power 1 by 3, right? You will get 1 by 3 by x raised to power 1 by 3. If you get 1 by 3 by x raised to power 1 by 3, you put x equals to 0, what happens? This goes to infinity. This tends to infinity, right? This tends to infinity. So yeah, this is the case for this thing. So yeah, at x equals to 0, this is obviously going to infinity, which is not possible. So hence we can't put x equal to 0, which is not in this domain. Hence that is why we say that this is not differentiable at x equals to 0. Okay, this is another what do you say, another reason for non-differentiable, right? So yeah, let's I've done this wrong. Yeah, this will be n actually here. So like what is the relationship between continuity and differentiability? So I have already explained this previously, but let's get this thing more clearer. Okay, let's understand this thing between continuity and differentiability. What is the relationship, right? Everyone has some relationship, right, with everything. So yeah, let's learn this also. So the right hand derivative is equals to f of a plus equals to L, right? And the left hand derivative is equals to f of a minus equals to m. So this is the left hand and right hand derivative. So I should write this. This is f dash. Okay, this f dash. This f dash. Okay. So if my L equals to m equals to some finite value, then the function f of x is differentiable as well as continuous. We already know this. We have already studied this. Okay. Just hold on a second. Let me check if this is recording or not. Yeah, this is recording. Fine. Okay. So yeah, let's get to the case 2. The case 2 is very important. Okay. Again, this is f dash of x. So here again, if L is not equals to m, so L and m are not equal, but are some finite values, then f of x is not differentiable but continuous. Okay. So yeah, I should write here, right? L is not equals to m. Oh yeah, L is not equals to n but are some finite values. So the value of the differentiation are some finite values, then the function f of x is not differentiable but it is continuous. So even if the left hand derivative and the right hand derivative aren't equal but they are some finite values, it will be continuous. Okay. So how we can say, even take the example of mod of x. Okay, mod of x, left hand derivative and the right hand derivative are different. Okay, there is a what do you say, there is a corner right at x equals 0. They are different but the function is continuous. Okay, function is continuous as the left hand derivative and the right hand derivative are both finite, they are not infinite, hence this is continuous. So this case is very important. You have to remember this. What is the example is, just remember with the example, f of x equals to mod of x. Okay, the left hand derivative and the right hand derivative are finite. Okay, are finite, but basically there is a certain change, right? So that is the main point over here. So yeah, what is another thing? This is again f dash of x. If at least one of L or m is infinite, then the function of f of x is not differentiable, but we cannot comment about continuity. So yeah, we cannot comment about continuity. So this is not an important. You can skip this. The main like what example you can take? You can just take the example of f of x equals to x of 1 by 3. Obviously, what we can observe is that around just 0 minus 0 plus. Okay, the left hand derivative and the right hand derivative is tending towards positive infinity. It is tending towards positive infinity. So yeah, that is fine. But is the function continuous? It is continuous. But it may so happen for any other function, it may not be continuous. We cannot comment about the continuity. This is very important point to note over here. Okay, so let's do a question, and from there we'll grasp the concept of differentiability much better. This is just the revision of limits, nothing else. Okay, differentiability will be just the revision of limits and differentiation, these two things. Okay, so let's read the question. So if f of x equals to x into e raised to power this, and for x not equal to 0, for x equal to 0 this, then f of x is discontinuous everywhere, continuous as well as differentiable. Continuous for x, not differentiable, neither differentiable not continuous. So as this is talking about both things, hence we'll first compute the differentiation. Okay, differentiability. If we compute the differentiability, hence we can obviously talk about the both obviously talk about continuity, right? So hence both continuity and differentiability is present in options hence what we can do, check differentiability. And another important point is, like I told you, two methods, right? One is the simple LHD RSD method, another one was the differentiate it then put the value, differentiate then put the value. But is differentiating this simple? Okay, differentiating this seems difficult. Okay, differentiating f dash of x difficult. Okay, f dash of x difficult, right? So yeah, f dash of x is difficult. So now what we'll do, we'll compute the left hand derivative and the right hand derivative. So x tends to 0 and this is 0 minus, and this is again the same form, right? The left hand derivative will be what? F of a minus f of a minus h divided by h. So what is this? What is f of a? F of a is simple. This side when x is equal to 0, this is 0, right? So a is 0 because that is the only break point. Okay, else this is continuous, because x equal to 0, this is becoming also like this continuous, but differentiability not present. So there is something going on at around x equal to 0. So we are only concerned with x equal to 0. So 0 minus f of a minus 0, which is anyways this definition, same definition only. So this will be f of minus h. So f of minus h will be, this is minus h e raised to power mod of minus h. Mod of minus h will be h only, okay, because this is positive quantity and this is minus h, right, divided by h. So what we observe is that this h gets cancelled, okay, and we have this e raised to power, okay, we have a minus sign also here. Don't forget this limit. Okay, this is understood that limit is already present, but sometimes people tend to forget limits. This is actually h tending to 0, not. This is like this is minus h. So this will be 0, e raised to power 0 only. So this will be 1 only, right? This will be simply 1 only. Okay, so e raised to minus 0 is 1. Now let's compute the right hand derivative. Okay, so right hand derivative, again limit as h tends to 0, f of a plus h minus f of a divided by h. Okay, so this is equals to f of h minus f of 0. So f of 0 is again 0 and f of h is interesting. F of h is again this, so this time, right, it will be simply e raised to power 2 upon h, because mod of 1 by h will be h only, right? And here we obviously have h over here. Okay, and also we have minus over here, right? H is below, so I'm directly computing it. Okay, you guys can solve in between, I'm skipping few steps. Okay, sorry, yeah, minus h and minus h, right? This time it will become, yeah, plus minus 2h. So h will get cancelled and this will be e raised to power minus infinity, okay, as h tends to 0, okay, because minus 2 upon 0, it will tend to minus infinity, right? So limit as h tends to 0, so this will be almost 0. So what we observe is right hand derivative is not equals to left hand derivative, but is finite. It is finite. So if these two are finite, what does that mean? That means that my function will be continuous. My function will be continuous. Function continuous but not differentiable. Okay, function not continuous but differentiable, not differentiable, right? So what are the options? It is continuous every, no. Continuous as well as differentiable, no. Continuous for all x but not differentiable for x equal to 0. At x equal to 0 obviously it is not differentiable, but for all other points it is differentiable. Neither differentiable, not continuous. Okay, so obviously it is continuous and it is not differentiable at x equal to 0. Can you just do this simply? Okay, what you can do is that for continuity you can simply check, right? Differentiability you have to solve, you have to simply solve. Continuity, what you can say is that this is 0 and at x equal to 0 this is anyways continuous, right? This is anyways continuous and this tending to this is anyways, like if I come from the left hand side, if I come from the right hand side, this is anyways tending to infinity, and positive infinity this is tending to, and this is tending to, sometimes this is tending to negative infinity and sometimes this is tending to positive infinity. Okay, so yeah, you also won't be able to comment about continuity because you have to again calculate the right hand and left hand limit. Okay, so yeah, I was trying some things. Okay, you can't use shortcut over here, so you have to compute the like this LHD and RHD. Okay, and if those come out to be finite, if these come out to be finite, then for sure they will be continuous. You have to remember this concept, right? This case 2 is very important. Else you will waste your time again solving for continuity. Okay, yeah, because the function is not differentiable. Obviously you say, sir, how I might know that the function will be continuous or not? You don't have to waste your time if the LHD and the RHD are finite. Okay, that is the main thing. So let's go to the next question. Okay, we don't have any question, we have properties. So what are the properties of differentiable function? Again, same as continuous function. Okay, if I multiply scalar, if I just add those two up, if I multiply those two up, they will be differentiable. If two functions are differentiable, the same thing. Okay, so same thing, just again the same thing you have to keep in mind. If we are dividing two functions which are differentiable, we have to take care that g of x is not equals to 0 for any real, for x of any real value. Okay, that is the important function. Then also that function will also be differentiable. Okay, for any real value g of x cannot be equals to 0. Okay, also yeah, because if you recall the quotient rule, the g of x, right? Okay, the quotient rule, in the denominator g of this g square x comes up, right? So obviously g of x cannot be equals to 0 for any value of x. If it is equals to 0, then what will happen? It will be again become a indeterminate format, so we have to take care of that. Yeah, that is the thing. Now again, right, properties of differentiable function for case 2. Case 1 is if two functions both are real valued and both are differentiable. Okay, that is the easier case. Now let's solve for case 2. So what is the case 2? If f of x is non-differentiable at x equals to c and g of x is differentiable at x equals to c, then f of plus minus g of x is always non-differentiable at x equals to c. Why is this the case? Because if you simply apply the differentiation, right, you can individually differentiate the two functions. If you are individually differentiating the two functions, that means one of them is non-differentiable, so overall the function will not be anyways differentiable, right? That is the first thing. Okay, then the second thing is f of x into g of x can still be differentiable. Okay, that is a more important point. F of x into g of x can still be differentiable. Example is mod of x into and g of x, okay, equals to x cube. So if you multiply this mod of x into x cube, what will happen over here? So the basic thing will be my x cube is something like this, and mod of x is something like this, right? So what will happen? This is negative, so this is positive and this is negative, so this will overall be like this only. Okay, this will overall be like this only. So this will make the function differentiable and continuous. Okay, this will make the function differentiable and continuous. So yeah, there is a possibility, we have to check. What to check? It can or it cannot also. Okay, if f of x and g of x are both non-differentiable, case 3, then obviously like you might say, sir, then this f of x plus minus g of x can like will not be differentiable, right? You might say, sir, we are individually differentiating it, it may not be differentiable. But the interesting fact is they can still be differentiable. Okay, because you are subtracting the same function. Okay, here I am subtracting the same function. Okay, I am subtracting the same function which becomes 0, so it becomes differentiable again. But here one is differentiable and another one is non-differentiable. We cannot combine those two functions. Here I can combine these two functions, just I am subtracting the same function only, right? If I am subtracting the same function only, it becomes 0, right? So that is the thing. Then if I multiply f of x into g of x, they can still also be differentiable. Again, this same example, mod of x into mod of x becomes x square, and x square is differentiable. Okay, mod of x into mod of x becomes x square. I hope you know this. Okay, so these are the few examples. So let's do few questions again. So let's check which of the following functions are differentiable at x equals to 0. So can you just see from the this options and check which are differentiable? So here, right, this mod of x individually is not differentiable. Now what is cos of mod of x? Is cos of mod of x differentiable? Like we have to check cos of x is what? Cos of x is what? So if I plot this, so mod of x is not differentiable, that we know. Mod of x is not differentiable, but is cos of mod of x differentiable or not differentiable? Okay, so what is cos of x? Cos of x is something like this. Okay, and what will be mod of cos of x? Basically we are ignoring the whatever the negative values, right? This is the negative values of x. Okay. We are ignoring this. Okay, we will never be in the mod of cos of x, right? So basically what will happen, the function will be something like this. Okay, there won't be any negative values. So basically for even negative values, like this won't change anything actually. This won't change anything because for negative values this already is even function. Okay, this won't change anything, this will be same only. Okay, cos of x and cos of mod of x. Why is this the case? Okay, let me explain why is this the case. Basically what you're doing, if you replace x with minus x, what will happen? Okay, so I will show you what do you say, theoretically, and then I will show you graphically. So what is mod of x? What is mod of x? Mod of x is basically x for x greater than equals to 0, okay, minus x for x less than 0. Okay, that is the definition. So what you will do, you will just replace cos of mod of x, right? Now for x greater than 0, it will be cos of x, okay, x greater than equal to 0, and it will be cos of minus x for x less than 0. And what we know, cos of minus x is simply cos of x itself. Okay, so these two are same only. Okay, no definition change. So cos of x, cos of mod x is cos of x itself. Okay, okay, or how you want to understand, this is a even function. Okay, so here I am giving cos of minus 1. Okay, now mod of minus 1 is 1 and 1 will lie here. Okay, this is a even function and the amplitude will be same only. So graphically also this will be same. Okay, so this is already even function. So here what we can say is that a is not differentiable. Okay, why? Because this is a differentiable function, cos of x is a differentiable function, but mod of x is not a differentiable function. Okay, so I will say cos of mod x differentiable, but mod x so basically what will happen over here, it will be simply not differentiable, a not differentiable. So a I will cross over, not differentiable, right? A is not differentiable. What about this, right? Again this is also not differentiable because this is differentiable and this is not differentiable, so this is again not differentiable. What about this? Now this part is very interesting, this part is very interesting. So here what is happening, for C part, right? For C part I can say that sine of mod x, I can write it like this. I am not plotting it graphically right now, you can plot it, that is a homework for you. It will be equals to sine x for x greater than equals to 0, it will be equals to sine of minus x for x less than 0. I can further express this as sine of x. Okay, further express this as sine of x. So this is sine of x minus sine of x, and this is plus sine of x, which are different. Now what we do, we have to find the differentiability, right? Talk about differentiability. I can simply differentiate this will be cos of x. Okay, cos of x, and this will be minus cos of x. Differentiation of sin x is cos x. For x greater, let me name this as g of x. Okay, and this is g dash of x. Okay, so this is the definition. What do we observe? At x equal to 0, this is minus 1 and this is 1. Okay, these are not same, right? These are not same. Okay, these are not same. 0 minus 1. Okay, so what we can do, we can totally write the function. Okay, our, what do you say, this f of x, right, equals to sine of mod of x plus mod of x. Now we can like, it is continuous because just before 0 and after 0, this is 0 and this is also 0. This is continuous, right? Left hand limit and right hand limit are same. But let's talk about the LHD and RHD, left hand derivative and the right hand derivative. Okay, so which is cos of x this is cos of x plus 1, because okay, this mod of x, right, mod of x will also become, I have already mentioned this previously. Okay, where is it? Okay, this isn't here. Okay, I haven't mentioned it. Mod of x is x only when my x is greater than equals to 0, and minus x when my x is less than 0. Okay, so like the differentiation of this will be plus x and this will be minus cos x minus 1. Okay, so this will be like around 0, right? Around 0, like the LHD is minus 2 and the RHD is plus 2, right? Minus 2 and plus 2. Okay, so hence obviously my C is also not differentiable, right? C is also not differentiable. C is also con. Let's talk about this. If you see this, right, you might at first glance this might seem not differentiable, but this is actually differentiable. What is interesting here is okay, if I just copy this function, oh no, my pen, right, pen these days are not giving me support. So here, if I just copy this function again, I will write the definition, right? I will write the definition. Okay, definition of this function is sine of x minus x for x greater than equals to 0, and this is minus sine of x plus x for x less than 0. Okay, so this is the case. Now if you like put this LHD, right, what is LHD? LHD will be 0 and RHD will also be 0. Okay, sorry, I haven't differentiated this. I have to differentiate, I forgot to differentiate. This is cos x minus 1 and this is minus cos x plus 1. Okay, and this I will copy. Okay, so which is equals to 0. Hence obviously the function is differentiable around 0 for this, right? D is correct. Function is differentiable at x equals 0, so D is differentiable at x equals to 0. So let's solve another question. So what I will do is give you homework this question, okay, and another question is there which I will not show, because if I show that, okay, you will see the notes anyways. This is also another question, you can take the screenshot, and we'll solve these questions in the next lecture, okay. Plus before going, I want to quickly summarize the difference between continuity and differentiability. So here, if f of x is said to be a continuous function, then this following condition has to be satisfied. The left hand limit and the right hand limit has to be equal, okay, and obviously they have to be equal to f of a, okay, and they can be infinite as well. Okay, they can be infinite. Can they be? Because they are in the domain, right? If they are in the domain, that is fine. If they're in the domain, that is fine. If they're not in the domain, then that is not fine, okay. So then if f of x is said to be differentiable at x equals to a, then the left hand derivative and the right hand derivative has to be equal and they have to be finite, okay. Then if f of x is said to be continuous at x equals to a, then there is no break in the graph of the function a comma f of a, right? So basically a comma y, there is no break, right? I can totally plot the graph without lifting up the pen, okay. And if f of x is differentiable, then it has to be then there is no break in the slope of the graph, okay. This is very important point, the slope of the graph, right? There is no break in the slope of the graph, there is no break in the function, right, in the f of x, but there is no break in the slope of f of x, f dash of x, okay. F dash of x must be continuous. So that is what we have been doing right here. What have we done in the previous lecture, in the previous question? What have we done? We have calculated the f dash of x, and we are computing basically the left hand limit and the right hand limit of f dash of x, and we are equating that. So that is the important point. So the slope of this should be same, the limits of this should be same. Basically f dash of x must be continuous, basically slope must be continuous, okay. And for continuity we check limits, the left hand and the right hand limits. That is what we are doing here exactly, right? Indirectly that is what we have been doing up until now, right? So yeah, this is what this point summarizes here, okay. So I hope this point also gets into your head. Then in an open interval a comma b, a function f of x is said to be continuous if it is continuous at all points in the interval. If it is continuous at all points in the interval, okay. In an open interval a comma b, a function f of x is to be differentiable if it is differentiable at all points. This is like self-explanatory, okay. Then continuity. In a closed interval a function f of x is said to be continuous if f of x is continuous in a comma b, okay. And also it has to be right continuous and left continuous, okay. This should be x b, right? This should be b minus, right and left continuous, okay. Not all continuous functions are differentiable. Not all continuous functions are not differentiable, okay. But all differentiable functions are continuous. This is the difference between these two. And here also basically in a closed interval a comma b, okay, this should be not open brackets, this should be closed brackets, right? A function f of x is said to be differentiable. Basically f dash of x exists for every point of a comma b. RHD and LHD should exist, okay. They should exist and they should be obviously finite, and f dash of x should exist for every point, okay. And okay, what do we mean by this is here, right, the right hand derivative and the right hand limit and the left hand limit should exist at the endpoint. Similar case, the right hand derivative and the left hand derivative should exist at the endpoint. So this is about the open interval. I just didn't explained you in some broad manner, just helping you in the summarizing part, because you can relate, right? How many things you will remember? You just remember this and you will automatically be able to recall this, okay. The right hand limit and the left hand limit should exist for the left hand endpoint, right? The right hand limit should exist, and for the right hand endpoint the left hand limit should exist, because just after the right hand the function doesn't we don't know the value of the function. Just before the left hand we don't know the value of the function, right? So that is more important. So similar case for here also, okay. So this obviously I have explained already. So this is the end of this lecture. I hope you will solve the questions what I have given you, and we will solve more questions on differentiability in the next lecture, and we'll finish the topic of differentiability in the next lecture. Thank you for watching, and I will see you in the next lecture.